So let's talk about what we're going to cover in this class. The goal of this class is really to give you a solid foundation, not only in Java, but in object-oriented programming as well. And so we're going to cover all of the basics of Java syntax. We're going to talk about classes and interfaces, abstract classes, and a lot more. And I also know that some of you are planning on taking the associate exam, and this is going to be a fantastic class for you to use in your preparation. But I will tell you, I just recently took the exam, and it's tough. I did pass, but it is tough. And what you're going to find is that this is going to be one component, one major component of your preparation, but you're going to want to do other things as well. Namely, you're going to want to practice, 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 practice. And there are other resources that you might want to consider using as well. There are practice exams, there are online quizzes, and so on. So, this will be, as I said, a major component of your preparation, but you are going to want to add to that a little bit with practice. So let's move on to the first section where we're going to talk about Java as a language and Java as a platform and give you the basics about what it is you're going to be working with.
Okay, so the very first thing that we're going to do is download the Java platform. Now this is known as the JDK, or the Java Development Kit. And the URL to get to this page is listed in the resources section for this lecture. So when you get to this page, you may see a slightly different version than the one I'm showing you right now. Here's what's really important. It needs to say Java SE Development Kit, and it needs to be version 8. The number that follows the letter U, like in this case down here, we've got the 8U91. As long as it's U91 or greater, you're fine. The really important thing here is that it's version 8. So what you have to do is accept the license agreement. Now you can read the license agreement by clicking on this link. Once you're okay with that, you click that you accept the license. And then you have to choose the version for your particular operating system. So I'm using a Mac OS. If you're using Windows 64, that's listed there as well. Windows 64-bit, I mean. So let's do that. I'm just going to click on this and download. And as you can see down in the bottom left, the download has begun. And once that's done, we'll begin the installation. All right, so the development kit has been downloaded, and so we're ready to run through the installation. Now, I downloaded this for the Mac. If you download it for another operating system, your options may be a little different than mine, but basically it's going to be the same thing. It's going to be a wizard. And really all that I do is just run through the wizard. I tend to accept whatever default directories that they suggest, default installation information as well, and it'll let me know when it's finished. Now that the JDK installation is finished, the next thing to do is test it. And I'm on a Mac, so what I've done is I've opened up a terminal program. If you're on Windows, you'll open up a command prompt. But once that is open, you'll type exactly the same thing that I'm showing here. The one thing you want to make sure is that you're not using a terminal or command prompt that was already open when you were doing the installation. If you do that, the environment variables won't be set up correctly, and this will not work. So you open up the program, and we just simply type Java -version. And if it works, then you'll see Java version 1.8.0 underscore, and then whatever that underscore value is. I downloaded U91, so that's what I see here. You might see something different if you've downloaded a later version. Remember, the main thing that's important for this class is that we're using version 1.8. Now, that might seem a little odd that we've got 1.8 even though we've downloaded 8. I'll talk about version numbering in the next section, but basically they're the same thing. 1.8 is the same thing as JDK 8. So with that said, we're done installing Java. The next thing to do is install our integrated development environment, which is called Eclipse, and we'll do that in the next lecture. The final thing that we need to install for this class is Eclipse. Eclipse is an integrated development environment, or an IDE, and we're going to use it to write our code. So in the resources section for this lecture, you'll find a link to the Eclipse download page, and that'll bring you here. And so what we're going to do is download and run the Eclipse installer. Now you may notice that I am downloading the Eclipse Mars release. Depending on when you're taking this class, you might not see Mars here. It may say Neon, and really Mars or Neon will be fine. Neon is the next release that's coming out very, very soon. So again, it doesn't matter if it's Mars or if it's Neon, but it does matter that you choose the right one for your operating system. So here I'm on a Mac, and I'm going to download the 64-bit version. So that'll bring you to a mirror, and over on the left side is the download. So I'll click this download button, and we'll give it a few seconds to finish downloading, and then we'll run the installer. I've finished downloading the Eclipse installer, and I've run it. And so now this is the first main screen that it shows, where we will choose which edition of Eclipse we want to download. So for this class, we're going to download the Eclipse IDE for Java developers. There is a version for Java EE, the Enterprise Edition, but we're not going to be doing anything with that in this particular class, so we'll stick with the basics, the Eclipse IDE for Java developers. All right, then it's going to let you choose your installation folder. I'm just going to let it choose its default. Click the Install button. Read through and accept the user agreement. And there it goes. So now it is installing. And once it's finished installing, we will run the application and make sure it's working. All right, so just a couple of minutes pass by, and now we're ready to launch Eclipse just to make sure it's working. So I'm going to click on the launch button. And it gives me a little splash screen for Eclipse. Remember, I'm using Mars. You might be using Neon if that's the version that's out at the time you are watching this course. So then it's going to ask you to select a workspace. And a workspace is, think of it like a place to hold all of your projects. And so what I'm going to do is, instead of just calling it workspace, I'm going to call mine Java 101. You can call it whatever you want, but it will be the workspace for all the labs that we do in this class. Now I'm going to click OK. And it'll just take a second as it's loading all of the stuff for Eclipse. And here it is, Eclipse. This is the first screen that you have. If this is the first time you've used Eclipse, it wouldn't hurt to go through some of the tutorials that they have here or get an overview of the features. But what I'm going to do is just quickly show you around just a little bit. So I'm going to move this a little bit over. So here is my workspace. And there really isn't a whole lot to see here yet. So in order to just talk about some of the features of Eclipse, I'm going to write a little bit of Java code. I'm not going to explain the Java code, and you are not expected to understand it. But I'm just going to do that so we can see some of the features of Eclipse. So the first thing I'm going to do is create a new project. So I'm going to go to, I right-clicked on the Package Explorer, and I'm going to do a new Java project, and we'll call this Hello World. And I'm just going to leave all the defaults. It's asking me what version of the JRE that I want to use. That's the Java runtime environment. And so we installed 1.8, so that's what we're going to use. Say Finish. And now I've got a project. And you can have multiple projects in a single workspace. So what I'm going to do now is right-click and create an actual Java class. Again, we'll go through these wizards in more detail a little bit later, but now I'm just going to create a class called Hello World and add that. And now you can see in the middle that we have our Java code. So I'll write a very simple program here. Public static void main string args system out println hello world. Now this program that I'm writing right now, it's your traditional hello world program. I will be explaining this in great detail in the next section, and you will end up doing a lab where you'll write this very program. So I'm going to save it, and now I'm going to run it. I'm going to right-click on the program here and say Run as Java Application. And you can see down at the very bottom, we have a tab called Console, and it printed out Hello World. You're not going to have to do this. I'm just, once again, just want to show you what Eclipse looks like, how we're going to be using it. If you were able to run Eclipse and you were able to just see the blank screen, then it's working. You're ready for the labs. One thing I want to point out here, though, is that now that we've got some code written, what these tabs are. And so on the very top left, this is our Package Explorer. And by the way, the official term is view. So if I accidentally remove a view and I need to re-add it, I can do that through the Eclipse menu. In fact, I'll do that right now. I'll get rid of this console view. Oops, I got rid of the console view. How do I get it back? So to get it back, all I have to do is go to the Window menu. At the very top here, we've got Window, and you'll see Show View. And all of the common views that we can use are listed here. If you don't see the one you need, you can click on Other, and they'll list a bunch of others as well. So I'm just going to click on Console, and then it's added back here. So that's what you can do if you accidentally delete one of the views. Sometimes the whole environment can get a little messed up. You might have accidentally dragged the console over here and now things are getting squished. So another thing we can do is what's called resetting the perspective. So if each of these tabs is a view, then the collection of views is known as a perspective. So once again, if I go to Window, you see a perspective menu, and I can just reset the perspective. If I do that, it goes back to all the Java defaults, and we're good to go. Now you may notice that console has disappeared, and that's because when we first started with this particular perspective, console wasn't there. It was added as soon as I ran the program, but I can re-add it again. I can go to Show View, put console, and there's the console view that we just had. And that's really all you need to know for right now. Again, you don't really need to write the code that I just did. You just had to open Eclipse and make sure that it was working. So with that said, you're good to go. It's time to move on to the next section where we'll start to dive into Java as a programming language and Java as a platform.
All right, now you have all the software you're going to need to be able to do the labs, so we can finally start talking about Java. In this section, we are going to look at Java as a language and Java as a platform. So consider this your 50,000-foot view of Java. You'll also have a chance to look at your first Java program, and if you do the lab, and I recommend you do the lab, you'll write your first Java program. So let's move right on to lecture number 1.
In this lecture, we're going to start right at the beginning, and we're going to answer the question, what is Java? Now, when you decided to sign up for this class, I'm sure you had a pretty good idea of what Java is. Java, as most people would say, is a programming language, and that is true. But in fact, Java is really two different things. Java is a programming language, but there's also a Java platform. And so in this section, we're going to talk about both of these things. However, in this lecture, the focus is on Java as a programming language. So when Java was created, there were some design goals in mind, and you can actually read the full paper that lists the design goals. I have in the resources section a link that will bring you to that paper. But I'm going to cover the high-level bullet points right now. So Java was designed to be simple, object-oriented, and familiar. Simple, they just wanted it to be an easy language to learn. Object-oriented meant that they wanted the ability to create modules in an object-oriented way. That's kind of a mouthful. We'll talk about what object-oriented means throughout the rest of this class. But for now, just think of it as a way of organizing your code into reusable modules. And they wanted it to be familiar. That really does tie back into it being simple, but they didn't want to reinvent the wheel. So a lot of the language syntax was based on C++. And C++ was arguably the most popular object-oriented language at that time. Java was to be robust and secure. So when you write code, you're going to go through several different processes. You're going to write what's called source code. And then you're going to take that source code and run it through a compiler. A compiler is another program that takes your code and turns it into something that the Java platform can understand. And then eventually you'll run that code. So with it being robust, there's actually a lot of different checks that happen to make sure that your code will run well. There's compile time checking, so you can find out if you did anything syntactically wrong at that time. And then there's runtime checking, things that can't be resolved until the program's actually running. For example, if a database is down, you don't really know that when you're compiling the program. You can only discover that when the program is running. And so it checks for these kind of issues and lets you know when they happen. Also, they wanted Java to be secure, so everything is sandboxed. There's a lot of effort in protecting memory that's being used by Java, and so on. They wanted it to be architecturally neutral and portable. This is also known as platform independent. And this is a big, big bullet point for Java. Java popularized the term write once, run anywhere. So the idea that we can write a program and we can run it on Unix or on Windows PC, and we can use the same code that we wrote for both. Now, the way that they are able to achieve platform independence is that we never compile our programs into a machine code that's native for a specific architecture. Other programming languages, for example, let's say I'm creating an exe for Windows, I would write my code with that in mind and I would compile it for that underlying architecture, that underlying operating system. But with Java, we don't have to do that. We write our code once, it gets compiled into something the Java platform understands, and that achieves platform independence. It's interpreted, threaded, and dynamic. So I mentioned that we have the Java platform that includes an interpreter. And so it's going to interpret the bytecode that we write. I just used a new term there, bytecode. That's what we call the code that has been run through the Java compiler. So that bytecode is going to be interpreted. It's threaded, so that helps us achieve high performance, and it's dynamic, meaning that it can resolve at runtime how things should be linked together. In other words, let's say I'm writing some code that's going to use a database service. At runtime, we can actually choose what that database service is going to be, and so that makes our code more dynamic. High performing, that's related to the interpreter and threading. And again, the URL where you can dive deeper into these bullet points is listed right here, but it's also found in the resources section for this lecture. Now let's talk about Java as a platform. In the very first section of this class, I had you download the Java platform so that we could write and run programs. And let's dive just a little bit deeper into seeing what it is we have. So the Java platform has two different components. The first component is called the Java Virtual Machine, better known as the JVM. And the Java Virtual Machine is what's going to actually run our programs. So when you downloaded your JDK, the Java Development Kit, that included the Java Virtual Machine. And remember that you had to pick a download that was for your specific operating system. So each JVM is coded in a way that it's able to interpret Java code, the stuff that we're going to write, and it's able to interpret it for the underlying operating system. So I'm running on a Mac right now. My JVM is going to be different than those that are running on a 64-bit Windows operating system. So the Java Virtual Machine, the JVM, that's what it helps us achieve our platform independence. We are also given what's called an Application Programming Interface, or an API. And you can just think of an API as code someone else has written that we get to use. It's a bunch of libraries of code, things like input-output, so input, accepting input from the keyboard, output, writing to the file system, connecting to a database, creating GUIs, graphical user interface, and so on. Lots and lots of libraries that are available for us. And the specific API that we get really depends on what version and edition of Java that we're going to use, and that's something we'll talk about in an upcoming lecture. Another thing that's interesting about the Java platform is that it can be used to run languages that aren't Java. So if you've heard of the programming languages, Groovy, Scala, Clojure. There's a bunch of other ones as well. These are programming languages that aren't Java, but have been written for the Java platform. So at a high level, this is how we're going to interact with the Java platform. First of all, we're going to write a Java application, which is in part going to use the Java API. The great thing about the Java API is not only is it code that we didn't write, they're libraries that we get to use, but the Java API is already bundled with the Java platform. That means if we're using a ton of code from the API, we don't have to bundle it with our own application. It's already there on the client's computer that has the Java platform. So we distribute our Java application. We're using the Java API. All of this code is going to be interpreted by the Java virtual machine for the underlying hardware or operating system. And that's how we interact with the Java platform. We distribute our code, the Java application, and the platform has the API and the virtual machine. Now, these two things together are known as the Java Runtime Environment, or the JRE. And we'll talk more about that in a little bit. In a previous lecture, I mentioned that our Java applications are both compiled and they're interpreted. So let's take a closer look to see what that means. So you and I, as Java developers, we're going to write what's called source code. And source code is what we write, but it's not what is actually run on a computer. Eventually, what we've written has to be turned into machine code. But when we're writing Java, we don't go immediately from source code to machine code. What we do is we take our source code and we run it through a compiler, and the compiler will produce an intermediate language. And that's something that will be then interpreted by our Java platform, the JVM. Now, that intermediate language is called bytecode. And bytecode is still not machine code. It's still not the kind of language that an operating system will understand natively. Bytecode instead is going to be fed to the Java platform. So the JVM will take that bytecode and it will translate it. It will turn it into machine code, which is run by the underlying platform. So you can think of bytecode as like machine code, but for the JVM. So this is where we get our platform independence. When we write our program and we run it through the compiler, that gives us the bytecode, and we're able to distribute that bytecode to anyone that has the Java platform. And the reason that that works is because when you download the Java platform, as I mentioned previously, it's specific for the underlying hardware and operating system. I'm on a Mac, so that's going to be different than someone who has downloaded a Java platform for Windows. We'll have two different JVMs, but both JVMs understand how to read and interpret bytecode for the underlying hardware and operating system. So with that in mind, let's take a look at the flow. So what's going to happen is we're writing our Java application and we run it through a compiler, and that's going to produce some bytecode. So we distribute that bytecode, and that's going to be run on the Java virtual machine. The Java virtual machine will interpret the bytecode into machine code, which is then executed on the underlying hardware operating system. When you're first learning Java, one of the challenges that you're going to run into is picking the right Java platform. And to add to this complexity, there are actually many different kinds of Java platforms. So one of the primary components of the platform is the JVM, the Java Virtual Machine. And we've already seen that there are a number of JVMs. Essentially every hardware and operating system combination has their own JVM. And that makes sense because the JVM would have to be written a little bit differently for different architectures. And plus, it's going to take our bytecode and interpret it into machine code for that underlying hardware and operating system. So the JVM comes in different editions. I mentioned editions in the previous lecture when I said that we get this Java API, it's great, it's a library of code that we can use, but part of what's going to determine of what's in that API is specifically what edition of Java we've downloaded. Not just edition, but also versions, but we'll get to versions in just a second. So there are three primary editions of Java. We have Java EE, Java SE, and Java ME. EE stands for Enterprise Edition, SE stands for Standard Edition, and ME stands for Micro Edition. And as you can see here, Java EE is a superset of Java SE. So we are learning in this class Java SE, the Standard Edition. You can think of that as the base syntax of the language, all the regular features that you need to write desktop applications. And Java EE, the Enterprise Edition, this is something that we're going to use when we're writing distributed applications. So if you're doing anything for the web, you're going to use Enterprise Edition. And there's a lot of different use cases. In fact, Enterprise Edition is really, really big. Some people will argue that you could spend a lifetime learning the libraries of EE and still not get to the end. So there's a lot of stuff there. You tend to focus on specific areas of EE that you need to incorporate into your application. But regardless, we're focusing on Java SE, and that stuff does not go away when you later learn Java EE. You're still going to use all the syntax and the libraries that are found in Java SE. Java ME Micro Edition, this is for embedded systems, limited devices. We'll probably see a resurgence, arguably, of Java ME with the Internet of Things. If you haven't heard of the term Internet of Things, Google it. It's a term that refers to adding software connectability to components like, for example, our refrigerator or our thermostat, and being able to access these components through the internet. So technically speaking, there's also a fourth edition, Java FX, but as of Java SE 8, Java FX is now bundled with Java SE. And so Java FX, that's an edition that focuses on creating graphical user interfaces. So each of these three Java editions will target different kinds of applications running on different types of hardware. And that brings us to Java versions. Now, there's a lot of information here on the slide. I'm not going to read it all to you. Feel free to pause and check out the features for each of the different versions. But what I want to point out is what happened with the version numbering over time. So in 1995, when Java was first released, it was just called the JDK. You just downloaded the Java Development Kit. And 1.0 was released, and eventually 1.1. But when 1.2 came out in 1998, Sun said, this is a bigger deal than just a point release. We want to have some sort of marketing that conveys how important this release is. And so they came out with the term J2 SE. And J2 SE was used officially all the way until about 2006. But unofficially, people still use it. You'll hear J2 SE, J2 EE, J2 ME over and over again from developers. But officially, that was dropped in 2006. The other change was actually 2 years before they dropped the J2 SE, 2 years before. And that was when they decided, instead of having it be called 1.4, 1.5, let's just call it 5 and 6 and 7. And that's what they do. That's the official marketing number. However, if you open up a command prompt or a terminal and you type Java-version, you'll see that underneath the covers, they're still referring to Java with these points. So in other words, in fact, you may remember in a previous lecture, we tested Java. And when I did the Java-version command, it said Java SE 1.8. And I said, don't worry, that's fine. 1.8 is the same as 8. And so that is the case. So the reason I'm bringing up the versions, there's several reasons why I'm bringing up versions. First of all, there's the idea of backwards compatibility. So if you write a program and you compile it with a Java SE 8 compiler, then it can be run on a Java SE 8 platform or anything built later in the future. So let's say that you had an older program, something that you wrote and compiled with Java SE6. That should, in theory, still be able to be run on a Java SE8 platform. That's the backwards compatibility. The opposite is not true. If I write a program and compile it with Java SE8, and I've downloaded the Java SE6 platform, it's not going to run. I'm going to see an error that's going to say there's a major minor mismatch problem. We can't run this code. So just remember that there is backwards compatibility. Older code can be run on newer platforms, but the opposite is not true. Also, versions are going to help us understand what features are available. So if I have Java SE6 as my compiler, as what I'm writing the code with, then that is going to have more features than J2 SE 1.4 would. And finally, often you're going to use libraries that were written by other people, maybe in your own organization or maybe from a third-party group. And there's usually requirements that are included with the library. They'll say, we compiled this with Java SE7. And so you're going to ask yourself, can I run this in my platform? And if you've got Java SE7 or greater as your platform, then you can run code that was written with Java SE7. But because of the naming changes that happened over time and the fact that not every developer is on board yet with these changes, sometimes you'll see weird numberings and names. So for example, if someone happens to say, I wrote this code with J2SE 1.6, and you're wondering, will that run in Java SE8? The answer is yes, it will. And the reason is that J2SE is the same as Java Standard Edition, Java SE, and 1.6 is the same as 6. So that's a little bit about Java editions and versions. We're focusing on Java SE8 in this class, which was released in 2014. And down the road, we should see Java SE9 being released. That's tentatively scheduled for the spring or summer of 2017. The Java platform that we downloaded was the JDK, the Java Development Kit. Let's take a look at that installation and see what we have. Now, as you know, I'm showing this to you on a Mac. If you are on a Windows machine, it's often installed into C program files Java. Check around there and you should be able to find similar directories that I'm about to show you. On the Mac, you're going to want to go into your library. And by the way, this is not the library folder that's associated with your login. This is right off of the Macintosh hard drive. So Macintosh hard drive library, rather than, for me, there's also a Intertech library, which is a different folder. So Macintosh hard drive library, go to Java, and then after Java, there's the Java virtual machines, and finally the JDK folder. One other difference between Mac and Windows is you'll often see a second directory listed right next to the JDK, which will be the JRE. And just as a reminder, the JRE contains the APIs, and it also contains the Java virtual machine. And the JDK contains everything that we need to write programs. So I'm going to open up the JDK here, and we've got some contents and home. And here's what we need. Under home, we've got several different directories. The first one is bin, and this is where all of our Java tools exist. For example, we've got Java. That's what we will use to run a program from the command line. We've got Java C, that's the Java compiler. Java Doc, that's a documentation tool, and so on. So all the programs that we need to be able to write and compile and run programs from the command line exist in the bin directory. There's a DB directory. This is just a simple database that we have access to. It's nothing that I personally would use in production code, but it's nice for smaller programs, for prototyping, and so on. Include contains what we would need if we were writing advanced programs that are going to communicate with libraries written in other languages like C or C++. Remember, I mentioned that there is another edition called Java FX, and that it is bundled with Java SE8 now. That's the source code for the Java FX library. We also have a JRE folder here. This is the Java runtime environment, so that'll allow us to run programs as well. Lib, this is where the Java API lives. Man, that's a folder that you're not going to see on Windows. Those are the man files, the manual files for all the different Java tools. And then finally, we got the source.zip, and that contains all of the source code for the Java SE8 API. So that's our JDK. We're going to learn next how to write a program and then use this JDK bin tool called javac to be able to compile the file and eventually run it with Java. So let's move on to the next lecture and look at some Java code. We've made it. We are finally at the point where we can start writing and talking about code. This is the fun stuff. But a couple of notes before we do. First thing is that if this is your first object-oriented programming language, this may feel a little overwhelming. There are really just a ton of concepts behind even the smallest amount of code that we're going to be writing, and eventually it'll become, second nature to you. But when you're first learning it, it can be a bit overwhelming. So my advice right now is don't worry about it. If you're feeling a little overwhelmed with this example, if you're feeling a little confused, that's okay. We will be diving into all of these concepts in much greater detail throughout the remainder of this course. Right now, it's just going to be kind of a 50,000-foot view of a short Java program. So what I'm going to do is I'm going to create a new file for our program, and I'm going to call it Hello World. That's the standard program that we write when we're learning a new language. So Hello World. And the extension for our Java source code is going to be .java. Has to be .java. Now, let's write our first line of code. The first line is going to be public class hello world, and then I'll put two little brackets. So, a couple things to note. When you're writing a program, we call the different components in the program, the main components, a class. And you can think of a class right now as like a blueprint. This is going to be the blueprint for our program. Another way to think of a class is that it's a type. It's a type of a thing. So for example, let's say you're writing a banking application. You might have a class for an account, a class for a customer, and so on. So this class, we're just calling it Hello World. We say public class to say that this can be run and used basically anywhere. We'll talk more about what it means to be public and not public later, but for right now, just know that we have to have public class so that it can be, the code can be used anywhere. And so we also put the name of the type here, the name of the class, and the name is Hello World. Notice that it doesn't have the .java extension in the code, but the name Hello World matches exactly the name of the file. In fact, the H and the W have to have the same capitalization. So Hello World with a capital H, capital W, that's what we'll have in the name of the file. And then again, the file name has the Java extension. The curly braces here are really just kind of showing ownership. So any code that we write in between these two curly braces belongs to the class Hello World. So let's do that. We're going to write something here called a method. I'm going to type it and then I will explain it. So we've got public static void main string brackets args. And again, I'm going to put in the curly braces. So what do we have here? This is what we call a method. And the purpose of the method is to contain any number of statements. So what's a statement? A statement really is just kind of an instruction in code. Do something. This is what I want you to do. Now, the nice thing about methods is that, let's say that we're constantly doing 4 things: step A, step B, step C, step D. It would be a pain in my code if I had to keep writing A, B, C, D everywhere that I wanted that code to run. With a method, I can simply just call that method, and it will run all of the code that are in between these curly braces. So it is a collection of statements. Now, we're going to keep this pretty simple. We're going to have one statement inside of here, and it's going to be system out println hello world. Okay, so let's talk about the statement, and then we'll go back to the method. So the statement that's going to be run whenever this method is called is that it's going to print out to what's called the standard out, which is typically going to be the console. It might be a log file, but basically wherever we run the program, it's going to print out this message. It's just simply going to print out hello world. The method, jumping back to line 3 here, is a little bit more complex. So the first thing that I'm going to highlight here is the name main, and you can see that it's written in purple here. So main, this is the name of the method, which means that when we want to invoke, when we want to call and run all the statements that this method contains, that's the name of the method that we'll call. So whenever we make a method, the method is going to have immediately to its left what's called a return type. So that simply means it's going to do all the statements that it contains, execute all of those statements, and then whoever called this method and said that it should run, we have the option to pass it back some information. In addition to running all the statements, we can give it something back. Now, we're not doing that here, so we're just going to say void, and void means we're not giving anything back. We're not returning anything once the main method has finished executing all of the statements. And to the right of the name main, we have parentheses, and we have listed in here what are called parameters. So in this case, we only have one parameter. It's a type string, which is just text. These square brackets mean that it's not just necessarily one string, it can be a collection of strings. Specifically, they call it an array of strings. And then we specify what is the name of that string array. So we've explained what a parameter looks like, but it's still a little hard to understand. What's it doing? So somewhere we're going to have some code that at some point is going to call main. It's going to say, main, I want you to run. And when it calls it, it's going to have the opportunity to pass in arguments. So arguments are just any data that it wants to pass into the method that method might be able to use. So that's what this array of strings is saying. It's saying that main accepts a collection of text, and if this method wanted to refer to the collection of text that was passed into it, then it will refer to it with this name args. Okay. Now, in this particular example, we're not doing anything with the array of strings, so if someone passes us in an array of strings when this method is called, we're just kind of ignoring it. But we're declaring it that it's possible, that we may be interested in working with this array. That essentially is what you need for a method. You have your return type on the left, your name of your method, you have parentheses, and then in the parentheses you specify any arguments, any parameters that you will accept. Now, I've used those two terms a bit interchangeably, parameters and arguments, and frankly, most people do. But if we want to be academic about it and proper, when you declare a method like this, what you write inside of here, these are your parameters. But at runtime, when we actually call the method and pass something into it, we pass in arguments. Okay, but again, a lot of people just use those terms interchangeably. The other thing a method is going to have are these curly braces to specify what are the statements that will be run when the method is called. And then to the left of the return type, these things are just called modifiers. And they do exactly what it sounds like. They modify the method in some sort of way. So public static, the only thing you need to worry about with that is that it's saying this method can be run by any code, and static simply means that we can do it by sending the message to the class itself rather than an object that has been made from the class. Now that is definitely a mouthful, and we will talk about objects and instantiating objects from classes and what that means a little bit later. But the most important thing to know is that to the left of the return type are the modifiers of how this method should behave and how it's accessed and so on. So like I said, it can be a little overwhelming. There are a lot of concepts in just a little bit of code, but we will go through all of these concepts through the remainder of the class. Now, this method that I made here for Hello World is not just any ordinary method. I mean, it's a legal method in the Java programming language, but it has a very, very special purpose. It's the front door to our application. So in the next lecture, when we compile and run this program, what we're going to do is we're going to say, run the Hello World program. And what the JVM is going to do is it's going to look for this method main in the Hello World class to run it. So this is the first method that's called when we say run this program. As such, there are rules for the main method. And I'm going to go over the rules right now. If you need to, watch this portion of the lecture a couple of times. There will be a quiz right after this lecture to see if you absorbed all the rules for the main method. The first rule is that the modifiers for main must be public and static. The interesting thing about modifiers is that the order of modifiers does not matter. So you could write static public. That's legal too, and that's fine for the main method. Although, strictly speaking, most people will write public static. The most important rule is that they're together for the main method, and all modifiers must be to the left of the return type. The return type for the main method must be void. It's not going to return anything back to whoever calls it. The name of the method main must be in all lowercase letters. So Java is a case-sensitive language. If I have a method here and I write main with a capital M, very common mistake when you're first learning Java, it's a legal method, but it is not the front door that the JVM is looking for. The method main with a capital M is a different method than main that is all lowercase. For the parameters, it must accept an array of strings. Now, the interesting thing about the array symbol is that it can go right up to against the type string. There can be a space in between, that's okay. And in fact, although you don't see this as often, it can be to the right of the name, the identifier, args, as well. All of that is legal. I'm going to put it where I normally keep it, where most people normally keep it, which is right against the type. And that's nice because we can quickly see that this isn't just a single string, this is an array of strings. The final rule for the main method is this name args. And the name can be anything you want. Traditionally speaking, most people put args, short for arguments, but we could put it in Java is great if we wanted to. And that would be legal as well. You can put whatever identifier you want. So there is our first Java programming language example. And so what I want you to do now is maybe watch this lecture a couple of times, make sure you get the rules for the main method, and then take the quiz that follows. After you're done with the quiz, we'll talk about compiling and running this program. So now that the Hello World program has been written and it's been saved with the .java extension, should also mention .java should be in all lowercase. Now that it's written and saved, we can compile and run it. And so we're going to do this with the command line tool. Now after this lecture, we're going to move on to Eclipse. And when you do the lab, you'll do both the command line and use Eclipse as well. But the reason that we are doing the command line at all is because, number one, it's good to know. You may be in a situation where you don't have access to an IDE like Eclipse. And also, if you're taking the exam, it is one of the topics. You have to know how to compile and run a program using the command line. So I have a terminal opened up. You would use a command prompt if you're using Windows. And what we'll do is we'll compile it. So first of all, I'm going to look at the directory here. And you can see that we've got a file called helloworld.java. So the way that we compile it is we say Java C, and that has the C is for compile. So we're going to run the Java C, and we put in the name of the file, the whole name of the file, helloworld.java, and I'll hit enter. And now it doesn't look like it really did much. In the Java world, no news is good news. So if I take a look at the directory again, we now have two different files. We've got helloworld.java, which is the source code, and we have helloworld.class, and that's the bytecode. If we were to open up the helloworld.class, we wouldn't be able to read it. There'd be a lot of binary characters, but that's what the compiler has produced. That wouldn't be, in fact, the class that we distribute. We'd say, here's our program, helloworld.class, and then people would be able to run it if they have the Java platform installed. So how do we run a program? It's very similar. We say Java, leaving off the C, because we're just going to run Java, and the name of the class. Now notice that I'm not putting .class when I run this. I just simply say Java hello world, the name of the type. I'm going to hit enter, and now you can see it's wrote out the words hello world right below. So the program worked, and when you do the lab, that's what you should expect to see as well. Now, that was the happy path. That's where everything went as expected, which is great when it happens, but it doesn't always work out that way. So let's just introduce a couple of errors into our program and take a look at that robustness of Java, where we're able to see compile time checking. So what I'm going to do is change the name of the class. If you remember, the name of the class must match in spelling and capitalization the name of the file. So I'm just going to make this a lowercase w. And I'm going to go back to the terminal, and let's run that Java C again. And now you can see I got an error. So it did a check, and it says class hello world is public. It's telling us that it should be declared in a file named hello world with a lowercase w. So it's telling us exactly what the problem was. So I'll fix that. Let's do another error where I forget some of the syntax. Now, we'll talk more about syntax in upcoming lectures, but I'll just tell you right now that when you make a statement, it has to end with a semicolon. So I'm going to get rid of that semicolon, hit save, and now let's compile it again. And we get a different error. And it tells us the semicolon was expected, and it points to the line of code. It's hello world, Java, line 5. It prints out line 5 and puts a little caret underneath saying where that semicolon should go. So anyway, as you make different kinds of mistakes, the compiler will catch many of these. And those that the compiler doesn't catch, well, then there's runtime checking as well when we actually run the application. So that's it for this particular lesson. Just remember that when you save the file, that it's got to be helloworld.java. It has to end in .java. It has to match the capitalization of the name of the class. When we compile, we'll do it with Java C. And, whoops, let me save this file here. Run that again. We compile with Java C, and no news is good news. That means it compiled perfectly. And if we take a look at the directory, we'll see that we'll have another file there with the same name, except a different extension. And the extension is .class. That is our bytecode. That's what we distribute as our application. We have one final topic to cover for this section, and that's on the documentation for the Java API. So as a reminder, the Java API is a set of libraries available to us so that we can use pre-existing code in our applications. And there is a ton of it, so you are going to refer to these documents over and over and over again. And I'll go through them in just a second, but first of all, how did I get to the documentation? I'm currently using the web to access the documentation, so I have this link to the Java Platform Standard Edition 8 API spec. I have that in the resources for this particular lecture. And there is another option, of course. You can download the documentation as well. And so if you go to the Java download page and scroll down a bit, you'll see additional resources, and then there is a download to download the Java SE8 documentation. So I have that link to the download page as well in the resources section for this lecture. But let's take a look and see what we have here. The API documentation has three main areas. Now at the top left is what we have, it's called packages. And so what a package is think of it like a folder. Think of it as a directory. It's a way of organizing all the libraries that are available to us. So for example, if I scroll down, there is a Java Lang package. And when I clicked on that, it changed what was right below it. So now the section below it, the frame below it, that lists the interfaces and classes that are available in that package, that are in that folder. And we'll talk about the difference between interfaces and classes, but this is the code that we get to use. So what if I wanted to learn more about strings? I can click on string here, and in the main frame of the page are all the details that we need to understand how to use the string class, how to use this particular code. And so it starts off by telling you a little bit about strings. It gives a few examples. And then if you scroll down, there are methods and constructors and so on. And if you click on any of these methods, I'll just click on one, it will tell you a little bit more about it. How is it used? How should you call it? If you recall, when we made Hello World, you made a method, the public static void main method. So that's what these are. These are just methods that can be called. And so they tell you what's the proper syntax to invoke them. Now, a lot of the concepts that we're seeing here, we haven't really gotten into yet, so the usage of the Java doc will make more sense as the course continues, but just be aware that it's there. If you're going to use anything from the API library from Java, that there is a Java doc available, and it contains all the information you need on how to use those classes.
You just finished building your very first Java application. And we've been talking about the programming as an object-oriented programming language. So what we're going to do in this particular section is really dive down into that concept. What do we mean when we say objects? And we'll also compare and contrast that to something else called a primitive. So let's get into the first lecture.
At this point, everyone that's taking this course knows that Java is an object-oriented programming language. But what does it mean to be an object-oriented programming language? And that's a mouthful, right? Object-oriented programming language. Most people will just say OO or OOP for short. So OO represents a way of creating our code. It represents a way of organizing our code. And one of the things that we're trying to do often in software is take a real-world process and then convert it to something that's in a software solution space. So the nice thing about OO programming is that the organization tends to mimic the way that we see and interact with the real world. Now, that's not to say you're always going to be writing code that mimics the real world, but organizing our code as if we're dealing with real world things tends to make it easier to reuse, to maintain, and so on. So what do we mean by an object? Well, an object is anything that has data and related procedures. Now, we'll often call this state and behavior. So let's take a real-world example. Let's say you're writing a banking application, and one of the real-world objects that you run into is a bank account. Now, think about a bank account. It's going to have state and behavior. The state would be things like the balance, the ID, the owner, and so on. And a bank account also has behavior. We can debit the bank account, we can credit, we can open, close, apply interest, and so on. So that's really what we're trying to do with OO programming. We're trying to assemble our code into modules that mimic the real world, that have state and behavior. And I should say that not everything is going to have state and behavior. Some objects will only have state. Some objects will only have behavior. But typically, if you think about the real world that you interact with, most things have both. They have state and behavior. So that's one of the nice side effects, if not goal, of OO programming, is that it's easier to mimic the real world so that when we look at our code, it's easier to organize, reuse, etc. So this process of writing code to be like the real world is called abstraction. We are simplifying the real world into a software solution space. As we continue to talk about object-oriented programming, we'll talk about the pillars of OO. And abstraction is one of the pillars. There are 3 or 4 pillars depending on who you talk to. So there's abstraction, encapsulation, inheritance, and polymorphism. And we're going to cover all of those in this class. Abstraction really means to simplify, to make things less complex. And as we learn more about objects and object hierarchies, object graphs, that term and that process will start to make a lot more sense. But for right now, just think of abstraction as simplifying. So what are the advantages then of doing OO programming? First of all, it's more extensible, and we can extend it faster than we can than other types of programming. So we'll learn about something called inheritance a little bit later. And what we'll find is if there's some sort of object that already exists, and I want to make something that's a specialized form of it. For example, maybe we have a person object, and I want to make an employee object as well. The employee is going to pretty closely resemble a person, but there's going to be a few things added to it. So with object-oriented programming, they have something called inheritance, they have composition, and it allows us to create new objects that are built from existing objects. Arguably, object-oriented programming is easier to maintain. Now, this is debatable, okay? I tend to think it is easier to maintain. There are plenty of people that would argue against that bullet point. But the idea is that if we're mimicking the real world, it's going to be easier to figure out where I would look for certain parts of code, where new parts of code belong. Maintenance becomes a lot easier, and so on. OO provides better organization for code reuse and library functionality. So let's say that I create a person object and I make it available to anyone in my company that wants to write code that are using people. So they'd be able to get reuse out of this person. Maybe they're going to specialize it by turning it into employee. Maybe they're going to include it as a object for an order or for a registration for a class, and so on. So once we define the class, which is the object, well, I should just say right now, the difference between a class and an object, because we're going to be throwing these terms around back and forth. Think of a class as a blueprint and an object as the thing that's made from that blueprint, okay? So if we just start with that, that'll get you through a lot of these definitions that we're going to hit. So with objects, we have the ability to, just reuse these. And once we reuse them, that means that's code we don't have to rewrite. That's not code we have to test as aggressively. I'm always a little weary of saying that we should always test aggressively. But, if you've got a good object that's already been written, hopefully it has a test harness already built for it. So those are the basics of object-oriented programming. We're going to dive deeper into those pillars I mentioned, and we'll see lots and lots of examples as we continue on through this class. At this point, we know Java is an object-oriented programming language, which means that we're really going to spend a lot of time writing and reading and interacting with objects. But it's not the only type that we'll interact with. There is also something called a primitive data type, and usually you just say the word primitive. There are 8 primitives to learn, and most of them, 6 of the 8, are just numeric. So we've got byte, short, int, and long, and those are integer values. They're whole numbers. We have float, double. Those are decimal or real numbers. We've got a Boolean, which is just true or false, and then we've got a char, which is a single character. Now, I know that saying the word char is going to drive some of you crazy. This is one of those words in software that there's no agreement on how it should be pronounced. A lot of people will say, it should be pronounced care because it's short for character. And I tend to agree with that, but so many people that I work with have said char, and I've been programming for way too long. I'm just going to continue to say char. That's what I got used to. That's what I'm going to say. Now, besides that, everything else in Java that we're going to work with is an object. So we'll talk a little bit more about primitives in an upcoming section, but one little thing that I want to mention in terms of the difference between a primitive and an object is that a primitive is really just a single value. That's all it is. So we talk about objects having state and behavior, and remember, some objects might just have state, some objects might just have behavior, but they have the potential to have both. And with the state, it can be any number of pieces of state. With a primitive, it's just one piece of state and absolutely no behavior. Okay, it just has a value. The other thing that's different between all of these different types, so I mentioned, for example, a float and a double are both decimal numbers. So what's the difference? The difference is really in the size. So a float has 32 bits and a double has 64 bits. And we'll go over those details a little bit later. Oh, the other thing is that the JVM does treat primitives differently. And so one of the reasons that these were primitives were added to the Java programming language was because they can be treated more efficiently than an object. Now let's go back to objects. So Java is an OO programming language. We're going to be using a lot of objects. First thing to learn is how do we instantiate a Java object? So here are a couple of examples. 3 different examples of instantiating an object. I'll go into the syntax a little bit more deeply in a minute, but we have 3 examples. We've got a string object that we're instantiating first. We've got a customer object that we're instantiating second, and then a circle object. And whenever you instantiate an object, we're probably going to use it more than once. So what you're seeing here is we're assigning that object to some kind of a variable. As a reminder, a variable is just something to hold a piece of information. And so what this piece of information is a reference. It's going to create the object, and that reference is going to refer to the object that was created. In other words, string s equals new string. We're creating the string object on the right side of the equals, and then we're assigning it to a variable called s on the left side of the equals. Let's start with the left side, looking at this example of customer. So the first thing that we have is the reference type. Whenever we're going to declare a variable in Java, we have to specify what its type is. It might be an object type, it might be a primitive type, but we have to declare what it is. So in this case here, we're saying that this variable C is of type customer. And Java is a strongly typed language, which means that when we compile our program, it's going to run some checks and try to make sure that, in fact, what we're assigning to C is, in fact, a customer object. Now, there are a couple of instances where that can get muddied a bit, and we might not find out about the problem until runtime, but we'll talk about those scenarios a little bit later. So the first thing, left side, we're creating a reference variable. And what will happen is I'll use that variable C in the future to send messages to the object to say, hey, I need you to do something, or I need to find out some information about your current state. On the right side of the equals, we have a special keyword called new. And so that's saying that we're creating an instance of a type. We're creating an object. A new object. So what's the type of object that we're creating? In this case, it's customer. Now notice that there's parentheses on the right side of that type. We'll talk about why later, very soon actually, but for now just know that we need that. When we're going to be creating a new object, we're going to have to call a method, and it's a special kind of a method. It's known as a constructor. And so that's what we're doing here. This is how we call a constructor, to construct the object. The very last thing to notice is that there is a semicolon, and all statements in Java must end with a semicolon. Now, how about primitives? Primitives don't have state. They don't have behavior. So we don't need to create a new object from some sort of a blueprint. What we just need to do is assign the value. And so that's what we're doing here. We've got 3 examples. I've got my data type in the first example is int. My variable is I, and I'm assigning it the value of 5. There's one for the char where I'm assigning it the value of a, and I've got a double called pi that I'm assigning 3.14. So that's all you have to do for primitives. You just declare the variable, and then you assign the value. Now, when we create an object, and I already used this term, it's called instantiation. So let's try that word again. It's called instantiation. And so we typically say that we're instantiating an object. Another thing that's interesting is to realize when an object is actually being created. The thing to note is that when you create a reference variable, that's not when we're creating the object. It's only defining the reference variable so that we can send a message to the object later on in the program. The object's actually created when we say the keyword new. So here's an example where we've created circle C, semicolon. That is a legal Java statement. All that we've done is said we're creating a variable that's called C, and its type is circle. At that point, we have a reference variable, but no object exists yet. The object does not exist until we say C equals new circle. And it's really the right side of that equal sign that's creating the object, that's instantiating the object. So we say new circle, that creates the circle object, and then it assigns it to the variable C. Now notice that I didn't repeat the reference type in that second line. And that's very, very important. In fact, if I had said circle C equals new circle, I would have gotten a compile error because it would have said C already exists. You've already told me what the type is. You can't just change C here with a new reference type. And actually, there is a way to do it, but we'll get to that later. For right now, just note that you can't just say circle again because that would redefine the variable as a new variable. And that's not legal in Java. It's already been set, and so we just assign new circle to C. Now, why is it important to understand about the single reference? Well, we can keep using a single reference over and over again as long as it changes to objects of the same type. So let's start with a customer. Here I've got a new customer that I'm assigning to a customer variable. The variable is called C. And notice that inside of the parentheses now, we're passing in some information. If you think back to when we were talking about main, and I gave you that 50,000 foot walkthrough, I said, one of the things that can happen with main is we can accept parameters. We can accept an array of strings. And we weren't dealing with the array string at that time, but we were defining in that method that, yes, we take an array of strings. So what's happening here is this customer constructor is accepting a parameter. Apparently, it's accepting a string parameter. Now, you don't get to just make this up when you're calling a constructor or instantiating an object. What you have to do is look at the actual class and say, what constructors do you have? Now, that's something we'll talk about later, but for now, just pretend that the customer class, which is what we're calling here, has a constructor that says, I take a string. And so that's what we're passing in. So now what I'm going to do is I'm going to take that same C variable and I'm going to assign it to a new customer. And I'm going to do it again and again and so on. And that's perfectly legal. But what's going to happen is that every time I point C to a new customer, then C is no longer pointing to the old customer. And I really shouldn't use the term pointing, even though it's fairly correct. It's not precise. The precise term would be referencing. We're not really pointing to the object. We're referencing the object. There has to be a lookup of where that object exists in memory. But referencing, pointing, when you hear me use it, I mean it in the same way. It's referring to a customer object. So in that second, third, and fourth line, every time C is assigned to refer to a new customer, it's no longer referring to the old customer. And what will happen in Java is that we've got something called a garbage collector. And it's just going to run periodically. We really can't force it to run. The best thing we can even do is give it a hint. Hey, it would be really cool if you'd think about running right now. And it may or may not run. We'll talk about garbage collectors a little bit later, but in general, it's just going to go and run on its own, and it's going to look at all the objects that exist and say, is anyone referring to this object? And if no one is referring to the object, then it's able to be destroyed. It's able to be garbage collected. And so destroying objects is actually a good thing. We want to do that because we're getting rid of the objects that are no longer needed, and we're re-accessing the memory that they were taking. So we'll talk again more about garbage collection, destruction, cleanup of objects a little bit later. One of the key concepts that you're going to have to master in order to become a very proficient Java developer is how our data is being organized in memory. If we don't understand how the data is being organized in memory, we'll try to access information when it's not available. We'll keep stuff around for too long, and so on. So in order to understand how memory is managed in Java, we can deal with two concepts. One is called the stack, and the other is called the heap. And this is how memory is organized. Now, the heap is a large portion of memory, and it's where all the objects are going to live. And the stack is a more short-term piece of memory where we have reference variables and so on. And as we continue on with different lectures and we look at code, we'll occasionally come back to the stack and heap to see how all of our code is being organized. So the stack is a list of references that are defined within a given block of code. So we refer to this as scope. And scope simply means, when is this available, who can see it, who is it available to, and when does it go away? That's the idea of scope. So one of the ways that we can recognize scope when we're looking at code is just by looking at curly braces, because the curly braces are going to define ownership. We refer to that as a code block. And so that gives us a sense of scope, when something will come into existence, who can see it, and when will it go away. And again, this is something we'll dive into a little bit deeper into a future lecture. As I mentioned, the heap is where all objects are stored in memory. The heap is a larger portion of memory, and really just calling it the heap is a bit of an abstraction. There's different areas of the heap for specific purposes, but just dealing with sort of a general idea of objects live in this space is good enough for what we need to learn. Now, the references in the stack, whenever we create a reference variable, those references can point to objects in the heap, and some references will point to the very same object. So here's just a very simple stack and heap example. If you see our code, we've got customer C equals new customer, and we know that what we're doing is we are creating a customer object on the right side, and that object, that point, gets put into the heap. And then we assign a reference to that object, that's the arrow that you're seeing down below, and we assign that to a variable called C on the stack. So we'll dive deeper into this concept of stack and heap, but we want to just set a nice foundation for the terms at this point. Now that we've seen how we can create an object, let's look at how we can use the object. And using an object really means sending it messages to do things. So objects contain state and behavior, and when we talk about behavior, we have a special name for that in Java. The term is method. So all of our behavior in Java is put together in a method. And remember that a method is really just a code block. It contains one or more statements that we can call or invoke. The term call and invoke are the same thing. And once it's called, it's able to then execute all of those statements. It's able to provide the behavior that we need. So if you've used other programming languages, you've probably run into the same concept. They have different names: procedures, functions, subroutines. These are all different names for more or less the same thing. Now, I say more or less because, some people will argue, well, there's a difference between a function and a method, and they'll go through and break down the differences. But for our purposes, at a high level, when we're referring to behavior that's executed through code, we're more or less talking about the same thing. So how do we invoke behavior? And what we do in object-oriented programming is we use something called the dot notation. And we call it the dot notation because you use a dot to send a message. So assume that, we created a string. We had some code that said string s equals new string. The way that I could send a message now to that string object to do something is I can use the dot operator on the variable, on the reference variable. And if I want to pass in some data, I can do that too. And that's what's happening here. So there's some sort of reference variable called s. And we are sending a message to it to say, hey, I want you to do something for me. I want you to run your substring method. And so we use the dot, and then we say the name of the method that we're calling. And then we've got parentheses there. And the parentheses have two numbers, 4, 10. So remember that a method can accept parameters. And then at runtime, when we actually call the method, what we're doing is we're passing in arguments. So if we were to look at the definition of the substring method, we'd see that it takes 2 ints. And so at runtime, we're passing in 2 int arguments. We're passing in 4 and 10. And you may be wondering, well, okay, what does that do? Well, we could go to the Java API documentation, and we'd see that substring is going to create a brand new string, and it's going to create it out of the old string that s is referring to. The number 4 is saying what character should it start at, and number 10 is saying, and up to what character should it include. So that's just cutting a string, some text, out of an existing string and making a new one. So that is that's how we invoke a method. We use the dot operator. And methods can return things. You remember that we saw a method that returns void, public static void main. And void means we're not returning anything. Well, if we were to look at the actual implementation of the substring method, we'd see that it's going to return to us a new string, the one that it just made. And so we can take what it returns after it's done doing all of its executing all of its statements, we can take what's returned and now assign that to another variable if we'd like. So here we're creating a variable called sub. We're taking the return value of that substring and assigning it to sub. So now we've got 2 variables. We've got s and we got sub, and we can keep sending messages to both objects. Now, what if a method doesn't take any parameters? Well, in that case, you'd still have the parentheses. You just wouldn't have anything inside there. We wouldn't have 4, 10. We would just have the empty parentheses. So another way to think of the dot is call the method on the object that this reference is pointing to. And you can see it right here. On our stack, we've got the s variable, and it is referring to the string object. In this case, the string says hello world. And strings have lots of different methods, substring, trim, char at, and so on. And we'd be able to invoke those methods. We're able to call the methods just by using the dot operator. And I really like the analogy of calling, because a little bit later we're going to talk about access modifiers. And understanding that concept tends to make a lot more sense when we think of it as we're kind of picking up a telephone, that S is like a bat phone, picking it up, and it instantly dials the object that's at the other end, connects us through, and then we say, hey, we want you to execute substring. And the string says, well, that's great. Do you have any arguments for me? And we say, yes, we do. Here's a 4 and here's a 10. And it says, thank you, and it does its work, and then it sends back a new string, which we are assigning now to a variable called sub. Let's look at some more examples. So here's that hello world string that we're creating. So string s equals new string hello world. And notice that we've got a few spaces at the end of the string, just adding some white space there. So after we create the object, what we can now do is send it messages. So we've already seen the substring method that we just talked about, and that's going to return OWORL, O-W-O-R-L. And you can kind of count that. Like if I go using my mouse here, we can count to the 4th character, 0. By the way, most things in Java start with an index of 0. So 0, 1, 2, 3, 4, there's the O. And we're going to go all the way up to 10. So 5, 6, 7, 8, 9, 10. So D is where 10 is. Now, if we went to the Java doc and read the details of this, we'd learn that 10 is exclusive. it's not going to include the 10th character. It's going to stop right before it. So that method gives us OWHRL. And now sub is pointing to a string called OWHRL. Strings also have a method called trim, and what trim will do is it'll remove all the white space before and after, at the beginning and at the end of the string. So what it's going to do is create a brand new string, just called hello world, without any extra spaces, and it's going to return that. And so we're grabbing the return value and assigning it to a new variable, string trimmed. Now you'll notice that I keep saying that strings create a new string. We'll refer to that again a little bit later, but something to remember, very, very important about strings, is that you can't really change a string. You can only make a new string out of some old string. You can base it on an old string. But strings are what we call immutable. Can't change them. And we'll talk about that a little bit later. Here's another example. We've got two uppercase sending that message using the dot operator. It's creating a brand new string called hello world, which we're then assigning to the upper variable. And one final example, we've got the car at. So here we're trying to get a single character at index 2, and that's going to return the first L. So at the beginning of this section, I reiterated that objects are bundles made out of state and behavior. We know that the behavior is referred to as a method in Java, but objects aren't limited to just having behavior, although some objects might be. You may have an object that only does behavior. It's not as common, but they do exist. Objects typically also contain data, and so this data is referred to as an instance variable. And actually, there's a bunch of different places where we can store data. An instance variable is the most common space for storing data for an object. We'll talk about others a little bit later. Now, instance variables have a lot of different names, and people will use these sort of haphazardly. They'll say instance variables, they'll say attributes, properties, fields, member variables, and so on. State, of course. And a way to see how we actually use an instance variable can be demonstrated here with a point object. So what is a point? Now just think about it, without software for a second. A point is an x and y value on a graph. So what would be the state of the object? Well, it'd be an x value and a y value. So how would that look in code? Here is our code where we are going to use a point object. The first thing we're going to have to do is instantiate an object. So we create a reference variable called point myPoint. So the name of the variable is myPoint, and we've said that it has to refer to a point object. And then on the right side, we're saying new point. And so that will create our point object. Now, if I want to change the state, I'm still going to use that dot operator that we used before. So myPoint.x, myPoint.y. The difference is, notice that there's no parentheses. That's your biggest clue as to whether you're referring to a piece of state or behavior. If it has parentheses, we're referring to behavior. If it doesn't, we're referring to state. So what's happening here is we are taking the literal value of 2 and we're assigning it to the x instance variable on myPoint. We're taking the value 5 and assigning it to myPoint's y variable. And so the question is, when I send a message to an object with state, am I trying to read the value or am I trying to write over the value? And the way you can tell here is whether or not it's on the left side of an equals. If the call, such as myPoint.x, is on the left side of an equals, then that means we're not reading the value. We're going to assign it. In fact, the equals sign, which is the assignment operator, you always read it from the right side to the left. So we're taking the value of 2, and then we're going to assign it to myPoint.x. We're taking the value of 5, and we're going to assign it to the myPoint value of y. And if we had myPoint.x on the right side, then it would be a read if it was on the right side of the equals. So all the assignment is going to happen towards the left side of that equals. So here's my myPoint object. It's pointing to an object on the heap, and at the end of this code, x is now set to 2 and y is now set to 5. So A point is an object, so it probably has more than just data. It's probably going to have methods as well. And like I said, you can tell if you're referring to a field or calling a method just by seeing whether or not there's parentheses there after the dot. Fields, instance variables, state does not use parentheses. And when we have methods, they will always use parentheses, even if no arguments are passed in. So let's look at some examples. And we don't really need to know what these are doing. We're really just looking at the syntax at this point. So reading from right to left, I see we're calling agent.id. So we've got some kind of a reference variable called agent, and we're sending it a message and saying, I want your value. Tell me what ID is. And it says, well, the ID at this moment in time is, and it gives us some value. And then what we're doing is we're assigning it to this variable called int badge. So ID must be returning to us an integer, and we are assigning it to a new variable called badge. Here we're taking what's called a string literal. So we're just writing some text in quotes, and we are taking Marcus and we're assigning it to the name variable that's located in the agent object. Now the first two that we had were fields. They were instance variables, and we can tell because we are using the dot operator and there are no parentheses. Now here we've got agent.spy, and we do see parentheses. So that tells us that we're calling a method. So we call spy, and in this case it's returning some sort of an object whose type is called data. And we're assigning that to a variable called secret. Here's another method where we are calling abort mission. I know it's a method because there's parentheses. And this time we're passing in a parameter. Spy didn't have any parameters that were specified. So with abort mission, I'm taking the argument false and passing that in. Now notice we're not assigning anything to a new instance variable or a new variable. And like, data secret equals agent.spy, there we were taking the return value and assigning it to a variable. We're not doing that with this one. So the question is, does that mean abort mission is returning void, that it's not returning anything? And the answer is maybe. But even if a method says that it's going to return something to us, if we're not interested in it, we can drop it. And so that may be what's happening here, that we were just not interested in whatever was returning. We wanted it to execute its code, do its thing, but we didn't really care about what it was returning to us. And the same thing with agent.showBadge. We really can't tell here if there is no return type, if there's nothing being returned. We're just saying, we don't care. And by the way, if it doesn't return something, then you got to make sure that you aren't trying to assign. In other words, agent.spy that I have right here. If agent.spy says that it returns void, which means it doesn't return anything, then I can't have that equal sign and data secret. I have to get rid of that because it won't even compile. It'll say, sorry, agent.spy doesn't return anything. You can't try to assign nothing to data secret. So going back to agent.showBadge, this is just another method that we're calling. It doesn't take any arguments. And so we still use the parentheses to be able to say, you're a method and I want you to execute your code. So we've seen how to create objects, and we've seen how we can send it messages, accessing and setting fields, accessing methods, and so on. The next thing that we're going to do is just dive a little deeper into how objects are created, and that process is called instantiation. So we've seen that in order to instantiate an object, we use the new keyword. And we've also seen that some objects will allow us to pass in additional information, arguments, when we are trying to instantiate the object. If you think about a previous lecture, we saw an example of a string, and we saw an example of a customer, and in both cases we were able to pass in some text. That is known as a parameter, and we were passing in the argument. So we can do that when we create certain objects. And the reason for this is it allows the object to be initialized with the required data. So think about if we were designing some sort of an object. Let's say we're designing a bank account. Maybe we would force the user to give a an account number when it's created, because it doesn't really make sense for us to have an account with no account number. So a lot of times the business rules, the real world processes determine what it is we are going to insist that someone passes in when they instantiate the object. The other option, of course, is that we don't accept anything. We just say new customer and just have the parentheses. We don't pass in any arguments. And then what would happen is that the user of that object would modify the data after the object is created. We saw an example of this in the previous lecture where we saw the point object. And so we said myPoint.x and myPoint.y. We did that after the point object was created. So we could change what we had done with point, and we could pass in some data. So now the people that created the point object for us to use, or rather created the point class, remember that a class is a blueprint, and we instantiate objects from that blueprint. So someone created the blueprint for that new point, and they've said, well, you can pass in 2 integers to us when you create the object, and then we'll make sure that that point is created with those 2 integers. The first one will be an x value, and the second one will be a y value. So that's what we're doing here. We're saying new point. Remember that the new keyword is necessary to create an object. We specify the type of object that we're creating, and we're passing in 2 arguments, 2 and a 5. And that's going to create a point object, which is being returned to us. And so then what we're going to do is assign that point object to a brand new variable, and that is the myPoint variable that we've created here. So whenever we create an object with that new keyword, what we're really calling is a method, but it is a special method. It's called a constructor. And so here's an example of what a constructor might look like. So this would be in the class. This would be in the blueprint. So we would make a method that looks like this. And so we'll talk more about the syntax a little later, but notice that it has the name point. That's the type that we're trying to create. Notice that it doesn't have a return value. So that's something that's very special about constructors. Not only does it have to have the exact same name of the type, which type is synonymous with class, so it has to have the exact same name, but it can't return any value. You don't even put void. So a constructor's purpose is just to initialize a brand new object. So for the point, what they've done is they said we take 2 parameters. We've got our param number 1, which is an int, and we've got our param number 2, which is an int. And so those are the parameters that this method accepts. We are passing in 2 and 5. So 2 gets assigned to param 1, and 5 gets assigned to param 2. So now that the constructor has these parameters, now what they're going to do is they're going to assign it to the instance variables of the class. Now we don't see the whole class here, but you can imagine that this class has an int x and an int y. And so what they're doing now is they're taking param 1, which value is 2, and they're assigning that to x. And then they're taking the value of param 2, which is 5, and we're assigning that to y. So the constructor's whole purpose is it must initialize the object when it's instantiated with the new keyword. And by the way, constructor methods can only be called during instantiation. I can't just use the point operator that we've been talking about. So I can't use that point and say, hey, let's call the constructor again. You can't do that. The only time that the constructor is going to be called is when you use the keyword new. And because of that, it's going to create a brand new object. You can never call a constructor on an existing object. You can only call the constructor for brand new objects. All objects have to have at least one constructor, but they can have many more if we needed them. And the reason is for flexibility. So let's look at a couple of examples of how we would have some flexibility with multiple constructors. So imagine we've got a type of customer, and we want to give people that use this customer, those that are going to instantiate objects from our customer type, we want to give them different ways to create them, to initialize them. So here's an example where we're passing in 4 different strings. They're going to give us the first name, the city they live in, the phone number, and an email address. We might have another constructor that we provide that says, if you only pass in one string, then it'll be the email address. Or we might have another one that has two different parameters. In this case, we're passing in two strings. The first string is the first name, and then the second string is the city. So as you can see now, we've got three different customer constructors, which gives us flexibility in how we want to build our object. The Java API includes a ton of objects that we're able to use in our own programs. We've seen objects already in this class like string and point. They're already built. All we got to do is instantiate them and then send them messages. And that's fantastic, but that's not enough. We're going to have to create our own object types at some point to suit the needs of our application. And at this point, you've already created an object type. Can you think of what that was? Well, of course, it was Hello World. When we created a class called Hello World, what we were doing is creating an object type. So specifically, class is really going to be the blueprint. And when we instantiate an object of a specific type, this is the blueprint that we're going to instantiate it from. So Hello World was our very first object type that we created. And an object type is called a class. So inside of the class, that's where we're going to specify all the things that objects of this type can do. So we're going to specify the state that will be available and the behavior that will be available as well. So you can think of the class as a template for object creation. I like to think of it as a blueprint for object creation. And then an object, when we say new customer, new point, new string, what we're doing is we're making an instance of that class, an instance from that blueprint. And we can generate any number of objects from a single class, unless the class has been written in a way to prevent that from happening. There's a design pattern called a singleton, which ensures that only one object is made. But generally speaking, when you make a blueprint, when you make a class, many objects can be generated from that single class. One note about classes is that you can only have one public top-level class. You might remember when we were creating the Hello World class that we had to say public class Hello World. And there were no curly braces outside of that class. So it was at the very top level. If you think of your file as sort of a hierarchy, a tree. In this example I've got right below, we've got public class Hello World and then class A Helper class. These are two top-level classes. Neither encloses the other with their curly braces, and there are no outside curly braces that are enclosing either of them. So they're both at the top. And when that happens in the same file, only one of those classes can be public. And the one that is called public, that's going to be the name of the file. So this particular file would be called helloworld.java. Now, when you first start learning Java, you're only going to have one class per file. In fact, that's going to be the majority of the time until you start getting into more advanced programming. So, but just keep that rule in mind. That's one of those things that they expect you to know for the exam. So let's take a quick look at an example of a car class. All right, so what we're going to do is we're going to slowly create a class called a car, and we're going to talk about it. And what I'm going to do now is just make sort of the shell of the class. I'm going to say public class car, and remember all of the code that's going to belong to this car will go inside of the curly braces. So we're going to create this blueprint of a car type. So what I want you to do is just take a quick look at this, and then what I'm going to do is have you take a small quiz just to answer some syntax about the class that I've created right here. And after that, we'll come back and we'll start adding more code to it. All right, let's start to add some state and behavior to this class. Let's start with the state. What kind of things do we want to have in our car? We'll make it simple. We just want to have a color and a type. Now, Java gives us an object that we can use to store this kind of information, and that would be a string. So remember, the string is just text. So we'll create a string color. Can't type color, and we'll put a semicolon. Remember, all of our statements end with a semicolon. And we'll have a string type. So now we've created two instance variables, and we call them instance variables because every time we create an object from this class, when we create an object from this blueprint, that object will get its own color and its own type. And that'll be different from any other object that also is created, any other car object that's created, because they'll get a color and a type as well. So that's the simplest way that we can create a type. We basically say whatever is the type, and then we also include some sort of a name, some sort of an identifier. But there's other things that we can do with our instance variables. We could add some modifiers to the left. Haven't really talked about modifiers yet, except for our example of main, but they modify either methods or fields. And so, for example, I could put the word public in front of this, and we'll talk about access modifiers later, but this simply means color is available to all code in this program. We can also give it a default value. I can say equals blue. So that's optional as well. But we're going to keep it simple. We're just going to have our string color and our string type, and we'll deal with populating the values in a little bit. Now let's add some behavior, which means we're going to add some methods. So I'll make the simplest methods I can. We'll have one called start, which will just print out a string that says get started. And then we'll have one that'll be print description, which will actually print out the color and type. So let's do the first one. Remember that a method has to have a return type. In both cases here, I'm going to say void. I'm not returning anything after the statements inside of this method have been executing. So I'll just say void, and we'll have our method called start. And all methods have to have parentheses, even if you're not accepting any arguments. So I'm going to say void start, and all methods must have curly braces as well. And so now I'll just type out the system out print line, get started. All right, and if I had more statements, then I could add them in between these two curly braces. But I don't. We'll leave it like that. And that's sort of the minimal method that you would, syntax that you would need. The return type, which in this case is void, the name of the method, the parentheses, and then a set of curly braces. I mentioned another method that we're going to use, which is going to be print description. So void print description. And in this one, we're going to do the same thing that we did before. We're going to print out this is a, and we want the color and type. Now, I don't want it to print out literally that string. This is a color and type. In fact, I just want it to be this is a color type. Let's get rid of that word and. So what I want to do is replace it so that this word color actually takes the value from the instance variable and replaces it right here. And I want to do the same thing with type. I want to take whatever the type is, it's going to retrieve it from the instance variable up here and replace that down here. So for example, if we've got a blue sedan, then I wanted to say this is a blue sedan. So how would I do that? So this is what we do. First of all, let's fix up that sentence. This is a color type. Eventually, I will be able to complete a full sentence here in this lecture. So this is a color type. How do I change that? So what I'm going to do is I'm going to close off the string. So don't worry about the red underline. It's an illegal statement at the moment, but we're going to fix it. So it says this is a, and it's going to print out exactly what it says in the quotes. And now I'm going to use the plus sign. And when we're working with strings, the plus sign is a concatenation operator, meaning it's going to take the string and then concatenate it, put it together with something else, some other value. So then I've got color. Now notice that I didn't put color in quotes. And so what's going to happen is colors, the JVM is going to try to resolve what is color, and it's going to look in this method and say, hey, do you have a variable called color? And the answer will be no. And so then it'll ask the class, do you have a color? And really it'll ask the object, do you have a color? And the answer will be, yeah, I do. And so it will replace the word color with that actual value. So I'm going to do the same thing with type. I'm going to just put another plus sign. And we can get rid of that last quote here. So now it's going to print out this is a, it's going to look up color, and it's going to look up type. Now, unfortunately, that would put the two, color and type, right up against each other, so I want to put a space in between color and type. And I'll do that with another string. I'll put quote, space, quote. There's a space. And then I need to concatenate that space with the type. So we add another plus sign. So there we go. Now we've got a class with state and behavior. And before we end this lecture, I want to show you what else you could do with a method. So this is the base syntax of the method, the return type, the name, the parentheses, and the curly braces. We could also put modifiers in front of a method. We've seen public, we've seen static. So we'll talk more about modifiers through the remainder of this course. We could add those to the left side. We could add parameters, and we can add as many parameters as we want. We could say we are taking 3 ints. The only thing we have to do is specify the type, a name, and we comma separate them all. And now we're saying whoever calls start is going to have to pass us 3 integers. But we're not going to take anything right now, so I'll get rid of that. And there's another thing that we can do with methods, but it's called throwing, and it deals with exceptions. That's the very last lecture of this course, so we'll hold off on that syntax. But there we go. We've created an actual class that we can instantiate and use. So we've done it. We've created our own class. We've created our own object type. And when we did that, you might have noticed that the instance variables were at the top and the methods were below. And strictly speaking, the order of the variables and the methods is not important to Java. I could have mixed them up. I could have had a variable color and then a method start and then another variable if I wanted to, and it would compile and it would run just fine. However, conventionally, we typically put the variables near the top of the class, and then we have the methods follow below that. Also conventionally, our instance variables, our constructors, our methods, all of our different types are grouped together, and it just makes it for easier organization and readability. With that said, how do we work with the car class? And what we're going to do is create it just like we would any other object. So we create a reference variable. Here's car, my car. We're going to assign to that a new car. It's going to instantiate an object from the car type that we just created. And we could call that over and over again. We could make as many cars as we need to from that single class, from that single blueprint. And every single instance, every single object, remember an instance is an object, every single instance would have their own color and their own type. So to change the color of the car we just created, we'd say mycar.color equals white. And so we are going to create the color white, and we're going to assign it to the mycar.color. We can do the same thing with the type, mycar.type equals sedan. And then we can call the methods. We can execute the behavior, mycar.printDescription. And what that would do is it would say, this is a white sedan. We could also call mycar.start, and that would just say, get started. And we notice that we're using the dot operator to access the state and the behavior. And you can tell the difference between the two because if there's no parentheses, that means it's a field. If there are parentheses, that means it's a method. Start has a parentheses, so we're calling a method. Color doesn't have parentheses, so we're referring to some sort of a variable. Both of our car methods returned a void type, which said, do your work, execute all the statements that are in your code block, and then you're done. You're not going to return anything to the caller. So we could add a new method or change the one that we have here and change it to print description and change it so that we're actually returning something. So the method would look like this. Instead of it being public void, we would now say public string. So the return type is a string. We are saying that after we execute these statements, we will return a string back to the caller. So what we're doing here is we're creating a string called desk, and its value will be this is a, in this case it would be white sedan, and then we're returning that string. And so whoever calls it can get a hold of that string and store it in a new variable. Now, without that return statement at the very bottom, return desk, the code would not compile. So when you put in your signature, I'm going to return a string, the compiler is going to hold you to it. You got to return something. You got to return a string. Now, there's a couple ways we could get around that, but we'll see those exceptional situations a little bit later. So the return statement here terminates the method. Any code that would be below the desk, return desk, would be ignored. In fact, it wouldn't even let you compile because it would say there's code after your return. It's not going to work. Now, there's always exceptions to these rules that I'm mentioning. We'll talk about conditional statements a little bit later. And so it is possible that you could have the return inside of a conditional statement. A conditional statement means if something's true, run this code. If it's not true, don't run this code. That kind of a thing is a conditional statement. So there is a way for us to have code below return, but in general, just know that any code that's below the return, unless we have these exceptional situations, will never be executed, and therefore it won't even compile. It'll tell you, why are you wasting your time? You're writing code that won't run. So now, using that return type, we can substitute this method call anywhere that we'd use a normal string. So we can do things like this. We can say car, my car equals new car. Now we've got a car. And we can set the color to be silver. We can set the type to be DeLorean DMC12. And now when I call get description, that's going to return that new string. And I can take that return value and assign it to a variable. So now this is a silver DeLorean DMC12. That's the string that will be returned from getDescription, and I can store that in a variable, as I'm doing here, string desk. And then I can do whatever I want with desk. I can pass it into system.out.println, which will then print out this is a silver DeLorean DMC12. If I'm not going to use the variable desk for more than just printing it out, as I'm doing right here, I can even inline this whole thing. I could say system.out.println, and then in the parentheses say mycar.getDescription. And what's going to happen is the mycar.getDescription will run first, and then the return value, which is that string, will then be passed in to the system.out.println message. One thing we didn't do with our car is take advantage of the fact that we can create unique constructors for initializing the object. And just as a remind you, instead of just calling new point, we were able to pass in a x and y value to the constructor. So here we've got a point, my point, there's my reference variable, equals new point, passing in 2 and 5. And that's great because then I don't have to wait until after the point has been created to set the x and y value. And in fact, that can help prevent a lot of errors. You can imagine that it doesn't make much sense to have a point object without an x or y. Or you could argue, well, sure it does. Just let's make it a default of 0, 0. But those are the kinds of things that you have to debate with your fellow developers when you're writing a program. The important thing to know is that we can specify those rules. We can specify what constructors are available to those that are creating a type or creating an object from our type. So how do we do that? First of all, remember that constructors are really just methods, but they're special methods. Constructor methods have the exact same name, spelling, and capitalization of the class itself. And they look like methods, except that they have no return type, not even void. And there's an exam gotcha. Just make sure that the return type for what looks like a constructor doesn't exist. If you're looking at something and you think it's a constructor because it has the same name of the class, but it has the type void, well, now you know it's not a constructor. It's just a regular method. And the only way that we can call constructors is by using the new keyword. We can't use that dot notation that we use for fields and methods. So here is our public class car. We've got our color and type. And here is a constructor. So no return value. We have the name of the class, car, and now we're specifying that we will accept 2 strings. And what we're doing is when we specify the parameters, we say what is the type of the parameter, and we give it a name so that we can refer to the parameter inside of the method. So here we have string C and string T, and what we'll do is whatever that first parameter is that's passed in, we'll assign that to our color instance variable. And whatever is the second one, we'll assign that to our type. We use these constructors simply to initialize data. And again, in this case, we're taking 2 strings. We are initializing the variables color and type using whatever the person passed into us. So how would that work in code? Well, now this is what it looks like to create a car. So the left side is still the same, car, my car. That's our reference variable. And on the right side, we say new car, but this time we're passing in the 2 strings. So we've got silver as our first string and DeLorean DMC12 as our second. And so what that means is silver will be assigned to color and DeLorean DMC12 will be assigned to type. So the nice thing about the constructor is that it saves us this step of having to then take the car and one by one specify what data should exist for that car. And if you think about it, we could make a mistake. We might forget to put the color or the type. When you have a constructor, you don't get that luxury. You can't forget. If I only pass in 1 string to the car constructor, the compiler is going to complain. It's going to say, hey, I looked in this class and there's no constructor that only takes 1 string. So what's going to happen underneath the covers here? So what happens is when we create the car, when we say, in this case, we're saying car, wife's car equals new car, and when we call that, the stack is going to have the variable, and the heap will have some space allocated for the car object. Now, the next thing that's going to happen is it's going to go through and deal with all of the instance variables. Now, instance variables have default values. Talk about that in just a second. But if it's an object, a string is an object, then that means the default value for that instance variable will be null. Now, we've got 2 strings. We've got color and we have type. So both of those will be set to null when it's first created. I mentioned that we could specify a default initialization value for an instance variable. Remember, we looked at our car and I said string color equals blue. Well, here's an example of saying string color equals black. If we had done that, then that null for the color would be replaced with the string black. And then the final step is to call the constructor. And then the constructor would run, and in this case, red and BMW was passed in, so our car would then be a red BMW. So I mentioned that there's some default values. What are those default values? And it really depends on what is the type of the instance variable. And by the way, it's not just instance variables, it's static variables as well that have default values. We'll talk about static variables in the next section. Any variables declared in a method or in a constructor must be explicitly initialized before they are used. Here's what I mean. I've got my car. I can say string color here without saying color equals blue or color equals black. That's okay. It's legal. There is a default value and it's null. Now here I've got a method called printVin, and this is a just a simple method, and I'm declaring a variable called intVin. Okay, now if I try to use that variable before I've initialized it, intVin equals 32. If I don't actually give it a value, then I will get a compile error. I'm trying to use a variable inside of a method before it has been initialized. There are no default values. Here's another example. Here I'm saying string plate inside of a method, and I didn't give it a value right away. It's legal because on the very next line, I'm initializing it, and we're initializing it with a value before we use it. So it's being initialized with A, B, C, D, E, F, and then that plate is going to be used. And so we didn't use the string plate until it had a value. So that is legal. So here are the default values. Any Java object will be null. Any Boolean will be false. Any of our whole number types will be 0. Our real numbers will be 0.0. And a char will be a null character. The \U is an escape code to specify that this is a Unicode character. And so it uses the null Blake character. So now we know how to create a constructor, but a thought might have just passed your mind. You might have thought, well, that's weird. We didn't have a constructor when we first wrote car, but it seemed legal that we could say new car. And that was correct. What we had was something called a default constructor. And so what a default constructor is, it is simply a no argument constructor, meaning that there are no parameters passed in. And what happens is Java looks at the class that you've created, and if you haven't created a constructor, then it provides that for you. It doesn't do anything. It takes no parameters. It does no initialization, but it provides it for you so that calling new car is legal. Now that can actually get you into a little bit of trouble. So let's take a look at our car. Now imagine that we had the car that we've created for several weeks, and there are lots of people that are instantiating objects from our car type. And one of the members of our team comes in and says, you know, it's kind of silly that we're forcing people to instantiate the car, and then they are explicitly setting the color and type after the car has been created. Why don't we just help them out? We know how to make constructors. We'll make a constructor that takes two strings. We'll assign the first string to the color. We'll assign the second string to the type, and then they're good to go. And so they add this constructor to our car class. So given this constructor, what could go wrong? Let's take a look at some code. So someone creates a new car. They found out about the new constructor, and they say new car, silver DeLorean DMC12, and we're good. That works as expected. And someone else writes a call where they say car, wife's car, equals new car, and that worked for a long time. All of a sudden, this code breaks right here, right on this line. And the reason is, well, the question is why? And the reason is that if you create a constructor, as we've done above, we've created a car constructor, then Java will no longer put in the default no argument constructor for you. So in effect, if this car class had been out in the wild and someone made this change, we've effectively broke the class for everyone that was using it, because everyone else would have used this default no argument constructor call. They would have simply said new car and expect it to work, and now it doesn't. So all the rest of these lines, mycar.type sedan, mycar.color equals white, not even going to get that far. The compile error would happen right when we try to call a no argument constructor, because it just doesn't exist anymore. So if we wanted to fix the code, we could go in and just say, well, let's just add a no argument constructor. And it's pretty small, right? We just have the name of the class, parentheses with no parameters declared, and we have our curly braces. And that essentially is the no argument constructor. But one of the questions you're going to want to ask yourself is, do we want to have a no argument constructor? Does it ever make sense to have a car that doesn't have a color and type? Take a look at this mycar.type, mycar.color. What if we forget to issue one of those commands? What if I forget to say mycar.type equals sedan? What's going to happen? Well, now we've got a car with null as the type. Remember, we have default values. Color is null, type is null, until we actually set it. If we say mycar.color equals white and forget the mycar.type equals sedan, well, now we've got a car that has no type. And does that really make sense? So those are the kind of questions we need to ask ourselves. It might make more sense to enforce the constructor we've just created here that says, no, you've got to give us a color and a type. So we've got one final lecture in this section, and it's on the initialization block. So what is an initialization block? It's just a block of code that will be run every time an object is instantiated. It'll initialize that object. We've seen that we already have a number of different places that we can do initialization logic. I can do inline initialization. For example, I can say that the color is green, and that's the default color. We've seen that we can have a constructor. Here's my car constructor. And inside of there, I could also say the color is blue. So the initialization block is yet another place that we can put some logic. And it looks a little weird. It's just two sets of curly braces, and they're kind of floating in space. Everything that's between the two curly braces on lines 6 and 8 would be part of the initialization. So I'm going to add just another color here. You wouldn't normally have color being initialized in all of these different places, but I want you to see what the ordering is and how things are invoked. So let's imagine that someone creates a car. They're creating an instance of a car. They've said new car. So here's what happens. The new car constructor is called, but it's then going to initialize all of the instance variables. So string color is going to be created and string type is going to be created, and they're both going to be null. Then it's going to execute this inline initialization, so color turns to be green. Then the initialization block is going to be executed, and the color turns to red. And finally, the statements inside of the constructor are called. So once it's all done, in this case, the color would be blue. So that's all that an initialization block does. It's just another place for us to do logic. The nice thing about an initialization block is that we can do more complex logic in there than we could necessarily do cleanly anyway with inline initialization. Now, we haven't learned a lot of complex code yet. So you'll just have to imagine that we could write some complex code and it wouldn't lend itself well to an inline initialization here like we're doing with green. And so it's nice is to have just this block of code where we can do that logic. Now you may think, well, okay, fine, but why don't we just put that complex logic in the constructor? Isn't the constructor meant to initialize? And the answer is, yeah, you could. You certainly could do that. But it really helps if you have multiple constructors. I could have another constructor, a car that takes a string color, and another one that's a constructor that's car that takes a string color and a string type, and so on. And so I can have multiple constructors. The nice thing is that the initialization block will always be run for all of the constructors. And then I don't have to repeat myself. That is a kind of a best practice in software. You shouldn't repeat yourself. In fact, the term is DRY, D-R-Y. Don't repeat yourself. If you find that you're having blocks of code that are doing the exact same thing as other blocks of code, try to remove it so there's only one block that's actually executing that logic. And so if I was repeating the same code over and over again in all of my constructors, better to have it in one place. And why? Well, it's easier to write. It's easier to maintain. Imagine that we decide to change our strategy and remove some of the code. I'd have to remember to go into every single constructor and pull out the code we wanted to remove. And that could be problematic. I might miss something. And what happens then is we've got kind of an inconsistent application. Sometimes it's doing what we thought it would do, and sometimes it's doing things we didn't expect. So you can introduce strange bugs when you have inconsistencies in scenarios where you meant to be consistent. So, long story short, initialization block is just another way for us to do some initialization. One final point on this. I mentioned that what will happen when someone creates a new car is that the green would be set before the initialization block is called. And the only reason that's true in this example is because the initialization block is after that green. What I mean is, if I grab this and I cut and paste it and I put it at the top of the class, this is legal. And now what will happen is color and type will be set to null. Then color will be set to red. and then color will be set to green, and then the color of the constructor is set to blue. So the placement of the instance variables and the initialization blocks matter. Okay, that does matter. The constructor does not. Just to illustrate that, if I put this at the very top, so now my constructor is at the top, the same ordering is going to take place. So it's going to create the color and the type variables, set them both to null. It's going to run the initialization block. It's going to keep moving down. Then it's going to set this to green. And then the very last thing is that the constructor is called. So even though the constructor is above all that stuff, it's still going to be called last. And actually, there is one other thing. You can have multiple initialization blocks. That's perfectly legal anywhere that you want. And they'll simply be executed in the order that they're listed from top down to the bottom.
So in the previous section, we were focusing on what is an object. In order to be able to build an object, we have to have something called a class, and that's what we're going to focus on in this section. So we'll be looking at classes, we're going to talk about the concept of a scope, and we'll also finish with a talk on garbage collection.
At this point, you've worked with both classes and objects. Let's just do a quick review of the terminology. So a class is your template, and the purpose of a class is to be a template for object creation. And then an object is just really an instantiation from that template. So we talked about a couple of ways to think about this. The main analogy that I like is a class is a blueprint, and then an object is something you build from that blueprint. It could be a house, for example. Another analogy is that a class is a cookie cutter, and the object would be a cookie. So the blueprint house analogy works pretty well up to a point for understanding the differences between a class and an object. You know, we can look at a blueprint and it'll tell us a whole bunch of information about the house. It'll tell us how many rooms there are and square footage and things like that, but you can't actually live in a blueprint. So really, when we're working in an object-oriented programming language, we predominantly work with the objects that have been produced by the blueprint. So the house is where we actually live rather than the blueprint, but the house was built from the blueprint's instructions. Now, this is kind of where the analogy of a blueprint sort of hits a wall, because one of the things that we can do in Java is tie variables, tie state and behavior, not just to an object, but actually to the class itself. Example of this might be we have a variable that's used to tally how many homes have been created from this blueprint. So this data that would be associated with the blueprint is known as a class variable, and that's different than the instance variables that we've been talking about so far. Another term for class variables is static variables, and the reason we call them a static variable is because you use the word static in code. So let's go back to the car example we've been working with and see how we can add some static members to our class. So what we're going to do now is we're going to add an instance variable called a serial number, or a VIN, a vehicle identification number. And the class here is pretty simple. We've got our color and our type that we had before. And now we've got this new instance variable that's a serial number. So fine, nothing new there other than we've got another instance variable. So now let's add a class variable to this. What we're going to do is pretty simple. We're going to have a class variable that's going to be called car count. And the purpose of car count is that every single time we make a car, we will increment that count, and then we'll take that value and store that as the serial number for the latest and greatest car that we just made. So let's look at the syntax. If you look right below the serial number variable, you'll see int car count. But it doesn't just say int car count, it says static int car count. So static is a modifier, which means this variable is tied to the class itself. So if we have 50 or 100 car objects that have been created and we change the car count, all 50 or 100 objects will see that new value. So with modifiers, such as static, just remember that they always go to the left of the type, which in this case is an int. Okay, so the variable's there. Now how do we access it? In order to do that, you're going to use the name of the class. So here's an example of setting the car count to be 1. So you type in the name of the class, which in this case is car. We still use the dot operator just like we do for instance variables. So dot car count, and we set the value. The most important thing though is note that we are using the name of the class rather than an instance. Now you could use an instance variable to access car count if you'd like. Here's an example of doing that. We've got our car that we've created, a black Ranger, and we're using the myCar variable to access the car count. And this is legal, but it is not recommended. In fact, if you are using an IDE, it'll give you some kind of a warning that says something like, a class variable should be accessed in a static way or vice versa, something like that. Anyway, and it's telling you that's not a good idea. And one of the main reasons is just because when you're looking at the code, it's hard to see that car count is in fact a static variable. And knowing that it's a static variable may influence how you decide to use it. And that's the primary reason. Just want to keep our code as readable as possible. And this sort of obscures the fact that the car count is a class variable. One other thing to note is that the car count variable is going to be both created and initialized not when the object is instantiated, but when the class is actually loaded by the JVM. So anytime that we even reference a car, just putting a reference variable, car, myCar, semicolon. If you do that, then what's going to happen to the JVM is it's going to say, have I loaded this class already? And if it hasn't, it'll load the class, and all the static variables that are in this class will be initialized at that time. So it's available before you even create an instance of an object. And that's just really because the car count is associated with the class. It's not associated with any object, so it doesn't need to wait until the object is created. Instance variables do need to wait. They won't be initialized until you've created a new object from the class. So no matter how many cars get created, there's still just going to be one car count. So going back to our use case, we need a unique serial number. And so we're going to use this car count to achieve that goal. So let's take a look at some more code that we need to write. In fact, what we're going to do is amend our constructors. So at this point, we've got two constructors for car. We've got a simple car, no argument, default constructor, and we've got a car constructor that takes a color and a type, 2 strings. Now what we're going to do is we're going to grab that car count variable and we're going to increment it. And we haven't talked about this operator, the plus. We'll talk about it in an upcoming section, but basically the plus is just going to increment it by 1. And then what we're going to do is we're going to take that car count value and we will then store it in the instance variable called the serial number. And because we want to make sure this happens no matter whether you're using the no argument constructor or you're using the constructor with 2 strings, that code has been repeated. And if you think about what I just said in a previous lecture about dry, don't repeat yourself, you'll know that I'm not a big fan of this kind of code. But we'll talk a little bit later about how we can solve that. So the code will increment the number of cars every single time a car is created. And then it's going to assign that car count to the serial number. And at that point, every single object that we make will have a unique serial number that was created from that class variable. Every single time a car is created, the constructor will increase the value of the car count by 1. And so we know that the car count represents the total number of cars, and therefore every number will be unique. So let's take a look at some code here. This is a little bit of new syntax. I've got a car, and I have then 3 variables that are defined right after it, comma separated. This is completely legal. If I just want to create some variables, and they're all of the same type, then I can do that. You just define the type once, car, and then comma separate all the different variable names you'd like. So now what we're going to do is create 3 different cars. We've got 3 statements here. Each statement is creating a car. And every time we create a car, that car count variable will be incremented by 1. The value will then be taken and put into the serial number instance variable for each car. So now if we take a look at the JVM memory, and you look down below at the very bottom here, right down here, this is where our class lives on the heap. So there's a special area for classes, and you can see that the car has some information about every time an instance is made, what instance variables it should have, but it also has something called a car count. And notice that if you look above in the heap, for car 1, car 2, and car 3, they all have instance variables. They all have color, type, and serial number, but they do not have car count. So that means any time car count needs to be accessed, they're all going to see the same number. And anytime car count is changed, that will change for all instances. And if there are no instances, that's okay too. The class still lives in the heap and car count is available. So we have car count before any objects exist. We have car count while objects exist and they all see the same car count. And then we also have car count even after all of the objects have been garbage collected. Static variables are just one type of class member that we can add. We can also add static methods, and just like a static variable, they belong to the class itself. And the way we define a static method is also the same way. We use the exact same modifier, static, and put that right in front of the method. Another term for static method is a class method, and we differentiate a class method from an instance method, just like the variables. But let's remind ourselves of what an instance method is. So that's basically everything that we've seen so far. We've got here our car class, and we've got a color and a type. And if you take a look at the drive method, you'll notice that it doesn't have the word static. And that's it. That's all we have to do to say it's an instance method is just leave off the word static. If we put static in front of there, then it would be a class method. So this method drive is going to print out a message. And the question would be, okay, well, how do we call drive? So here's an example of us creating a car. Car C equals new car. So we've got our reference variable of C, creating the car type. And the correct way is listed first. So C.drive. That is the correct way to call an instance method. We must, in fact, it's not just an option. We must use the instance variable to send the message and say, hey, we want you to run that drive method. What you can't do is what's on the third line, car.drive, car being the name of the class. You can't do that. And the question is, well, which car are we supposed to call this method drive on? Now, if we go back to the method here, you might think, well, what does it matter? I mean, it's always going to print out the same message. Put her in gear and drive it like you stole it every single time that drive is called. It'll be the same for each object, so what does it matter? But the thing is that I shouldn't say most, but often instance methods will have instance variables. Think back to that getDescription method we were looking at. And so getDescription was saying this is a color and type. And so it had to look at the object that was associated with that method to know exactly which color and type you were expecting. So if I have a car and another car, they're going to have different colors and they're going to have different types, potentially. So the instance method has to know which instance object it is associated with so that if it needs to get some instance variable data, again, it knows where to find it. So let's create a static method. As I mentioned, all that you have to do is add the static keyword to a method, and now there it is a class method. So here we've got reset car count. We put the modifier static in front of the return type, and that is a requirement. The any modifier that we use has to be to the left of the return type. In this case, the return type is void. And all that this is going to do is set the car count to be 0. Now, how do we call it? To call a static method, you just need the name of the class. Now let's look at a couple of examples. So if I have a car instance, I've created car C equals new car, and I say c.resetCarCount, well, much like accessing a static variable, this is legal, but it's a little confusing for those of us that are reading it. It looks like resetCarCount is an instance method, and it's not. It's a static method. It's a class method. So what you really should do is use the name of the class, car.resetCarCount. That's what we would call the proper way to code this. Now, there are some rules regarding the use of static methods. The most important rule is that a static method does not have access to any instance variables or any instance methods. And if you think about it logically, it makes sense. Let's look at an example, and then we'll talk about it in more detail. So we've got this example here of resetCarCount, and it is a static method. Now, the first line where we're setting car count to be 0 is perfectly legal. Car count is a static variable, and so it's available. It's not a problem. But color is something that belongs to an instance. So the question is, which of the instances are we changing? Which car should be changed to blue here? You may even be in a situation where no car object has even been created. In that case, it's even stranger. We're trying to change the color of a car that doesn't even exist. Car count, totally legal. It belongs to the class itself. It's initialized when the class is loaded. It's going to be alive before any objects, during any objects, and after any objects have been garbage collected. So the static method has access to that variable, but you cannot call any instance variables or any instance methods. And by the way, if you forget this rule, no problem. The compiler is going to tell you pretty quickly that you can't do that. Okay, so that's pretty much it for creating a static method. The question is probably now, what's the point? And if that's your question, that's good. That's a fair question. So really, static methods have two primary purposes. First of all, they're used to access class variable data. Now, of course, we could access class variable data from an instance, but it's just generally considered more appropriate to use a static method when accessing static data. We may even have a scenario where, we need to access the data before any objects have been created or after they've all gone away. So if we had to have an instance method, that would be a problem. We would need at least one object around to be able to access the data. And we don't want to do that, right? We don't want to just create an object simply to access class variables. We want to be able to read and change them as we need to. And the second reason is similar to the first, but not quite exactly the same. So with the first reason, I was saying that if you want to access a static variable, that it's nice to just have a static method to do it. The second reason here, which says static methods provide functionality without the need for an object instance, what we're really saying there is that you may have a class that provides functionality, that has methods, and maybe it's not accessing any static variables at all, but it just provides a service, and it doesn't need to rely on instance data, on state that would be associated with an object. So a good example of this would be mathematical formulas. Let's say that I have a simple add method, and I take two parameters, your first operand and your second operand, and we add those two numbers together. And so do I need to have state to do that? I don't. You've just given me the two numbers I'm going to add together. I could then return the response, and we're done. Our transaction with each other is finished. Did we really need to make an instance for that? And the answer is no, not really. So if you look at the Java Lang math class in the Java API, you'll see that's exactly what they do. They have a bunch of static methods that say, give me the data that I need and tell me what you want me to do with it, and I'll handle it. But you don't need to make an instance to access that functionality. Now, you want to be a little bit careful with this. There's a lot of people that would argue, you really shouldn't have classes that only have static methods. There's, of course, a lot of debate in the software world about how to write good software. But just keep that in mind that is a topic of debate. In general, this is an object-oriented programming language, so we really should be using objects as much as possible. And when using objects, that means using instance data and instance methods. All right, let's look at another construct that's related to static, and that's the static initialization block. So the static initialization block is similar to a regular initialization block, and just as a reminder, let's do that. Let's make a regular initialization block. So I'm going to put in my two curly braces here, and we'll say that color is equal to green. So there's my initialization block. And what we learned before was that the initialization blocks are executed in the order that they are listed. So what is a static initialization block? All that it is adding the word static, and that is a static initialization block. Now, what does it mean to be a static initialization block? It means that the code in this block will only be executed once when the class is loaded. Now, that's different than a regular initialization block. This will be executed every single time a new object is instantiated, every single time. So static just once, and the regular every time an object is initialized. Now, notice that there's a red line under color. It's complaining here. So what's the problem? The problem is that a static block, just like a static method, can only access static variables and static methods. The problem here, what it's complaining about, is it's saying color, what color? There is no, which particular instance do you want me to change the color on? I have no idea. And let's just look at the actual error message. If I put my mouse over the error, it says cannot make a static reference to the non-static field color. So it tells you right there, it can't do that. However, I can access car count. So if I say car count equals 3, the error goes away and everything is fine. I can call static methods from a static block. So I can say static car count. And here I'm calling the static method that's on line 10. That's perfectly legal. Can I call print description from in here? Nope, can't do that either. And it's the same reason as why we couldn't access color. Print description is an instance method. And remember what I said about static methods. You can't access anything that's instance related from a static method. That includes instance methods, that includes instance variables. And I think seeing the code here makes it really obvious as to why. If I was to call print description, what is print description it's going to do? It's going to say this is a color. And so it's going to want to go to an object on the heap and find out what is the color of this object. But the problem is there is no object at this point. This static block is going to be executed right when the class is loaded. There is no object. So there's no color that's been created yet and no type that's been created yet. So that's why it won't let us access print description. And finally, just like having instance initialization blocks, the static initialization block can be repeated. So I can have another one down here, and I can add another one down here if I wanted to, and so on. And each would be accessed in the order that we've listed them from top all the way down to the bottom. So that's really it for a static initialization block. We use them just like we would a regular initialization block, but to access static state and to initialize that static state. The next few lectures are going to talk about a keyword called this. And it's a slightly confusing subject at first, but by the end of the next few lectures, you'll have it mastered. Let's go to our car class, and we'll see how the keyword this is used. So we've got a color and type, which we're setting to a red Celica. We've got two methods, get description and customize. Now, let's just talk a little bit more about what happens when we call customize. So let's say we've created a car, my car, and we say mycar.customize, and we pass in blue, and now we say convertible. So what we're going to do is turn our Celica into a convertible. What happens is when we call the method customize or any other method, that on the stack a frame is placed, and that frame is going to contain all the variables that have been declared with this method, so local variables. Now the first variables that are declared with a method are always the parameters, Every single parameter is a brand new variable that's been declared with the method, so they're going to be added to the frame. So I'm just going to kind of type here. Let's say this is my frame. This is my customized frame, and it has a new color, and it has a new type. So let's say we call it and we're passing in blue and convertible. So what's going to happen is new color is now equal to blue and new type is equal to convertible. And those are the only variables that are going to be added to this frame. There are no other variables inside of Kustomize that are brand new, that have been declared. Color and type here, they're referring to existing variables. And I know that because there's no reference type in front of them. If I was to write string color, well, that's actually creating a brand new variable because there is a type here. So when you have a reference type, that's a brand new variable. When you don't, you're referring to one that's already been declared. So what happens then when we execute line 19? So new color is going to be searched for. They're going to say, I have to find the value of new color. And because it's an assignment operator, we are evaluating from the right side, and then we'll do the left side. So we say, let's get the new color. And it says, frame, do you have a new color? And the answer is yes. I've got the color blue. Great, we know what the value is. Now we need to assign that value to a variable called color. And it looks in its own frame and says, do I have something called color? And the answer is no, we do not. So then what it does is it goes to the object on the heap, and not just any object on the heap, it's the object that had invoked this method. So let me show you what I mean. I'm just going to put just some code here. This is not where the code would necessarily be invoked from. I just wanted you to see the code. But what we had done is we'd said my car equals new car. We instantiated our car object. And then we said my car.customize, and we passed in blue, and we passed in convertible. So that's what kicked off this whole method being called. So when it can't find, in this case, color in the frame, then what it's going to do is it's going to say, well, what object actually called me? How was I invoked? And that object was my car. So it's going to go to this new car object on the heap to find out what the value is of color. So let's get rid of this. And so now what we have here is we've got our color that's on the object on the heap, and we're going to set it to blue. And then we continue on and we do the same thing with new type. It says, do I have it in the frame? And the answer is yes, it's convertible. And then it concatenates it to type. It says, do I have type in the frame? And the answer is no. So it goes to the object on the heap and says, do you have a type? And the answer is yeah, it's a Celica. So now I've got a new type, which is a convertible Celica. And then we're going to assign that to type. And it's once again, it's going to ask, frame, do you have type? The answer is no. It goes to the object on the heap and changes that type to be a convertible Celica. So now when we call get description, it's basically going to do the same thing. A frame is going to be added to the stack. It's going to have a variable here called desk, and it's going to put together this string. So it's going to say, desk, do you have something called color? And the answer is no. So it goes to the object on the heap. And the object on the heap says, do you have color? And it says, yeah, it's blue. So this is a blue. Does the same thing for type. Finds out it is a convertible Celica. So desk is then going to equal, this is a blue convertible Celica. And it will return that description, and in this case, it'll print it out to the console. So this worked as expected. This just, it changed the color, it changed the type, and when we printed out the color and type, it, used the new values. So that's what we would expect to have happen. That's kind of the happy path. So where does this come into play? Well, I've mentioned that every single time it's trying to resolve a variable, what it's doing is it's looking in the frame to see if it can find it. We can bypass looking in the frame, and we can say, just go to the object on the heap. Go directly to the object on the heap. And we do that by saying this dot. So here's this dot color, this dot type. Can even do it in initialization blocks, this dot color, this dot type. Down here in my customize method, this dot color, this dot type. We could even do it in front of a method, an instance method called this.getDescription. And what it's saying is, don't even look on the frame. If there's a value there, I don't care. I want you to skip it, go directly to the object in the heap. Now, for this program, it's not really going to have any effect. The net effect is going to be exactly the same whether we use this or not. So why do we have it? Here's the reason. A lot of Java developers, by convention, don't like having new variables for the parameter names. So what they do is they have the same. Instead of having new color here, I'm going to have string color. And actually, let's get rid of all of this stuff I just added. And what I'm going to do now is change new color. I'm also going to show you here something that you can do with Eclipse. I'm going to change color. Rather than just typing it here, I'm going to right-click, and then under Refactor, I'm going to choose Rename. And what happens now is that as I type the new thing, look at line 20, you can see that it's changing with me. So it finds all the variables that this would be referred to, and changes the other ones with it. It's not just a simple search and replace, it's actually contextual. It makes sure that it's changing things that are referring to the name that we are changing. So there I've got color. Oh, it's telling me there's a name collision. That's okay. That's the problem I'm trying to show you, actually. And I'll do a refactor, rename, say type, same kind of problem. So they're warning us already. It's saying this is not a good idea. Well, why is it not a good idea? Notice that this is underlined. Notice that we got those warnings. And what it's telling me is the assignment to variable color has no effect anymore. And the question is, why? Why isn't it having an effect? Are you trying to tell me that when we pass in blue and convertible, that we're not creating a blue convertible Celica? And the answer is yes, that's exactly what I'm telling you. And in the next lecture, you'll see why. In the last lecture, we left with a problem. The problem is that when we change the variable names, the parameter names in Kustomize, that we got a warning message. It said, this is not doing anything. And we're thinking, what are you talking about? We're calling Kustomize. We're passing in a blue convertible. What's the problem? Well, let's take a look and see what's happening underneath the covers and then see how the keyword this can help us. So here's a main method, and we're creating a car. Just saying, simple car, my car equals new car. And when that line is done executing, this is what we've got on the stack and the heap. On the stack, we've got a frame, and all the variables from the main method that have been declared are in this frame. And yes, I didn't list the string array. Note that there is a string array that's passed into main, and I did not list it here, but I'm doing that to keep this focused. It would be in the actual frame. But we do have my car, and my car is referring to an object on the heap called a car, and its color is red, and its type is a Celica. So then what we're going to do is we're going to call Kustomize on this car that we just created, and we're going to say mycar.kustomize. We're going to create two new strings, blue and convertible, and those are going to be passed into Kustomized. So when Kustomize is called, it's going to get a frame on the stack. And this is what the stack would look like. We're passing in blue to color, so color is referring to blue. Type is referring to convertible. And then once we call the first line of code, it's going to start by looking on the right side. This is an assignment. So it's going to evaluate the right side so it knows what to assign to the left. And so it says, oh, we've got a color. I need to find the color locally first. And it goes right to the Kustomize and says, do you have color? And the answer is, yes, I do. It's blue. Great. We now know what the value is. It's blue. Let's assign blue to some variable called color. And once again, it goes to the frame and says, do you have something called color? Because I've got a value I need to assign. And it says, yes, I'm color. And it says, fantastic. Your new value is blue. But the old value was also blue, so we did nothing. We had no impact. Take a look at the object on the heap. Nothing has happened here. And the same kind of thing happens with the second line. It says, do you have type? And the answer is yes, convertible. Now it's a little different because we are making a new string, and so it's concatenating type with type. So now we're having a string called convertible, which is just pretty bizarre. And we are assigning that to this type. Okay, so what does it look like when we now call getDescription? So here's getDescription. Color is pointing to blue. Type is pointing to convertible, and once again, car is looking exactly as it did before. So now getDescription is called, and it gets a frame on the stack. It has one variable that's been declared inside of here that's called desk. And so now this behaves a slightly different way. What's going to happen is it's going to say we need to create this string, so what's the value of color? And it's going to go into the frame and say, do you have color? And the answer is no. Now it's not going to go up the stack, or in this case down the stack, to find the variable color. What it does instead is it says, if I can't find it in this frame, then I will go back to the object that I've been spawned from. Remember, we had a car that we called getDescription on, so now we're going back to that very car, which is this object on the heap. And it says, do you have a color? And the answer is yes, red. And the same thing happens with type. Yes, the answer is Celica. So once this is done, and we've got this new string, this is a red Celica. And so now getDescription has the desk variable, which is pointing to this is a red Celica, and that's what gets printed out in the system out print line. So the message is wrong. This is a red Celica. The type of the car is wrong. We still have a red Celica. Nothing was changed in the way that we had intended. And once getDescription is done, it's popped off the stack, and its string is eligible for garbage collection. And customize finishes, and so it's popped off the stack. And the blue and convertible are eligible for garbage collection. And we're left back where we started. We're right back where we started. So calling convertible had no impact on the car whatsoever. So the problem is, whenever you're calling a method or whenever you're defining a method and you create parameters, if you have the same name of a parameter, same spelling, same capitalization as an instance variable, then within that method you are hiding that variable. So how do we fix it? Well, we could go back to the using different names. I could go in and change this color. Let's refactor it. Rename to new color. That actually did a little bad refactoring because they were both starting with the same name. So here I could just say color equals new color. That fixed that. And now they're different names, so we're no longer hiding the value. When it looks for new color, it's going to find the local variable, new color. When it looks for color, it's not going to find it locally, so it'll go to the instance variable on the heap. And that's one way to solve it. But like I said, there's a convention where Java developers are not happy with that. They like to use the same parameter names rather than coming up with brand new ones. So that's where the keyword this comes into play. If I say this dot on the left side, then what's going to happen is when it evaluates the right side, it's going to say, hey, frame for customize, is there a color in there? And the answer would be yes, in this case. And then when we assign it to this dot color, it's not even going to look in the frame. It's going to assign it to the instance variable. So this always means bypass the local variables and go right to the object. This means this object. And that's one of the forms of this. Let's also fix type. What we wanted to do here is take the new type, concatenate it with the type that was on the heap, and assign it to the instance variable on the heap. So now it's all fixed. That's, as I said, one of the cases of using this. We're going to look at another one where we use this to chain constructors, and that's in the next lecture. Now you know how to use the keyword this and why you'd want to. It's really to disambiguate so that when you have a scenario like I've just created here, line 14, we've got a constructor and it's got two parameters, color and type. And color and type happen to match the same spelling, the same capitalization as the instance variables above. And so when I try to set them and I say color equals color and type equals type, that is really not doing anything because it's always going to find the local variable first. So if I want to refer to the instance variables, well, then I just put this dot right in front of them. So now I've got this dot color, which is referring to the instance variable, whereas this color is referring to the local variable, the constructor's color. And same thing with type. But that's just one of the ways that we can use this. There's another use case in which we would chain constructors together. Now let me show you the problem, and then we'll talk about what it means to chain constructors together. So here are two car constructors, and what they're doing is they're incrementing car count, and then they're taking that value of car count and setting it to be the serial number. And that's happening in both constructors. Now, if you remember what I said about dry, don't repeat yourself, you'll know that I am not happy with this. That we shouldn't really be repeating the same logic over and over again, because what if we decide to change our strategy? I'm going to have to find every single place that I implemented this strategy and make the changes. And if I miss one, well, now there's some inconsistency in my application, which might produce a really hard to find bug. So we really want one source of authority. How could we do that? Well, you already know one way. We've got an initialization block. And initialization blocks are always called before the constructors are executed. So I could move all that logic here. I could just grab that car count, put it in here, and now I can get rid of it in the second constructor as well. And that is actually a good, legitimate strategy. That'll work. But how about this case? What if I create another constructor? So car, and I'm just going to have string color on this one. And in this particular constructor, I don't actually want to have the serial number incremented. Why not? Maybe it's not ready to be shipped yet. This is just something where we're just creating a prototype car or something, some sort of use case where I don't want this stuff to be executed. This car count plus plus serial number is equal car count, and it will, because an initialization block is always going to be called before each constructor. So that is a problem. So what are my other options? Well, let's put everything back here. Okay, so now I've got my car count inside of the two constructors. What's my other option? Well, what I could do is I could decide that one of these constructors is going to be the source of authority. Let's say that I decide this constructor is going to be the one that maintains that code. So what I could do is call that constructor. I could say car, and now it would execute car count plus plus and the serial number, and everything looks good, except for that red line. Okay. Now let's ignore the red line for just a second. What I'm doing here is what's called chaining a constructor. So someone's going to call this car constructor, and then we're chaining it to this constructor just by invoking it. After that car constructor is done, then we're setting the color of the car and the type of the car, and we continue on. And if I want to make any changes to this car, I can go in here and make the changes in one place. So the strategy is good, but the syntax is bad, and that's why I'm getting the red X. Instead of saying the name of the constructor, what you do is you say this. No dot, just this is parentheses. And that will then say, well, which constructor should I call? And it looks at the parameter list and it matches it. Now in this case, there are no parameters, so it's looking for the no argument constructor. Now we could go the other way. Let's put this back. I could call into this constructor if that seemed reasonable. And the way we would think we would do it, I'm going to do this invalid first. We'd say car, and I'd pass in green, try to spell that correctly, and then I'd pass in convertible. All right, and then that would call into this constructor. But unfortunately, of course, we know that you can't do that. You can't use the name of the constructor. So we'd say this. And now it's going to look for a constructor that has two variables that are strings. This one takes two strings, so this is the constructor it's being chained to. And now it would execute this code. Which one is the right way? Well, it just depends on what your business case is, you know, how you want cars to be constructed. There's no real right answer to that. Putting this all back now, one thing I want to show you is the rules of this. So if I put here this, everything is fine, but watch what happens if I put it as the second line. We get a red X. You can't do that. When you are going to chain constructors together, it has to be the first line. That's the first rule. The second rule is that I can't just place this inside of methods. So this is strictly for chaining constructors together. I cannot place it inside of a method. I'll get an error. So that's it. That is the keyword this, the reason we have it, the way you should use it. And granted, it is a confusing subject, so if you have any questions, please do let me know. We've discussed the concepts of the stack and the heap a few times already, and these are really important concepts because they give us an idea of why code is behaving the way it's behaving. And it's really important to understand the stack and the heap, to really understand how memory is being organized. Because if you don't, you'll write code that makes poor assumptions, which will be either buggy or at least inconsistent at times. So in order to write really good code, to write quality code, what we have to do is understand concepts like the stack and the heap, and a related concept, which is scope. So scope is the idea of when will something become alive? When is it available? And while it's available, who can see it? Who has access to it? And at what point will it go away? So that whole concept is known as scope. Now, there are different levels of scope, and there are a number of different ways to identify the levels of scope. So, for example, we can look at curly brackets in our code, and anytime you see curly brackets, that's a code block, and that's defining a new level of scope. We'll look at some code in the next lecture where we can see how the brackets play into that usage. But let's talk about the different kinds of variables that we've had so far. Now, variables are either going to store a literal value themselves. They might store an integer or a real number or a character or a Boolean. Or the variables are going to store a reference that is referring to an object on the heap. So what we'll find is that these variables become alive at certain times and they go away at other times and so on. So understanding the different kind of variables is important to understanding this concept of scope. So we've got variables that are inside of a class. Those are going to be our instance variables. And remember that depending on who you're talking to, some people might refer to them as fields, attributes, properties. They all mean the same thing. And I should say that sometimes there are languages or APIs that will differentiate between those terms. For example, someone might say that a property is not just an instance variable. It is an instance variable that's backed by two methods, one method to get the variable and one method to set the variable. So, when I say that they're the same, I'm saying that in general usage, people tend to refer to them, sort of interchangeably with these terms. But do keep in mind that there are some frameworks, there are some languages and APIs where they will differentiate a difference between a field and a property, for example. So, with that said, we've got the instance variables that are inside of a class. We have variables inside of the class, but they're using the modifier static. And when you see the modifier static, that means it's going to belong to the class itself. And then we've got variables that have been defined inside of a method. And the method variables, they can be placed in two different areas. One would be as parameters to the method. Those would be brand new variables that have been declared for this method. And then we've got this example here of getDescription. So anytime you see the reference type next to the variable, like we've got string desc, then that means that this is a brand new variable that has just been declared. When we look to the right of desc where we've got this.color and this.type, we're not really seeing a reference type here. We're just seeing the variable names, color and type. So those are not they're not new variables that have been declared. We are referring to variables that already exist. So if we were to say what method variables do we have here, we really only have one in getDescription, and that's desc. So when we're referring to scope and we're referring to these different variables, we have different words for them. And it's really to define their scope. I mean, at least in large part. As I mentioned, we've got instance variables. We have static variables. We have local variables. And local variables, most people think that that means they are method variables, but not always. Later on, we're going to learn about control structures. We're going to learn about loops. We're going to learn about conditionals. And when we learn of those particular control structures, we'll see that they have curly braces and they define their own local scope as well. So just remember that anytime we see those curly braces, we're defining a code block, and that's really defining a new local scope. Another term that you may hear used is this term most local or local most. And all that they mean is that there is a variable that will be used before some other variable will. We saw an example of that a couple of lectures ago when we were talking about this. And we saw that, for example, if there is a variable called color inside of a method, and there's a variable called color that's an instance variable for the object on the heap, that the most local variable, the one that's in the method itself, will win. That's the one that will be found. And so that can influence, once again, whether our program is working as we expected or not. We saw that example where we were accidentally doing nothing. We were saying color equals color. And when we did that, it had no net effect. So that is another term related to scope, most local. And what we're going to do in the next lecture is just take a look at code and see how the curly braces really help us identify these levels of scope. So the type of variable is really going to help us understand its scope. We can also see it visually when we look at code as well. And so I want to show you what that looks like. Let's start with a car class. And the car class has two curly braces. And everything that's inside of those curly braces belongs to that car scope. So we add some instance variables, and we can see that the instance variables are part of that car scope. So they are available to everything that's inside of that car. We've got color, we've got type, and we've got serial number. Now, instance variables are created, or available, I should say, once an object has been created. So the object is created, the instance variables are added to that object, and now they're alive, and they're available to any code that's been declared inside of this car scope. We also have a static car count, and static is a modifier, which means it belongs to the class itself. So as soon as the car class has been loaded, and all that we mean by that is that at some point code was written that declared the term car, declared the type car. And Java says, whoa, car, what is this? Let's make sure that I know what car is. And it looks to see if it's been loaded already into memory, into the heap. And if it's there, great. And if it hasn't, then that car class is loaded into memory. And at that time, all of the static methods and static variables will also become alive and become available. So the car count belongs to the class. It's created with the class and available to all the code that's in the car scope as well. Then we've got our car constructor. And you see that we've got two more curly braces to define what code, what statements belongs to the car constructor itself. That's another code block. So any variables that are declared inside of this constructor are local to that constructor. They are not available outside of that scope. So we've got string C and string T. All parameters are always local variables to the method or constructor. So those are brand new. Looking down, I see color, I see type, I see car count and serial number. Those are not defined inside of the constructor. Remember, it has to have the reference type for it to be declared or defined inside of a method or a constructor. So just C and T, that's it. Those are the only local variables. They become alive when the car constructor is called. And as soon as the car constructor is finished, those two variables disappear. That's the only time they're alive while the car constructor is being invoked. We also have getDescription. The only local variable inside of here is that string desc. All of the other variables, color and type, are referring to instance variables. And so Remember, all the instance variables and static variables, they belong to the car scope. So everything that's in the car scope, such as the car constructor and the getDescription method, have access to those variables. However, anything that's been declared locally inside of a code block, like a method or a constructor, then those become alive when the method or constructor is called, and then they go away once the method or constructor has finished executing. So as you can see, the curly braces kind of give us a sense of who can see what. So now let's bring this back to the whole concept of the stack and the heap. Whenever we call or invoke a method, that method call is going to get its own frame on the stack. And we've seen that. We were seeing that a frame gets added for every method call. And then once the method is finished executing, the frame is popped off the stack. We also say that the variables that are in those frames fall out of scope. So let's look at that type of code again. Let's look at a class here called a bank account. And now the bank account's a pretty simple class. We've got a balance that's of type double, so $150. That's an instance variable. We've got the method withdraw that is declaring a parameter called amount, so that'll be a local variable that's used. And then it'll just take the balance, subtract the amount, and store that as the new balance. Now, suppose the following code was run to use these bank account objects. We've got an ATM, and there's our main method. So on line 1, it's going to create a bank account. On line 2, it's creating a new local variable to main called amount, set to 20. On line 3, we've got our account withdraw method. So if you remember that the bank account has that method withdraw, we're passing in the amount. And then we're going to just print out a message, cha-ching. So now let's take each of those lines and see what is actually happening on the stack and in the heap. So in line 1 of the main method, first of all, main has a frame which is put on the stack, and we declare a new variable here, account. So bank account equals new bank account. So the value of that account variable is a reference, and the reference is referring to this bank account on the heap. Now the object in the heap has a balance of 150. So then what we're doing is we're adding another variable to the frame in the main scope, and that is amount. The amount is set to 20. Line 3 is where we say account. Using that dot operator, we want you to execute the method withdraw, and we're passing in the amount. Now what happens is withdraw gets its own frame on the stack. And so you'll notice that there are now 2 variables called amount, both with the value of 20. We'll talk a little bit more about passing by value and what's actually happening when we're passing in amount. But for right now, just note that we have 2 separate variables. They happen to have the same name, though they didn't need to. And they have the same value at this moment in time. But they are 2 separate variables. So when that method is executed, it's going to subtract 20 and change the balance, and you can see that our balance is now 130. And then at that point, the withdraw method is finished. And when a method is finished, it gets popped off the stack. So the amount equals 20 that was a part of that frame is gone. It just doesn't exist anymore. And so at the end, it prints out the message cha-ching, and we can now see that the bank account's balance has been changed to 130. So the main lesson learned here is that any variable that has been declared inside of a method gets put into a frame on the stack, and that's when it becomes alive. It is not alive, it's not available until it's been placed on the stack. And as soon as the method is done executing, it will be popped off the stack and is no longer available as well. We will dive deeper into the stack and heap. We'll talk about passing by value when we get to the string section. But for now, that's the important lesson, how long local variables will live. And the lesson is, once again, they live as soon as the frame has been added to the stack. And as soon as the method is done executing, they go away. They're popped off the stack at that time. This is the example that we left with in the previous lecture. we have a frame that has a variable called account, and account is referring to a bank account object on the heap. Now, for a minute, imagine that this method wasn't main, that we're in some other method, and the program is going to continue to run. So what would happen when the current method that we're looking at finishes? Well, we already said that it'll be popped off the stack, and so the variables will go away. In that case, the only thing we would have left then is this object called bank account. And it's really not available at that point. We have no way of accessing it. We have no way of using it. And so it's just kind of wasting space there. Now, in other programming languages, we would have had to explicitly destroy that object while we still had the account variable. And once the account variable goes away, we wouldn't really have any way to access it to destroy it. And that creates what's known as a memory leak. It's occupying space, but we can't use it. It's just a waste of space. So question is, how does Java deal with that? What do we do to get rid of the bank account object? And with Java, we're pretty lucky. The Java runtime environment will manage the memory for us. We never actually have to destroy an object explicitly. There are a few gotchas that we're going to talk about in the next lecture. It is possible to create what is the equivalent of a memory leak, and we'll talk about that. But in general, there is this program that's running, the garbage collector, and it's going to handle most of the big issues of memory leaks and so on for us. So what's going to happen is the garbage collector will run. It will look at each of the objects in the heap. It will determine which of the objects are no longer being used. That is to say, there's no longer a reference that is pointing to it. And once that happens, it'll get rid of it, and the whole process is known as garbage collection. So when does it run? How do we make it run? It's going to run on its own terms. Now, there are some ways to configure the garbage collector. You can choose specific algorithms that you want your server to use. But for the most part, it's just going to run when it wants to and not run when it doesn't want to. There is a command that you will hear about. Let me switch over to Eclipse. I'm just going to write it in the middle here. There is a command called system.gc, and you'll see that that's also sometimes talked about in regard to the exam. GC is standing for garbage collector. It's a hint. It's a hint to say, garbage collector, I think you should run. But it's actually just a hint. It's just a suggestion. And the garbage collector can choose to ignore it if it decides that now is not the optimal time for it to run. So just remember that if you see any kind of questions that ask about, does this cause the garbage collector to run? The answer is it might, but it is not guaranteed. So the garbage collector runs. It finds an object that has no references pointing to it, and then it removes it from the heap. Now, in that previous example, the object was no longer referenced because the frame fell out of scope. All the variables that were defined in that frame went away, including account. So this is kind of known as an indirect dereference. What we're saying is that the reference just automatically went away because the method finished. Now, let's look at some other code here to see how we can explicitly do a dereference. What I have here is a customer. So we're creating a new customer, and then what I'm doing is I'm taking the same variable C and I'm assigning it to a different customer. And what ends up happening is this. Whenever we change the reference, the old object is no longer being pointed to. It's no longer being referenced. So eventually, if nothing else is referring to the customer at the very top with the ID of 10394, then that will be removed. The garbage collector will take care of and get rid of that for us. Now, changing the reference is only one of our options in terms of dereferencing an object to make it eligible for garbage collection. Another thing we can do is set it to null. And let me just show you an example. So let's say I've got a car, my car equals new car, created a car object. Sure, I could say my car is now equal to another car, and the first car that was created would be eligible for garbage collection. But you don't always have to keep changing the reference to some new object. You could also just say, my car equals null. And if I do that, null means nothing. It means that the reference is just completely removed. And so if nothing else is referencing the car that was created in line 21, now that will be eligible for garbage collection. So that's one way that we can explicitly remove a reference if we want to. Now the fact is, I'm in this method getDescription, so with what we've learned about the stack and the frame, is that the myCar variable will exist when the getDescription method is called. And as soon as the getDescription method is finished, the myCar variable is popped off the stack. We say it falls out of scope. And so then presumably nothing else would be referring to the car we created in line 21. And so that would eventually get garbage collected as well. Garbage collection is pretty cool. It really saves us from a lot of headaches that typically accompany manual memory management. But that doesn't mean we can just be completely complacent. It is possible for us to introduce our own leaks in memory. And let me show you an example. So I'm just going to make a very, very simple example here. I am going to create a variable for a car. And we'll just call it myCar. It's just an instance variable that we'll keep. Let's make it even worse. Let's make it a static variable for some reason. Why is that worse? Because anything that we assign to myCar is going to live for the whole life of the class. So I'm now going to make a static method. I've got a static method called, let's just say, do something. And let's say someone passes in a car object. Let's call it car. All right, so I've got a very simple method. Someone's going to call it. They're going to pass in a car. And all that I want to do is print out the color of the car. So let's say that I assign now my car to be car. What I'm doing is I'm taking the car that was passed into this method. I'm assigning it to the static variable my car. And now I'm going to do a quick printout of the message. The color of the car is, and we'll print out the car color. All right, now let's think this through. So the method is called do something. Someone passes in a car. We're assigning it to the variable myCar. We're printing out the car and we're done. So what happens? The car parameter certainly disappears. That particular variable exists as soon as the do something method is created, invoked. It adds the do something frame to the stack, and one of the variables there would be the car. So that variable goes away as soon as the frame is popped off the stack. But because we assigned that object to myCar, and myCar is a static variable, well, it's going to sit there for pretty much ever. It's going to sit there until we pass in a new car and replace it with something. And the question we have to ask ourselves is, did we need to do that? I mean, we're not even really referencing it here. Maybe we're referencing it in other code, and it makes perfect sense to do that. But if we are just storing the variable that was passed in, and we are storing it in the static myCar, then we're just wasting space. So we've created what's kind of a manual memory leak. So if for some reason you are working with this myCar, you'd want to make sure at the very end you would say myCar equals null. So that way we could we could clean up the myCar that we had temporarily stored in there. Now this method is a little silly. We're not even doing anything with myCar. Maybe we would have said myCar here. We could have done that. So we're working with the myCar. We're just going to want to make sure that we clean up after ourselves in that case. So garbage collection, it's going to handle most of the big problems for you, but don't get complacent. Lazy code, poor code can introduce its own memory leaks. And in this case, the memory leak is nothing more than just we have a variable that we're not even really using.
When we write code, we're going to want to organize that code, and we organize Java code into something called a package. So in this section, we'll cover packages, we'll talk about the concept of a class path, and we'll also talk about bundling our applications into a compressed file called a jar.
If you happen to have a bunch of music files on your computer, I want you to think about how are those music files organized. And of course, it doesn't have to be music files. It can be anything. If you've got a collection of files, how do you organize them? For music, I have a sort of a top-level music directory, and inside of there, I'll have folders for all of the different artists. If you open up one of the artist folders, you'll see more folders for all of their album names and so on. And I do that to organize my music. Well, Java has the same concept. They want to give you a way to be able to organize your classes, and they call this organization packages. So a package is something that'll make it easier to find and use all the different Java types you're going to be working with. So classes. Later we're going to learn about interfaces and enumerations, but basically all the structures that we're going to work with in Java can be organized. So that's one of the reasons we use packages. The other reason is to avoid naming conflicts. One of the benefits of object-oriented programming is the ability to use libraries. Libraries of code that maybe you wrote for yourself and stored away, maybe someone else wrote, but we have access to all these objects that we can reuse in different applications. Now imagine that you've written a class called a customer, and you're also using a library that has a class called a customer. The question for the Java platform is, when you say, I want to instantiate a customer, which one did you mean? Did you mean the customer you made, the customer that's in the library? When it can't differentiate which class you're referring to, that's known as a naming conflict. And what happens is we are going to assign a name to our package, and that package name gets concatenated with the name of the class. So it becomes what's called a fully qualified name. And now that helps us have unique names for every single class in our application. You might have a package name of my stuff, and the other group has a package called our stuff. And now you really have two different customers. You have my stuff customer and their stuff or our stuff customer, right? So it just helps us avoid naming conflicts. And also packages are going to help control access to the code. Now, when you do the lab, you're going to see this firsthand, but there is a way in Java for us to say the code that's declared in this class is only available if something is in the same package with me. If the code has been written and it's in some other package, then we shouldn't have access to this code. So that's abstractly what a package is. If you want to think more concretely about a package, think of it just as a folder. It's a directory. And they are used to bundle groups of related types together. Now, what are the related types? That's up to you. There are no rules about how you organize your folders, just like on your computer. You know, I just described to you how I organize my music. You might do it a completely different way. So the organization of your packages, totally up to you. But as an example, maybe you have a security package. Maybe you have a package for data access, for persistence. Maybe another package for formatting, and so on. So how do we create the package in Java? Well, the first thing that you're going to do is create the folder to hold all the code, or folders, I should say. And that's if you're doing it manually. If you're using an IDE, there are other ways to create packages. You just simply say you're creating a new package, and you'll have experience with that in the lab. So once we've got our folder set up, then we just have to specify as a statement, as a Java statement, that this particular class belongs in this folder, in this package. So in this case here, I've got a package transport semicolon. Now that package statement has to be the very first non-commented line of code. We'll look at comments a little bit later. It's a way of saying this line shouldn't be interpreted as code. It's just text for the developer to read. So you can have comments above this if you need to, but the first line of actual code, the first line that's a statement, should be your package statement. So package transport semicolon. Now, of course, like a folder on your file system, you're not just going to have one class in every single package. I mean, you might, but it's not common. So typically, you're going to have another class in the package, and the rule is that for every class that's in a package, the name of the class must be unique. So here I have a unique class. I've got something called truck, and it's been added to that transport package. Now, it's not very common to just have a single name for a package. Normally, we're going to have a hierarchy of folders to store all of our code. And we do this for a couple of reasons. Again, code organization, but also the naming conflict that I mentioned. Imagine that you're creating some application that has a transport package and you have a car class. You're using a third-party library. They have a transport package and also a car class. So even though we've got packages in that scenario, we haven't really gotten rid of the naming conflict problem. So what we typically do, this is a convention that most Java programmers follow, is we start our package structure with our domain name. Now, I work for Intertek, and Intertek has a domain name of intertek.com. So what I would do is I would take that intertek.com, and that would be the start of my package name. But what we also do is we reverse that so that it's com.intertek. And the reason we do that will become obvious a little bit later, but we're going to introduce in just a little bit a term called importing. And so when we have everything organized with all of our coms first and our orgs second and so on, our import statements become a lot easier to read. So you'll see it in action in just a little bit, but just for now, know that the convention is to take your domain name to make sure it's unique for the start of your package, and then reverse your domain name. So that's what we've done here. We've got a package, com intertek transport, and if you look at the image below, you'll see that we've got a folder called com. Inside of there, we've got a folder called intertek, and below that, we've got a folder called transport. And so the way that we represent that hierarchy in the package statement is using a dot. So com.intertek.transport. And that's describing this structure. And it's really important that the class lives exactly where you say it's going to. Otherwise, when the class loader is looking for the class, it won't be able to find it. So when the car file is compiled, the compiler will find or create these three folders. Again, the com folder, the intertek folder, which is inside of com, and then the transport folder, which is inside the intertek folder. And it's inside of that transport folder that we'll find the bytecode, the car.class. Now that we have a package name, remember that our fully qualified class name becomes the package plus the name of the class. And that can really become a pain to type. As you can see above, we've got a reference type variable of com.intertek.transport.car. And when I want to call the constructor, I have to use that same fully qualified name. So sure, we've got uniqueness. Sure, we've got a nice structure for all of our code in terms of the file system organization. But what a pain to type. Well, the good news is that you're not going to have to keep typing that. We have an import statement, and this is what I just mentioned previously in terms of why we like to reverse our domain names. So what you do is above your class, but below any package statements, you write import, and then you put a space, and then you put the names of the classes that you want to reference here. So in this case, we are importing com.intertek.transport.car. And what's going to happen is when the Java platform runs into the lines car, my car, and new car, what it's going to do is say, can I find this car? Where would I look for it? And so it will look in the package that it's currently running in. It will look in java.lang, which is part of the Java API. And then it will also look in case you've specified specifically, here's where car is. And that's what we've done. We've said very specifically, car is in com, in a subfolder of com called intertek, in a subfolder of intertek called transport. So that's what the import statement is doing. It's helping the Java platform resolve where the car can be found. Of course, we're not likely going to just be using one car or one class. We're probably going to have a lot of imports, and we may be importing a bunch of things from the same package. So the way that we handle that is we can use a wildcard. So here I've got import com.intertech.transport.star. And by putting that star, the asterisk, then that means get everything. I want to import all the different classes that are in this particular class. And so now I don't have to have separate imports for car and truck. It'll just look in the transport folder and it will find them. With that said, a class can have as many import statements as you need. Here's an example where we've got two packages, wildcard package imports. We've got the Java AWT.star. We've got Java util.star. So it's going to grab all of the classes that are in those packages and not really grab them. It's just that when it's going to try to resolve the variables in car, that's where it's going to look first. And also we have a specific class here that we're importing java.net.url. So I kind of corrected myself there. I said it grabbed, that's grabbing all those classes. And the reason I corrected myself is because I don't want you to worry about, if I have a package with 1,000 classes, is my code suddenly going to become huge? What if I'm just using one class from that package? And the answer is there, you don't have to worry about it. This is not like an include statement that you might have seen in languages such as C++. The import statements do not actually make your bytecode any larger. All that it's going to do is allow you to type less. And by less, I mean you don't have to type the fully qualified name of the class over and over again. Now, imports that are package imports can make the compile take a little bit longer. But that's about it. The compilation time might be impacted, but the size of your application will not. So using the wildcard is fine. It's not going to grab every single class that's in there. It's just going to be used so that when the Java platform hits a variable, it'll say, I know where I can look to see if I can resolve its actual type. But there are some rules with the asterisk. First of all, the asterisk is just representing the package that you've listed. It can't be used to match a subset of the classes, and it can't be used in a recursive way where it would go into any of the sub-package or nested packages as well. You have to use that asterisk for every single package. Here's an example of something that won't work. We can't do partial wildcards. I can't say import transport.a star, and I would assume the goal here would be we're trying to just import anything that begins with the capital letter A. That's just simply not legal in Java. And this won't do anything either. The Java API begins with a package called Java, but there's nothing in just that folder. If you looked in the Java folder, there's nothing there. There's other subfolders there. Shouldn't say there's nothing, but there's no classes available. So if you said import java.star, that's not actually going to import anything. You'd have to specify the specific Java directories, the specific packages that you want to import, such as java.util or java.io. Now, what happens if you happen to have a reference variable called customer, and it can be found, a customer class can be found in multiple packages that you happen to be importing with a wildcard? Well, first of all, it won't compile. You'll have to resolve it. And what you do is you make sure that the customer you actually want to use, that your import statement for that customer or for that object doesn't use a wildcard, that you explicitly state it. So if I've got a customer class in both COM Intertech Consulting and COM Intertech Training, and I want to use the training one here, note that I've got the wildcard for consulting, but I've explicitly named training customer. Now, up to this point, you haven't listed any imports, but you've still been able to use code, right, that you haven't written. So where did that come from? Well, first of all, you have access to two packages by default. The first is the package that you're currently in. You just have access to all the code that you're currently in. There is a way to actually prevent code in the same package from being able to see each other. But by default, if you're referencing something that you have the ability to reference, and if it's in the same package, you do not have to import it. You also have implicitly the java.lang package. So anything that's in part of the Java API that's in the java.lang package, you have access to. And you're going to use those things over and over again, all the classes that are in java.lang for pretty much every program you write. For example, we've got system. We've been typing system out println quite a few times. That's part of the java.lang package. We've got string. String is also part of the java.lang package. So if you're accessing code that's in the same package, you don't need an import, and if it's in java.lang, you don't need an import for there either. We're organizing our classes into packages, and once we have a really big application, we're going to have lots and lots of classes. We're going to have lots of packages, all organized nicely on the file system. So the question is, how does the Java platform know where to look for those classes? Like as an example, we have a car class, and the car class is stored in a transport folder. Now that transport folder is a subfolder of Intertech, and Intertech is a subfolder of COM. Now we've got that com/intertech/transport folder structure. That's all well and good, but how does Java know where to find that tree? What if we have a directory structure that's C:\Java? Again, I'm doing a Windows here, but let's say we've got a Java folder right off of C. And underneath that, that's where we have the COM Intertech transport hierarchy. How do we tell Java that it's got to start looking in that Java directory? And the way that happens is we have to tell it. We have to tell it where to look. And we do that through the class path. Now, class path is a system variable which will allow us to tell the compiler and the class loader where we're storing all of our classes. The class path can contain multiple directories. It can also contain jars, which we'll talk about in the next lecture, and it can also contain zip files. So we're going to talk about that in just a bit, but we can start to concatenate all of these directories and jar and zip files using whatever operating system path separator we would normally use. In other words, if we've got a class path system variable and we are on Windows, we would separate each of the directories that it should look in with a semicolon. If we're using some form of Unix, then we would use a colon. So that is the class path variable. And you don't need to list, we wouldn't need to list COM, Intertech, transport. We would need to list the parent directory that includes COM, Intertech, transport. Because what's going to happen is, you remember we had a package statement. And when we list that package statement, it's specifying what that hierarchy is. It's saying car can be found in transport, which is part of the com.intertech.transport hierarchy. So once Java can find that root directory, in this example that was C Java, once it can find the Java folder, then it knows where to find car. It'll see there's a subdirectory called com and a subdirectory of that called Intertech, and so on. Now we can set it up as a system variable, or we can pass in an argument when we're using the compiler or using the command line Java program. So here we've got an example of saying Java C, and we're using the argument -classPath. And so what follows that is going to be the places it should look for the directories. So we're saying that all of our packages are going to be in C:temp my classes. So start there and then use the package statements to figure out specifically underneath my classes where all the additional classes you're about to compile happen to live. Now this is a Windows example, so there's a semicolon and then a dot. The dot simply means, oh, and also look in the directory that we're in right now. Remember that with Java C, that's our compiler. So the very last thing that we have listed here, someclass.java, is the name of the class that we're going to compile. Now, although I said that you can create a class path system variable, an environment variable, it's not actually recommended that you do that. Why? Well, because most projects that you're doing will have unique class path locations. And if you don't change that, you might be looking for code in an outdated directory, or it might just not even find the code that it's looking for. So because you're constantly having unique class path locations, it doesn't really make sense to set up one for your entire system. Also, if you use that -classPath option, the argument to Java C, then it will ignore the class path environment variable anyway. It's just going to completely ignore it. And most IDEs also ignore the environment variable as well. So, when you first learn about ClassPath, they always give you that example of setting up the ClassPath system or environment variable, and you certainly can do it, but it's really not that necessary. And the good news is when you're using a tool like Eclipse, for the most part, all the classes that you're using will automatically be added to the ClassPath. And if you happen to be using some class that's somewhere on your file system, there's a very easy way to add it to your build. Most of our applications are going to be a combination of many Java classes. And so we're probably going to want to bundle them in some sort of way to send them off to people interested in the application as a single compact file or a library that they can use. And the way that we do that is with what's called a jar, a Java archive. And so it allows multiple files to be stored in a single archive. And really all that it is it's just a zip file. It's a zip file with a different extension. So instead of .zip, it's .jar. And typically a jar file will contain class files, although there can be some other resource files that are also associated with your application. So like if you have images or property files, those will be contained in there as well. But really it is just a zip file, so you can put anything that you'd like in a jar file. In fact, when I used to create jar files long time ago, if I didn't have access to the command line utility, which comes with the JDK, I would use some kind of a zip tool. I would zip up all my stuff. I just go in and I would change the extension. Or if I wanted to see what was inside of a jar, I would use some kind of an unzip tool. So why do we want to use a jar? Well, one of the reasons is security. We could digitally sign the contents of the jar file, and then people could check, make sure that the contents hadn't been altered on its way from me to them. It's one reason we can do that with a jar. Easier to sign just a whole jar rather than each individual file. And speaking of each individual file, compression is a big thing. It'd be a total pain to have to download 50, 60, 70 different classes. And also, by putting them together, it makes them smaller in size. Think of a zip file. It's going to compress, so that will reduce the amount of space and the time needed to download it. It's a lot easier to version packages. It's a lot easier for me to say, here's a new jar and it's version 1.2, rather than saying, here's 18 different classes that you need to replace from your current program. Much easier to just give a new jar and give it a version number. Jars are also portable, and all that means is that jars are a standard part of the Java platform. So the Java platform understands how to work with jars. So that's what we typically do. We take our class files, we create a jar, and that's what we distribute. Whenever you hear someone refer to a library or an API in Java, typically that means it's going to be one or more jar files. In fact, the whole Java API that we've been using is distributed in a jar file. If we open up the JDK, look in the lib directory, we would see a tools.jar. And if you open up the tools.jar, you would find that we've got your Java library. The JDK does come with a tool for creating our jars. It's in the bin directory, and it's simply called jar. It allows you to create the jars, and the syntax is you start with the name of the executable, the jar, and then we have some options. The C option is saying that we want to create a jar. The F option is saying when you're creating the jar, make sure all that output goes into a file rather than to the standard output. The standard output would be the console or the command line that you just executed this command. Jar file is going to be the name of the jar file we're trying to create, so it can be any file name. Once it's done, let's say we call the name Intertech. The name of the file then would be intertech.jar. You don't need to put the .jar extension. It'll automatically add that when it creates the jar. So we would change this to say jar cf intertech. By convention, jar file names are given a .jar extension, but you should know it's not actually required. And then finally, the input files. This is a space-separated list of one or more files that we want to include in the jar. We can also, though, contain a wildcard symbol. So if any of the input files that we list are directories, then all the contents of those directories will be added to the jar recursively. In other words, we can list the top level directory and it will grab everything below that as well. So although it's nice to have that command line tool, you don't actually need it. I mean, in the real world, you're going to be using an IDE. And so there are tools in the IDE to take care of that. And we refer to this whole process as jarring up our files. And most IDEs are going to provide some kind of a tool to help you with that. We're looking at Eclipse, and Eclipse has this export feature. Most IDEs are going to have something similar. And then it'll just guide you through a wizard to decide which of the files in this project do I want to include. And then finally, the nice thing about the jar, besides just distributing all our code simply with one big file, is that everything in the jar can be added to the class path very, very simply. So imagine that I've got a vehicle.jar, and we've got our car and our truck in there, and we've got a bunch of other packages and a bunch of other code. I don't have to then put every single top-level directory that's in there. I could simply say class path equals, and then specify the class path to that vehicle.jar. And automatically, everything in that jar will be a part of the class path. If I happen to have multiple jars in a directory, I can load them all with a wildcard, the asterisk. So here I'm loading every single jar that happens to be in Java lib. One note about the asterisk, however, is that it's only used to load jars. If I need to load .class files and they happen to be in the same directory as the jars, then I'd have to list that directory again without the asterisk. So again, imagine I've got a directory called Java, and underneath that is lib, and I've got a vehicle.jar in lib, and then I also have some loose class files. This is what my class path would have to look like. I'd have the Java lib directory listed, semicolon to separate the next directory, and then I have Java lib /* and that would grab every single jar that's also in that directory.
As soon as you start coding on a team, the first thing that team is going to notice is your coding style. So the coding style is just really the aesthetics of how you lay out your code, how you organize your code. And so we're going to talk about some of the conventions that are popular and common in the Java programming language. We'll also talk about commenting your code, how to create the documentation that we saw in the first section, the Java docs. We'll show you how to do it for your own code. And we'll also talk about primitives. So primitives are the little building blocks that we can use in our classes.
Whether you realize it or not, your code has style. And by style, we're simply talking about the aesthetic way that you write your code. Now, of course, there's the syntax of Java, which you just have to follow. But there is the ability in Java for us to sort of organize our code in a way that's aesthetic and legible. And the reason that we can do this is that Java is a free-form language. So you can put whitespace anywhere you want. And we do it for, again, aesthetic reasons, but also for legibility. So what we mean by white space is that you can add spaces, you can put a horizontal tab, you can have line terminators, form feed characters, etc. And you can use all of this white space to arrange your code. So if you want to make your code readable, you should follow some simple spacing conventions. And I will tell you there's really no agreement in some of these conventions, but I will tell you what they are. So let's start with the curly brackets or curly braces. Same thing. I know I use that term interchangeably, brackets, braces. I mean exactly the same thing. So with our curly brackets, there's the option of where we're going to put the opening curly bracket. So here we've got the public void foo method, and notice that we've got our opening curly brace on the same line as the signature. This is the classic C way of laying out code blocks, and a lot of people in Java have adopted this as well. But other people argue this is actually a little hard to read. Now think about what the purpose of the curly brace is. It's to show ownership. It's to show scope. This is a code block. And when we start to have lots of nested constructs, it can be a little difficult for your eyes to kind of make this diagonal motion to figure out where it starts and where it ends, especially as you have nested constructs inside of this. So the alternative is what you see here. So this is our public void foo method. And notice that we've got our opening curly brace on the next line. Now, when you have lots and lots of code, this is nice because it just sort of indents everything in a way that some of us would argue makes it more readable. So I prefer this particular style. Not everyone else does. I think it's easier to read. I think it makes lining the opening and closing brackets easier, figuring where the brackets should go. If I accidentally forget a bracket, it's easier for me to see where I missed one. But that's an opinion. That's just not a fact. And I guarantee you, whichever standard you choose here, someone's going to argue against it. Now, in addition to spacing, there's some naming conventions that you should consider using. So remember that Java is case sensitive. And so we can use this case sensitivity to have different naming formats depending on what it is we're creating. So for example, class names. Class names are always capitalized, and if they have multiple words, each word is going to be capitalized. So here is a public class car, notice the capital C. Here's compact disk with a capital C, capital D. Java course material with a capital J, capital C, and capital M, and so on. And that's a pretty standard naming convention for Java classes. That is known as camel casing. And this is specifically upper camel casing. So with the capital I, the capital J, the capital T. And you can see they call it camel casing because of the humps. Now, lower camel casing is just a little bit different. We have the first letter lowercase. The rest of the words will have capital letters. And so there's a lower camel case where I is now lowercase, the J and the T are capitalized. Later, we're going to talk about some structures called interface and enums, but they follow the exact same convention as classes. They use upper camel casing. Now, unlike classes, we have variables and methods which will use lower camel casing. So for example, here's my dog, all lowercase. Now here's my dog with a lowercase m and a capital D. Here's my neighbor's dog, capital N, capital D, and so on. And you can see we use it for variables and we use it for methods, and that's a standard, lower camel casing for variables and methods. And then package names are conventionally all lowercase. So here's a couple of packages. Notice that they're all lowercase. And this is nice for when we are creating our fully qualified name. The name of the class is capitalized, but everything else leading up to it is lowercase. And it just gives a nice, consistent look and feel. So those are just a couple of the conventions to consider. There are some rules that we have to follow when we are choosing things that you might think you have more control of. Like, for example, the names of your classes, the names of your packages, and so on. You certainly do have control over what they will be, and you have control over the capitalization, but there are some rules for what we call identifiers. So a name of a field is an identifier. The name of a variable is an identifier, a method, a class, and so on. And so here are the rules for when you're choosing a valid identifier. They have to follow 3 rules. First of all, they can only contain numbers, letters, underscores, and dollar signs. Absolutely no other character. And even though it's okay to have a number in an identifier, it can't start with a number. And it can't collide with a Java reserved word. So here's a list of the Java reserved words. These are things that you can't use as an identifier. Now, Java's a case-sensitive language, so strictly speaking, we could capitalize some of the letters in here and then it would be valid to use. But you really shouldn't do it. People would find it confusing. And you may also be a little worried, like, wow, do I have to remember all these words? And the answer is no, for 2 reasons. One, you're going to find that you use most of these words daily as you are coding, and so you'll be aware that they have another meaning. We've only had a few sections in this class so far, but you've seen many of these identifiers. At some point, you've seen things like public and true. We've seen char, double, import, new, return, Boolean, class, and so on and so on. So most of these anyway, are words that have specific meaning in Java. There's some that don't. Here's goto. There's no goto in Java, but they've made that a reserved word. So, and let's say you forget. Well, the compiler is going to tell you. All right, let's jump to code for a second. So I'm going to just create a variable here. So I've got my int x. And what are some of the things that we can use for the identifier of x? Well, we know that we can have letters, we can have numbers, we can have underscores, and we can have dollar signs. So even though this is a pretty ridiculous identifier, here we'll give it a value too, equals 5. It's a pretty ridiculous identifier, but it's legal. Remember that one of the rules is that you can't put a number at the start. See how I get a red X? It says, nope, you can't do that. I can't add other characters that wouldn't be legal. Won't let me do that. And it won't let me do reserved words. So what's a reserved word? Boolean is a reserved word. Can't use that as an identifier. What else was a reserved word? Public. Won't let me do it. So that's what I mean when I say you don't really have to memorize them because the compiler is going to tell you. But if you're taking the exam, yeah, you're probably going to want to make sure you're at least aware of all the words just in case for that exam. So, and even though I can't put the word public, I could put a capital P. Remember, it's case sensitive. All the reserved words are all lowercase. So that's legal, but you really, really, really shouldn't do that. It's confusing code. Now let's talk about comments. We can add notes to ourselves and to other developers, and we can do it right in the code. And so what a comment is a section that says, this is not executable code, just leave it alone, ignore it, it's really for the developer. And there are a couple of comments that we can do. First of all, there's the line comment, which is the // And so anything that follows the / is a comment, and it won't be executed. But as soon as I go to another line, this is not a comment, and we're going to get a little syntax error. So the // only lasts till the end of the line. Now, what if I wanted to comment out a whole bunch of stuff? And when I say comment out, sometimes when we want to remove code, but we don't want to delete it yet. We want to keep it there just in case, or if we want to add it back later, we can comment out some code. So the way we could do that is, first of all, I could put // in front of every line. And what I've just done right now is comment out this particular constructor. But we're using an IDE, so we get a little bit of help. We can highlight this, and I can do Control/, or on a Mac, Command/. You can see that it added the comments for me. I can do the same command again, and it will toggle. You can also find this up in the source menu. So there's the toggle comments and so on. We can do block comments. Rather than having every single line have a comment, we can put a /*, and then the IDE here is putting an extra star. So there is a star here, and there's another star. And every time I'm hitting enter, it's adding a star. We don't actually need that there. That's just an aesthetic thing that the IDE is doing. Strictly speaking, all that we need for a block comment is a /* at the top and a // at the bottom. And now everything that's in between here will be treated as a comment rather than just a single line. And that's known as a block comment. If I was to add a nested block comment, so I'm going to add another right in here, that's a problem. What's really happening is that it's assuming this is the start, this is just text, and then it hits what it considers to be the end of the comment. So then you've got this other end tag sort of floating there. So you can't have nested block comments. It's just not legal. And then there's one final type of a comment that you will use in your code, and we'll look at that next. That is the java.comment. Now we're going to look at arguably the most important type of comment, and that is the java.comment. And these are comments that are used to produce the Java.doc API. If you remember, right in the first section, we were looking at the API so that we could see all the different methods and variables that existed for the string class. you can make your own API documentation, and there's a special kind of comment to do it. So just as a reminder, we could add block comments, right? /*, and we end with */. The difference between a block comment and a Java doc comment is really just with the opening tag. So a Java doc comment is going to be /*. It still ends with // but it starts with /*. And the reason that we have a separate comment is that when we run this through the JavaDoc tool, which I'll show you how to do in a minute, it will look for all of these comments, block comments that start with /*, and it will turn it into some documentation. So let's start to add some documentation to this car class. So above the class, and by the way, this is what you do in general. You choose the thing that you want to add a comment to, and then you put the JavaDoc comment right on top. So I want to put some information, general information about the car class. So I'll do /*, and notice that it added a tag there, @author. There's a number of different tags that you can use, and in the resource section for this lecture, I've included a URL that shows you some of the different tags that you can use as well. So what I'll do is I'm just going to leave the author as Intertech. Let's say that this class creates a car that is able to print out its description. Not entirely exciting, but hey, that's what it does. And let's put a little bit of information on some of these variables. So we've got a color. So here I've got a color, and I'll say that the color is the color of the car. And do another one here on the static car count. Used to generate a unique number for the serial number. Okay, whatever it is that we want to do. And so now I've got this constructor. And so with the constructor, I'm just going to do **, and we'll say this builds a green sedan. Now here's a constructor that has two parameters. Let's put a Java comment there, and notice it adds a tag called param. So I can say this creates, can I type? This creates a custom car, and it says what is param C? This is the color. What is param T? This is the type. Let's do one more, get description. Now we've got another tag that was generated for us, the @return. So this is going to create a string that is the description of the car. And what is it returning? It's returning the generated string. All right, I've got some comments in here now. And so what I'm going to do is run the JavaDoc. Now, if you go into your JDK bin directory, there is a JavaDoc tool in there as well. But we'll just use the IDE. So I'm going to go up to Project, and down here is Generate JavaDoc. Click on that. And now we've got a JavaDoc wizard. And some of these options will make a lot more sense a little bit later. But one of the most important things it's asking me is, what do I want to include? I'm not going to include everything. I'm just going to go into the default package and just make sure car is selected. I don't really have any comments on the other classes, hello world, and course examples, but you know, we could make our entire project JavaDoc, which is pretty cool. So I am just going to say finish here, and it's generating over on the left. You can see a doc folder was just created. So I'm going to open that up, and I'm going to click on index.html. And there it is. There is our website. It's pretty simple. We didn't add a lot of comments, and we don't have a lot of packages or classes, but that would all be listed here if we had enabled those features. But here it tells you this is the car. It creates a car that is able to print out its description. The author is Intertech. Here are the different fields that we have. We've got a static car count. It tells me what it does. We've got our color. If I scroll down a little bit, we've got our two different constructors. This builds a green sedan. And if I click on one of these, it brings me a little bit farther, which tells me the rest of the documentation. This creates a custom car. And notice that that param tag took that information and just put it in a separate area. So now we know what the parameters are. C is color, T is type. Here's that @return that we had. It's returning the generated string. So that's JavaDoc, and now you have no excuse to not generate comments and generate some documentation for your fellow teammates. If you've been doing the labs from the previous sections, then you have run into some primitives. In fact, you've been using ints quite a bit. We had 3 pieces of state in the MyDate class. Each was an int. We had int year, int day, and int month. And it's really important when you're learning Java to understand the difference between objects and primitives. So there are 8 primitives in Java, and these primitives only have state. There's absolutely no behavior. And it's not just a lot of state, it's one piece of state. We say that a primitive has a value. The reason that primitives were included in Java was to make programming easier, nice little building blocks to use, and to speed up execution. Now, when we look at the 8 primitive data types, they fall into 4 different categories. We have our integer types. This is byte, short, int, and long. We have 2 floating point types, float and double. A Boolean type, that's just a bit. It's a true or false. And then we have that character type, the char. And those 8 types, that's it. That's all that we have in terms of primitives. There's other languages like C that have more options. Like, for example, you might have an unsigned int. An unsigned int would be an int that the range of numbers is 0 to some positive number. In Java, everything is signed. And so signed means that it's a range that starts in the negative and moves all the way to a positive number. And they do that to ensure portability, really. The primitive types are guaranteed by the JVM to work the same on any platform. So as it says here, an int is an int is an int. Different operating systems and machines will treat primitives in the same way, and that's going to help with Java's portability. So let's take a look at how we declare primitive types. Whenever we declare a variable, we have to have some sort of a type. It might be an object type. In this case, it'll be a primitive type. So there is a byte. Notice that it's all lowercase, byte B. And we have short as a type, so short S. And just to be clear, the B and the S there, those are the variables. Those are the identifiers that we're using. They're not the types. Byte is the type, short is the type. We have int, int I, long, char, float, double, and Boolean. So those are our 8 different types. Now, let's just talk about each one, and starting with the Boolean, because that's probably the easiest to understand. A Boolean's just a bit. It can hold one of 2 values, true or false. A Boolean cannot be converted into any other type, and that's, again, different than some languages. In some languages, we could treat false as a 0. We can convert things into other types, and we can actually do some of that in Java, but not with a Boolean. A Boolean's either going to be true or false, and that's it. Boolean is not a limited type of int like it is in C. It's just a completely unique data type that we have in Java. And so here's an example of using a Boolean. If you've never seen a conditional statement before, this might seem a little weird. We are going to talk about conditionals in the next section. But let's just take a quick look here. We've defined our Boolean B, and we're setting the value to be true. Notice that there's no quotation marks there. It's just the word true. And this is the conditional. The conditional is where we say if, because we're going to check something. If this is true, then I want to do something. So you say if, and you have some parentheses. And in the parentheses, we are passing in that Boolean variable. So we're testing, is B true? The parentheses are the test. If B is true, then we're going to print out B is true. Else, if B is not true, then we'll print out B is false. It's the basic idea of a conditional and how a conditional can be used. Now, just once again, we will talk more about conditionals in the next section. Character type is pretty simple. It is a Unicode text character. To support Unicode, the Java character is 16 bits. It includes ASCII. Now, ASCII is a subset of Unicode. The last 8 bits of Unicode represent ASCII if the first 8 bits are 0. So let's look at some character literals. Here is the literal A. And so you can see the single quotes, not double quotes, but single quotes. That is going to represent a character. There are some escape characters as well. So whenever it starts with a backslash, it's an escape character. And escape just simply means we're escaping its normal meaning. So we're saying that \n, we're escaping the n. We're saying don't treat it like a character n. It actually means something important. And so \n means a new line. \t represents a tab. And what if we actually need a backslash? Well, we got to put 2 backslashes, \\. We can also do hexadecimal notation if we have to include some Unicode characters that we don't have access to on the keyboard. And the way that we do that is we use \u, and then we have 4 numbers. The numbers are hexadecimal numbers, and so then we can choose a Unicode code point that represents a character. Just to summarize Unicode, you can think of Unicode as, think of it like a big table. And there are these codes on the left side, and then the characters that the codes represent on the right side. So if we saw a code of 61 in the Unicode book, we'd see the character that it's representing is A. So in this case, we could use that Unicode character, that Unicode code point, to be able to print that character. Now, why wouldn't you just type the letter A? Well, you probably would. This is often going to be used for characters that you're not going to find on your keyboard. Now, integer types. Let's talk about the different kinds of integer types. The main difference between these are the size. What's the range of numbers that we can put in? So we start with a byte. That's only going to be 8 bits long, and it holds -2 to the power of 7 to 2 to the power of 7 minus 1. Now, why the -1? Well, that's because 0 is counted in that range as a positive number. So that basically means that if you have a byte, you're going to have a range of, -128 to 127. Now, a short is a little bit bigger. It's 16 bits. And so that's roughly going to store something like -32,700 to 32,700. Somewhere, I'm just rounding these numbers at this point. An int is 32 bits. That's going to get us into the billions. It's like -2.1 billion to 2.1 billion, somewhere around there. And then finally, we've got the long, which is the biggest integer type. It's 64 bits, and that's getting us all the way in the range of -9.2 quintillion to 9.2 quintillion. So you pick the type of number that you want based on what number you're trying to represent. It has to fall legally within the range that each type supports. Working with literals seems pretty easy. We just declare the literal type and assign a value. But there are a few pitfalls to be aware of. We're going to go over the topic of default literals in this lecture, and then the next lecture we'll talk about casting. So we've already seen some literal values already. What we mean by saying literal value is that we can look at the value of a primitive, and just by looking at how it's been typed, we can tell what data type it is. So we have, for example, any single character that has single quotes, that's going to be interpreted as a char, as a character. If the word true or the word false is written in all lowercase and has no quotation marks, then that literal type is going to be a Boolean. We have some literal types for our numbers as well. So let's start with any number that doesn't have a decimal is an int literal by default. If I want to have a long, and I would need to add a letter, L, right after the number. Any floating point or decimal number is by default a double, unless we add the letter F to the end, which makes it a float. We could add the letter D if we wanted to make a decimal a double, but it's kind of redundant. It's a double anyway. So let's take these rules and look at some code. So if I have a value 2, then by default it's going to be an int. And in just a second I'm going to show you a couple of use cases where that's not true. But so the 2 in this case, it's a whole number. It's going to be assumed to be an int. If you have the letter L, it's going to be a long. Notice that the second version is also an L, but it's a lowercase l. And that kind of looks like a 1. You might mistake that for 21. So bottom line, don't use a lowercase l. Even though it's legal, it can be hard to read. 2.2, there's a decimal, so that's going to be interpreted as a double. And then we have another decimal number, but with an F, so that's going to be interpreted to be a float. There's the D added to another decimal number, but as we've already said, it's redundant, it's not necessary. Any decimal number is going to be assumed to be a double. We can work with other number types as well. We can work with octal and hexadecimal numbers. Any integer that starts with a 0 is considered an octal, and that can throw people off, especially if you're trying to pad numbers. So for example, if I have the number 070, you might think that's 70, but it's 70 in octal, which is a base 8 numbering system. And so if we were to convert that to the numbering system we typically use, which is base 10, that would be equivalent to the number 56. We can do hexadecimal with 0x. If you start off any of the numbers with 0x, it's assumed to be base 16. And so 7e here is hexadecimal for 126 in our normal base 10 numbering system. In Java 7, we had a new literal that was created. So it's the binary literal. You can use a capital B or a lowercase b that follows a 0. So 0b101 is binary, which is the same as saying the number 5 in base 10 numbering. Another cool thing that was added in Java 7 was the underscore. And the underscore doesn't change the numeric value, but it gives us a separator so that we can better read what the number is. If I was to ask you to look at this number and tell me what it is quickly, some of you would say 12.3 million and others would say 1.2 million. Just depends on how often you read numbers without commas. But so many of us are used to having a separator in the numbers. If you're from the United States, that separator is going to be a comma. If you're from other countries, that might be a space or a decimal. So they used something that was neutral, not a comma, not a space, not a decimal. They used the underscore. And so now we can add the underscore to the value, and it just makes it easier to read. And there are a couple of rules about the underscore I'll mention in just a minute. But here's just another example. We've got the 1.2345667 number, and we could use the underscore to make that a little bit more readable as well. So the feature is really just to separate natural groups of digits in numeric literals. The underscore character is ignored wherever they are placed, but there are a few rules. First of all, it can't be used as the first or final character. It can't be used immediately in front of or after a decimal. So there's an example of something that's legal. This second y int is illegal because we have the underscore at the very end. Here we have a underscore and a decimal, totally legal. And now we've got the underscore right in front of the decimal, and that is illegal. There are going to be times when you're working with primitives that you're going to need to convert them from one type to another type. And so this is called conversion or casting. And there's really two directions that this can go. There's a widening conversion and there's a narrowing conversion. So let me show you a few examples here. Let's start with what a widening conversion would be. So imagine that I have int x equals 5. Now I have a little chart above the int x in case you're ever trying to remember how many bits is a specific type. Well, int is 32 bits. And so that we're saying that we've got a variable called x that can store a 32-bit number. Now 5 is a pretty small number, but remember that the literal type is going to be an integer. So can I take a 32-bit number and store it in a 32-bit variable? And the answer is yes, of course I can. That works great. How about if I have a long, let's just call it y, and I have the number 5 again? Does that work? And the answer is sure it does. Now, how many bits is this number 5? Well, it's still 32 bits. The literal data type is an int. And an int, could we store a 32-bit number into a 64-bit variable called y? Sure, The variable's huge. It only needs 32 bits. So that was what's known as a widening conversion. And so if we look at our smallest, we can't do booleans. That's really our smallest primitive, but we can't cast booleans. That was something we mentioned in the last lecture. But we can cast bytes. So if I've got a byte, and let's just make that. I'll make a byte b equals 4. Now you might be thinking, wait a second, I thought you said if it's a whole number, it's an int and it's 32 bits. Well, I also mentioned that there was a slightly strange rule that breaks the int literal. And what I mean by breaking the int literal is that if I take a number, which would normally be interpreted as a 32-bit number, and I immediately, in the same statement, assign it to a smaller byte or short, well, it's just going to work. It's going to convert this 32-bit number into an 8-bit number, and then it will work. It'll do the same thing for short. Short s equals 5, and also char. Char c equals 4, and that's legal. Now, you might be thinking, wait a second. There's a lot of wait a seconds here, right? I thought 4 is a number and char is a character. Well, when you assign a number to a character, it's the Unicode code point. And so 4 will be looked up in that table, and we could interpret it as a character. Not going to do that a whole bunch, but it is legal. The main thing that's really important here is just to note that when we have a single statement, even though a whole number would normally be interpreted as a 32-bit, we can legally assign it to be a byte or a short if needed. Now, getting back to this idea of widening conversion, if I've got this byte b equals 4, could I store the value of b in my int? And let's just get rid of some code here just to clean this up. Well, I mean, you can tell it works, right? We don't have any x's, no red underlines. So it's valid. What it's doing is it's reading the value of b, which is 4, an 8-bit number, and then it's taking that 8-bit number and storing it into a 32-bit variable. That's widening. It just works out of the box. We don't have to worry about it. The only thing that you really have to worry about is when you do something like if I've got an int, and I've got some kind of a number here for an int x2 equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Just make it some big number. And then I try to store that in a float. Float f equals x2. It is possible because a float, even though these are both 32-bit numbers, so they would fit, within each other, the problem is that some of the bits mean different things to the float. We have to have some way of representing what bit represents the decimal. And so you can lose precision. That's the only thing that you have to worry about. You might lose a little bit of precision between a whole number and converting it into, say, a float here. But otherwise, widening conversion just works. Now let's go the opposite direction. Let's say that I've got my int x equals, let's do this, x2 equals 10. And now I'm going to say byte b2 equals x2. Nope, that's not going to work. What's happening? We have a 32-bit number that was assigned to a 32-bit variable. We're taking the value of that 32-bit variable and assigning it to an 8-bit variable called byte b2. So 8 bits on this side, 32 bits on this side. And the answer is, nope, that's not going to work. Now you could actually look at this number and say, yeah, but I know a little bit about bytes. And 10 is a reasonable number. It fits in between negative 128 and 127. So it's a legal byte number. So if you know it's legal and you want to store it in the byte, well, then what you do is what's called casting. And so we simply write in parentheses immediately to the left of what it is we're trying to convert, and we put the type. So what we're doing is we're saying, hey, compiler, just trust us that x2 is legally a byte, so convert it into 8 bits. And what it'll do is it'll cut it down into 8 bits. If the number was really too big, it would do either an overflow or an underflow. So what do I mean by that? Well, let's say I've got, for example, let's make a big number, 200. And you know what, I'm going to put this in a, let's just do this. Put it in main. Public static void main string args. Let's put all this stuff in there. That way we can run it. So let's see what happens when I put a number that's, actually a little too big for this B2. Let's print it out. So system out println B2. All right, let's run it. Any guesses while we're getting this configured? All right, there's the number, -56. That's not probably what we expected. Oh, look, I had 2 semicolons and it still worked. Sometimes Java can be forgiving. But the problem that I was talking about was this number 200, it's a legal int. 200 fits within 32 bits, but the number 200 does not fit within 8 bits. Okay, so when we converted it to an 8-bit number, what it did is it had to get rid of some bits, and it does either an overflow or underflow, which means that it recalculates the number. If any of you remember the video game Defender, it's kind of like going off the other side of the screen and then appearing, on the opposite side. It's that kind of an idea. So the top number for an int would be 127. Let's run that. And there you can see down below that it says 127. That's great. But watch when I put 128. Now we're out of the range of a byte. Our value is -128. What if I go to 129? Now it's -127. I put 130, -126, and so on. So what happened is when we have an overflow or underflow, it goes to the very top or the very bottom of the range, and then it starts over on the other side. Okay, that's what's happening. And that can be confusing. That can give you numbers that you wouldn't expect. So, long story short, we can legally and easy do widening conversion. It's not a problem. But we can't do narrowing conversion unless we explicitly cast it. And we cast it by having parentheses in the data type. We put it to the left of the value that we're trying to cast. And we just got to be careful. We just got to make sure that it is, in fact, legal, that it's going to fit within the range that that we're casting it to. One of the obvious limitations of the primitive is its size. There is a finite amount of data that we can store in a primitive. And there'll be times where that doesn't work for us. We may need a larger or a more precise number than what is provided for us with our primitives. So for example, we've got a long, and a long can hold a really big number from -2 to the power of 63 to 2 to the power of 63 minus 1, which is roughly like 9.2 quintillion. And we also have a Java double, which is 64 bits, and that can allow us to store a very precise negative number. But what if we got a large number like 9.3 quintillion, which is outside the range, outside the top range of a long? So if you're doing any science or any kind of serious engineering, physics, astronomy, cryptography, you're going to run into algorithms and processes where you're going to need larger numbers or more precise numbers. And so when you hit that limitation of primitives, Java gives us an API which we can work with that will allow us to have larger numbers and more precise numbers. So 2 of the classes they give us are big integer and big decimal, and both are in the Java math package. Now with big integer, you can work with arbitrarily large whole numbers. And with big decimal, now we can have arbitrary precision at our fingertips. And so when we say the word arbitrary here, what we're meaning is that at that point, we're really just limited to our computer's memory capacity. It's not the size of the variable, it's the memory in our computer. Now these are just regular Java classes, so you're going to have to instantiate them in the same way you would other objects. There are different constructors that are available for each of these different types. Some allow you to pass in a string or a byte array. Here's a couple of examples. Here we've got big integer and big decimal, and in both cases we are passing in a string. as the constructor. That's a common mistake when you first start working with big integer or big decimal, that you forget you're passing in a string. The string will be converted into the big or precise number that you're trying to create. So now we've got, for example, a my big int, which is the 9.3 quintillion. In the next chapter, we're going to learn about some of the different operators, like the plus, the minus, the multiplication, division, and so on. We can't use that with big integer and big decimal because these are objects, and these kind of operators only work with primitives. So what we do is we use methods that are available in big integer and big decimal, and they'll perform the calculations. So remember that we had our big int previously. We're creating another big integer. This one is called 2. We're passing in the number 2. And now if I want to multiply, I can take my big int, which was the big integer we created in the previous slide, and we're calling a method multiply on that, passing in the big integer, which is called 2. And that will do the math, and then it will return to us a new big integer object, which is even bigger. Can do the same thing with big decimal as well. So each of these classes have lots of methods where we can perform mathematical computations on them.
This next section is going to focus on Java syntax. So all the things that we're going to use when we build classes and use objects. We're going to talk about conditionals for branching our logic. We're going to talk about loops for iterating through logic. We'll talk about some other constructs such as enums, and then we'll look at all the different operators that are available to us.
All right, we're going to start by looking at conditionals. In this lecture, we're going to look at the if statement. So let's start with that. What is an if statement? An if statement is where we can run a test, and if the test is true, we'll do something, and if the test is not true, if it's false, then we won't. So let's look at a very simple if statement. First of all, in order to work with a conditional, we're going to need a Boolean value. So I'm going to make a Boolean variable. So Boolean in Minneapolis equals false. And now we're going to write our if statement. So I say if, and then in parentheses, right next to it, we'll write our test. And so my test is going to be in Minneapolis. Now, this test can be any Boolean value. So it can be a Boolean variable. It could be just a literal, like true. It could be a method that returns a Boolean variable. And it also can be a Boolean operator. So if we had, for example, greater than or equal to, if my age is greater than or equal to 21, then do something. And if it's not, then don't do it. That kind of a thing. So greater than equal to there would be a Boolean operator. And we have a whole lecture on operators coming up, so we'll look at those in greater detail just a little bit. But for right now, we've got our test. If in Minneapolis, then we're going to do something. So we put some curly braces. We have a code block. Notice the errors just went away. And so what we're saying is, if this is true, if we are in Minneapolis, let's do something. And we'll just print out a little message. We'll say, hello from Minneapolis. All right, that's it. That's a simple condition. And we use conditionals in code to branch our logic so that we can make decisions at runtime to say, should we do something or shouldn't we? So let's actually run this and see what happens. So if I run it, I'm not going to expect too much. Let's run that. Nothing. There's nothing down here in the console. Why not? Well, in Minneapolis right now is set to false. So when it does this test, is in Minneapolis true? The answer is no, it's false. What would happen if we changed it to true? Well, probably exactly what you would expect. It now says hello from Minneapolis. Okay, well, let's change it back to false. What are some of our other options? Another thing we could do is we could then check to see if we're in another city. So let's add another variable here, Boolean in St. Paul. So now let's check that. And we do that by saying else if. And we have some parentheses. And inside the parentheses, we add our test. So in St. Paul. All right, and if we're in St. Paul, now we'll say hello from St. Paul. So let's take a look at the code in more detail, and then we'll run it. What's going to happen? First of all, it's going to check to say, are we in Minneapolis? And the answer is nope, false. So then it goes to the next statement here, else if, in St. Paul? And the answer is true, in which case it will enter this block and execute that code. Let's run it to make sure. And there it is. It says hello from St. Paul. Now the rule is, once a statement is true, once one of these conditional checks evaluates to be true, it enters that code block, and then it exits below. So if in Minneapolis happened to be true, it wouldn't even check to see if we're in St. Paul. It would run this line 8, it would say hello from Minneapolis, and then it would continue on with line 12. So you only enter one of the blocks of an if statement. Now we could have as many of these else ifs if we want. Let's turn this to false. So now none of these are going to be true. What else could we do? Well, we can have an else. And an else is sort of a catch-all. If nothing else above these statements evaluated to be true, then let's just say, hello from somewhere. And let's run it. And that's what it says, hello from somewhere. Because both in Minneapolis and in St. Paul were false. None of these were true. If I turn in Minneapolis to be true, it will only print out hello from Minneapolis. None of the other code blocks would be entered. So that's the basics of the if statement. You can have an if alone. You can have an if with an else. You can have an if with as many else ifs as you'd like. And you can have an if with an else if, as many else ifs if you like, and an else. You can't have an else if just floating in space. You can't just have an else. There always has to be the if statement. Now the parentheses that we're seeing here, these are required. Your test has to be in parentheses. What's not required are these curly braces. I'm just going to get rid of them just to show you. So we'll just get rid of that. And we'll get rid of that. And as you can see, that is legal. But it's not always going to do what you expect. Now let me show you what I mean. Let's add another statement here. So we've got this in Minneapolis, in St. Paul, else, system out, print line, hello from somewhere. And let's just save it and run it. Make sure it's still doing what we expect. And I'm going to set both of these to false. So what I would expect is it's going to say hello from somewhere. And that's what it did. It said hello from somewhere. Now what I'm going to do is change one of these to be true. Let's just grab is St. Paul, test it again. You should know what's going to happen next. It'll say hello from St. Paul. It's looking good. Okay, so let's put another statement here. Let's say that if it's not, if we're going to say hello from somewhere, we'll also say system out, print line, can we visit you in St. Paul? All right. So if we get to this hello from somewhere, I want to print out this message, can we visit you in St. Paul? Once again, let's put false, false. We'll run it. And there it says exactly what we expect. Hello from somewhere, can we visit you in St. Paul? Let's put that St. Paul to true again. What do you think is going to happen? Let's run it. Hello from St. Paul, can we visit you in St. Paul? Now that's weird. Why did this line run? And the answer is that if you don't put the curly braces, then the first statement that follows is associated with the conditional, but the second statement is not. It's just there. It's just a statement. So this is one of the reasons why it's a really good practice to make sure you do put in your curly braces. I'm going to just clean this up a bit. Let's just take a look. Now that I've got the curly braces, if I run it, now it does what we'd expect, hello from St. Paul, because the curly braces allow us to put in multiple statements within a single block. So those are the basics of the if, else if, and else statement. We're going to look at a different kind of a conditional statement now. It's called a switch statement. And the syntax is a little weird, so let's jump right into it. First of all, we got on line 8 here the word switch. And then in parentheses, we're checking something called J. We're checking to see what is the value of j. So the parentheses here, they're different than what we were seeing in the if statement. With an if statement, the parentheses was a conditional check. It was a test. Anything that was going in the parentheses had to evaluate to a Boolean, which meant it could be a Boolean literal, it could have been a variable that was a Boolean, it could have been a method that returns a Boolean. That's not what we're doing here. We are just checking to see what is the value of j. And then we've got these curly braces on line 8 and 23. And so that's our code block. And we're saying based on whatever j is, let's run these tests. So the tests are really inside of the curly braces. So the test is really going to be a case. And so we write the word case, and then we say, what do we think it might be? So case 1 colon. And what that means is if j is 1, then enter here and run this code. String equals 1 and break. Now, what does break mean? Break means that's it. Once you've finished here, don't check any of the other cases. Just continue on after this block, which would be with line 24. Well, let's run this. So I'm just going to run, right now j is equal to 3, and I'm going to run it. If you look down below, you'll see that it prints out the string 3. So int j equals 3. We switch on j, so it says, what is j? J is 3. Is it case 1? Nope. Is the case 2? Nope. Is the case 3? Yes. And so we enter, and our string becomes the word 3. We break on line 17, which brings us all the way to the end of the code statement. And so then we enter line 24, where we print out the string, and that's why it says 3. If I change this to some other number that isn't here, like 0, and run it, you'll see that it prints out our default, which is unknown. Now, what would happen if we forgot a break? Let's do that with case 2. I'm going to get rid of the break here, and I'm going to set my value to be 2. And so what will happen? Well, it prints 3. Why did it do that? Well, what happened was we switched. The value of j was 2, and it did enter case 2. And it did set the string to be 2. But there was no break, so it continued on. Even though the case 3 is not true, it ignores that. And so it falls through to the next case, and string became 3, and then we hit the break. So put that break back. And that's the basics of a switch statement. Now, the j that we're testing on right here, what can we put in a switch? We're actually fairly limited into what we can put here. The first thing is that it could be anything that is an int or can be converted into an int implicitly. And so if you remember, we saw that we can do widening conversions without having to explicitly cast a number. So that means we can switch on an int. We could switch on a short. Notice there's no compile error there. We could switch on a byte. No compile error. We can even switch on a char. Remember that it's legal to use numbers for characters. So all of those are legal. How about what's legal for each case? So for each case, we have to have something that's known at compile time, which is usually going to be a literal, some literal value that we use here. We couldn't have a variable for a case. We couldn't call a method for a case. It has to be known at compile time. So let's look at a few other examples. Scroll down here. Here's an example of using a char. This time we're using an actual literal character. So if it's A, we're switching on that character. Here's our case. If it's A, let's print out it's A. Otherwise, we'll print out the character. Run that, and it does say is A. Another thing that we can switch on is a string, and this is new to Java 7. This didn't used to be available. So now we can have a string, switch on it, and there's our case. It has to be a string literal because the value has to be known at at compile time. So what's it going to do? It's AM, should print out good morning. And it does. Now let's look at one final example where we purposely leave out some of those breaks. And we do that so that we can have a couple of different conditions that can be true. So now we've got j is equal to 3, and we're going to switch on j. And if it's case 1 or case 3, then we want it to print out odd. And if it's case 2 or 4, the string should be even, and so on. All right, I'm going to print out my printout, otherwise it will not print it out. And print out string. So let's run this. And it says odd. So what happened was it was 3. Case 1 wasn't true, but case 3 was. There was no break, so both of these are considered part of the same test, really. And we entered here, and string became odd. What if I had changed it to 2? And now it says even. So that's an alternative syntax for issuing a conditional. What you're looking at here is a table that shows the order of precedence for Java operators. We're going to use operators in expressions all over the place, so it's really important that you know these. And especially if you're taking the exam, you really want to know not only what the operators do, but what the order of precedence is. So what do I mean by order of precedence? It's what is going to be executed first. Let me show you an example. So if I've got an equation here where I say int x is equal to 3 plus 2 times 5. So the question is, what is x going to be after this is done? Well, because of the order of precedence, you don't just read this left to right. What you have to do is know which of the operators have a higher order of precedence. And so multiply has a higher precedence than addition. So the 5 times 2 would be executed first, and then the plus 3 would be executed next. So if we run this, I would expect it to say 13. Let's run that real quick, and there it is, 13. So the higher level the row, the higher the order of precedence. And then within any given row, these are all equal. And so you would simply read them left to right in the equation. In other words, if I have plus and minus, neither of those have precedence over the other. We would just keep moving left to right in the equation to see how the equation should be evaluated. So let's go over some of these different operators. We have Boolean operators. These return true or false. Reading all the way from left to right, we've got less than, greater than, less than or equal to, greater than or equal to. Sometimes people call this the bang operator or not. This is not equal to, and this is equivalence. So it's equal to. If you have a single equals, that's an assignment. 2 equals means we're checking for equivalency. Now let's talk about bit shifting and bitwise operators. And I'm going to go to code just because it's a little easier to see it there. So don't worry, you're probably not going to have to learn binary, but I'm going to show you the binary representations here because it makes these operators a little easier to understand. So here I've got int I equals 8, and the binary representation is listed right over here. When we have the bit shifting operator, and we have 3 of them, what it's going to do is do exactly what it says. It's going to shift the bits. So we're taking the value of I here, and we are shifting it over one place. And we're shifting it to the right. That's what the 2 arrows means. So here we're taking that 1, shifting it over, and so once we're done, this is our new number, which would be the number 4. Now that is a signed shift. When you have the 3 arrows, that's what's called an unsigned shift. So what it means to be signed is that the range of numbers can be from the negative to the positive, and unsigned means it's just a positive number. So the way that we are able to tell if a number is negative or not is whether the most significant bit, which is the one all the way to the left, if it's a 0 or 1. If it's a 0, it's a positive number. If it's a 1, like we have down here, then it's a negative number. So when we do a signed shift, then what it does is it respects whatever that most significant bit is, and it keeps repeating it as it does its shift. So in this case, when we shifted over one place, the most significant bit was a 0, and so it just kept adding zeros on the left side. When we do the unsigned shift here, then what it's going to do is even if this was a 1, it would fill it in with zeros. So it's unsigned. Every number is going to be positive. And then we have the left shift, At this point, after line 8 had executed, the number was 1. And when we shifted it over 3, now we're back to 8. So now let's look at the negative number example. We've got a negative number 8. Here's the binary representation. Notice that the most significant bit has a 1 in it. So now we're going to shift it over to the right one place. Notice I'm using a slightly different operator here. This is an assignment operator. It's a shorthand. So this operator means take x, shift it to the right one, and then assign that new value back to x. It's just a shorthand. So what happens when we shift it over to the 1? Well, it is a signed shift, so it fills in the left side with more 1s. In this case, it filled it in with a single 1. And you can see that everything moved over to the right by 1 place. This is an unsigned shift right here. So when it fills it in with 2 more digits, it's going to fill it in with a 0 because the 0 makes it a positive number. Now let's take a look at the bitwise operations. So here we've got 2 numbers, 2 ints. We've got the number 8 and the number 10, and here's their binary representation. When you see the single AND here, as a bitwise AND, what it's going to do is it's going to look at the 2 numbers, and if both of the digits in that place are a 1, then it will have the number 1. Otherwise, it'll be a 0. So when we do that calculation, we get 1, 0, 0, 0. 1, because here, in this place, both of the digits were 1. Then they were 0. The third one has a 0 and a 1. That doesn't count either. They both have to be a 1 in order for it to result in a 1. And the final is a 0. So that gives us 1,000. Or not 1,000. It gives us 1, 0, 0, 0. And then we've got OR, which is going to go through the same 2 numbers. And it's going to say if either one of these digits is a 1, then the result is a 1. So first place would be a 1. Second would be a 0. The third, we've got a 1 here, so that counts. The third would be a 1. And the fourth would be a 0. So we're left with 1, 0, 1, 0. Exclusive OR is kind of like OR, except it says that only one side has the 1 in order to result in a 1. So even though there are 2 1s here, with the exclusive OR, that's going to result in a 0. Second would be a 0. Third would be a 1. And the fourth would be a 0. And that's what we got right down here. And finally, this tilde is called the complement operator. It just flips all the bits. So here's all the bits for x, and you can see down below we just flipped them. If it was a 0, it becomes a 1. If it was a 1, it becomes a 0. And the last operator we're going to talk about in this lecture, we're going to continue with operators in the next lecture, but for this particular one, let's look at Booleans. So I'm going to create 2 methods here. I've got is sleeping, and it'll print out the words is sleeping, so you know that the method was called, and it's going to return false. And is home is going to print out that it's calling is home and return true. Now here's my first Boolean example, and we're using the bitwise AND here. It's treated as a Boolean operator in this case. And we could use the OR as well. I'll show you that in a minute. But here we have AND. And what happens is we're saying if this side is true, the left side, and the right side is true, then do whatever we're going to do in this Boolean operation. So let's run it. And when we run it, we can see down below here that it says is sleeping, because that was called here. And it enters this method, prints out is sleeping, returns false, and then calls is home and returns true. It evaluates both of these and it says, well, this is false, this is true, so they're not both true, therefore we won't enter this if block. If we change this to an OR, it calls both methods, and now it does give us the response we were looking for, because this is saying if the left side is true or the right side is true. But typically when we're making Boolean methods, we don't use the bitwise operators. Instead, you probably have seen this, where we have 2 of the ands and 2 of the ors. And the difference is that this is short-circuiting. Let me demonstrate. I'll hit the play. Notice that it says is sleeping. It did not even call is home. It's short-circuiting because as soon as it knows the answer, it doesn't evaluate the other side. So in this case, we're saying that both sides have to be true. when it evaluated is sleeping, that returned false. And so it said, well, this can't possibly be true, so I'm not even going to call the right side. If we did an or, now it had to call both because the is sleeping was false, so it still had to check the other side to see if is home was true. If we change this, if I instead do is sleeping, and we run this, notice that it never called is sleeping. It didn't need to. It short-circuited because it already knew the answer. And one of the places that you're going to find short-circuiting used is when we're trying to prevent something from running if it'll cause a problem. Very common is checking for null. So let me show you a quick example of that, and we'll finish up with this lecture. So what I'm going to do now is just say string x equals null. And I'm going to just trim x. So I'm going to say x.trim, and let's run it. And down below you can see that I've got a null pointer exception. The reason is that anytime we try to invoke a method or read a variable, anytime we're using the dot operator on a null reference, it's saying there's no object for me to refer to, so it throws the null pointer exception. So we can use the short-circuiting operator to our advantage. We can do things like if x is not equal to null and x.trim.length is greater than 0. It's kind of a common thing that we do. So here we're checking to see, making sure it's not null, getting rid of the white space. After we get rid of the white space before and after the string, we're checking the length to make sure it's greater than 0. So we're basically saying it's not an empty string. Then it will execute this code. So now if I run this, notice the null pointer goes away because we're checking to make sure it's not null. And what's happening is this is going to fail. It's going to say, but x is null, so it's not even going to bother to evaluate the right side. Let's look at a few more operators. This is the post and pre-increment operator, where you see the plus plus. If you saw a minus minus, that would be the decrement operator. And what it does is it either increases for the increment or decreases for the decrement the current value of a variable. But whether it's to the right side of the variable or the left side of the variable does make a difference. And here's what I mean. Whenever we have this operator, it's going to assign a new value, in this case to x, but it's also going to return a value to be used in an expression. So here we've got int x equals 0. When we say x plus plus, the old value is 0. The new value is 1, so x is now equal to 1. But then it returns the old value to be used in an expression. The pre-increment operator, now the old value is 1 because we've incremented it. The new value is 2, and it returns the new value. So let's see how that would manifest itself. Here we've got a system out print line, and we're doing an x plus plus. It's going to print out 0 because it's going to print out the old value. Then when we print out x again, it'll print out the new value because x has that new value of 1. Here's the pre-increment operator, so it will print out 2. And when we print out x again, it has already been incremented in the previous print line, so it stays at 2. And this is one of those things that you're going to want to play around with, especially if you're going to be taking the exam. Just sit down and start doing things like, I've got int y, it's equal to 0, and what happens if I do plus plus y, and now I'm going to print out y. All right, so what would happen if I ran that? All right, so we can see it was 0, 1, 2, 2, just like we expected, and here it's printing 1. And that should be what you expected, right? That it's going to print out the number 1. We started with 0, we did a pre-increment, and now it's printing out 1. What do you think will happen if I change that to the other side? Will it print out 0 or will it print out 1? And I'm just going to comment these out so that we don't get all that other stuff, and run it. And it also prints out 1. Now why is that? The reason is that y here is doing the post increment, which means the old value is 0, the new value is 1, and then it's returning the old value here to be used in an expression. But it's not really being used in an expression. So that's it. It returned the value, its current value is, or it returned the old value, but its current value is now 1. So once we print it out, it's already been incremented, so it prints out the new value. How about this? This will be a little strange. What do you think will happen here? All I did now is say y is equal to y plus plus. We'll run that. Now y is 0. Did the increment not happen? What occurred? Well, here's what happened. Y is 0. So y goes through the post-increment process. The old value is 0. The new value is 1. Return the old value. So it returns the old value of 0 and assigns it back to itself. So effectively, we just lost the new value. And when we print it out, y will be equal to 0. All right, let's look at another operator. Here is the ternary operator. It is a shorthand for doing a Boolean expression. So for example, if I've got a string that I'm creating, here I'm checking to see if is sleeping is true. If it is, we'll set status to be sleeping, else status will be working. We can do this all in one line with the ternary operator, and it looks like this. You put your conditional check first, and then you have a question mark. Anything after the question mark is what should be returned if is sleeping is true. And then the colon is everything after the colon is what should happen if is sleeping is false. This is your else. So that's just a nice shorthand. It's called the ternary operator. And finally, just one other note about precedence. And again, if you're taking the exam, spend some time looking at that table that I showed you so you can remember all the different orders of precedence. So with this first one, int x equals 3 plus 2 times 5, because multiplication occurs first, it would be 5 times 2 plus 3, so the value would be 13. We can influence the order, however, using parentheses. So if I wrap 3 plus 2 in this way, then that will be executed first because the parentheses have the highest order of precedence. So now it'll be 3 plus 2 times 5, which would give us 25. One of the things I tend to do is even though this wouldn't change the outcome, I'll often still wrap what I want to have happen first in parentheses just to make it really clear to the reader what the order is, what's going to be called first, what's going to be called second, and so on. The next kind of syntax that we're going to look at is the loop. And there are a number of different loops in Java. We'll talk about a few now. And once we start talking about arrays and collections, we'll come back to the loop and look at another syntax, another way of doing a loop. So what is the purpose of a loop? It's really just to keep iterating and iterating over and over again until some kind of condition has been met. So let's make a simple example, and let's use one of the operators that we just learned in a previous lecture, the modulo operator. So what I'm going to do is I'm going to start with x being 0. So int x is equal to 0. And what I'm going to do is I'm going to keep incrementing x until it hits the number 20. And if the number is divisible by 2, if it's evenly divisible by 2, then I will print out that number. In other words, we're just going to keep looping from 0 to 20, and every time that the number is even, we will print out that number. So we're going to start with the first loop, which is called a while loop. So I type the word while, and then I have parentheses. And in the parentheses, I'm going to do some kind of a conditional check. I want to see if x is less than or equal to 20. So we're going to go all the way through 20, from 0 to 20. And then you put your curly braces. So now we've got a code block. And what we're saying is while this condition is true, execute everything in the code block, and then check the condition again. So what we'll do is we'll say if x modulo 2 is equal to 0, then we will print out, let's just print out the number. All right, let's take a quick look at that. So it's going to go through all the numbers from 0 to 20. If it's evenly divisible by 2, it'll print out that number. Now, if I ran this right now as we'd have it, the loop would continue forever. Now, just take a second, maybe even hit pause. And why would this keep going over and over and over again forever? The reason is that we're never changing x. X is always going to be 0 every time it checks. So when you create a loop, you got to make sure that the condition at some point is going to be false so that the loop will stop. So what we'll do is we will, first of all, increment x at the end, x plus plus, and now it will eventually stop. So let's run it. All right, I'm just going to make this a little bit bigger. So we have all the even numbers, 0, 2, 4, 6, 8, 10, 12, all the way through 20. So it did just exactly as we had hoped. So there's your first loop. While x is less than or equal to 20, we're checking to see if it's evenly divisible by 0, evenly divisible by 2, and then we're printing out the value. We can't forget to increment x, otherwise this will go on forever until we lose it, until we're out of memory or something else happens. So that's one kind of a loop. The while loop will execute 0 to infinity times, depending on the condition. Let's look at another kind of a loop. I'm going to change this. It's called a do-while loop. And I'm going to do the same kind of syntax here. So a do-while loop looks like this. You say do, and then you put your code block. And after the code block, that's where you put your conditional check. So we'd say while x is less than or equal to 20, and then you do put a semicolon at the end. So what's the difference between these two loops? Well, the while loop down here on line 11, that's going to do the check first, and if it's true, then it enters the block. So as I mentioned, it will execute 0 to infinity times. Whereas this do-while loop, this is always going to execute at least once because the conditional check doesn't happen until after it's done whatever's in the code block. So here I'm going to put the same logic that I had before. Just put that inside here. And let's get rid of this old while loop. All right, let's run it. And I'm going to just kind of scroll down here in the bottom. You can see that it went from 0 to 20 and everything worked well. So in this case, it will always execute at least once, and then it will do its check. One little gotcha here that I should point out. Notice that I've set the value of x to be 0 outside of the do. If I move this inside, which is a bad reason for a number of reasons, but the main reason that I'm doing it here is to show you this. Notice that it wouldn't even compile. So we've been talking about scope, and we said that curly braces can help us identify scope. So this do code block has its own scope. It's a very local scope. Int x is defined in that scope, and this while is checking x outside of that scope. Here's the curly braces. Everything that's inside of these curly braces has its own scope. So when we try to check x outside of that scope, it doesn't exist. It's not in the right frame. So that's why I had this int x outside of the do block. And now the final loop that we'll look at, it's a for loop. So the for loop looks like this. You say the word for, and you have parentheses and your curly braces, just like you would expect. But the for loop has three components. First of all, you are going to define your variables that will be used in this code block. So I will put int x equals 0. This is our initialization section. And then we put a semicolon. And the semicolon is what's going to separate each of these different components in the for loop. So the first component is going to be the initialization block. We're initializing a variable called x to 0. The second is going to be the test. And so what I'm going to do here is check to see if x is less than or equal to 20. Put a semicolon. And then finally, it's going to be our post operation. So after all the statements have finished in this code block, what should it do? And we'll increment x right here. So three different parts to the for loop. Your initialization section, your conditional test, and then your post operation. What should happen once the loop once the statements have been run inside of the loop. And once again, we can just grab that if statement that we had below. Let's get rid of this. And we'll run it, just make sure it does the same thing. And down below, you can see that it did, in fact, run from 0 to 20. So those are your 3 different types of loops that you can work with. And like I said, when we come back and look at collections and arrays, we'll look at another type of a for loop that helps us deal with those type of objects. We just have a couple of other things to talk about in regard to loops. We're going to look at 2 different keywords. We're going to look at continue and we're going to look at break. And then we'll also talk about labels. So take a look at the code that we've got on lines 5 through 8. Pretty simple. We are setting up an int on line 5 here to be I equals 0. On line 6, we're starting our while loop. We're checking to see if I is less than 3. And on line 7, what we're doing is we're printing out the value of I. But we're not just printing out I, we're also incrementing I. That is the post increment operator. So what that means is it will return the current value of I and then increment it afterwards. So instead of seeing the numbers 1, 2, and 3, we'll see 0, 1, and 2. Hopefully you're able to see why. In fact, I'll just run both. So if I run this, we see down here 0, 1, and 2. But if I change it to be a pre-increment operator, then the value of I is going to be incremented before it prints it out, in which case we'll see 1, 2, 3. All right, let's move that back to I++. And what I'm going to do now is change this while to be true. Now, is that legal? Sure it is. Look, there's no compile errors, no red X's in Eclipse here. So remember that anything that's in the while loop can be a Boolean, and a Boolean literal is certainly a Boolean value. So what do you think would happen if I ran this? You probably made a pretty good guess that it'll just keep running, right? And you're right. So you can see it's just going to keep running because there's nothing to stop this condition. So I'm going to hit stop, since that's not what I want to do, but I'm going to keep this true here. I want to show you another way to get out of a loop. And so what I'm going to do is put a check in here, and I'm going to say, if I is equal to 10, then I want to break. And so we're starting at 0, we're going to keep incrementing. Once it gets to 10, then I want to break. And so what the keyword break does is it says, whatever loop I'm currently in, I want to break out of it. So this is the loop we're in, which means that once we hit break, once I is in fact equal to 10, then we continue on after that loop, and it will continue on with the rest of the code. So we'll run that, and it went from 0 to 9. The 0's hidden because it scrolled off, but it did say 0. So that's another way that we can break out of a loop using the keyword break. Let's look at the word continue and see how that works. Just going to scroll down here. Got another example. So here we've got a for loop, and what we're doing is we're starting with k equal to 0. That's our initialization section. We're then checking to see if k is less than 100, and if it is, then do whatever's inside of this for block. After the code in the block has been executed, we're going to increment k by 1. So that should be fairly clear. Next, what we're doing is we're checking here with an if. We're saying if k is evenly divisible by 7, then we want to continue. Now, what does continue mean? Continue means that we should continue with the loop. We're not breaking out, but don't bother doing anything below. Don't do any of the additional statements that are inside of this for loop. So if k is evenly divisible by 7, it just goes to the next iteration of the loop. Let's say it's not evenly divisible by 7. Well, then it's going to print out this message, k is not divisible by 7. And if I run that, you can see that it went through and it printed out all of the different numbers that are not evenly divisible by 7. So that's continue. Continue says, go to the next iteration of the loop. Do not execute any more statements for this current iteration. Now I have one other example for you to look at, and it's going to be a little bit of a challenge for you. What I'd like you to do is to pause the video for a second and take a look at the code in lines 42 through 51 and try to make a guess as to what it's going to do. So pause the video and come back once you've figured it out. All right, let's take a look and see what it's going to do. I'm just going to run it and see if it's doing what you thought it would do. I don't know if you can really tell, but it is continually going, and it's starting over and over again, going through the numbers 0 through 9 over and over again, never stopping. Now, why is that? Well, let's start with line 42. So we've got our while, and we're saying while it's true. Now, when will that not be true? It's always true. It's the Boolean true, the literal value. And so that is always going to evaluate to be true. So it's going to go into this loop, and it's going to set z to be 0. And now we've got another nested loop, which is always set to true as well. So then it's checking it, saying, hey, if z is greater than or equal to 10, then I want you to break. Otherwise, let's print out the value of z and increment it. So why isn't it breaking out? Well, in fact, it is breaking, but it only breaks out of the current loop. So once z is equal to 10, then this loop on line 44 is done executing. It continues on at the end of that loop, which is actually still in this other loop. So the loop on line 42 evaluates once again and says, is this true? And the answer is yes. And it resets z to be 0 again. So that's why it's constantly reset and why it continues forever. So how would we get out of both loops? Break is clearly not doing it. We have something called a label. And it's pretty simple to use. What you do is you put some sort of text right above the loop that you want to break out of. So I'm going to say outer underscore label. And then you put a colon. And what we've done now is we've created a label for this loop. And you don't have to put label. Some people put loop. Some people don't put anything. But by convention, the words are typically separated with an underscore. And by convention, they're typically all lowercase. I guess, I've seen both, all uppercase and all lowercase, but most of the people I work with use all lowercase. And then what we need to do is reference that label in our break statement. So I simply say break outer label. And now when we run it, now it's just going from 0 to 9. Again, the 0 scrolled off, but trust me, it was there. And now when we hit z is greater than or equal to 10, it breaks all the way past the outer label and continues on with the rest of the code. This is the last lecture in this section, and we're going to look at enums. An enum is short for an enumeration, which is more or less a label. And the reason I say more or less is because you can use an enum as simply a label, or you can use it as something more robust. Java allows you to create enums with methods and other things as well. So I will show you some examples of that in just a minute, but before I do, I want to show you an example of one of the reasons why we have enums. So take a look at line 8. I've got a switch statement, and we're going to switch on a variable called today. Today is just a string for whatever day it is. Now, if it's Monday, we'll create a string called get to work. And if it's Friday, we'll create a string called time to relax. And otherwise, if it's not Monday, if it's not Friday, we'll say practice Java. So up here on line 5, we've created that string today, and it's called Friday. So let's run it. If you look down below in the console, you'll see that it says practice Java, which is, good advice, but it's not the response that I think we were expecting. We were expecting, since it's Friday, to say time to relax. And you probably have seen, you've already seen what the reason is, right? You found it. It's a capital F in line 5, a lowercase f in line 12. And remember, Java is a case-sensitive language. So those are really two different strings, even though you and I would just read them as both being Friday. And it's kind of easy to see the problem here, but a lot of times we'll be writing code where we're trying to branch our logic or using some kind of text as an input. And the text could be coming from anywhere, from a user who's typing it in, from a database, from a web service. There's so many places that the text can come from, and there's a good chance that it won't match. Now, there are ways that we could normalize this. I could have taken the today and run it to all lowercase. I could have done something like this: today equals today dot to lowercase. So that would have made sure that they're all normalized together. But believe me, it can still be a problem even when we're just writing the variables directly. So how do we get around this? How do we make sure that Friday is Friday? And one of the ways that we can get around it is with an enum. So I'm going to show you an enum here. This is our days enum. You write public enum instead of public class, and then the name. In this case, the name is days. And then in the code block, between the curly braces, you just write a comma-separated list of all the labels that you want, all of the names. By convention, we do this all in all capitals. So I've got Sunday, Monday, Tuesday, and so on. And even though we don't see it here, each one of these labels has what's called an ordinal. It's just an integer value. Sunday is 0, Monday is 1, Tuesday is 2, and so on. So that's a very simple type of an enum. And let's see how that can fix what we were just working with. So rather than switching on a string, what I'm going to do is I'm going to change this to the days type. And watch what happens if I write days.Friday. I get a compile error. It's telling me right now that there's no such thing as Friday. So Friday with all lowercase. So I tried writing with a capital letter, still a problem. It's not until I type it exactly with the right spelling, with the right capitalization, that I'm even able to continue. And so that's one of the nice things. We get compile time checking on our enums. So what I'm going to do now is I'm going to switch on that today. So my case can no longer be the string. It's got to be an enum. So I'll put Monday here and Friday here. And now when we run it, now it says time to relax, which is what we had expected. One thing to note is that when I'm working with the enum just in this class, I do need to put the type. So I have to say days.Friday. But inside of the switch, you just put the value. And if you forget, well, the compiler will tell you. If I put days.Monday, it's just not going to allow that. So you simply put the value. Now let's look at a more complex enum. And so here is my music type enum. And I've got all of my labels just like I had before, but in parentheses, I have a number in here. And what's really happening is when I have this parentheses, it's calling a constructor. So an enum can have a constructor. So here's my constructor. I've got my music type constructor that takes an int, and we're just putting an ear damage factor. And we're storing that ear damage factor as a variable, as some state inside of this enum. And we can even provide methods. We can do a calculate the hearing loss, pass in some hours, and it will tell us what the ear damage factor is multiplied by the hours so that we know what our hearing loss is going to be. You can even have a toString. So note that there's some cool things you can do with an enum. We can say, what is the name? That'll give a string representation of the name. So if it was jazz, it would print out a string of jazz. We've got the ordinal, which is the number that's backing it up. And don't be confused by ordinal and what you're seeing up here, 1, 4, 6, and 11. 1, 4, 6, and 11 are not ordinals. That's just the number that's being passed into the constructor. Classical is still 0. Jazz is 1, rock is 2, and metal is 3. Now, why do you care about the ordinal? Later we'll talk about working with an array, and one of the things that you can do is get a music type array. It's just a collection of all the different values. You can pass in the ordinal, like I could say, hey, music type array, I want whatever's in the first indexed element, and that would be jazz. It's jazz and not classical because classical is 0, and jazz is 1. So if we pass in the number 1, then we would get jazz. Now that's a little abstract for you at this point because we haven't talked about arrays in any detail, but we will be looking at them in a future section. One last thing that we can do here to show you. So again, if I want to convert one of these words to a string, the day. I can say days.friday, and then I can just say name. And that will return a string representation of Friday. It'll just be Friday in all capital letters. I can also create a strongly typed music type. Well, let's do day. Let's stay with the same example. So let's say days. Let's say I want to create Tuesday. So I'm just going to say days. It's going to be Tuesday. So sure, I could say days.tuesday. That's the literal way to do it. But I could also take some input to see what day they want to pass in. So in fact, let's just make this the user's day, whatever it is that the user gives us. And so the user passes in some kind of a day, and let's say they pass in Tuesday. So what we can do to turn a string into an enum value type is we would say days.valueof. And then in the quotes, you would just pass in that string. And then that gives us a strongly typed days enum. So that's it for enums. Enums are used as labels, although they can have methods as well. And they're really used to enable us to do strong typing, that we can check at compile time to see if we've done anything silly.
In this section, we're going to focus on strings. And you've been working with strings, so you know that that's just text. But strings are very unique in the Java programming language. They're objects, but we can do things to strings that we normally can only do with primitives. We're also going to cover the subject of immutability in this section.
I'm willing to bet that as you code more and more in Java, and you take a look at your applications, that the number one, or very, very close to number one object that you'll use over and over again is going to be the string object. So we're going to take a little bit of time to talk about strings and how they behave in Java. They are special in Java, and they're special for a couple of reasons. Now, first and foremost, a string is an object, and so it behaves just like an object. There is state, which would be the text, and then there's a lot of behavior. There's tons of methods that you can use on a string. And as a side note, for those of you taking the exam, we're not going to cover all the string methods that are available here, but it is your job to go and read the string API and learn the methods that they have. I'll talk about some high-level things to remember about strings, but you're going to want to become familiar with most of the methods that are in the API. So strings behave like objects, but we can do things with strings in Java that you typically can only do with primitives. And we'll show you some of that syntax coming up in this section. Now let's start by looking at the string object. So here's some code where we say string s equals new string, and we're creating a string object for hello world. So s right now is on the stack, and it is referring to the hello world object on the heap. And you can see that the heap are a set of characters, a set of chars. Now these chars are sequenced, and they are sequenced starting with the index of 0. So here's what hello world really looks like. Index 0 has the letter H, index 6 has the letter W, index 10 has the letter D, and so on. And this index, the numbers that we're seeing here become important because whenever you're using methods on the string object, sometimes they want to know ranges. Like if I wanted to get a substring, I want to get just the word hello out of there. So what I could do is pass in the numbers 0, 5, and it would go from 0 up till 5, and would then would return a string that just contains hello. So keep that in mind, that a string is a sequence of characters, and those characters are indexed starting with 0. So getting back to how strings are instantiated, it's a normal object. It's a class that's written in part of the Java API. It's in the the java.lang package. And here again, another way, or the same way to create the string that we just saw, string s1 equals new string mulligan. However, because we use strings so often in Java that they've given us a literal syntax to use as well. And so the literal syntax says you can drop the whole new string if you'd like, just put quotes around the text that you want, and that will become a string object. So double quotes is a string literal, just like single quotes is a character literal, or a whole number is a integer literal, and a number with a decimal is a double literal. So now we've got string s2 equals Seamus. Now there is one key difference between those two strings, and it's really how Java treats the objects on the heap. What happens is when you create a string object using the new keyword, like we did with mulligan, then what happens is the string object will be created even if another string exists with the same name. And that'll be true even if all the characters are the same of another string. What do I mean by that? Well, let's look at some code. So here we've got two strings that we're creating, and they both have the exact same sequence of characters. We've got mulligan and mulligan. And so as you say new string mulligan, every time you say it, it creates a new object on the heap. Now, you're probably thinking, well, duh. I mean, of course it does. That's what I would expect. You made two objects. Why wouldn't you have two strings? Well, because strings are so predominant in application that it's kind of a waste of space to keep having the same string on the heap over and over again. So when you use the string literal syntax, like we're doing here, string mystring3 is Seamus and mystring4 is also Seamus, then what it does is it looks in a string pool. And it says, does this string already exist? Is there a sequence of characters that matches the literal that you've just tried to create? And if so, then both of these string variables on the stack will be pointing to the exact same string on the heap. Now, of course, the benefit is that we're saving some memory, but there's some problems there too, right? Imagine that mystring3 is in one section of code and mystring4 is in some section of code. What would happen if mystring3 changed the string? Would mystring4 see that change? And that's a question we're going to answer in a little bit. It's also legal to create a string with no characters. So here we've got string s equals quote quote, and we refer to that as an empty string. We want to be clear that is not the same thing as null. That's different than saying string s equals null. Null and empty string are totally different. An empty string is still a string object. All of the methods that are available to string are available on that empty string. Null means that the reference isn't referring to anything, so there is no object to back it up. Now, before we talk about the whole what happens if a reference variable tries to change a string, what happens to the other variables that are pointing to that string, we'll talk about what happens there in just a little bit, but before we do, let's talk about string operations and operators in the next lecture. We've been looking at some of the different methods for a string in many of the previous lectures. We saw substring at one point, we saw trim at another, and what we're going to do is kind of revisit those methods and just take a look at how the string can be manipulated. Now, so we'll start by creating a string. We're doing a new string saying hello world. Notice that there's some spaces after the word world. So we've got a little bit of white space in the string itself. Then we're calling the method substring. So we're using that dot operator saying s.substring, and we're passing in two integers. Now, how would I know that it requires two integers? Well, I'd have to go to the API documentation. From there, I would discover that there's a method called substring, and we'd see that it takes two parameters. The first parameter is the index that we should start at. It's inclusive. It'll include that character. In other words, think about a string, hello world. We've got 0 for the H, 1, 2, 3, 4. So we're going to start with the letter O. And then it says it's going to continue on until the 10th character, but that's exclusive. So that will get us all the way to L because D is the 10th indexed character. So that gives us O whirl back. Now here's something that's very interesting about strings and something you have to remember, especially for the exam, that a string is immutable. Now I'm going to talk a lot more about that in a second, but I want to bring it up now so that you know that when we call substring, that it's not actually changing the original string. Okay, what it's going to do is it's going to create a whole brand new string, and then it's going to return it. So if I didn't capture that return value, like I'm doing here with string sub, if I didn't capture that new OWorld string, then we'd lose it and it would eventually be garbage collected. So that's a gotcha on the exams. Make sure that whenever you're working with strings and you call these methods, that in fact it does return a string and that string is captured. Otherwise, it kind of looks like you're changing the string, and we're not really doing that. We're creating a new string. So here's another one, s.trim. And so what that's going to do, trim will remove the white space before and after at the end. Doesn't do anything in the middle. So in that case, it's going to return a brand new string called hello world with no white space. And we also have to uppercase. That would return hello world. Notice the spaces are back because when we called on S never changed. That hello world string still exists. And so it still has the spaces, even though we called trim, because trim isn't removing the spaces of the existing string. It's creating a brand new string without the spaces. So now we've got to uppercase, and that's going to return hello world. Here's a method called char@, character at. And so here we're passing the index of 2. So remember that's 0, 1, 2. So that will return an L. And we take that return value and store it with a character. And so there are lots and lots of methods that are available to you, and that's because a string is an object. It's an object that has lots of methods. So how do you find out what methods there are? Like I said, go to the API documentation for Java Lang String. Here's a little snippet. You'll see all of the different methods and what they return. Just remember that whenever you are calling a method here like concat or substring and it returns a string, that it is in fact a brand new string. So that's Java behaving like an object, as we would expect. It has methods, it has behavior. But I mentioned that we can do things with strings that we typically can only do with a primitive. And one of those things is that we can use the plus operator on a string. And what that does is it appends or concatenates strings to one another. So here's an example. I've got a string here called greet. It says hello. I make another string called name. It's set to Dave. And now I have a third string where I'm concatenating greet plus name. All right, so that str string would be hello Dave. And that's something you can't do with any other object. I couldn't use the plus operator on anything other than a primitive or on a string. So again, the str string now points to a literal called hello Dave. We can also use assignment operators with string objects. So here's another example. We've got a string str for my dog, and we can now say str plus equals. If you remember, the plus equals assignment operator means that we're taking the string and we're going to concatenate has fleas to it and then assign that new value back to the variable str. So now if we print out the str variable, it'll say my dog has fleas. In the last lecture, I mentioned that strings are immutable. And all that I mean by that is that once a string is created, we can't change it. And that's actually a good thing. Think about the question I posed in the first lecture of this section. I said, if we've got string literals, 2 string literals, and they are pointing at the exact same string, what if one of those reference variables changes the string? Wouldn't that change for everyone? And that would be a problem. So to get around that, the strings are immutable. Once it's created, it's guaranteed to never change. Now, of course, we saw that the string object does have methods. We've got methods like, trim to uppercase, substring. And each one of those methods appears to do something to the string, but really all that it's doing is taking the existing string, creating a new string out of it that has whatever rules we've just invoked through a method. So if it was to uppercase, it's going to basically take the same characters, but make every character uppercase. and that will be a new string. They didn't change the original string. So that's it. That's what it means to be an immutable object. So let's take a look at an example. We can see that this is true even with the concatenation operator. So I've got 3 strings. It is, a dog, and day afternoon. And if we look at the JVM, we'd see that on the heap, we've got our 3 objects, and we have 3 variables, each pointing to their respective string. So nothing out of the ordinary there. But now let's start to play around with this. So now I've got my strings A up here in the top right, and I'm going to set A to be A plus B plus C. And then I'm going to take C and set that to be wow. And what happens now to the memory? Well, now we've got a little bit of a mess. So A is pointing to this completely new string. It is a dog day afternoon. B is still pointing to a dog, and C is pointing to wow. So now we've got 2 strings that are just sort of sitting there. Nothing is referring to them. And so the question is, well, so is that a problem? And the problem ends up being related to performance. So remember that anytime we start to have a lot of objects that have no references, that the garbage collector is going to be kicked off, and it's going to remove these objects from memory. And that can impact performance. Now, how bad can that impact be? There's a whole lot of variables to that. You know, what version of the Java platform are you using? Are you on a multiprocessor server? Did you customize the algorithm, or did you choose a custom algorithm for the garbage collector? There's so many variables, but it is possible for garbage collection to impact performance if it's being kicked off too many times. So what developers are encouraged to do is use string builder and string buffer instead, because these are classes that have a mutable sequence of characters. The strings that they wrap are in fact mutable. So what's the difference between string builder and string buffer? If you look at the API, the methods are similar. They do the same kind of thing. They essentially allow us to work with strings. But the main difference is that string buffer is thread safe and string builder is not. Now, talking about threads and concurrency, that's really out of scope for this particular course. But just know that if something is thread safe in Java, that it's going to be a little slower so that it can add some protection to deal with the problems that multiple threads can bring with them. So if you're not doing multi-threaded programming, if your collection is not in any danger of being attacked by multiple threads at the same time, you don't need to slow it down and use something that's thread safe. You can just use something that isn't, and it'll perform a little bit better. So in general, unless you're doing concurrent programming, you're probably going to choose the string builder. So let's look at an example. We're only going to look at a small example of this class. For the exam, you should know that they do ask about string builder and string buffer. And so you're going to want to just be familiar with those APIs as well, just like you were with string. The big thing to remember is that a string is immutable. So if you call a method on a string, make sure that the code is actually dealing with the return value. Because if it's not, if it's just calling substring or trim and it's not capturing the return value, assigning the return variable to another variable, then you're going to run into issues. It's not really doing anything. So let's look at some code. So here's an example of concatenation. So we've got our string message, which is set to hello. We're doing the assignment operator to change message to be hello and whatever the name is, and then adding today is, and so on and so on. And this is going to create any number of strings. Now, Java can do some optimizations when it's being compiled. It can recognize in certain scenarios that the concatenation operator is happening, and if it's able to determine what it would be for sure, that there's no variables and no runtime resolution of how this is going to be concatenated together, then it can actually, underneath the covers, decide to use string builder which is nice. But you shouldn't really depend upon it. If you're writing code like this that's doing a lot of concatenation, then what you should do instead is use the string builder. So here's string builder. We create it just like we would any other object. String builder SB equals new string builder. And then instead of using the plus sign or plus equals, we use append. And so we don't need to capture the return value because we are actually, changing the string that's inside of there, the sequence of characters. So the bottom style of using string builder is what's preferable. And again, for the exam, take some time to read the string builder API and read the string buffer API, and just make sure you're aware that these are mutable classes versus the string, which is immutable. Now that we spent a little bit of time talking about strings, we can revisit the topic about methods and method invocation. Remember that invoking a method, calling a method, these are terms that mean the same thing. Now, oftentimes when we invoke a method, they've listed some parameters that we are to pass in. So when we pass in variables to a method, what's really happening? And it's no matter what I tell you, the answer is always going to be the same. We are passing in the value of the variable. But when you actually run your code, it can look like different things are happening. It manifests itself in kind of an interesting way. So we're going to dive down into this topic and see what happens when we pass in a parameter to a method. Now, there's really just two kinds of things we're going to pass in, at least at this point. A primitive, so we can pass in a primitive, and when we do that, we pass by value. Remember what I said, everything is always going to be passing by value. So what that means is it would look at the primitive, look at its value. Let's say we've got int x equals 10. So if we pass in x, the value of x is 10. And it's going to copy that value, 10, and then pass that into the method. With an object, it's still passing by value, but the value is different. The value isn't an object. The value is a reference to an object. And so the reference of that object is passed into the method. So what we'll do is we'll look at two different classes to show what that looks like, what happens when we pass in by value with primitives and objects. So here's the program that we're going to run. There are two classes, and do remember that you can only have one public class per file. So there'd be an account.java for this file. There'd be a bank.java for that file. And the bank is what's going to really be running the program. That's where our main method is. Bank has three different methods: discount loan, which accepts a double; debit fee, which accepts an account, an object reference; and then salutation, which takes a string. And what they're going to do is they're just going to manipulate the data that was passed in some sort of way, and then we're going to look at the original variable that we passed in and say, what happened? Do we see anything different? Now, the account, I should point out right here, just has one piece of state. It's a double. It's called balance, and it has a value of 100. So now let's run through the code. All right, so remember, every time a method is going to be called, that it's going to get its own space on the stack, which is a frame. And so that frame is going to contain all of the variables that were declared once that method was called. So even the main method is going to get its own stack space. So let's take a look and see what happens on the stack once main is invoked. So here's our method, public static void main, and it's going to be added as a frame to the stack. Now, looking at this right here, we can see that there's already at least one variable that's been declared, and that's an array of strings. So remember, we can tell that something's been declared because it has the type next to the variable name, and a string array is a type. So we're going to create our account. My account is going to be referencing an account object. We have a primitive, which is our proposed loan at $250. We've got a customer named Jason Shapiro, so it's a string. And this is what the stack is going to look like, the stack and the heap, after these lines have been executed. So you can see my account is referring to that account object. The account object has that balance of 100. Proposed loan is a primitive, so we have 250 there right on the stack. and customer name is referring to Jason Shapiro. So in code, what that's going to look like is we'll call discount loan, passing in that proposed loan, and then we're going to print out proposed loan to see what its value is. Is it still $250 after we have passed it in a discount loan? We'll do the same thing with debit fee. We'll pass in the my account reference, and then we'll print out myaccount.balance to see if anything has changed. And then finally, with salutation, we'll pass in the customer name, and we'll print out the customer's name. Same thing, see if anything has changed after we have passed in the variable. So discount loan is called. A new frame is added to the stack, and the proposed loan primitive will be passed by value to that method. So here's the method that we're invoking. We're going to call discount loan, and we're passing in that variable proposed loan. And the method that we're actually calling here is discount loan is going to get a frame on the stack, and take a look, what variables will be in that frame? Hopefully you can see that there's only one variable here that has its type referenced, and that's the double X. So that'll be a part of the frame. It's going to take the value of X, multiply it by 95%, and then we'll get our new loan, which is $237.50. We're reassigning that value to X. So we're taking X, multiplying it by 95%, and then reassigning that new value to X. So the question is, what's going to happen after we print out proposed loan again? So let's look. So here's what ends up happening. On the stack, we now have the discount loan frame. And when we invoked discount loan, it copied the value of proposed loan. It didn't copy the variable. It copied the value. So 250 was passed in and assigned to X. So at this point, we now have two different variables. We have X that's at 250 and proposed loan that's at 250. So now inside of discount loan, X is going to be changed. So now we've got two different values on the stack. We've got X, which has the brand new value of $237.50, but notice that proposed loan wasn't touched at all. All right, we copied the value. So discount loan was really working with a completely different copy. And what happens now when discount loan is finished? Well, anytime a method is finished, it's popped off the stack. So discount loan is floating away. The memory there is going to be reclaimed and reused. And so discount loan disappears, and so does the value of X. And so what are we left with? Well, we're left with 250. So if we printed out proposed loan, we'd still see 250. Bottom line there is that whenever you are passing in a primitive to a variable, passing in a primitive variable to a method, just remember that any changes that are done in that method will not affect the original variable. Now, can you think of a way that we could affect the original variable? What we could do is return. Actually, I'm going to jump back to the code here. So if we look at this discount loan, rather than just assigning a X and returning void, what we could have done is return the new value. We could have said public static double and returned a double, returned the new value of $237.50. Proposed loan could have, instead of just saying discount loan, proposed loan, they could have said proposed loan equals discount loan. You following me? So we would return the value and then reassign it to the proposed loan variable. That's the only way we could change the original variable. Now let's go on to the next lecture where we'll look at what it means to pass in an object reference to a method. All right, now let's look and see what happens when we pass in an object reference to a method. So we've got a method called debit fee, and we're going to pass in the account reference. So when debit fee is called, a new frame will be created. This is the method invocation. We're going to say debit fee, passing in the my account variable. And here's the definition. So what's going to happen is debit fee is going to accept in an account. And when debit fee is added to the stack, gets its own frame, you can see that there's only one variable that's going to be added to that frame, and that's the account. So this account right, where's my cursor? There, the account right here. So that's what's going to be added to the frame. And then inside of the method, what are we doing? Well, we're using the dot operator to send that object a message. We're picking up that telephone and saying, hey, account, can you tell me what your balance is? Can you read me your balance? Now that's a read because it's on the right side of the equal sign. So it does a read. It says, hey, it's 100. And we do a little calculation in here. We subtract 250. Then we're going to take that new total and call account again and say, I want you to set your balance. I want to do a write. Set your balance to be this new 197.50. So how does that manifest itself? What happens then when we go back into our main method and say myaccount.balance? What will we see? Well, here's what the stack and the heap look like. So debit fee gets a frame on the stack, and the main method is going to copy the reference. So remember, what is the value of the myaccount? It's this arrow. That's the value. It's the object is not the value. It's the reference to the value. So that arrow, that reference, is getting copied into the debit fee frame, into the account ACCT variable. So they each have their own reference, but they are referring to the exact same account. So now when I do something to it, when I do a write on the account balance, that write is actually going to happen here on the heap rather than just in the debit fee frame. So because we were sending a message to the account object on the heap rather than just doing some kind of a calculation on the inside of the debit fee method itself, that we really changed the balance. We changed the balance of the object on the heap to 97.50. So once debit fee is done, that frame is popped off the stack. The account balance is still 97.50. So now when we say system out print line myaccount.balance, we're still picking up the phone in my account, sending a message to the account object on the heap and saying, hey, what is your balance? And so in the main method, we do see the new balance. So for the final example, we're going to look and see what happens with the string. So the method we're going to call is salutation, and we're going to pass in that customer name, which is referring to the string Jason Shapiro, into the method. Now the method definition accepts a string, and once it executes, it's going to concatenate the word dear in front of the name and then reset a name to this new value. So a name equals dear a name. So when we first call salutation, this is what the stack and the heap look like. Once again, customer name is going to be passed in by value, and the value is the reference. String is an object, right? So this is the reference to the object. That's going to be copied and passed into the salutation method. A name gets its own space in the frame, salutation, which is now referring to the exact same string. They're both referring to them, just like was happening with account in the previous example. But what happens now when we try to execute the code, dear a name? The problem with, or not the problem, the reality of strings is that they're immutable. And so as soon as we make a change, it's not going to change the original string. It's going to create a brand new one. So customer name is still referring to Jason Shapiro, whereas a name is now referring to a brand new string called Dear Jason Shapiro. So once salutation is finished executing, it's going to get popped off the stack. That whole a name variable is gone. It's fallen out of scope. And so that string, Dear Jason Shapiro, nothing's referring to it anymore. And so eventually it'll be garbage collected.
We're now going to turn our focus to the concept of object-oriented programming. Now, of course, we've been doing object-oriented programming all along, but we're going to really focus on the pillars of object-oriented programming. In this section, we're going to focus on encapsulation, and we're going to see specifically what is encapsulation, why do we want to do encapsulation, and then how do we apply it to the Java programming language.
The term encapsulation is often used a little differently depending on who you speak to. There are really two terms that are that go with each other, encapsulation and data hiding. And because they're so frequently used together, people often use them interchangeably, although they are really two different things. Encapsulation is strictly just the technique of bundling data with methods that operate on that data. So an object is encapsulation. But Data hiding is this idea of how the object should be accessed. And specifically, we prohibit the data of the object to be accessed directly. Instead, we provide these methods, the encapsulating methods, and depending on what we expose, other clients, other users can then access the data through these methods. They can either read the data or set the data depending on what rules we've established. And the way that we establish rules are through access modifiers. Now, there are 4, but there are, really there's only 3 words, keywords that we can use as access modifiers. And then there's a 4th, which is the absence of a modifier and what that means. But the 2 most popular are public and private. And public simply means this piece of code can be accessed anywhere. So if we're running a program and we try to access this piece of code, it's available. It's public. If we say private, then we mean this is only available to the class itself. And that is different than saying it's available to the object that's been built on this class. So it's literally only available inside the class itself. And we'll see some examples to help solidify this concept. So the idea of encapsulation and data hiding is that the data we have in our objects are going to be hidden, and we'll hide them by using the private access modifier. And then we'll create some public methods to expose that data in any way that we see fit. Now let's take a look at the MyDate class that we've been working on and see how encapsulation can help improve the quality of our program. So when we don't have encapsulation, which by the way we don't have at this point, the class is going to look something like this. Now we've cut out some of the methods, but just looking at the data, we've got a public int day, public int month, public int year. They're all public, which means the day, the month, and the year can be seen and manipulated by any code in our program. And if you remember when we did the lab for the packages, we felt like we had to do that. We were trying to access these fields from another package, and so in order to make them available to that test code, we had to make these fields public. And all of a sudden, all the code worked and everything was fine. When you first start programming, this feels kind of natural. Of course, I want all of my code to be available to the other parts of my program. Why wouldn't I? Well, let's see what can happen. So first of all, someone decides to use the MyDate and they use it correctly. They create a MyDate object. They set the day, they set the month, they set the year, and everything works great. If we run this program and we use the date, it's being used exactly as we intended. No problems there. But now someone else creates a date that doesn't actually make sense. They're creating this leap day. It's February 29th, 2017. And the problem is that the 29th doesn't actually exist. Like here's another example. Here's a February 1999 calendar. There's no 29 there because that's not a leap year. So what's the problem? Well, if we're trying to mimic the real world with our objects, if we create some kind of a class that can be used in a way that breaks the rules that we're trying to follow, that is, in this case, valid dates, we're not really mimicking the real world and we're not achieving our goal. Other things that could go wrong. Someone could decide, well, I've got a day and I want it to go to tomorrow. So what are they going to do? They're going to increment the day. So they do a day plus plus. Now, if today's date is February 7th, that's fine. If you do a day plus plus, then it's going to say it's now February 8th and everything works correctly. But what happens if we're at, say, January 31st and you do plus plus? Well, to the JVM, a day is just an int. It's a 32-bit number that has a range from a negative value to a positive value. And so when you say day plus plus, it doesn't think, wait a second, that's not a real day. It just does it. And so at that point, our date would be January 32nd, 2008. And imagine if it was December. Then it's completely screwed up because we really are trying to get to January 1st and whatever, increment the year, in this case to 2009. So what we see is that when we expose the data, that people can use and set the data in a way that really wasn't intended. So we've got a validation issue when people access data directly, but we have other issues as well, namely flexibility. Imagine that we think about Well, imagine that a lot of people are using the MyDate object, and we're finding that it's using quite a bit of memory. So the question we are asked is, do we really need an int to store that day and month? I mean, really, how big can a day and a month get? I mean, we're talking for a month between the numbers of 1 and 12. An int is a 32-bit number. That's overkill. So what if we decide to change it and we go into our class and we say, yeah, we hear what you're saying. Let's change the day and the month to be a byte, an 8-bit number. I mean, that's still going to go all the way to 127 on the positive side, which is more than enough that we need. So we make that change and we put this code back into our code base. All of our teammates download the new code and they try to compile their program, and it breaks. We've broken everyone else. And how did it break? What happened? Well, imagine that someone is creating a date, and they had said previously arm.day equals 11, arm.month equals 11. That worked fine. That was legal. The problem here is that what is the literal type of 11? The literal type of 11 is an int, and then we're setting this arm.day to be an int. We've just changed day to be a byte. Same thing with month. Now, a 32-bit number cannot be stored in an 8-bit variable without casting, right? And since no one had written casting code before, all of their code just broke. Now, you may remember that I said if we do something like byte b equals 11, that would work. So byte b equals 11. Sure, that would work because we are declaring the variable and initializing it all on the same line. And so it does sort of this implicit cast. That's different than what we're seeing here. We're not declaring the variable. The variable already exists. It's already been declared, day and month. And so when we try to set an integer value to the byte variable, it's not going to let that happen. We've seen that allowing direct access to the data from anyone using an object of the class is really not a good idea in general. What we want to do is we want to make sure we're not having any issues of validation, any issues in terms of our own flexibility for making internal changes. And the best way that we can do that is with encapsulation. So encapsulation hides the detail of how things are getting done. And what we'll do instead is we'll expose certain methods, and those methods will be referred to as the interface of the class. That's what everyone else is going to be able to interact with. Now later we're going to talk about a construct called an interface with a capital I guess. And that interface has similar functionality, but it's different than what I'm talking about here. I'm simply saying that when we design a class, anything that we set as public is the public interface of the class. Those are the methods and the variables that we've exposed to anyone that wants to use an object of this type. So we can use accessors and mutators to create this interface of the class while we hide all the data details. Now, accessors and mutators are more commonly referred to as getters and setters, and that'll be pretty obvious why once you see the code. So here is the code once we've applied encapsulation and data hiding. First thing to note is that all of our instance variables are now private. All right, so we've got our day, month, year, we've got a Boolean leap year. They are all private. And then what we do is we create our getters. Now, this syntax that I'm showing you, this comes from, or at least is used by, something called a Java bean. You might have heard of this term before. A Java bean is different than an enterprise Java bean. So it's a totally different construct. A Java bean is really a simple class that has some private fields and then getters and setters. There are a couple of other rules regarding Java beans. If you want to be very strict, you can't extend any other class. There needs to be a default constructor. But in general, this is what a Java bean looks like. So our getters are what exposes the data. If someone wants to actually look at the day, the month, year, or leap year, we use the get method. So get day, get month, get year Notice that none of these methods take any parameters, and then they just simply return the type that the user has requested. Whenever we're dealing with Booleans, we use a slightly different naming convention. Rather than get leap year, we say is leap year, which just makes a little more sense. Setters are a little bit different, so this is how the user can manipulate the data. So we've got set methods for set day, set month, set year, and so on, set leap year. And they accept one parameter, and that's going to be the new value. Now, the reason we're using setters, instead of just allowing them to access the data directly, is that now we can run all of this code through some sort of validation. So you notice here that what we're doing is we're checking. We're saying, hey, they've given us a day in the set day method. Let's make sure that this day is still valid with the current month and the current year. And if it is, great, then we'll set it. And if it's not, we won't. One other thing about the naming convention that we're seeing here, and again, this is the naming convention of Java Beans, is that we're using lower camel case. I'm going to jump back to where we can see the variables. So we've got all lowercase day, month, year, and then lower camel case leap year. Notice that our getter methods apply lower camel case as well. They start with the word get, and then they capitalize the name, the type. So we've got get day with a capital D, get month with a capital M, and so on. Is leap year, we've got a capital L and a capital Y. Same thing for the setters. Set day, set month, set year, set leap year. They're all lower camel case, and that is the naming convention to follow. So here we've got our valid month method, and feel free to pause this screen and take a look and see if you can figure out what it's doing. I'll tell you at this point, that's not what is important. The important part is noting that we are able to create a method, and we can then validate what people are passing into us and prevent them from giving us bad data. So no one would be able to accidentally create a February 29th when it's not actually a leap year, for example. Also notice that this method is private. So here's kind of a general rule that I always follow when I write code. I make everything private. I just start with a completely closed off class. And then as I start to add more functionality, I think, what do I really want to be exposing at this point? And then those methods I turn public. Now, with this valid method, I don't really have any reason for anyone outside of the class to use this. This is private for me to determine whether or not I want to allow someone else to set the day, to set the month, or set the year. But maybe at some point I don't want to use this valid method anymore. I can just get rid of it if it's private because no one else would be using it. And that's one of the other rules that we want to follow when we're coding is when we create a method, when we create something that's public, I should say, that anyone could be using, we do not want to get rid of it as much as possible. Because as soon as we get rid of something that's public, we've probably broken a lot of code that others have written. So there's a general rule that types should be open for extension, but really shouldn't be open for modification. And what they're saying is, don't remove stuff that people are using. Don't change the signature of a method if someone's already using it. Obviously, there are times where that's just not possible. You have to go in and make changes, but we really want to reduce that as much as possible. Granted, now that we're employing encapsulation, our classes are going to be a little bit bigger, but it's worth it. Trust me, it is absolutely worth it. Let's just once again remind ourselves of what we can and can't do. So if we set all of our fields to be private, now when someone instantiates a MyDay class, let's say they called it D, that they will not be able to read or set the variables directly. They won't be able to say d.month equals 12. That's illegal. It's not even going to compile. What we are doing, though, is we're forcing them to use the methods, to use the interface of the class that we are exposing them to, which in this case is the method setMonth. So now they pass in the number 12, and we can employ our validation logic. We can actually check to see if it's okay, and if it's not, we don't have to set it. We can't really make that same kind of stop when they're setting the data directly. It's just setting the value. If we can legally say d.month equals 12. There's no way for us to get in between there and say, well, let me check it first and then we'll see if you can do that. But we can do that with a method. So that's one of the reasons we do this. We make sure that what they're giving us is valid. And also, we now have the flexibility to change the inner structure of our objects. So I can go in and I can change all of my day, month to be a byte. And what we do at that time is, remember I said a best practice is really to, let's leave those methods alone that we've said are public, that, other people are using them. But we would have that problem, right? If we changed the day and the month to a byte, if they try to set the day or the month with an int, which is what they had been doing, it will break. We saw that earlier. But what we can do now is we've got the set day. They give us an integer, the day. We run it through our validation to make sure it's okay. And then at the very end, here we're casting. We're taking their int day, casting it to be a byte, and setting it. And that's legal and good. Same thing here. We're taking their int month they passed in, casting it to be a byte, and now we can set it to our new data type, which is a byte. So, and that makes a lot of sense, right? It makes much more sense for us to fix the code in one place than to simply break everyone else that was using this class and expect them to fix it in the hundreds or thousands of places that they were using it. Now, of course, some mutator methods, some setter methods will not fit the mold of what we've done here so far. You remember we had this day plus plus, and we said that, that could produce an invalid day. Well, how would we, what kind of method could we create to allow the user to do what they were trying to do here? And, well, we could make a method called tomorrow. And here, when they call tomorrow, we'll double check to see if we should increment the day or if we should reset the day to 1. Should we increment the month or should we reset the month to 1? And then we can increment the year if that makes sense as well. So you can make any methods in addition to the getters and setters that we've shown as long as it supports the class. All right, now let's review what access modifiers we have available to us. So if we're going to do encapsulation, we have to limit some of the parts of the objects, and we do that through access modifiers. Now, in the MyDate example, what we did is we took all those instance variables and we changed them from public to private. And private means they're only available to the class itself. We can add access modifiers really to almost any part of the class definition. You can do it on not just instance variables, but static variables, static or instance methods, constructors, even the class itself. Although there are some rules for a top-level class in your file, it can only be public or the default, which I'll show you what that means in just a second. But really only those two access modifiers are available to the class itself. So let's look at the different access modifiers. Here's a table of the ones that we have available, and I'm really only going to focus on 3 of them right now. In the next chapter, we'll talk about inheritance, and then we'll talk about the 4th modifier at that time. So the 3 I want to focus on are public, private, and default. Whenever we have the modifier public, it means that access is not limited. Any code in our program can either read. If it's a field, they could read it, they could set it. If it's a method, it can be invoked. It can be invoked from anywhere. Private is the most restrictive, and it just says that absolutely nothing can read, change, or invoke this member unless it's being called from the class itself. And then the final type here that I'm going to talk about is just called default. Sometimes you'll hear it referred to as package or friendly. Basically, it means the absence of a modifier. And let's look at some code so I can show you what I mean. So this represents the state of our MyDate class as it exists right now. And we set everything to be public so that any code could access it from anywhere. And we did that in our lab because we had some test classes which were in different packages, and we wanted that code to be able to see and change these fields. But before we had that, we really didn't have any modifier at all. It really just said int day, int month, and int year. That's what I'm referring to when I talk about the default access modifier or the package or friendly. So anything that doesn't have an access modifier is assumed to be available to the class itself and any classes that are in the same package. If we change this to private, now we are only going to have access to this code in the class itself. And it seems like a simple concept, but I want to further define this. Let's make some public methods. I'm just going to make one. Public int get day. And we'll return the day. So I've got a private int day for my field and a public method to call it. Now let's go into another class. It happens to be in the same package. And I'm just going to give us some space here, ignore everything that's below. And let's instantiate the day that we just created, the myDate. So I'm going to say myDate d equals new myDate. This is, I think, the first part that confuses people when you're first learning Java. There's this feeling that myDate d is actually the myDate object. So I should be able to say day equals 12. And of course, I can't do that. You can see that I'm getting an X. And the reason that we can't do that is if we look at the myDate, day is private. I can only access this field in the class itself, as I'm doing right here. On line 9, I'm accessing that private field, and that's legal because I'm in the class itself. But in my course examples here, I'm not in the class itself. I'm in a completely different class, so I don't have access to day. And I think the reason that's confusing is most people start to think of D as being the object itself. They're saying, well, why can't the object access its own day? That seems odd. But that's not, in fact, what's happening. The value of D is a reference to the myDate object. And that's why I use that analogy of a telephone. So we pick up the telephone, and that dials the object that D is pointing to. And then we say, listen, we want you to set your day to be 12. And the object says, okay, but where are you calling from? And we say, well, we're in course examples. We're in the same package as you, but we're in a different class. And then the object on the other end of the phone says, sorry, unless you're in the class itself, I'm not going to allow you to change that. So that's why I like that telephone analogy. It helps us understand access modifiers and the rules a little bit better. Of course, I can call d.getDay because that is a public method. That's completely legal. So those are the three access modifiers that we're working with so far: public, private, and then just sort of the default package level, which means it's available to the code itself. In fact, I'm going to just put this back one more time to D is day. And I'm going to show that if I get rid of this whole private here, now we have the access modifier of default, and in my example, it's legal because we happen to be in the same package. Now, most people are pretty much going to stick with public and private for the access modifiers, but especially if you're taking the exam or if you're writing some more complex hierarchies and structures of your code, you may want to use some of these other modifiers. There is one modifier we haven't looked at yet, and that's protected. It's going to make a lot more sense after we look at the next section because it's tied to the concept of inheritance. But let me just tell you what it is. I'll show you what it looks like, and then we'll revisit this modifier in the next section. So if I jump to the myDate, I can change the access modifier to protected. And so here is a protected int day. And what that means is that this variable day is available to the class itself. It's available to any code in the same package, and it's also available to any subclass that's in any other package. And there's a few little fine points to that last rule, so I'll show you that a little bit later when we start talking about inheritance.
In the beginning of this course, we mentioned that object-oriented programming languages are very extensible, easily extensible. And so that's one of the things that we're going to see in this particular section called inheritance. So we're going to see how we can take an existing class and then add stuff and change stuff to create a more specialized version of it.
When we look at the classes that we build for our applications, we often find that there's a lot of similar structures, a lot of similar functionality in multiple classes. And of course, we could rewrite everything over and over and over again, or we could take advantage of object-oriented programming and reuse some of the code between the classes. So one of the ways that we can do that is to take the common functionality and put that into a separate class which everyone else is dependent upon. And that follows the whole DRY principle I mentioned before. Don't repeat yourself. So if you find that the same code is written over and over and over again, maybe it makes sense for that code to be in its own object. We have, for example, the MyDate class. And MyDate can be reused in a whole number of classes. People have dates. We've got such as birth dates and anniversaries. Companies have dates, such as the fiscal year, IPO date. Orders have dates, such as shipping and billing dates, and so on. So what we can do is reuse that MyDate class in a whole bunch of other classes itself. So look at person here. We've got person, and it has a first name and a last name, and that's some reuse right there as well. String is an object. We are taking all the functionality of what it means to be a string, putting it in one object, and then reusing that in our custom classes. Same thing with address that we have down below. And below that, we've got the MyDate. So here we've got our date of birth that we've just created. And so this act of taking other classes and using it to build our own class here is called composition. So we are being composed of other objects. Composition is one tool that we can use for code reuse, but the other is inheritance. So let's look at the problem and then we'll fix it. So this is an employee. An employee is using composition. It's using strings and address objects. It's using MyDate and so on. And we also have, what's kind of cool here is we've got two MyDates, right? We've got a MyDate for the date of birth, and then we've got a MyDate for the hire date as well. So we are using composition to build another type of a object, an employee. But if we look at this, we'll see that we're still repeating ourselves. An employee makes sense, right? That they have a first name, a last name, a home address, and so on. But if I jump back to the person, all of that information is in person too. The only thing that's different is that we went in and we added two new fields. We've got a hire date and a salary, and we added a new method, promote. And so this is a style of coding, probably the oldest methodology of coding, called the copy and paste coding. And it's something we don't want to do. We want to make sure we follow and adhere to the DRY principle. Why? Once again, what happens if we change our strategy, our tactic of what it means to be a person? Well, not only do I have to go into the person class that we have here and make that change, I'm going to have to find every other type that's in our project and follow those same rules. And if I don't, then we're going to have an inconsistent application. So composition is a really great tool for achieving code reuse, but it's not the only tool. One other thing I want to say about composition is that it follows what's called the HAZA rule. And so if you're wondering if you should use composition, one of the things that you can say is put the words HAZA into a sentence with the type and the class. Let me give you an example. An employee has a first name. An employee has a last name. An employee has a home address, and so on. And so that shows this is great. This is a great usage of composition because the HAZA rule has passed. So there's another similar rule. It's called the ISA rule. And inheritance describes an ISA relationship. For example, the employee is a kind of type or person. And we can just say it right in a sentence. An employee is a person. Does that make sense? And the answer is, yeah, that makes sense. How about an employee is a hire date? Doesn't really make as much sense, right? An employee is a salary. No, an employee has a hire date. An employee has a salary, but an employee is a person. And while there's a lot of debate about how strictly you should follow these rules, it's a nice way to start. It's a good way to help you start thinking about how to organize your classes. So let's look at this code that we have here. We've got our public class employee, and the way that we set up the inheritance structures, we say extends person. So extends is the key word here to say we are doing inheritance. An employee is a person, but you don't write is a, you write employee extends person. Now, one of the benefits of inheritance is pretty obvious. Look at all the code that we just got rid of, right? We had all that code that we were repeating that had originally been in person, and we just basically cut and pasted right into our employee class. Now by saying extends person, we can get rid of all that code. But it's still part of the class that we created. All that person code that we had originally is still a part of employee. To show you what I mean by that, look at the code at the very bottom. So here we've got our employee equals new employee, and then we're going to promote employee. Now that's a method you can see up here was added to the employee class. But we can also do e.getFullName. Now you don't see getFullName as a method in employee, but it is in person, and we extend person. So not only do we get to type less with the inheritance relationship, but we get to reuse all that code that was available in the class that we're inheriting from. So when you extend another class, you inherit all of the attributes and all the behaviors of the superclass. In other words, you get all of the methods and the instance variables that, in this case, were in the person class. You might be thinking, I'd love to inherit from a lot of classes in that case. Well, we do have a restriction. Java is a single inheritance object-oriented programming language, which means that each class can only extend one class. There are other languages like C++ that have multiple inheritance where you can inherit from multiple classes, but that is not available in Java. Well, it's not available in Java, but there are some other features in Java that kind of help us get similar functionality. A little bit later, we'll talk about interfaces. When we're describing inheritance, whether you're reading about it or you're talking to a fellow developer, there are a number of different ways that people will describe inheritance. If we look at the Java syntax, we saw that we use the word extends. An employee extends person. Sometimes you'll hear people say that the top level class, the person in this case, is the superclass, and then the employee is the sub or the subordinate class. Some people will say that person is the more general class and employee is the more specific. So you can think about it. Person has some general functionality, some general state and behavior, whereas an employee has all of that, but some more specific state and behavior as well, such as a salary and the method promote. Educators, such as myself, tend to like the idea of a parent and child relationship. So the person would be the parent, and the employee would be the child. And I like that one in particular because it does give you a little hint about the rules of object creation, and that's when we have inheritance, the parent class must be created before the subclass, the child. So parent-child kind of keeps that terminology in the front of your mind. So back to this idea of inheritance being single inheritance in Java. You might think, well, that's too bad. There's a number of classes I'd like to inherit from, but the fact is you can actually inherit from multiple classes, just not directly. So, for example, we've got a person and we've said that an employee inherits from our person, so an employee extends person. Well, what if I want to make multiple types of employees, like an instructor? So now I can say an instructor extends employee, and I get everything in that entire inheritance chain. So in this case here, we're adding the method getSchedule, and so I can call getSchedule on an instructor. Let's just do that. We'll create the instructor object. Here's George. And I can call getSchedule, but I can also call getFullName, which is in the person class as well. So you get everything in that whole inheritance chain. One other note about the inheritance chain, even though we're showing just a very single chain here, that you can actually have multiple classes inherit from the same class. So what I mean by that is person, in this case, has employee as a subtype, and employee has an instructor as a subtype. And when we look at each class and go up, each class can only extend one class. An instructor can only extend employee. An employee can only extend person. They can only extend one class. However, employee could have lots of subtypes. I could have a consultant that extends employee, and a secretary that extends employee, and a manager that extends employee, and so on and so on. So you can have, well, class can have multiple subtypes, but each class can only have one supertype, one parent. Let's add a few constructors to our person class. So here is our person class, and we've got some state and a little bit of behavior. So we've got our first name, last name, home address, date of birth, and we also have that method for get full name. Now let's add some constructors. So the first constructor that we're making is a constructor that accepts a first name, last name, address, my date, and it's going to take all that state and then assign it to our instance variables, which makes perfect sense. The purpose of a constructor is to initialize. We're initializing all of our fields. This seems like a great constructor to add. And now we're also going to include a no argument constructor just in case. And so in this case, we're adding one that is going to set up some default names and addresses and date of birth and so on. So in this case, what's happening is when you call person, and if you don't pass in any parameters, then it's going to use this. And if you recall, this is a way for us to chain constructors in the same class. So it's going to go from this person to this constructor. And it'll pass in Jane, Doe. It's not going to pass in anything for an address, just putting in null. And then some MyDate object for the date of birth. Now, if we're going to have a subclass called employee, so an employee extends person, we're also going to need to add a constructor to the employee class. So that's one of the first rules about inheritance that's easy to screw up, that every type is going to need their own constructor. In other words, if I create an employee subclass, an employee extends person, I can't use any of these constructors directly. I can't say employee equals new employee and then pass in a first name, last name, address, my date. I can't say employee equals new employee and then just have a no argument constructor. So it's not entirely correct to say we don't inherit the constructors, but when you're instantiating an object, we don't have direct access to these constructors from the parent class. We have to call a constructor from the type itself. So person has its own constructors. Now employee is going to have its own constructor as well. So here's our employee class that extends person. We've added a little bit of state, a little bit of behavior. And now we're going to add a constructor because we have to. We have to have some kind of constructor. Well, I mean, we could use the default no argument constructor, but that could actually be problematic, and we'll see why in a little bit later. But let's add a constructor. So we're going to add a constructor that takes in basically all the same stuff that the person constructor takes, except it's also going to include the state that is specific for the employee, namely the hiring date and the salary. So let's take a look at this. We're going to take the first name. We inherit the first name instance variable from person. So we're going to take fname, which is passed into this constructor, and then assign it to first name, which we inherited. Going to do the same for lname and last name, home address, and so on. And then we're going to take the new hdate and assign that to hire date, take the new sal and assign that to salary, and now we've got a fully initialized object. But we also have a problem. And the problem is that this will not compile. Now, why is that? It's nothing tricky. I'm not doing anything silly like misspelling anything or using, poor capitalization. That's not the issue. And the issue isn't that we don't have first name, last name, and home address. We do. When you create an employee, those fields do exist with that particular object. But let's go back to the previous example, person, and see what's happening. So here's what's happening. Notice that first name, last name, home address, and so on, they're all private. And what's the rule of private? Private is only available inside of the class itself. In other words, yes, I can reference first name here in the person constructor, even though it's private, because they're all in the same class. But in my employee, which we just created, I can't reference first name in the employee class because it's not the same class. So does an employee have a first name? Yes, but it can't access it directly. So there's several ways we can get around this problem. One of the things we could do is just loosen the restriction. So our access modifier right now is private, which is the most restrictive. We can make it a little bit less restrictive. We could have the default access modifier where there is nothing written. You just leave off the access modifier. And that would be the same thing as saying it's available to the class itself, but really also any other classes that are in the same package. We could make it even a little bit less restrictive than that. We could make it protected. And that was the access modifier I said I would get to once we learned inheritance. So let's get to it. Protected simply means it's available to the class itself. It's available to any class in the same package. And it's also available to any subclass, no matter where it is, anywhere else. It doesn't have to be in the same package. So, we could loosen up the restriction if we want to, but, then we're breaking encapsulation. We're breaking the data hiding, and we don't typically want to do that. So what other options would we have? Well, we could use the setter and getters, right? We could add all of our accessors and mutators as public, and that wouldn't break encapsulation. Could do something like this. Go back into person and keep the strings private, add some getters and setters and so on. Any issues with that? Just take a look, maybe even pause. Do you see any problems? And I'll tell you, it'll compile, it'll be fine. Obviously, the ellipsis that you're seeing here, that's not legal Java, but they're just saying, imagine there's more code. But what do you think will happen here? What are some of the problems? Well, a couple of problems. Number one, now for the rest of the existence of this person object that lives, it's always going to have public getters and setters, meaning that the state could change. Now, imagine that doesn't really fit our business rules. What if I don't want the first name to change? I don't want the first name and last name to ever change in this person class. By allowing getters and setters, we're saying that, yeah, you can read and you can change these values, and maybe we don't want to do that. The other thing is that we're putting the burden of how this person object should be created onto the employee. The employee has to not only know, but remember that it needs to call all of these different setters in order to build a complete object. One of the purposes of constructors is not only to initialize the object that we're creating, but to specifically say this is how you must initialize the object. So by letting us just simply, piece this together with one setter at a time, we're opening ourselves up to a number of potential bugs simply by leaving items out, or also making the object a little bit more accessible than we really want throughout the life of the application. So the best way to handle this is with what's called chain constructors. And we've already learned a little bit about chaining constructors with the this keyword. And remember, you say this in parentheses, and that will chain from one constructor to another. We can also do that with inheritance. So we use the super keyword to chain constructors from the child class to the parent class. And this is really the cleanest way to code our relationship between the parent and the child. So what's nice is that we can be in our employee constructor and we can defer to some other constructor. We can chain to some person constructor to pass in the data that it's expecting and needs. So here's an example of doing just that. We've got our employee constructor, and now what we're doing is we're using super so that we can call the constructor that is in the person class, passing in the fname, lname, add, and date of birth. And now, because we're calling the constructor, the person object is able to construct itself appropriately, and we're done with it. This is the proper way to initialize objects with inheritance. So after that's done, we then set our hire date, we set our salary, and we're ready to go. Even when a subclass doesn't call that super explicitly, the compiler will put that in there for you. Here's an example. What if we did go down that path where we were calling setters for everything? even though you don't see a call to the super constructor here, one will be placed in there for you. You'll never see it. It's in the bytecode. It's not going to be in your source code. But in fact, when you compile it, this is what gets put in there. We get this super no argument constructor call. And that just gets added to the first line if you don't explicitly call a super constructor yourself. So you can imagine that that might be a problem. What if the parent class doesn't have a no argument constructor? Well, if that was the case, you'd get the following error that you're seeing below. So it'd say cannot find symbol. A symbol is just a name. It's an identifier, a name of a method, a name of a field, a name of a constructor. And it's saying I can't find this symbol constructor person. And what they're telling you is that there is no argument constructor in the person class. And if you didn't know that underneath the covers it was adding this call to super, you probably would be wondering, why does it care? Why does it need a no argument constructor? And that's why. So either you put in an explicit call to super yourself in the constructor, or else it will put in one for you. If you recall, there was a rule whenever we chain constructors with this, and this had to be the first line of the constructor. Exactly the same with super. Super has to be the first line of the constructor, and that tends to make a lot of sense. Remember I said that we have a parent-child relationship, and the parent must exist before the child does. So what it's doing is when you call a child constructor, the first thing that constructor is going to do is call the parent's constructor so that the parent is fully initialized and ready to go before the child is. If you screw that up, you will get a compiler error. It'll warn you. It'll say call to super must be the first statement in the constructor. Now we know that whenever we instantiate an object, that we have not only the methods that were defined in that class available to us, but we also have the methods available that were defined in any of the ancestors, anything that it inherits from, provided that the access modifiers allow us to call those methods. And because of that, Java enforces a few rules. Java wants to make sure that when we try to call a method, that it's able to pick the exact method and only one method that would answer that request. And if there's any chance of an ambiguity where it's like, well, I'm not sure which of the methods I should choose, it won't even let you compile with those kind of ambiguities. So there's rules that we have to follow. And one of the rules we can use is called overloading methods. This is something that allows us to use the same name of a method as another one. And I'll explain the rule in just a second, but let's see how it's used. So for example, we got println. And we've been calling println all over the place with our code. We have been passing in strings. We've been passing in objects like myDates, passing in ints. And it's not like there was just this one big println method that said, I can accept any number of arguments and we'll figure out what we want to do with them. Instead, it says, in fact, there's a number of println methods that have been created, each one that takes a different parameter. So when we call println and we pass in a float, it calls a special method that knows what to deal with floats. And when we pass in an int, it calls the println that knows how to deal with ints. That's method overloading. So it's easy to use, but how do we take advantage of that ourselves when we're making our own classes? So the general rule is this, that whenever you create a method, the signature must be unique. There's one exception to this rule. It's called overriding methods, and that's what we'll look at that exception in the next lecture. So for now, let's just accept that the signatures must be unique for every method that we create. So what is the signature? The signature is the name of the method and then the parameter type in order. That's it. Nothing else in the method is considered part of the signature. Other parts might be considered in other cases. They'll refer to it as an extended signature. But when we just talk about the basic signature, it's the name of the method and then the number of parameters, number and type of parameters. So that has to be unique. Now let's apply that to println. So if everything is using the same name, println, then that means the parameter type and order has to be unique. If it's not, it just won't compile. Now, like I said, there is an exception to this rule with overriding, but we'll wait till the next lecture to see that exception. Let's just take a quick look at a couple of examples. Jump to some code here. So I've got two say hello methods, and they both take a string. The one is a string first name, and the other is a string nickname. And if I was to call this, I could say hello, Jay. Now, you know me as Jason, but let's say you didn't know me that well, and you're just not sure if my name is Jason or Jay. So maybe Jay is my nickname, maybe it's my first name. So my question for you is, as a human being, if you were to route this method call, which of the two methods would you invoke? Would you invoke the first one or the second one? And again, if you didn't know that my real name was Jason, you might be stumped. Jay could be a first name, Jay could be a nickname, we're not sure. So imagine how the Java platform feels. You probably already noticed that there are red lines here, so it's saying that, no, this isn't legal. So what we're looking at is we're breaking the rules of overloading a method. The signature is not unique. Now you might think, but this is unique. This one says first name and this one says nickname. Well, the identifier for the parameter, the name of the parameter, does not count. For the very reasons that you just saw, if I'm a computer, if I'm the Java platform, and a string is passed in, all I know is I'm trying to find a say hello that takes a string. I'm not really thinking about this name here, this identifier. That's for use inside of the method. That's a human readable thing, not a computer readable thing. So these types have to be unique. I could, for example, change this to also accept an age. And now look, all the red lines go away. It compiles because the signature is unique. Say hello, string, we've got one with a string, one with an int, and then one with just a string. So when I call and I just pass in a string, it knows exactly which one to go to. It's going to go to this method right here. If I want to call the method on top, I'm going to have to pass in, here I'll make myself 80, I'll pass in an age. Does that make sense? So we have to have each method be unique. And by the way, the return type doesn't fall into this at all. So, if we had, I'll get rid of this age again. Now we've got a problem. Let's say I change this to be, this one's going to return an int. That does not make it unique. The return type is not a part of the signature. But once you follow the rule where everything's unique, so I'll put age here, and I'm going to also show you this example. So I'll put int age and string. This is still unique because the order of parameters matters. This is a say hello that takes a string and then an int, and this is say hello that takes an int and then a string. That's unique. This one is definitively going to the second method, or so the first method, because it's passing in a string and then an int. This is the method that takes a string and then an int. Now, once you follow the rules of overloading methods, everything else can be unique. Like now I can change the return type. I could say this one returns an int. Now, why is it giving me a problem? Well, because I haven't returned an int yet. But if I return an int, now the problem goes away. That red line, the compile error, had nothing to do with overloading methods. It was just not returning the value. But you can see that once we have an overloaded method, which means the same name but a unique parameter type, anything else about it can be changed. We can change the return type, we can change the modifiers. Later we'll learn about exceptions, we'll see how we can change what the method throws, and so on. And that's overloading methods. The rule in Java is that every method signature needs to be unique, with one exception, and that's with overriding methods. So the general idea of overriding a method is that there is a method that is being inherited and we want to change the functionality. So we don't like how that method behaves, let's change it. Let's look at some code, it'll be easier to understand. So we've got two new classes. We got a class for a father and we got a class for a son. And father has a method called drive. So if I created a son s equals new son, and then I said s.drive, what happens? Well, even though son doesn't have a method called drive, it will inherit the drive method from the father, so it'll still work. The velocity will be set to 45, the path will be set to less traveled, and then it'll go. So that's great, but what if we didn't want to drive in the same way that the father drives? Well, what we could do is override the method. So in the subclass, we would create a method. Here's public void drive. It is the exact same method signature. The method signature is the name drive and then no parameters. That's the method signature. So this has the exact same method signature. And what will happen is now when we say s.drive, the version that's in the son will override the one that was in the father. The way you can think of this is that when we say s.drive, it's going to go to son first and say, hey, do you have a method called drive? And the answer is yes, and so it runs it. If it didn't, it would go up to the father and say, father, do you have a drive? And then it would run that one, and so on. So in order to successfully override a method, the overriding and the overridden method must have the exact same signature. They have to have the exact same name and the exact same parameters. And so this can't happen in the same class. You can't have a class that has the exact same signature. This is a relationship between a superclass and a subclass. If the method names are the same, but the parameters are different, well, then what you're doing is you're just overloading. You're not overriding the method anymore, you're overloading the method, and so then you just follow all the rules of overloading. But once it's determined that you are in fact overriding a method, there's a few more rules that have to be followed. First of all, the return type. The return type is going to have to be the exact same type that was declared in the overridden method, or it can be a subtype of whatever that overridden return type is. Now, I'll show you a little bit more detail of that. It's called covariant returns, and we have a whole lecture in this section that's dedicated to that topic. An overriding method cannot be less accessible than the inherited method. So the code that you're seeing here would not compile. The problem is this. Drive is overriding the method in father. It's overriding because there is an extension, there's an inheritance relationship. The method signature is exactly the same, but the problem is in father, the method is public, which is as accessible as it can get, and then we are using the default modifier, in other words, no modifier, which means that it's package level. That overridden method, the overriding method is less accessible, and therefore that is illegal. We could go the opposite way. If the father's drive was just void drive and the son's drive was public void drive, that would be okay because it became more accessible. So in the final section of this class, we're going to talk about exception handling. And when we do, this final rule about overriding methods will make a lot more sense. The only reason I'm going to mention it now is not that I expect you to understand it at this time, but eventually you'll probably come back. You'll do the whole class and you'll start to come back and watch certain lectures again. And when you're trying to remind yourself about the rules of overriding methods, I want all of the rules together. So the rule in regard to exceptions is that an overriding method can declare fewer exceptions, but it cannot declare more exceptions unless those exceptions are a subtype of the overridden exception, or if it's a runtime exception. Okay, like I said, don't worry about that if it doesn't make sense right now. It will once you get to the exceptions chapter, and if you happen to come back and review what it means to override a method, now you've got all the rules in one place. One other interesting tidbit is that you can't actually override static or private methods. It just doesn't work. You can't do it. They can only be hidden. And it's a little confusing at first to understand this, but what it means is that when we call, for example, a static method, then the static method is going to, which static method is going to be called is dependent on the reference variable, not on the actual object type. So it's resolved at compile time. Now, when we're dealing with overridden methods, those are actually resolved at runtime. Let me show you some code and you can see the difference between the two. So I've got a static method called say hello, and then I've got just a regular method called say hi. I've one set in father, one set in son, and then I've got a tester that's going to call this. So what I'm doing here is I'm just showing you, and this is actually kind of getting a little ahead of ourselves because in the next section, The next section we're going to talk about polymorphism, and this is a form of polymorphism. But what's happening here is that when I have father F, so that's my reference type is father, and then I say equals new son. Now that seems odd, right? But trust me in that it's legal. That's not the part I want you to focus on yet. We'll talk about this structure here in the next section. So it's legal. So if I say f dot say hello, it's actually looking at the reference type variable to figure out which one it should call. So it goes to the father's say hello, and it says static hello from father. Whereas if I say just a normal overridden method, say hi, then it's resolved at runtime, and it'll figure out that this is actually a son object. And so it will use the son's say hi. All right, again, just like that last rule with exceptions, this might be a little confusing right now. Don't let this stop you from continuing on with this particular section. We will talk a lot more about these issues in the upcoming section on polymorphism. So what if an instance of the son wants to drive like an instance of a father? We've overridden the method. How do we ever call the version that the father has? And we can do that with the super keyword. Just like we did with the constructors that were chained, we can also use super to just call methods in the super class. So now I've got my drive method, and then I got another drive method. It's called drive like dad. And I'm using the super keyword, and I just call drive. And what's going to happen is when you say super, instead of, well, let's pretend that super wasn't there. Let's just say it said drive. What would happen is it would come back into this object, son, and say, do you have a method called drive? And the answer would be yes, and it would answer it. But now when we say super.drive, it doesn't even look in the son for that particular method. It instantly goes to the parent class, which in this case is father, and use their version of drive. Now, that doesn't mean you can keep using super and chain them together to get to some ancestor. Like you can't say super.super.drive, hoping to get to grandfather's drive method. That will not work. You can only have one super. When we were talking about overriding methods, I said that the return type can either be the exact same type that you're overriding, or it can be a covariant return. So I just want to have a quick little lecture here to show you what a covariant return looks like. Imagine I've got a class called a grandfather registry, and we've got one method, who's my ancestor, and it's returning a grandfather type. Now, covariant return is where a subtype would be listed in the place of a supertype. So overridden methods can use the covariant return, and it looks like this. So my father registry extends grandfather registry, and if we look at the who's my ancestor method, it's got the same signature. We are overriding the method. But the return type is different. I am now returning here a father, and you can imagine that the grandfather is the supertype of the father class. That's all it is. That is a covariant return, and that's legal with overriding methods. Now, the reason that you want to do a covariant return is that it just allows other people, when they call a method, to get a more specific form of the object. If I was to call father registry who's my ancestor and it could only return a grandfather, then I'd be restricted to the methods that are available to a grandfather. This way I actually get a father object, and now I have more specific methods that would be available to that type. So the final lecture in this section is on the topic of final. Final is a modifier that we can apply to a number of different things, but in each case it really means just unable to change. So there are three primary places that we'll use the final modifier. One is in front of a variable, and when we do that, it makes the variable a constant, just some sort of value that won't change. If we use final with a method, then that means that method can't be overridden. And if we put final in front of a class, then that means that class is unextendable. You cannot inherit from that class. So let's start with the constant. We'll add a final modifier to the variable, and we can add this to a number of different variables. It can be local in a method, but it can also be a static or instance variable. Typically speaking, when we add final to a variable, it's going to be a static variable most often. By convention, the constant names are in uppercase, which means that if we have multiple words, we'll separate them with an underscore. Probably the most confusing part about using a final modifier in front of a variable is what are the rules for initializing the value of that variable. Let's look at an example. So here I've got two different final variables. I've got one called less_traveled and one called shortest. Now, the less_traveled is the most easy to understand. We've got explicit initialization, so we're setting less traveled to be 0. Because it's final, once it's set to 0, we can't change that. It is going to be 0 for the life of the application. Notice that the final is after public static. Just remember that that's not a rule. The rule is that modifiers can be in any order you'd like. If there's the other rule, of course, is that all modifiers must be to the left of the type. So final must be to the left of the int, but it doesn't have to be the most immediate thing to the left of the int. You could have had static public final or final public static. All of those would work too. If you look at shortest, that one's a little bit more confusing. So what's happening here is that we've got our final int shortest. We only have one constructor, so whenever final test is going to be created, we know that constructor will be called. And shortest is then set to 1. Once shortest is set to 1, it cannot change. And this is all legal because it knows that shortest will have some value before it's used. And since it must be set before it's used, that means there's some rules about how we set these variables. So for example, if I'm trying to set the final variable outside of some kind of explicit initialization or within a single constructor, we're probably going to get a compile error. Here's an example. If we look back at shortest down at the bottom here, we do have a method that's called foo, and it's going to set shortest to 1. But the problem here is that a method is nothing but potential for activity. If nobody ever calls the method foo, then this shortest is never going to be set, and that's possible. Or someone might try to access shortest before it has this value assigned. Because of that, the compiler is going to complain and just say, I can't help you, cannot assign a value to final variable shortest, and it just doesn't compile. When you put the final modifier in front of a method, what you're saying is that this method cannot be overridden. And so here we've got our father and son again. And remember, son was overriding the method drive. If we've got final in that version father has, then this won't even compile. It'll say this is illegal. You cannot override a final method. Now, why would we want to do that? I think that's going to become a little bit more obvious when we start looking at polymorphism. So let's hold off on that a little bit, but just know for now that adding final to in front of a method means you cannot override it. And the last version of final is when we put it in front of a class. So here we've got public final class father, and what that means is that the class itself cannot be extended. You cannot inherit from this. And once again, this will become more clear when we use polymorphism. Polymorphism is the idea of substituting one type for another. And so imagine that I've got some kind of a program that accepts a father or any other type, like a son. And so if I want to make sure that I'm only getting a father class and nothing that inherits from father, I can make it final, and then it's illegal for someone to try to substitute another object. That sounds a little confusing. Don't worry. That's another thing that we're going to talk about coming up here. In fact, the whole next section is on polymorphism, and so we'll clear up a lot of these concepts. As a side note, in the Java API, the string class is final. So you can't inherit from string, and you cannot change any of its functionality. Also, Java enums, when we write out all those labels, those are the constants that are used there are implicitly static and final, even though we don't write those modifiers on each of them. So if you remember, we had days, and days had Sunday, Monday, Tuesday, and so on. Each one of those was static and final.
All right, continuing on with the concepts of object-oriented programming, and this time we're going to hit the topic of polymorphism. Polymorphism is all about substitutability, and it gives us a way to make our applications future-proof in a way and flexible. It is a tough concept, just to be honest, and so we're going to spend quite a bit of time going over it. By the end, you'll be ready to work with polymorphism in Java.
Polymorphism has a pretty rough reputation in regards to how difficult it is to learn the concept. It's not just a Java thing, it's an object-oriented programming concept, and so it's considered to be tough across the board. But I really think it's a fairly simple concept when you focus on what benefits we get from it, how it's used, instead of kind of getting immediately lost in the syntax and the rules that are applied. So what I want to do is just kind of go through a short scenario here with you so you can see polymorphism in action. And I think once you're aware of what it does, the benefits that we get, that I think learning the rules is just a lot easier. So let's imagine a scenario where you've been hired as a developer to code an inventory manager. The company builds cars and trucks and different kinds of automobiles, and they do have a team of developers who've been working on cars and trucks, but their resources are thin. They need people to be hired to build this inventory manager. So there you are, you got a gig. And you take a look to see what they've done already, and you see that they build a car. That's what I'm showing you right now. And obviously I'm just showing you the skeletons of these classes. And they've got a truck, and you've noticed that both of these classes extends automobile. So you take a look at automobile, and if you remember back to our car example, this is kind of familiar. We've got a VIN count, and every time an automobile's instantiated, it's going to increase that VIN count, and then assign that to the local variable of VIN. So you see that there's inheritance going on. You see that they're doing encapsulation. So this is pretty good. They've got a pretty strong foundation here for you to work with. So you go in and you build your inventory manager, and you're familiar with the concept of overloading methods. So rather than confusing them with add truck, add car, and lots of different names, you said, let's make this easy on everyone. Just remember add automobile. And you can pass in a car or you can pass in a truck, and it should just work out of the box. And so you do your work, and they're ready to test the application you built. And so they've got a car dealership. They instantiate the inventory manager you built, and they're going to instantiate a car, throw that into your manager and into the add automobile method, doing the same thing with the truck. Let's run it. And there you can see we've got it adding car, and we've got the 202 for the ID, and we've got adding truck, and this one ends with 203. And so everything is working great. Everyone is really happy. And a little bit later, you get a call, and they say, you know what, we've been working on some more vehicles. We now have a motorcycle, and we'd like you to add that to the system. Can you do that? And you say, sure, let's take a look at the motorcycle. And the motorcycle extends automobile. It's basically the same kind of thing you've been working with. So you say, yeah, that's not a problem. And you go in, and so you add a new method here, public void, keeping along with the same name for to make it easier for the car dealership to use. You say add automobile, so same name, but this one's going to accept a motorcycle. And we'll do what we did before. We'll just print out that we've added a motorcycle. So adding motorcycle. All right, there's our method. Let's go back to the car dealership and add the motorcycle. Motorcycle test, C equals new motorcycle. And we're using that manager to add the motorcycle. And what I do, oh, we have car C, we want motorcycle M. That would be much, much better. There we go. All right, everything's looking good. So no compile errors, let's run it. And there it is, it added the motorcycle. So the system works, everyone is really happy. And you go off and you start another gig. And now you get a phone call and they say, hey, we've got yet another vehicle. It's a scooter. and they send it to you to take a look at, and you're like, it looks fine. This is a great scooter. You're still using inheritance. Everything looks perfect. But I'm on another gig. I can't help you with this. I'm really sorry. So now they're stuck. Now they have to go in and figure out, how did you actually build this inventory manager? And remember, we're just looking at a skeleton of what you actually built. So there's a learning curve there, and they have to take time from other projects and so on to work on this particular class. Wouldn't it have been kind of cool if we could have simplified this a bit? What if we could have just said, instead of us every single time having to go back into this code and say, add another overloaded method, what about if we just had one method and we said adding automobile, and instead of accepting a car, we just take an automobile? Now, we weren't creating automobiles, right? We were creating new cars, new trucks, new motorcycles. But what if we said, we'll take an automobile, and that just worked, that you could, in fact, give me a car? Well, let's look at the car again. A car extends automobile. And remember the is a rule. A car is an automobile. Truck is an automobile. Motorcycle is an automobile. So again, wouldn't it be cool if we could just say, we'll take any kind of automobile? As long as it is an automobile, we can accept it. So if we wrote this method, and we just did, didn't we? And now let's go look at the car dealership. I want you to notice there's an absence of something here. There's an absence of red X's. There are no compile errors here at all. This works. This just works out of the box. And that's it, guys. That's all that polymorphism is. Polymorphism means that we can substitute one object for another as long as they're of the same type. So in my inventory manager, when I say I accept automobile, what I'm really saying is I'll accept an automobile or any subtype of an automobile. And car, truck, motorcycle, scooter, they're all subtypes. In fact, we didn't even add a scooter yet, but let's do it. Scooter, S equals new scooter. Manager, add automobile, scooter. No compile error, run it, and it works. Other than my spelling error down here, right? That's no good. But other than that, it just works. So that's it. That's what polymorphism is. It's just the ability to substitute one object for another. And did we really have to do anything to make this work? We didn't, right? Every time in Java you have a reference variable, the type of the reference variable is saying, I accept this type or any subtype. It's just built into the language. So that's it, guys. That's polymorphism. What we're going to do is now dive into some of the rules that go along with using polymorphism. But keep this example in the back of your mind as we continue on with the next lecture. So you've had the opportunity now to see polymorphism in action, and you saw that it's really easy to set up. There are no special keywords that you have to learn. It's really just about how to apply something that's built into the language. And what's built into the language is this simple idea that anytime we have a reference variable inside of Java, that reference variable can store the object type it specifies or any subtype. And what that allows us to do is make applications that are very, very flexible and also future-proofed. And all that I mean by saying future-proof is that we can build another object that's of the same type, and it should just work with that method. That's the best case scenario, that it just happens to work. We saw an example before where I showed you we added a scooter to our inventory manager. And because the scooter extended automobile, it worked with all the methods that just said, we accept automobile. And that's it. But regardless, it's still a little bit of a struggle for a lot of people when they are learning Java and when they're learning object-oriented programming language. So we're going to have yet another example, and we're going to dive a little deeper into the rules of polymorphism. Now, regarding the name it has Greek origins. It loosely translates to many forms, but most people tend to use the term substitutability. So in programming, it means a class has the same interface or set of methods, but different implementation. So with our automobile, the same method was get the VIN, right? We could get the vehicle identification number. Now, in our particular implementation, they were all using the same method, but we could have overridden that method and the car could have had a different implementation from the truck, from the motorcycle, and so on. So that's the real use of polymorphism, not only for a method to be able to accept many different types of objects, but then to be able to send the same message to whatever object they get, and each object can then respond in its own way. Now, I realize that that's a little bit abstract to imagine in your head, so we are going to hit an example here in just a minute. So polymorphism is all about substitutability, the ability to say, I take this type of an object, and then at runtime, anyone can pass in any object provided it's of that type. So let's look at a couple of examples. First line, employee equals new employee. That's your regular let's create an employee syntax. But what we also can do because of polymorphism is we could say person P equals E, the second line right here. And we can do that because an employee extends person. It's part of the same family. So if the rules of polymorphism are, we will accept person or any subtype, then this is perfectly legal. In fact, we could do it all in one line if we wanted to. Person P equals new employee. And then if we looked on the stack, this is what we would have. We've got our E, which is referring to the employee, and we've got P, which is also referring to the exact same employee. Now you might wonder, why would I do that? Now, you were on board, when you saw the example about the automobile, but this is a little weird. Why would I ever say person P equals new employee? And the fact is you probably won't. You probably won't, or at least you won't do it often, where you'll just have a reference type and you'll list a new subtype. There's use cases where that makes sense, but here's what you're normally going to do. Let's jump to some code for a second. So I'm in my inventory manager here, and I've got a reference variable, an instance variable, that is of type automobile. It's a featured auto. And we also have a method here called add featured auto, which will take an automobile. So what I'm going to do now is just invoke this method. I'm going to pass in an automobile, which is then going to be stored in this automobile instance variable. Let's do that. So I'm going to go to my car dealership. On line 9, we're creating a car. Car C equals new car. And line 11, this is where we're calling that add featured auto. Now think about what it would look like in terms of having all the frames on the stack, what the variables would be. In a way, when I say car C equals new car, and I call this add featured auto, I could have, and to clean this up, I'm just going to comment out that line next to it. I could have, for convenience sake, really just passed in this new car, right? I could have gone in here and just said, oops, missing a parenthesis. So what I could have done is said new car and passed that right into the add featured auto. Hopefully that makes sense what I'm doing right here. Just creating a new car, passing it into the featured auto. So going back to that method, what's really happening? Well, on the frame, there's a frame being added for add featured auto. And in that frame, I'll just write some code right above. Here's my frame. And so in the frame, there's going to be an automobile, and its reference name is auto. And what is the value? Well, the value was the new car that we just passed in, right? Let's go back here. We are creating a new car. We're passing it into that method. That method gets its own frame. And so what is it doing? It's setting up this variable, automobile auto, and the value is the new car that we passed in. That makes sense, right? So now up here, even though we're not seeing it, this automobile, this featured auto, is really equal to the new car we passed in, temporarily anyway, right? So would you write person P equals new employee? Maybe not as much. Would you write automobile featured auto equals new car? Probably not as much. But what you will do is you'll have this variable. You'll have this instance variable that accepts a polymorphic type. And so when you invoke the method, passing in that new car, you're essentially doing the same thing as saying automobile featured auto equals new car, right? Going back to the code here. So that's all we're saying. A lot of times you're not going to do this all in one line, but maybe you have a method that accepts a person and you want to pass in a new employee. Maybe you have an instance variable that's of type person and you set it to be an employee. So that's the flexibility of polymorphism. We're saying that we'll accept a person of any type. Okay, so continuing on, this is the syntax. Our reference type will store any object type that is of the same reference type. In other words, person P would store a new person. Or if the object type is a descendant of the reference type, then that's perfectly legal. The opposite's not true. Let's look at this code right here. We have employee equals new person. That will not work. And if you think about it logically, it makes sense. In our application, all employees are persons, which means that when we send a message using all the things that are available to a person, the employee can respond. But imagine we do this. We've got an employee equals new person. So on the heap at runtime, we actually have a person object. And during compile time, we can send any messages that are legal to an employee. So if I was to say e.promote or e.getSalary, would the person object actually have a salary? Would they have a method called promote? And the answer is no, they won't. So Java just stops you from doing that right away. Java says you can't do this. It's illegal. It won't even let you compile. And you can always use the ISA rule just to check to see if it should work. Person P equals new employee. So what you do is you start on the right side. An employee is a person. It's right here. A person is an employee. Well, some people are, but not all, right? A person doesn't have to be an employee, so it won't work. Now that's it. That's the syntax of applying polymorphism. There's a couple more rules we'll hit, but getting back to why do we use polymorphism, it really promotes the flexibility and separation of concerns. The real power of polymorphism, however, ties into overriding methods. So remember, overriding methods means we are taking a method we inherited and we are going to create a new implementation. We have the exact same method signature and we are just going to provide a different way that it should work. So let's look at another example with the person employee class. So here I've got my person class. It has a first name and a last name and a get description. And then I have an employee that extends person. It has a title and it's overriding get description. So what happens now when we create an object of type employee and call that method? So we say person P equals new employee. Our person is storing an employee. Now if I say p.getDescription, is it legal to call that? p.getDescription, and the answer is yes. The reason it's legal is because if you look at the person class, there is a getDescription method available. But here's what happens at runtime. At runtime, and this is called dynamic method dispatching, what's going to happen is that the request for getDescription is going to come into here, into the employee, and it's going to say, employee, do you have a getDescription? And the answer is yes. So this is the one that will run at runtime. And so what it's going to do is it's going to print out in employee, and then we're calling super.getDescription. Remember that what super does is it's going to go to the parent. It says, don't look for getDescription right here, because if we just said getDescription and got rid of super, we'd actually have infinite recursion. It would just keep going until we'd see a Stack Overflow exception. Or Stack Overflow error, really. It's not an exception. We'll talk about errors versus exceptions in a little bit. So we've got our super.getDescription, and that's going to go up here. It's going to write in person. It's going to return the first name and last name, which will then be concatenated with a colon and the title. So let's just say that the first name, last name is Jason Shapiro. The title is instructor. When we say p.getDescription, it would say in employee, in person, Jason Shapiro, colon title. right? Just from calling that p.getDescription. So there's another example. If the name was John Smith and it was instructor, it would say in employee, in person, John Smith, instructor. So even though the reference type variable is of type person, at runtime it sends a message to the actual object. And so the actual object will run its version of the method. And that's why overriding methods are so popular. And by the way, that's why final is really interesting with a method, because you can stop that from happening. You can say, well, now that I know with polymorphism, we could do a person p equals new employee. If I want to make sure that employee doesn't change the way getDescription works, back in person, I could have said getDescription is a final method. And then we wouldn't be able to override it. So again, that's known as dynamic method dispatching. What happens is the virtual machine looks at the actual runtime object, in this case an employee, to see if it has getDescription. And if it doesn't, then it just keeps going up the inheritance tree trying to find it. And also, when you have final methods, that's why it executes faster, because it doesn't need to dynamically figure out where the method is defined. It knows where the last place is. So even though the actual method is discovered at runtime, the compiler has some rules. And the rule is fairly simple. It just takes a while to get used to it. But this is the rule. Whenever I have a reference variable, person p, I don't care what you say on the right side here. I don't care that you put new employee. When I use p, the only variables I can look at, the only methods that I can call are those that are available to p, to person. Okay, not to employee. So if I try to say p.title equals instructor, which is something only an employee has, that will not compile. And that can be really frustrating when you first learn this. You might look at this and say, but I can see it. It's a new employee. It says it right there. Doesn't matter. The way that the compiler works and the way that Java works is that it says I've got a person variable, so I can only send messages that a person can react to. So that code is illegal. At runtime, the JVM will figure it out. Aha, this is actually an employee object. But at compile time, it really doesn't know what that object is. It just knows that P is a person. In this particular case, the compiler is going to go, well, let's double check that title is something that a person can see. And it'll say, nope, that's not something that a person can see. It's nothing that a person would have. So the compilation will fail. So to help solidify the concept, let's look at yet another example. Let's imagine that we're part of a very large software team, and we've all been tasked with developing an accounting system, and this is for an IT company. So one of the things that we're going to have to know about in the system are the different kinds of employees. And so for our system, we really have three different kinds of employees. We have managers, instructors, and programmers. So we come up with a hierarchy here of a person at the very top, an employee extends person, and then manager, instructor, and programmer extend employee. So pretty simple object hierarchy, but makes logical sense. Each of the different employees is going to be paid a little differently, and so this is where overriding methods is really going to shine. We're going to see the power of overriding methods. We'll also have some kind of component that cuts a check for each of these employees, and that'll be the pay service. So because this is such a large project, we're going to split up the work amongst the team. Some team members are going to create the employee subclasses, and they're going to have to figure out how that employee should be paid. So what they do is they start looking at their hierarchy and they say, you know, why don't we override a method called pay that's been defined in the employee class, and that way each of the different subtypes can determine how they're paid. And that's great. Some other people decide that they are going to create the pay service class. So there's a lot of ways that the pay service class could be built. Maybe we have a cut check method for instructors, a cut check method for programmers, a cut check method for managers. But of course, we know better. We're aware of polymorphism. So we can create this kind of a method, cut check employee. And what we're saying polymorphically is that we'll accept an employee or any subtype. And what's a subtype of an employee? Well, programmer, instructor, and manager. And then what we're doing is we're going to send a message, a single message, and then that message is going to be handled differently depending on the subclass. So in every case, an employee will be passed a cut check and we'll say, pay. What is your pay? Tell us, and we'll cut the check for you. Wouldn't that be great? We could just start determining our own pay, but just go with the example for a second. So we say e.pay, and that gives us some sort of value, and we cut the check. There's a phrase you'll hear in software called, and roughly speaking, it's called separate the things that change from the things that stay the same. So how are we doing that here? Well, what changes? How we pay is not what changes. We're always going to be paying the same way. We ask an employee for their salary. We say, what's your pay? And then we cut the check. That stays the same. What changes is what the actual pay is, the implementation of the pay method. So again, that's the power of overriding methods. We can send one message, and depending on what kind of employee has been passed into this method, they can react differently. So the developer of the employee classes, they're going to have to override that pay method to determine how each employee will be paid. And it has to be the exact same interface, the exact same method. Otherwise, we would have to write ourselves in the pay system, we would have to write different methods for each different employee type. So they're all going to have to agree on that method pay. They're all going to have to override it. So now here is what we've got for our employees. Now, the very top, we've got our public class employee, which extends person, and they define the method pay. And so right now, we don't really have what would be a generic employee. So we're just setting up this method, for the interface. We're setting this up because if we did not have the method pay in employee, then in our cut check method, we couldn't call pay. Now think about that. What we were doing in cut check, let's jump back a little bit here. In cut check, we were saying we take an employee, and so then we're going to call the method pay. And remember the rule about polymorphism, which is when we have a reference variable, we can only send messages to it that are available to this type, that are available to employee. So what's available to employee? Is pay available to employee? Well, jumping back to that code, here is the pay. So there it is. Yeah, it's there. We can call that method. Now, obviously, if this was the method that we were calling directly, everyone would be paid 0 and no one would be happy. So instead, every class that extends employee is overriding pay. And they're coming up with their own computation of how they determine what their pay is. So let's say then someone creates a manager, passes it into my method, and I say e.pay, well, it's going to call this version of pay, and so on. Now, the one thing that I'm not super happy about here is what if someone made the instructor and forgot to override pay? Or maybe they made a little mistake and made it a capital P. Okay, that's a different method. Remember that everything's case sensitive in Java. So if they then created an instructor, instantiated an instructor object, passed it into our cut check method, and we called pay, the dynamic method dispatching would come in here and say, instructor, do you have pay all lowercase? And the answer would be, no, I've got pay with a capital P. So we'd say, nope, that's not what we're looking for, and it would go up to employee and say, do you have pay? And the answer would be, yes, we do. And what is it? It's 0. And now we cut a check for $0. That could be a problem. But in the next section, we'll talk about abstract classes and interfaces, and we'll see how we can kind of get around this issue. But for now, we'll leave it. Another benefit of this polymorphism is really the flexibility. So now we can actually change a pay method without changing any other code. And that's another software idiom, I guess, another software best practice, in that we should try to isolate our code so that when we make changes, we're only making them in one place. Anytime we open up some code and make changes, there's the chance that we introduced a bug. If we don't touch it, that limits and reduces the amount of bugs for that particular system. So now when I want to change the pay for some particular object, then I can go directly into that line of code and change that salary only. In other words, I could go to the programmers and just change how a programmer is paid, and I wouldn't affect any other type. So here, I'm going into my programmer, and now I go into the pay, and I just changed what it is. Did I affect the manager? Nope. Did I affect the consultant or instructor? Nope, didn't affect them either. So everything's nice and isolated in this way. How about pay service? Did I have to change the pay service? Nope, didn't have to change that either. Everything is nice and compartmentalized, so we can just fix the code that we need to fix. In addition, let's say we get a brand new kind of an employee. It's going to be really easy to fit them into the system. Let's say a tech writer position was added. So now we create this tech writer, we say that they extend employee, we override the pay method, and now they just work in the cut check system. We didn't have to make any changes to cut check. It just works with this new tech writer, and that's what I mean when I say you're future-proofing your application. We are making sure that as we add new employees, they'll just work in the system. Several sections ago, we talked about casting as it relates to primitive data types, and we saw that it was what we needed to do if we had a value that was larger than the reference, or larger than the variable that we were trying to store it into. So if I had a byte variable and I was working with an int, then I would need to cast that into a byte. And we did that with the parentheses. We can do the same thing with objects. And the idea with objects is that we take a more general type and cast it into a more specific type. So let me show you an example. I've got a person P equals new employee. Now remember, the rule of polymorphism says that while we are working with that P variable, we can only call methods and look at variables that are available to the person type, not the employee. Even though at runtime we're really sending the message to the employee, it's like we got blinders on. We can only see the things available to person. So I can do things like p.getDescription, and if employee happens to have overridden getDescription, it will behave like an employee. But again, we can only send messages or invoke methods that are available to the person type. So what if I wanted then to treat P like an employee? Well, this is what we can do. We can cast it. And it looks just like casting our primitives. The only difference is we say the type. So I'd say P, and to the left of it, we would cast it into an employee. And now I can store that in a variable and work with that variable, and it's an employee now. The compiler will not complain if I say things like e.title or e.promote. All of that will work. And there's an example. I'm setting e.title to instructor, and it's legal because title is something that's available to any types or any objects that are of type employee. So the reason we did this typecast is really to get functionality back into the reference so that we can treat this employee we created as an actual employee. But like any kind of a variable, if we don't really need to keep the variable around for future work that we need done, why keep a variable around at all? So one of the things we can do is shorten our code a little bit. So in this case here, I'm creating the same thing, person P equals new employee, calling out p.getDescription, but rather than casting P into an employee and keeping that employee E variable around, I'll just do the cast and the title switch all in one line. And so what we do here is, I'm going to walk you through this. We take our reference P and we cast it to employee. Now, if we didn't have the extra set of parentheses surrounding the whole cast, then this would still fail, because what would happen is p.title would execute first. So you have to think about your operations and the precedence of operations. So without the parentheses, p.title would be executed before the cast, and that would fail. So we put the whole cast in a set of parentheses to ensure it happens first, and then we set the title to instructor, and then that's it. P is back to being just a normal person object, even though, again, at runtime, the messages we send will be received by an employee. You do have to be pretty careful, though, when you are casting, which is similar to primitives. We saw that if you cast a really, really big number into something small, that you would get, you'd have a problem. You wouldn't get the value that you would expect. Well, what happens here, let's say I've got person P equals new person. And now I say, let's cast P to employee. Casting doesn't actually change the object. It only says, it changes the reference. It just says, I want you to know what you're really pointing to. That's all that it's doing. But it doesn't change the actual runtime object. So when we try to do this at compile time, it actually says, okay, because what's happening is the compiler trusts you. It says, listen, you're telling me P is an employee. I'm good with that. Let's move on. But at runtime, now when it tries to actually do the cast, it'll look and it'll say, wait a second, P is not referring to an employee. P is referring to a person. I can't do this compilation. And you will get an exception. You will get an exception called a class cast exception. There it is. The above code will generate a class cast exception. And we'll talk about exceptions a little later in this course. One of the ways that we can do what's called a type safe casting is we can check to make sure that it's legal. So there's another operator, it's called instance of. It's a Boolean operator and it just returns true or false. And what you do is you take your reference, you say instance of, and then you check a type. Now, since it's returning a Boolean, we can put this in an if statement. So if P instance of employee, we now know that it is an instance of an employee, then we will do the cast. And we know we're safe because we checked it before we try to do the cast. And that will prevent the class cast exception. The instance operator is used for a lot of things, not just casting. In fact, we can use it to do some conditional code based on a type of an object. So let's say that in our example, the CEO of the company has decided that everyone gets a bonus. It's a one-time bonus, but it's not available to managers. It's available to everyone else. So what we could do is use that instance of operator to make sure that we're not giving it to a manager. And so now our cut check method could look like this. Here we're checking, is E an instance of a manager? That's going to be true or false. This exclamation point, the bang, as they call it, that means we want the opposite. So if it's not an instance of a manager, then we will award the special bonus. Otherwise, then we just keep doing what we were going to do. We can see another example of the power of polymorphism from two very commonly overridden methods. One is the toString, which is used to convert objects to strings. And that should seem pretty familiar. Everyone that's done the labs here has overridden the toString method. There's also a method called equals that's used to compare two objects. So both of these methods, toString and equals, they're defined in a class called Java Lang Object. So yeah, there is in fact a class called Object. Now, here's the interesting thing of how that's applied in Java. Everything in Java, except for primitives, is an object, literally. And what we mean by that is that if you were to go up the inheritance chain for your classes, you would see that at the very, very top is Java Lang Object. Everything eventually extends that class. And how is that possible? You've written lots of classes where you didn't extend Java, or you didn't extend object. And what happens is that even if you don't extend it directly, as long as you don't extend anything, then you automatically extend Java Lang Object. So think back to the MyDate class that you created, or the car. We weren't extending anything. So underneath the covers, we were in fact extending Java Lang Object. So let's look at this example of a person class. We've got this public class person. We're not saying that we're extending anything. But that's really the same thing as saying public class person extends object. So therefore, every Java object is in fact an object with a capital O, whether you like it or not. So, since every class is going to extend object, that means every class inherits from object as well. And two of the methods that they inherit are toString and equals. So whenever we implement those methods, what we're really doing is overriding the methods. So even our MyDate class gets these methods, and they can be used with any of our MyDate instances. Let's look at a couple of examples. Here's our main method, and in our main we're creating two MyDates. So even if you didn't override toString or equals, they're available. And I could say party.toString and see what it prints out, and party.equals taxDo. So we'll look at each of these and see what happens when you don't override the methods. Now let's again take a quick look at what we're passing in here. So we're passing in the same date, April 15th, 2000, to both party and tax due. So what do you think is going to happen when we say party.equals tax due? Clearly, equals is a method that's going to test equality. It'll return true or false. Will it return true? Will it return false? Also, what do you think is going to happen when we say toString? Again, imagine that we haven't overridden the method toString. Well, if we haven't overridden the methods, they're not really going to do a whole lot. By default, toString is just going to create this string with the name of the type, the @ symbol, and then a hash code. Hash code is often used to look up the object reference on the heap. So, for example, if our MyDate is at memory address 1234FF01, depending on the JVM implementation, the hash code might be that address, or it might be something else. Just depends on the implementation. The equals, on the other hand, is just going to be defaulting to the equals operator. So we have two MyDate objects. Since they're actually different MyDate objects, what's going to happen when we call the equals? Well, in that case, it would return false. So this is what we get. We got the name of the class, MyDate, @ and then whatever its hash code is. And the comparison of the two objects is false because even though they had the same April 15th, 2000 date, they were two separate objects, right? They were different objects. So are they equal? Not by the default equals operator. Nope. So we tend to override these methods. Overriding toString is pretty easy. Everyone here that's done the lab has done just that. In the case of MyDate, we probably are just going to grab all of the instance variables, the day, the month, the year, concatenate it into a nice date string with using the slash, and return that whenever people ask for the toString of our MyDate. There it is. We've got our MyDate. And there's our public string toString method where we're concatenating month, day, and year. So that's something that everyone that's done the lab, you've already done that. So now when we call the method toString on the data object, it's a little bit more friendly. Here's an example. We're creating the tax due object. And then we do a system out print line tax due.toString. We get a nice date that's formatted as April 15th, 2017. As an interesting side note, every time we're using the concatenation operator, that plus, and we concatenate with some sort of a reference, that what it is doing is it's calling the toString for us. So here we've got a MyDate called Java release. The date is March 18th, 2014. And so when we concatenate a string with that Java release and we print out this new string, what we'll get is Java SE8 was released on, and there's our toString format. And that really demonstrates the power of polymorphism right there, that plus the concatenation operator. Java knows that if we're passing in an object reference, that it is perfectly safe to call toString because one or two scenarios have happened. One, we've overridden toString, in which case we'll give a nicely formatted string to be used when we're concatenated with another string. Or even if we haven't overridden the method, it's been defined in object, so at least somebody can answer the question, what's your toString? And that's exactly what's happening. The string class knows it can safely call toString on any object because every object is of type java.lang.object. And the power of overriding methods is that we can now override the toString and generate any kind of a toString that's appropriate for our type. And I keep using this term future-proofing. The string class was, in a way, future-proof. They had no idea that a MyDate object would work or ever exist. And they had no idea that we would override the toString method. But they said, it doesn't matter if you do or not. We know we can call toString, and somebody will answer the message. So that's toString. Let's look at equals. Equals is a little bit more work involved. As we saw, comparing two objects using equals is saying, are these the same object on the heap? And the only time it's going to return true is if they are actually the same object in memory. So when we created the two MyDate objects, even though they had the same dates, they were not equal in terms of equals. That would return false. They are different objects. So what we can do is we can override the equals method and use something that's a little bit more meaningful. So here's the method. It's public Boolean equals, and it accepts an object. Now, why does it accept an object? Because when this method was created, they had no idea who would be overriding it and what type would be passed in. So once we get an object passed into this method, we're going to have to cast it to the actual type we want to test against. So this is in MyDate. You can imagine I've got two MyDate objects. I'm going to pass one of the MyDate references into the other's equals method. So here's the equals method, and it accepts an object O, checking to see if O is an instance of MyDate, and if it is an instance of MyDate, then we'll do the cast. And then we're checking to see that the day that we just got passed in is the same as our day, checking to see if the month that got passed in is the same as our month, and the same thing for the year. And if it is, then we're, equivalent. We may not be the actual same object, but we have equal values. And so in that case, we'll return true. Otherwise, since we set up our Boolean result as false by default, then it would return false otherwise. So now that we've overridden toString and equals, we can see it in action. Here we're creating the two MyDate objects. One is a party, one is a tax due. They're of the same date. If I check to see if party is equal to tax due, the answer is no, that's false. They are two different objects. But if we say if party.equals, and we pass in the second object to the first, so here we are taking one MyDate, calling equals on it, passing in the tax due, that'll be true. And so it'll say the dates have the same day, month, and year. And below, you can see that that was the output. One last side note. Whenever you override equals, it is considered necessary, it's part of the contract, that you should override the hashcode method as well. So the hashcode method is something that's defined in Java Lang object, and what it does is it returns some kind of an int to identify the object. It's used very frequently when you're storing objects in hash data structures. So we'll be talking about collections a little bit later, and I'll show you a couple of hash data structures at that time. Later, we'll see that hash code is used by these structures basically to say, are these two objects in the same compartment? Doesn't necessarily mean that they're the same object. If I've got two objects and they have the same hash code, that doesn't mean they're necessarily the same object. It just means that they're in the same compartment. So the general rule is if two objects are considered equal based on the equals method, then they really should return the same hash code when you call the hash code on each of the different objects. But what's interesting is that the converse is not true. So if I've got two different objects, they don't actually have to return different hash codes, though they typically do. So there's the method we would override, public int hash code. We'd have some sort of a computation of how to generate the hash code and return that. And in fact, let me show you an example of a common use of hash code. We would often have to implement a fairly complex algorithm to generate the hash code. But in Java 7, there was a class called objects, and that's plural, objects. And it has a static method called hash. And you can pass in a bunch of variables into it, and it will then generate the hash code for you. So the way that we use that is we figure what are the different things that we are comparing in the equals method, and with the ones that we're comparing, then we pass those same variables into objects.hash. So here's a common implementation these days. Public int hash code, return, and we call objects hash, and then we grab all the values that we tested in the equals method, just to keep them in sync.
This is the final section in which we are going to be talking about the pillars of object-oriented programming, and this one is based on abstraction. Specifically, we're going to look at abstract classes and interfaces to see how we can create a consistency among our program, and also, again, like polymorphism, introduce substitutability and flexibility into our apps. So let's hit that first lecture.
We've talked about several different pillars of object-oriented programming. We've seen encapsulation, inheritance, polymorphism, and now we're going to look at abstraction. Although we've been dealing with abstraction for most of this time in this course. I'll give you an example. Well, actually, let me define it, and then I'll give you an example. So the definition of abstraction is really to simplify, to take something that's complex and break it up in a way that we can deal with it in a more general manner. If you think about in the polymorphism chapter, we had all those different employees and we had a pay service. The employee class itself was a form of abstraction because our pay service didn't really think about, is it talking to an instructor or is it talking to a programmer and so on. All that it cared about was it's talking to an employee and it's able to ask it, what is your pay? But in fact, the message was really getting to a more specific object, the instructor, the programmer, and so on. And their implementation of pay was hidden, was abstracted away from the pay service. That's the basic idea of abstraction. But we have a couple of other constructs we can use to help us implement abstraction. And so we're going to start with the abstract class. So again, abstraction is all about generalization, and that's what we're using abstract classes for. So this is particularly useful when we are capturing similarities between classes. So let's take a look at an example of a rectangle and a circle. So I've got two different classes here, our circle, I've got our rectangle, and if you take a look, you'll notice that there's some things that are different, but there's some things that are the same. Mainly the behavior is the same. They both compute an area. Now they do it in a different way. Circle is going to use pi r squared, and rectangle is going to use height times width. But in terms of behavior, if we abstract what they're doing, they're both computing area. And so when we find these kind of similarities, like we're seeing in the area method, then that can give us a chance or an opportunity to say, can we work with these type of objects in a more general way? Are they related in some way? And so here, the similarity between the two is that they're both shapes. So maybe we can create a more generalized abstract class called a shape. The problem, though, is once we pull area into this superclass, into this shape class, there's no real good way to define what that area method should look like. What does a general area method for a shape do? It's the same kind of problem we saw with employee. Remember, I was kind of complaining. I said, I'm not really happy with the fact that employee has this method pay that returns 0. That just doesn't sit well with me. So, it's the same problem here. We've got a shape, public class shape, but the area method, what do we put in the body? What should it do? So luckily, Java gives us this construct that we can work with, this modifier to say, we're defining a method signature, but we're not going to put a body in it. And it's known as an abstract method. And all that you do is put the abstract modifier in front of the name. You also have to make sure that there's no code block, no curly braces. In other words, abstract methods have absolutely no implementation. So here's an example. I've got the public abstract method double area. There's no curly braces, there's no body for that method, it's just the signature. And what we're doing is we're saying we're creating a method that should be used polymorphically. We're saying that this is a method we want available to all shapes. But when you say that it's abstract, then that's going to force any subtypes to implement that method, specifically to override it. And I really need to emphasize this point. When you make a subtype, something that extends an abstract class, the rule is you must implement all of the abstract methods. If you don't, the only way that you can get around that is if you say, I'm abstract as well. And what I mean by an abstract class is simply adding the abstract modifier to the class declaration. So you can see it right here, public abstract class shape. As long as I put abstract in front of a class, then it is not required to implement all of the abstract methods that it may have inherited. So if I've got a rectangle class and that extends shape, rectangle is going to have to implement area. And that's a good thing, right? That's what we're trying to do. Think back to the employee class. We want to make sure that every employee subtype implements the pay method. And by making the method abstract, then they will have to. They're forced to by the compiler. The only way they can get around it is if the employee, or in this case the shape, also said, I'm also abstract. In that case, you don't have to implement every abstract method. But as soon as you have a concrete class, which is just a class that is not abstract, That means that all of the abstract methods that have been defined in any of the ancestors must have some concrete implementation. Otherwise, the concrete class will not compile. Anytime you have a class that has even one single abstract method, then the entire class has to be declared abstract as well. And what that means is that you can't instantiate it. You can't ever say new shape. And if you think about it, that's probably a good thing. Again, go back to our idea of the employee class that we had for the pay service. You know, the employee was there to share state, to share behavior amongst all the different kinds of employees. But we're never going to say new employee. And wouldn't it be cool if we could be prevented? Let's say someone's new to the team and they don't realize that and they start creating new employees in our program. Wouldn't it be great if the compiler would stop them and say, no, you can't do that? Well, abstract classes, that's exactly what happens. When you try to say new shape or new employee, if we had made the employee class abstract, then it would say, nope, you can't do that. We can't instantiate an abstract class. Another kind of cool feature of abstract classes is that they can actually contain concrete methods, methods that are not abstract. So you can have real methods that do things. But the purpose of an abstract class is really just so that it can be used polymorphically, so that it can be extended. So we've got shape as an abstract class, and we've got circle and rectangle that will extend that shape. And so the abstraction is really in the shape. The shape is just going to define some general behavior. Any shape can compute an area. But it's the subtypes, circle and rectangle, that are really doing all the hard work. That's abstraction. The way that we create an abstract class is simply by applying the abstract modifier to the class. And remember, if anytime we have even a single abstract method in our class, we have to declare the class itself to be abstract. So that's all you have to do. Now the question is, why do we use it? And of course, I've already mentioned this several times. The reason is polymorphism. So what we're doing is when we create this abstract relationship between, say, rectangle and circle through the shape class, now we can write methods that say, you know, I don't really care if it's a circle or a rectangle. I just care that it's a shape. And I'm only going to be sending messages to it that have been defined in shape. Just like the pay service was saying, don't really care if it's an instructor, don't really care if it's a programmer. I just know that they're an employee, and that's how I'm going to interact with them. I know that all employees are going to have a pay method, so that's all I really care about. But you also get the added bonus that the compiler will then stop you from actually creating an object that should have never been made, such as the shape object. We want shape reference variables. We want to be able to accept shape parameters, but we don't want to be able to make a shape object. We want a circle, we want a rectangle. The same thing with the employee. I don't want an employee object. I want to be able to accept employees, so I want employee parameters. I want employee reference variables, but I don't want you to make a new employee. I want you to make a new instructor. So now that we're going to use an abstract class, this is what we have. We've got our circle and rectangle that we had before, and they are now extending shape. And shape is an abstract class with an abstract method called area. And as you can see, abstract classes, they don't actually reduce code. That's one of the things that, we were talking about with inheritance. We're saying this is great because it reduces code. You only have to write what's different. That's not the way abstract classes work. We're not reducing. In fact, we're adding code. But we're setting ourselves up to be able to use these objects polymorphically. And here's an example. It sounds, like a big word when I say that, use these polymorphically, but this is all that I mean. That we can create a method called area difference, and we can take any shapes. We're taking two shapes as parameters, and then to compute the area, we're going to take the area of the first shape, subtract the area of the second shape, and return that value. At this moment in time, inside of the area difference method, we don't really care what the shape is. We don't care if it's a circle. We don't care if it's a rectangle. We only care that it's a shape. And so what we're saying is that this gives us an opportunity to treat all shapes polymorphically. And here's how it would be instantiated. We're creating a circle, setting the radius to be 10, creating a rectangle, setting the height and the width, and then passing those objects into area difference. The actual object types they're real concrete classes, but when they're passed into area difference, if I jump back here to the method, you can imagine what happens when this is placed on the stack. Area difference gets its own frame on the stack. It has two variables, shape S1 and shape S2. What is shape S1 pointing to? Shape S1 is pointing to a circle. Shape S2 is pointing to a new rectangle. So again, this allows us to treat shapes polymorphically. And I do want to show you the error message that you'll get if you accidentally tried to say new shape. So if you do that, if you ever try to create an instance of an abstract class, this is what happens. So here we've got a shape S equals new shape. As soon as I try to compile, this is the error that I would see. Shape is abstract, cannot be instantiated. Boom, just tells you right there what the problem is and why you can't compile. So let's recap. Abstract methods have no curly braces, which means they have no body, no implementation, just the signature and a semicolon. If a class has even one single abstract method, then the entire class has to be declared as abstract. We can't instantiate an abstract class. You can't use the new keyword and create an instance of an abstract class. If a class is going to inherit from an abstract class, the rule is it has to implement all of the methods that have been declared abstract. The only way it can get out of not doing that is if the subclass is an abstract class itself. Part of the main reason that abstract classes exist is to create relationships between classes so that we can use them polymorphically. But it's also, just to share data, to share methods. Remember that we can have actual concrete data and methods in our abstract classes. Not everything has to be abstract in the abstract classes. So as we're building out our circle and rectangle class, we decide that each of the classes should be able to be drawn. And so for each class, we create a draw method, public void draw, and inside the method is all the logic we need to have each of our shapes drawn. And so we get together at a code review and we look at our shapes and we say, circle and rectangle both have this draw method. Maybe we can treat this polymorphically in the same way that we treated area. And we all agree that's a great idea. Let's employ some abstraction here. And we move draw into the shape class. We create it as an abstract method because how do you draw a generic shape? It's the same problem as computing a generic shape's area. We just want to make sure that the method is available so that whenever a method says, I take a shape object, that they know that they can call area and they know that they can call draw. So the meeting's about to end and everyone's happy except for one person. And they say, I've got a class too. And with this class, I have draw. Is there any way that I can be used in all these great methods you guys are coming up with that are accepting shapes? And we say, well, tell us a little bit about the class, and they show it to us. It's called public class cat. And they have, just like they said, a method called public void draw. And they like to be treated as just like the rectangle and the circle so that they can be drawn as well. And we understand that, but we say, I don't know, how do we make this work? And they say, it's not a problem. What we can do is just say public class cat extends shape, and by the rules of polymorphism, now I can pass in a cat to any method that accepts a shape, just like I could pass in a rectangle or a circle. Okay, technically speaking, that person is correct. But let's think through the ramifications of doing this. If we say that a cat extends shape, and we have this method, public void draw, will this compile? Will this class compile? And the answer is no, because what is one of the rules of extending an abstract class? You have to implement all of the abstract methods. So now the person that made the cat is also going to have to come up with a method called area. Now, sure, we could certainly figure out a way to compute the area of a cat, but probably not recommended, and we're probably getting outside the scope of what it means to be a cat. And, that's why we have that is a rule. If we can say something is a type of another, then as more and more methods are added to the parent class, it doesn't really negatively affect the child class. It makes sense. What I mean by that is if we add any other kind of method to a shape that is related to a shape, it's reasonable to think that a rectangle and a circle should implement those methods. Okay? But as we add more and more methods that are related to a shape, the cat is going to have to implement all those abstract methods too. And just like that area method, it's not always going to make sense. And so that's why we use that is a rule. A circle is a shape. Yep. A rectangle is a shape. Sounds good. A cat is a shape. No, we're getting outside of the scope of what it means to be a cat. But all is not lost. What we can do is create something called an interface. And this will allow us to treat the cat polymorphically just like we're treating the shapes. So what we do is we create an interface. It's just public interface and then the name. You replace the word class with the name interface, and then you define your methods. And there's some rules about the methods we'll talk about in just a second, but here's an example. We've got the public abstract void draw in here. And now what we can say is that the cat is going to implement this interface, and we can even say shape implements this interface. So it's another way of adding roles or responsibilities to a group of objects, and it allows us to treat those group of objects polymorphically. So an interface is a pseudo-class. Interfaces are going to be defined in their own files. They have the .java extension, so that last interface we just saw would have been drawable.java. We replace the word class with the word interface, so public interface drawable. All methods that we're going to put in the interface are public. And then they also have to be one of three types: abstract, default, or static. Now, we've already talked about abstract methods, so you know what those are. We'll talk about default and static coming up. Now, since the public modifier is implied, sometimes you won't see it. In other words, if you look at an interface and it doesn't say public, it's still public. Public is implicit, even if that modifier isn't written in the file. Also, if we don't have one of these modifiers, abstract, default, or static, then by default it is assumed to be an abstract method. In addition to the methods, interfaces can also contain variables, but they have to be constants. They have to be public, static, and final. And because they have to be, all of those modifiers have to be applied, if you don't put those modifiers on, they are assumed. So just remember that when you run into abstract methods in an interface, that they follow the exact same rules as abstract methods in abstract classes. Interestingly enough, up until Java SE8, that was the only kind of method that we could have in an interface. Once 8 came out, we had default and static methods that were added to the language, and we're going to define those in the next lecture. But do keep in mind, if you look at any old blog posts, read any old books, or see videos, that they may mention that interfaces can only contain abstract methods, and that was true for many, many years. But as of SE8, that is no longer true. We do have these other types of methods. So let's talk about those in the next lecture. We create these interfaces, and then these interfaces in turn are implemented by classes. So just like an abstract class, you can never create an instance of an interface. You can never just say new interface. That's not legal in Java. There is a concept called an anonymous class, which we don't cover in this course, and the syntax makes it look like you're creating a new interface, but you're never just saying new interface. And what the interface is doing is it's setting up a contract. It's defining the behavior that is expected by all of the classes that implements this particular interface. A class can implement any number of interfaces it chooses to do so. I'll show you how that looks in a minute, but it's just a comma-separated list of all of the interfaces. And when we do that, what we're saying is that this class overrides the methods that have been defined in the interface. At least it overrides the abstract methods in the interface. So here's an example of the cat class using the implements keyword. So now we've got the public class cat, and it's extending animal, extends animal. That makes a lot more sense than extends shape. After you specify your extends, if you have something that you're inheriting directly from, you then say implements and then the name of the interface. So public class cat extends animal implements drawable. And then what we do is we implement, or I should say override, all of the methods that were defined in the interface. And because cat implements drawable and drawable has the draw method, then by extension, cat must override draw. If it doesn't, just like we were seeing with the abstract classes, the compilation would fail. It would say, what are you doing? You said you were drawable and you haven't implemented this abstract method, and it will fail. So now here's our revised hierarchy. Notice that we've got the drawable interface, and both shape and cat will say that they implement that interface. Circle and rectangle extend shape, and everything looks pretty good. Now, of course, we could have said circle implements drawable and rectangle implements drawable. But the nice thing about what we're seeing here is that by saying shape implements drawable, that means if we make a brand new class later, let's say a triangle, and if we say triangle extends shape, then we, by just the hierarchy that's already been set up, we are saying that triangle also implements drawable. So that's one of the nice things about these diagrams. By the way, the diagrams that we're looking at, they're a form of UML, Unified Modeling Language. So what we're seeing here is you just kind of go up the line. So circle extends shape. Shape is implementing the drawable interface. Therefore, circle implements the drawable interface. It's just implied by the hierarchy. And so like I said, by having shape implement the interface rather than each class, then we're saying for the future, if someone creates a brand new class like triangle, then they too automatically implement drawable. And as you can see, both circle and rectangle must implement all of the methods. They have to do area, and they also have to do draw. Notice that shape doesn't have to implement the draw method. Why is that? Well, remember that shape is an abstract class. And I said one of the rules about abstract methods is that they must be overridden by any concrete class. Well, shape is not a concrete class. It's an abstract class, so it's not bound by those rules. It can override whatever method it wants, and it doesn't have to override any that it doesn't. If it doesn't override a method, such as draw, which is what it's doing, it's not overriding the method, then it's passing the buck. It's saying, okay, whoever extends shape now has to implement the draw method, and that's really the behavior that we want to see. So here's an example of what circle looks like. We've got our public abstract class shape, which implements drawable. Note once again that we do not have the method draw in that abstract class, though we could have. And if we did have draw implemented in shape, then circle wouldn't have to. They could. Circle could, override it if it would like, but it wouldn't have to. Same thing with rectangle, same thing with triangle, and so on. But the shape class did not override draw, so circle does. Circle now overrides area, which is the abstract method defined in shape, and it overrides draw, which is the method that was created in drawable. And now circle can be passed into any variable that's expecting either a circle, a shape, or a drawable. And that will continue on for any future class that's made that extends shape. If you extend shape, then you're going to have to override both area and the draw method, or declare your new class to be abstract as well. And remember that to override a method successfully, you're going to have to match that signature. And we're going to have to follow all the rules that we've talked about before on what it means to override a method. So an interface can be visualized with a few different analogies. I like this one the best, that an interface is a contract. And so when a class says, I implement this interface, what they're saying is, yes, I agree that I will provide implementations of all the abstract methods that have been defined in this interface. You can also think of an interface as like a role that the class plays. So in some cases, my circle will behave like a shape because it is a shape. But in other times, it will behave just like a drawable object, which is its role. Also, an interesting thing about creating interfaces can extend other interfaces. And what that means is that an interface can inherit all of the methods that were defined in another interface. Let's say I've got interface A and interface B. And interface B extends interface A. And now I say that I implement interface B. That means, by definition, I implement both interface B and interface A. I don't have to explicitly write that for the implementing class. I just have to say, I implement interface B, and if interface B extends any other interfaces, well, then I'm implementing those as well. Now let's talk about this concept of a default method. A default method is one that includes a body, so it's just a normal method, but it has the default modifier as well. And here's what it would look like. In my interface, I've got a draw method. There are now curly braces, which normally wouldn't be there. And then we just have our method, the body of the method. So why do we have to put the word default if it's just a normal method? And that's really about backwards compatibility. Because until we were able to even add default methods, which was Java 8, any method that didn't say abstract, the compiler would say, aha, I know you're abstract, I'll add that modifier for you. So because of that rule and because of backwards compatibility, we just have another modifier that we have to add. Because of this, the default modifier is something you're only going to see in interfaces. You won't see them in abstract classes. You won't see them in concrete classes. They're not necessary in those constructs. And the purpose of a default method is that it gives us the opportunity to say, I'm going to add some new methods to my interface, and it won't break people that have already been implementing the interface. So what I mean by that is, imagine that you implement an interface, and the rule of the interface is that you've got to override all the methods, right? If I say I implement drawable, then I've got to override all the methods that are abstract and drawable. So if I added another abstract method and then put it into the code base and you pull the new code, try to compile again, your code breaks because you are no longer implementing all of the abstract methods. So now we can put a default method here and you can decide whether or not you want to override the method. Here's an example. I've got a class Rectangle that implements drawable. I'm able to call draw inside of Rectangle even though I didn't override the method. It's legal because there is a default implementation in the interface. The only kind of drawback about using the default implementation is that when they write a default implementation in the interface, it doesn't have access to any instance variables. And that's because it is a method that only has access to what's available in the interface itself. And what kind of state do we have in the interface? We just have constants, public, static, and final. So no instance variables are available to a default method. But that's only if you're relying on the default implementation. If we override draw here in Rectangle, then sure, we have access to all of the instance variables of Rectangle. But the default implementation does not. So that's default methods. What about static? Static methods are very similar to default methods, but with two exceptions. First of all, they're going to list the static modifier instead of default. And then they'll also have to follow all the rules that we've talked about with static methods. The other thing that's interesting is that concrete classes don't actually inherit static methods in the same way that they do default. And if you think of the terminology, that explains why. Remember that we said that one of the rules about overriding methods is that you can't really override a static method. You can hide a static method. But the problem is that, or not the problem, but the way it's used, is that a static method is going to be invoked by the reference type, not by the real runtime object. So think polymorphically. Person P equals new employee. Person is the reference type. Employee is the actual run type. So if we call a static method on P, it's not going to call the static version that's an employee. It's going to call the static version in the reference type, which is person. So concrete classes don't actually inherit the static methods. We'll have to access them like we would any other static method. And here's an example of that. I've got drawable with a public static void draw, and it's got some kind of implementation. If I want to access that method, I can't just say draw, which we see right here. Like we could do that with the default method, right? That was perfectly legal. But with a static method, it's going to say, what are you talking about? Rectangle doesn't have a method called draw. So even though we implemented drawable, we do not inherit the static methods. I also can't say rectangle.draw for pretty much the same reason. Rectangle doesn't have draw. But I can say drawable.draw. That's legal. And now, just like abstract classes, we're posed with the same question. Why? Why do I have to learn interfaces? What's it going to do for me? And the answer is really the same. It's going to allow us to employ polymorphism. Because what we can do now is create variable reference types that are interface types, just like we were doing with abstract classes. So now we can store a circle, a rectangle, a cat, all of these things in a drawable reference variable. So for example, I've got drawable D1, that's going to have a cat. Drawable D2 has a circle. And then we can call draw on both of those objects. Now, of course, you may think, well, couldn't I have just created a cat and called draw? Couldn't I have created a circle and called draw? Certainly, but now this reference variable can store any of those, and then when we hit the code that wants to draw, we don't really care if it's a cat or a circle. We've abstracted that. We've said, we just know that you're drawable, and we want you to draw. Now, could I say d2.area? D2 is a circle, it has area, but the answer is no. Remember the rules about polymorphism, that when we're calling methods, when we are reading or writing to instance variables, that it's going to look at the reference type to see what's available. And the method area is not available to drawable. The method area is available to circle, it's available to shape, it's not available to drawable. So what we could do is cast it, just like we were doing with abstract classes. So here I've got my D2 reference. I'm casting it to be a circle. Remember, we put parentheses around that whole casting so that it gets done first. And then we call area. That's legal. And now we can make polymorphic methods as well. So I've got a print method that takes a drawable. And in this method, what we're saying is we don't really care what you are. We don't care that you're a circle, a rectangle, a cat. We've abstracted that away. We've simplified this. We just know that you're something that can be drawn and that we can call the draw method on it. That's the power of polymorphism. Now, interfaces also have give us the ability that we can implement many interfaces at the same time. And so this is kind of a way of giving us multiple inheritance, something we don't get from extending classes. Now, a class, remember, can only extend one class, but we can implement any number of interfaces. And here's an example of that. So I've got my public class foo. We're implementing drawable, runnable, serializable, and any other interface that we want to implement. The only rule we got to follow is that we make sure we override all of the abstract methods that these interfaces contain. But this flexibility does add another rule, and this is because of the addition of default methods in Java 8. If you happen to implement two or more interfaces and they have default methods, not abstract, but default methods, and the default methods have the same signature, then this class that's implementing the interfaces must override the methods. So we've got class foo here. It's implementing drawable and runnable. If drawable and runnable had the same method signature as a default method, then foo would be required to override it. We wouldn't be able to use the default implementations. Why is that? Well, think about it. There's an ambiguity there. Which of the default methods should be called? If we're relying on a default method and we implement more than one interface that has this exact signature, which one should be called? Since we don't know and the Java platform doesn't know, it forces us to override the method in the class itself. When you create an interface, you'll be tasked with coming up with a good name. Interface names are typically adjectives, or they include the word listener, or maybe even the word interface in the name. A lot of the interfaces end with able, like we saw drawable. If you look at the JDK and look at the API that's available, you'll see a ton of these. Runnable, serializable, clonable. We have some that use the listener syntax, so action listener. Ultimately, it's up to you how you name your interfaces, but this is fairly common. Are employees really going to be the only things that get paid for by the system? Maybe we've got other companies and other people that need to be paid, and we'd love to use that cut chetting service to issue the checks. So rather than having cut check take an employee, maybe we should have something that accepts an interface, maybe a payable interface. So we could rewrite pay service to take a payable. And what we're saying now is, well, you might be an employee. We don't know. We don't really care. We just know that you're something that's payable. And we know that if you're payable, that we'll be able to call this method pay. It's a method that was defined in the payable interface. And so we've got this payable interface. It would look like this: public interface payable. Notice it says public double pay. We don't have the word abstract, so it's assumed to be abstract. If we had default, if we had static, then that would be assumed to be default and static. But if it was default or static, we wouldn't be able to just have a semicolon right here at the end. We would have curly braces and a body for that method. And now anything that actually needs to be paid simply has to implement the payable interface. In fact, now we can really improve the architecture of our employee. So we could make employee abstract, which is what I really wanted to do. Remember, I said I'm not really happy with the fact that the pay method could return 0. I don't even want you to ever create a new employee. I want to make sure that we enforce all subtypes of employee, like programmer and instructor. I want to make sure that they override the method pay. And those are the objects that I actually want you to instantiate. So by making employee abstract while still implementing the payable interface, then that's going to pass that buck to all the subtypes. It's going to say all employees must implement the pay method, and you can never say new employee. This is perfect. So it would look like this: public abstract class employee extends person, implements payable.
In this section, we're going to learn about a new construct that was added to Java 8. It's called the Lambda. And the Lambda gives us a way to pass in a block of code to a method as a parameter. We'll also talk about static imports. So let's hit the first lecture and look at Lambdas.
In the previous section, you learned all about interfaces. You learned all of the syntax and the rules, and we really don't have a lot to add to that. But there are two different kinds of interfaces that I want to show you, especially the second one I'll be introducing, because it's related to the topic of this section, Lambdas. So when an interface doesn't contain any methods at all, it's referred to as a marker interface. And a marker interface is typically going to be used by the APIs of the Java platform, and it'll use it to figure out, does this object adhere to some kind of a rule? Can I depend on that the developer thought about and took care of some type of situation? Here's a really common marker interface. It's the interface called serializable. It's in the java.io package, and there are no abstract methods that an object or a class will need to implement. They just simply say implement serializable, and then that's it. No methods to implement. It's not all that common for a developer such as ourselves to write our own marker interfaces, but it's pretty common that as we write code in classes that we'll use marker interfaces that were provided by the Java API. Now, back to serializable, the purpose of this particular interface is to say, well, let me define serializable. Serializable means that we can take our object, take all the state in it, and turn it into a byte array. And then that byte array can be used to send it across the network or to save it to a file and so on. And so when we say that we implement serializable, what we're saying is we thought about it. We thought about which pieces of state should be serialized and which pieces shouldn't. Outside the scope of this course, but there's a keyword called transient. And if I mark a piece of state as transient, then it will not be serialized when the object goes through that process. And so we use these kind of marker interfaces to let the Java API know, yep, we're okay, we've taken care of this. So that's all that a marker interface is. Now, a functional interface is something that has one abstract method. Marker interface has no abstract methods. A functional has one. So here's an example. I've got my payable interface, and I have one abstract method, raise salary. Note that I don't have the word public or abstract in this definition, but remember that that's implicit. If I don't say public, it's definitely going to be public anyway. That's implicit. If I don't say abstract, static, or default, then it's assumed to be abstract. So that is a functional interface. Now, if I had additional methods in here that were default or static methods, it's still considered functional as long as there's only one abstract method. There's one little sort of gotcha rule about that. Maybe it's the kind of thing you might see on an exam, but the only one abstract method rule is bent if we make an abstract method that's overriding a method that comes from Java LangObject. In other words, if I had public abstract string toString, which is overriding the method toString in Java LangObject, then that would be okay. I could have additional abstract methods that come from object, but that's it. And the reason that we're focusing on functional interfaces is because it's tied directly to a new syntax that we have in Java SE8 called the Lambda expression. And in the next lecture, we'll take a look and see what that is. One of the most celebrated pieces of functionality that was added to Java 8 is called the Lambda expression, though most people just call it a lambda. It's a syntax that allows us to write a block of code and to pass it around in the same way that we would a primitive or an object reference. And so the use case is, imagine we got some kind of a functional interface. The functional interface, remember, defines one abstract method. And we've written a method that says, we accept a parameter. It's really any object that is an instance of this functional interface. So what we normally have to do, we would normally have to create a brand new class that implements the functional interface. We'd have to override the abstract method. We'd have to instantiate an object from that new class and then pass it into the method. Let's actually see that in action. So here is the traditional interface implementation. We start with our functional interface. We've got payable, and it's going to have one method here. It's an abstract method, raise salary. Then we're going to have some part of the code that's going to say, I accept a payable object so that I can call the method raise salary. So here's an example of that. We've got our cut check method. It accepts a payable object, and it knows that it can call raise salary on it because that's the only abstract method it has. At this moment in time, cut check doesn't really care what object you truly are, if you're an employee or if you're even a cat. As long as you are payable, it knows that it can say raise salary and you'll return some kind of a double. That's all it cares about. So that is, nothing's changed there in Java 8. That's how you would write a functional interface, and that's how you'd make a method that accepts a functional interface. But here's what's changed. Prior to Java 8, what we'd have to do is make sure that some class, some concrete class, implements that payable interface. And then we would create an implementation. We would override the raise salary method. Okay, fine. So then to use it at runtime, we would create a new consultant, call the cut check method, and pass in that consultant object. And of course, that seems fine. That seems like exactly how you would do it. It does work as expected. But the problem is that anytime we want to make a new raise salary implementation, we have to create an entirely new class. Now, I did mention previously that there's another construct we don't cover here called an anonymous class. That's an alternative way that we could do it, but it's still more code that we'd have to write than what we're about to see. Specifically, the Lambda is going to allow us to pass in a method implementation for that functional interface without having to create an entire class for it. So here's an example now. We've got our salary, which is $75,000. We're calling cut check, and the syntax you're seeing here, that is the Lambda expression. The syntax of the Lambda is, first of all, on the left side of the arrow token's right in the middle there, it's just a dash and a greater than symbol. In this case, what we're saying is we're implementing a method, and we're going to have one parameter passed into us. It's type double, and we're going to call that parameter percentage. Then on the right side of the arrow token, that's the implementation. We are implementing the abstract method without defining the whole signature again. We're just putting in the method body, the things that would be in between the curly braces. So in this case, we're saying we're going to return the salary plus the percentage multiplied by the salary. What if we had more than one parameter? If we had multiple parameters that are being passed into the interface method? Well, in that case, they just need to be comma separated. So here we're creating an implementation of a method. We're going to be passed in 3 parameters. We're naming those parameters A, B, and C. And then on the right side of the arrow token, that's where we're using them. Return A plus B plus C. If your functional interface defines a method that has no parameters, you just use an empty set of parentheses. So in this case, nothing's being passed into our method. We're just executing the code in the block. So that's the Lambda syntax. You're essentially just specifying what is the implementation of the method without having to create the class, without having to redefine the method signature. You just pass in the body. And of course, mention what the parameters are that are being passed into your method. But we can even simplify the syntax further. So let's start with the Lambda expression that we had in cutCheck. Let's review it. On the left side of the arrow token, we've got double percentage, which means when the body is executed, when our implementation is executed, a parameter is going to be passed in. And we're going to refer to that parameter as percentage. It's of type double. And then on the right side of the arrow token, that's the body. And we're saying we're going to return the salary plus the percentage multiplied by the salary. Now the parameter type on the left side is optional. I can just put percentage. We don't actually have to specify that it is double. If it turns out that on the left side there's only one parameter, we're only being passed in one parameter to the body of our method, then we don't even need the parentheses around it. So now on the left side, we just have percentage. We don't have the type double, we don't have the parentheses, and that's perfectly legal. But again, only if there is only one parameter. If we had more than one parameter, we wouldn't be able to do this. Now on the right side, where we're defining the body, if there is only one statement in the body, then we can get rid of the curly braces, we can get rid of the return keyword, and we can get rid of the semicolon. But we have to do that all as a group. You can't just say like, well, I think I'll just get rid of the curly braces, or just the return, or just the semicolon. They all appear together, or they're all omitted together. And so now this is the simplest version of the Lambda expression we can have. So we accept a parameter that we're calling percentage, and then the body, the execution is we are returning the salary plus the percentage multiplied by salary. So now the cutCheck method invocation looks like this. Here we've got our double salary, 75,000. We call cutCheck and we pass in that entire Lambda expression. And although that looks a little bit like more code than just simply passing in the consultant, we didn't have to actually make an implementation of the functional interface. We didn't have to override the method completely with the method signature. We were able to just simply create this nice, terse Lambda expression. As a side note, the parameter names between the Lambda and the functional interface don't actually have to match. I used percentage in both the method definition and the Lambda, but you can see here we could just have used X. I could have said X is the name of the first parameter passed in. As long as I use X in the body, then that's legal. You can use whatever parameter names you want. One of the more common functional interfaces that people write is where they are going to run some kind of a test. They accept a parameter, they run some kind of a test, and then they return true or false depending on whether or not the test passed. So when the Lambda expressions were introduced in Java 8, they included another interface called the predicate, and it handles that very scenario, that it's a test method. It's passed in a parameter, and then it returns a Boolean. So the type of the interface is predicate T, and notice those arrows with the T, that's known as a parameter type. So T, we just simply specify what is the type of object that's going to be passed into the test. So the method then is called test, and it takes an object of that type T and then returns a Boolean. So in other words, you just run test, we pass in a parameter, we execute some code to determine whether or not the test passes, and we return that result to the caller. So that T, I said it's a parameter type, that's a part of generics, and that's something that we're going to be talking about in the collections section. So let's look at an example. Let's say we've got a method where we're able to include a customer in a promotional mailing, but we want this to be fairly flexible so that someone who calls this method to kick off the mailing could give us some sort of a test to say whether or not a customer should in fact be included in the mailing. So here's our promotion service class. We've got a customer, and we've got our method send promotion, which takes a predicate, and the predicate is going to be passed a customer object. And so then what we do is we simply call test, we pass in the customer that we have, and whoever calls this method and passes in the predicate can run whatever arbitrary test they want. They'll return true or false, and then we'll find out if we should include them in the promotional mailing. So any code now that's going to call this sendPromotional method can pass in a Lambda expression to execute that test. So it might look like this. We instantiate the promotion service object, we call sendPromotion, and then we pass in our Lambda. So remember, the left side is the parameter that we're about to receive. We're receiving a customer, and then the test is going to be customer get age, and make sure that they're greater than, or their age is over 18, greater than or equal to 18. If it is, return true and they get the promotional mailing. If it's not, return false and they don't. Applications typically need some constant values to use in the life of the program. We've defined constants as variables that are typically public, static, and final in a class. We've also seen that interfaces can define constants alongside the abstract, static, and default methods. So for example, I could have a interface here called SafeDriver, and we've got some constants in here. We've got maximum speed, safe falling distance, minimum fuel level. We also have a static method, printMaxSpeed. In this case, it's going to print whatever the maximum speed is. These are just constants and static methods that are available in the interface. Now imagine a situation where you're implementing a class and you'd love to import these different constants, but you don't actually want to implement drive and stop. You don't really want to implement the interface, you just want the constants. Well, Java has a feature which does allow us to import constants and static methods without having to actually import the entire class or implement the entire interface. It's called a static import. And it's too bad it wasn't called an import static, because that's how you actually write it. You're never going to write static import, you write import static. It's an import that goes along with all of your other import statements, but just notice that it includes that keyword static. And then what you do is you put in the name of the static constant or the static method that you are trying to import. So in this case, we just want to call the method printMaxSpeed. So now here we have printMaxSpeed. Now, of course, we could have just said SafeDriver.printMaxSpeed here in the main method. That would have been perfectly fine, but this allows you to write a little less code. We don't have to put the name of the interface. We can just invoke the method. Now, the previous example showed us importing one specific static member. We can also implement all of the static members of an interface or a class using a wildcard. So in this case here, I've got import static com intertech safedriver.star. And so now I'm going to get all of the static members that are inside of SafeDriver. So I can refer to maximum speed, and that is perfectly legal. I can call printMaxSpeed. But one of the things about the wildcard is that it doesn't act as a traditional import. So what I couldn't do, oddly enough, is say SafeDriver.SafeFollowingDistance. And it's not the safe following distance that's the problem. If I got rid of SafeDriver, it would work. But the problem is that when this class is being compiled, they're going to see SafeDriver, and since it's not, we didn't do a traditional import, it's going to say, I'm not entirely sure what SafeDriver is. So if we did, for some reason, wanted to include the name of the interface occasionally, then we'd have to uncomment this line right here, which is your regular import com intertech SafeDriver, and then I wouldn't have to include, or then I would be able to include the type. Why would you want to do that? I'm not entirely sure, but that's one of those kind of gotchas that they may throw at you on the exam. So I want you to be aware that it's that's just not legal unless you have a normal traditional import. There's also a note down here that says, similar to regular imports, wildcards and static imports are not recursive. And really that should be kind of obvious, because the way we're using the wildcard here is different than a regular import. With a regular import, we're applying a wildcard to a package, and there could be sub-packages. But here we're applying the wildcard to either a class or an interface. So there are no sub-packages to a class or an interface. The wildcard simply means grab the stuff that's in this particular entity. But it's not just interfaces that the static import is used. It can be used to access static members of a class. For example, if you're using the Java Lang math class quite a bit, you could add a static import to reduce the amount of typing. Like, for example, math has e as a constant and pi as a constant. And of course, we don't have to import the math class because it's in the Java-Lang package. We get that out of the box. But anytime we'd refer to pi or e, we'd have to include the math.reference, which would look something like this. So here I've got my calculation, and I'm multiplying some stuff to math.pi, right? Math.pi. If I use a static import, now I can refer to pi without having to include the math dot. Does that really give you a whole lot? I don't know. I think that's debatable. I don't tend to use a lot of static imports myself, but they are part of the syntax, so you need to know, and it's definitely a part of the exam.
In this section, we're going to look at another new API that was added to Java 8. It's called the java.time library, and it's going to give us classes to work with, what it sounds like, time and date. So we'll look at local date time, local time, and another class called period. So let's start working with dates.
Java 8 gave us a brand new set of classes to work with for dealing with dates and times and durations, and they replaced a library that really wasn't all that popular. There were a number of reasons that people didn't like it, and this new set of classes and enums and so on addressed a lot of those concerns. So we're going to look at some of those classes, and we're going to focus on the classes that you'll find in the Java Associate exam. So if you're taking the Associate exam, these are the four you need to know: the local date class, the local date time, the local time, and finally period. And we're going to go over the more common methods and discuss how these objects are used, so you have a really good understanding of them after this lecture. However, if you are going to be taking the exam, you're going to want to go in and study these a little bit more. You can never have enough practice for this exam. So with that said, let's do some code. Let's go to a class that I've made here. Just a real simple class so that we can test some of these different constructs. I made a very simple print method just called p, so that I don't have to keep wasting space on my line with system.out.println, just so that it's just going to be easier for teaching. It's nothing I probably would do in my real world code. I would just type system.out.println, but just wanted you to understand what p was when you see that in my code. We're just printing out the object. So let's start with a local date. And local date represents, as it says, a date. It does not represent a time. So when we're dealing with a local date, if we try to use any print format specifiers, now I'll show you that in a little bit too. So there's a way for us to take an object, print it out with some kind of a format that we like. And when we do that, if we accidentally include any format specifiers that would include time, then it will fail because this is just a date. The other thing to keep in mind with all four of these classes is that it is immutable, just like our strings. Once a local date is created, you can't change it. Now, there's plenty of methods that make you think you're changing it. We've got plus weeks, minus days, and so on, plus hours, minus months. Lots and lots of these methods to what looks like we're changing the date. But what we're doing, just like a string, is we're really creating a brand new local date object. And so I'll show you some examples of that, but just remember that we are dealing with an immutable object. So we've got local date, and we'll just create one called now. And there is no constructor that we'll be using for these immutable objects. We will always be using static methods on the class itself. So if you're taking the exam and you see something like this, that is a gotcha. There is no constructor that we can call using new. That's for local date, local time, local date time, and period. So what we'll do is we'll say local date, and we'll make one that's really simple. This is local date now. So what I'm doing is I'm taking the date time that's right now and putting it, just the date, and putting it into this variable now. Let's print it out so you can see what it is. So I'll just print out now, and we'll run this. And if you look below, this is the default way it's printing it out. So you can see that it is 2016, it's May 21st. Like I said, if you don't like how it's printing this out, later I'll show you a formatter that we can use, and that will change the way that this is printed. What are some other ways that we can create a local date? Well, let's say I've got my hire date and I want to put that in there. One of the ways we can do this is with a method called of. And if you look at down below here, we've got a few different of methods that we can use. We can use the year, the month, and the day of month as ints. We can also use the year, and then we can use an enumeration called month, and that's really recommended. I'll show you how to do that in a minute, along with the day of month. There's of the epoch day. The epoch day is January 1st, 1970. It's how a lot of computers base their time. And then of year day, and so that is what year and then what day of year. Those are our options with of. So what I'm going to do is choose this one right here, the second one. And when was I hired at Intertech? I believe it was 2008. The month was April. There you see it's an enum. And the day of month was somewhere around the 21st. All right. So now I've got a hire date. And once again, if we just print that out, run that, there you can see the date. So now we've got a date that represents April 21st, 2008. Once we create dates, how do we change them? Well, there are a number of different methods. So what if I want to have a local date that is going to be a week from now? What I do is I'd say now dot plus, and we'll get to the generic plus where we can just pass in a temporal amount. That's where we can pass in a period. I'll show you how to do that in a little bit. But notice we got some nice helper methods here. We've got plus days, plus months, plus weeks, plus years. So if I wanted to add a week, I just pass in the number 1. And now if I print that out, a week from now, and run that, here we go. It was May 21st, and now it's going to be May 28th. You can go in the other direction as well. So I can say local date a week ago equals now minus weeks 1. Print that out, a week ago. And we see we've got May 14th. Now here would be the exam gotcha. We want to find out what a week ago is, so we want to change now. If they do something like this, okay, obviously you can't print it out if I'm not assigning it to a new variable. But so here I say now dot minus weeks. That doesn't do anything. Let's print out now again after we do minus weeks. And you can see that the original was May 21st. And the new version is May 21st because we didn't really change the object. It's an immutable object. That's a big gotcha. So make sure you're always assigning the value. If I really wanted to change now, all I'd have to do is say now equals. And now when we look at it, now has been changed to May 14th because we didn't really change the date, we changed the reference and what it's referring to. And there are other interesting methods that we can use. Like if I want to make sure that my hire date was before now, I could say hire date is before now, and that will return a true or false. Let's print that out. So was my hire date before now? Now obviously we would think it would be, but let's just run it, and it does say true. And you can do is before, is after, and there are a number of different methods that you can use. So that's local date. In the next lecture, we're going to look at local time and local date time. So the other two types of classes that we have, local time and local date time, are very, very, very similar. The difference, of course, is what type of data they hold. So if I've got local time now equals local time dot now. So a lot of the same methods that we've seen before. And then I'm going to print out now. Now, of course, I do have to comment out this other code since I'm reusing the same variable. But now I've got local time now, and let's print it out. And so notice that it's printing out just the time. It doesn't print out the date because it's not a date object. It is a time object. And so what we're seeing here is we've got the time 10, that's the hours, the minutes, the seconds, and then the nanoseconds. Just as we did with local date, we can use the of method. So let's say that I thought the local time, time hired was of, and just let's take a look and see what we can add here. We can add, if we go down to this one, the third one down, we can add the hour, the minute, the second, and then the nanosecond. We can also just add the hour, minute, and second, and we can also add the hour and the minute. There's a couple of other methods that start with of nano of day, the nano of day, and then of second of day. But we're going to start with this one. Let's start with what's probably more common. I'm not going to deal with nanoseconds. We'll just deal with the hour, minute, and seconds. And let's say that it was 1 o'clock. So I'll say 13:00. Don't even need that O and O. Now let's print out time hired. Run that. And there you can see that it is 1300 or 1 o'clock. Now, if we don't like that format, we can use a formatter, which I'll show you in the next lecture, and then we'll do that with all the dates and times as well. We can certainly create new dates based on old dates, just as we did with the local date. So I can say local time an hour from now equals now dot plus. And notice that we've got plus hours, plus minutes, plus seconds, and plus nanos. So an hour from now would be 1. And if I print out an hour from now, we'd see that it went from 10:34 to 11:34. We can go in the opposite direction, just as we did before. Local time an hour earlier equals now dot minus hours. And we'll print that out. And sure enough, it's 9:35. There are comparison methods as well. So if I do the same thing I did with local date, we could say that the time hired dot is after is before. Let's say is after now. And that'll give us a Boolean. So we would just wrap that in a system out print line just to see what the value is. And in this case, it's true. The time I was hired was 1 p.m. The time now is approximately 10:35. And so, sure, time hired is after now. Then we've got the local date time. Just give us a little more space here. So local date time now equals local date time dot now p now. Print it out. Let's comment this other stuff. And let's put a semicolon at the end and run it. And so now you can see that we have both the date and a timestamp. And the timestamp is delimited here with the T. So we've got the date, we've got a T, and then we have our timestamp. And now we've got a lot of options of what we can do with the of method. So local date time, time hired equals local date time of, and now we can just choose one that has a whole bunch of stuff. So what was the year? 2008. The month was April. The day of the month, the 21st. The hour is 1300. The minute. And we'll put the second as well. And now let's print out time hired. And run that. And here it's printing out 2008, April 21st at 1 o'clock. We have comparison methods just like we have with local date, local time. Let's just take a look. System out print line. Now is before time hired is false. And that's what we would expect. Now there's one more class that I want to share in this lecture, and that's called period. So period, just like everything else we've seen in this section, is immutable. So when I create it, I have to make sure that I'm assigning any changes or what appears to be changes to a reference variable. Also, we can't use a constructor. We have to use a static method. So in this case, I'm going to say, rather than saying new period, which would be wrong, it's not legal, what I'll do is I'll say period.of. And we could do of days, of months, of weeks, of years. But I'm going to just do the regular of method, which will allow me to put in years, months, and days. So I'm going to say 3 years, 5 months, and 12 days. And this is a generic period. This isn't a specific date time. This is something that we can use to add to another date or time. We could use it to subtract. In fact, let me show you. We've got our local date time now. Let's subtract this period from it. So what I'm going to do is reassign now. I'm going to say now equals, and we will then say now dot minus, and we'll just pass in that period that we just created. Let's print it out, see what the new value of now is. And it did exactly what it should. This was our now date time over here. Here's the 3 years, 5 months, and 12 days subtracted. Notice that it wasn't just, maths, just subtracting, 3 years. Because if that was the case, it would have been 2016, would have been then 2013. But it actually respects the local calendar, the actual local date that you're working in. Hence the name local date time. And we could have gone the other direction. We could have said now equals now dot plus and passed in the period. Period also has some nice comparison methods. So let's say that I want to create and find out what the duration is between, let's comment out all this stuff that we have so far. And I'm just going to uncomment out this local date now line and the higher date. Get both of those back. So now we've got our local date now and higher date. And let's say I wanted to get a period that's between the two dates. So what I could do is I could say period dot between, and I could say the start date was the higher date, and the now is the end date. That's an exclusive date, so it's going up to now. And we'll want to assign that to a period called period. And we could even print that out. So I'll just say P period. And it'll look a little funky. Let's see what we got. So what it's telling me is that the period is 8 years and 1 month. That's the difference between how long I've been hired at Intertek. So those are the basics of local date, local time, local date time, and period. What we're going to do now is look at how we can format the dates and times and so on into something that we'd like. That'll happen in the next lecture. There's one last class that I want to talk about before we finish this section, and that's on the date time formatter. Now, although the exam objectives don't state explicitly that you have to know a lot about that class, when we go into things like local date, we'll see that there is a method here called format, and it takes a date time formatter. So it's a good idea to know about this just in case they ask any of the questions. And really, just for coding, you're going to want to know this. So I think it's important to cover. Also, I'm going to want you to check out the API documentation, the Java doc, on this class as well, just like the other ones, local date, local time, local date time, and period. And the reason is that it's got a lot of great information about different constants that it has that we can use for formatting dates and what they'll look like. And then it goes through and tells you all the date format specifiers that we can use. So we have different symbols that we can add to a pattern, and then that pattern can be used to change what that date time looks like. So they give an example here where they're using D, MMM, UUU, and that'll take our date object, which would be, in this case, 2011-12-03, and change that into 3 December 2011. So let's write some code and take a look and see how the date time formatter can be used, some of the more common use cases. Jump to our code, and we've got a date. Let's run this. Right now it's printing out 2016-05-21. Let's look at some of our options. First of all, we'll create the date time formatter, and I'll just call this DTF. And we're not going to say new datetime formatter. We're going to use the static methods. So datetime formatter dot, and I'm going to use this method called of localized date. Notice that there's an of localized date, there's an of localized time, and an of localized date time. So make sure that you're using the right one for the type of object that you're working with. If I happen to choose of localized time and try to apply this formatter to the local date, it will fail. In fact, let's do that. Let's see it fail. This is an exam type of gotcha that you want to watch out for. So here I can say it's asking me for a format style. Format style has just a few options. We've got full, long, medium, and short. I will say full. And what we would do is we would print out the date. So now, and we use a method on our local date called formatter. And so if I try to use this method or this object that I've just created, the DTF. Let's see what happens. First of all, no compile errors. Let's run it. We get a runtime exception. And it's just telling me unsupported temporal type execution, unsupported field, clock, hour of AM, PM. So it was trying to add some time information because we said it's of localized time. And we don't have time. We just have a date. Totally different objects. So keep that in mind with the exam. Make sure everything is matching, that you have the right of localized method being called. So what do we want? We want of localized date. That's the method we want. Rerun this. And now you can see the difference between the two. Now we've got a full, which is Saturday, May 21st, 2016. If we do a long, that will just get rid of the Saturday. So now we have May 21st. If we do a medium, that one is exactly the same as long. Now in some locales it might not be, but for our locale, or for my locale here, it is. And then we've got short. And if we run that, now we've got the 5/21/16. So now let's look at using patterns with datetime formatters. Once again, I'll create my datetime formatter variable. I'll call it my pattern formatter. We'll say datetime formatter using a static method. That, like everything we've seen in this section so far, there are no constructors that you're going to use. You're going to use the static methods. In fact, there are no constructors you can use. Okay, so if you see on the exam that they say new datetime formatter, that's a gotcha. That will not compile. So we've got our datetime formatter. There's some constants. We could look at some of those constants, but as I mentioned, they're all shown in that documentation. Take a look. You can see what those formatters look like. What we're going to do is of pattern. So I'm just going to do an of pattern. And then the pattern that we can do, that's what's listed in that documentation as well, what all the different letters mean. But let's just put something here. I could say I want to have a pattern of, I'm going to do the 4-digit year, and then I'm going to put a slash, and then I'm going to just swap this around just so you can see things swapped. I'm going to put the day as 2 digits, and then I'm going to put a 1-digit month, unless of course it's 11 or 12, 10, 11, or 12. It'll be a 1-digit. So that's going to be my pattern. I need to put that in as a string. Running out of space here on this line. There we go. All right, now I've got my pattern formatter. Let's print out now using that format. There's my pattern formatter. And let's run it. And so now you can see that it swapped it out. So now it's the year, then the day, and then a 1-digit month. If I wanted 2-digit months, I could put another M there and run this. And now you can see it's 05. If I wanted to have any text, maybe I want to say year. Let's say I want to say the day at year. So I'd say DD, and then I put 2 single quotes in the year of, and close that. And then I would put the year. Save that. Run it. And now you can say as 21 in the year of 2016. And I actually have too many spaces here. I could get rid of that space. Make it a little cleaner. 21 in the year of 2016. So any kind of literal text that you want just goes within single quotes. Otherwise, you use the format specifiers that are documented on that Javadoc page. In any case, anytime we want to use the formatter, we take our object, we say now, and then format. I did show you that you have to be careful with the of localized methods, choosing the right ones. It matters as well with the patterns. Let me just show you. We'll create a local time. Time equals local time dot now, and we'll format that. We'll say, let's create our date time formatter. Well, actually, you know what? I'll just pass in the pattern formatter that we made here. There's nothing about time in here. This is all date stuff. So I've got that. We'll say p now dot or time dot format. We'll use that same pattern formatter. Now, in terms of it compiling, sure, it's going to compile. We're passing in a date time formatter. It's not until runtime that it realizes that it can't apply it. And so when we run it, we get this exception. Unsupported field day of month. So it's telling us right there, we got a problem. You're trying to apply a pattern that would be applied to a local date. You're applying it to a local time, and so it fails at runtime. So that's your introduction to the java.time library. As I mentioned before, if you're going to be taking the exam, spend a little bit of time playing around with patterns, date time formatters, create local dates, local date time, local time, and period objects, and spend a little bit of time in the documentation, the Java docs for those classes.
In this section, we're going to begin our discussion about different kinds of collections, and we're going to look at one of the most basic forms of collection, which is called an array. So an array is just a way for us to take a bunch of related things, put them all together, and store them in memory. Volatile memory, that is, memory that could be erased if the program shuts down. But while we're working with our program, we're going to need to access data, and this is a great way to create a collection and keep it all together. So let's look at our first lecture on arrays.
An array is an object, and what it does is it represents a collection of other objects. And there are rules for the objects that it represents. They all have to be homogeneous. They all have to be of the same type. And they'll be organized in a collection that has integers. So they're indexed by their integers. In other words, the first object that's put in an array has an index of 0. The next one has an index of 1, and so on. The way that we work with arrays is they're pretty similar to other objects, although they're slightly different syntax. But like other objects, we're going to declare an array reference. We'll instantiate the array with the new keyword. But normally, once we create an object, we go in and we initialize all of the different instance variables. With this, we don't really have instance variables, we have elements. So we go into the array and we populate each element in the array. And I'll tell you, one of the most common bugs when you're first working with arrays is to forget that. To think that you've made an array of, say, MyDate objects, you'll forget that you also have to create the MyDate objects that go inside of the array. So let's look at the syntax. When we looked at the main method, I showed you that there was a number of different ways that you could use the square brackets. You could put the square brackets to the right of the type. You could put the square brackets to the right of the identifier. Square brackets are what we use to say this is an array, and both of these syntaxes are completely legal. And given that there's only one variable here, there's really no difference between the two. But with that said, the first one is much more common in Java. You typically put the array syntax, the square brackets, to the right of the type, and it's just easier to see. If I look at this, I can say, oh, this is an int array. If I look at the second one, I think it's an int. And then I don't discover that it's an array unless I go through the whole name. But, syntactically, they're the same. The only time there's a difference is if you're declaring more than one array in a single line of code. So if we have this first line here, we're creating two char arrays, char array 1 and char array 2. The second one is different. We're creating char variables. The first variable is a char array called char array 3. The second variable is just a char. So when you do have more than one variable declaration on a line, the placement of those square brackets does matter. It does impact the definition. So let's create an array and see how this works. You're going to use the new keyword, but we're also going to have to set a size. So this is the way it works. On the left side, we've declared our int array variable. And on the right side, we say new, we say the type, and then you don't use parentheses, you use square brackets. The number inside of here, that's going to be the size of the array. Now we've said here that there are going to be 10 elements in this array, But when they're organized, they're going to be index-based. They're starting with the number 0. So we'd have the numbers 0 through 9 in terms of what index does each int live. After we've instantiated the array, the next job is to populate the elements of the array. Now, the first thing that's going to happen is the new keyword is going to cause all of the elements to be filled with a default value. If you remember, we talked about default values for instance variables. We said that anything that is type object would be null, anything that's type int would be 0, and so on. So when we go through this, we say new int 10, we're going to get an we're going to get an array that has elements 0 through 9. And if we looked in each of those indexes 0 through 9, we'd see that every int has been set to 0. So now we're going to go through and actually change that. We're going to grab int array at index 0 and set it to 1. We're going to grab int array at index 1 and set it to 2, and so on. Now, one of the mistakes that you could make is you could try to set int array at 10. Remember that the indexes are always going to start at 0. So if we've said that we've got an int array that has 10 elements, then the indexes will go from 0 to 9. If you try to set this to 10, it'll actually compile, but at runtime, you'll get an array index out of bounds exception. Arrays also have a special syntax that allows us to instantiate and define and assign all in one step. It's these curly braces right here. So on the left side, you define your int array variable. On the right side, you use the curly braces and then just add all the values that you want. And it'll figure out how big to make the array, and it'll put each of these values in the right indexed element. So this 1 will be added to the 0 index. This 2 will be added to the first index. This 10 will be added to the 9 index. And in any case, it counts it and says there are 10 elements, so the array is going to be of length 10. There are some rules for this syntax. It's only allowed when you first declare the array initially. And specifically, it has to all be in the same statement. In this example, we've got 2 different statements. So I've got the int array that I've defined and a semicolon, which makes it the end of that statement. And then I'm taking the int array and I'm trying to assign the literal value. That's illegal. Just can't do it. So an array holds a bunch of elements, but it also holds a piece of state, and that state is its length. We can access the length by using the dot operator, so myArray.length. In this case, it would return 3 because there are 3 elements in this array. One of the gotchas here is that the length of an array is a read-only attribute. You cannot set the length. And we typically use this length element to iterate through all of the members of the array. So here's an example of doing just that. We could iterate through any kind of a loop. It's usually done with a for loop. So here I've got an int array that has 10 elements. I'm using the for loop, and I'm using that length property right here to figure out how far should I go. So we're starting at 0, and we're going all the way until we're less than, as long as we're less than the array.length. So as long as we're less than 10. And that makes sense that we're doing less than because we're starting with 0, not 1. So we're going from 0 to 9 as opposed to 1 through 10. Now the rest of this, they're just going through and multiplying the current index of j and then assigning that to the current element. So element 0 would be 0, element 1 would be 1, element 2 would be 4, and so on. So that length property is read-only. You can't change it. In fact, the entire array is fixed in length. You can't resize an array. If I create an array and I try to say array.length, I know you were 10, but now I want to set you to 11, it won't even compile. That is illegal. Now, although an array can't be resized, there is a method in the system class that will allow you to create a brand new array and copy all the elements from the old one into the new array. And of course, this is just one method that system class provides. It's called array copy. I should note that although we are seeing this method in the system class, that a lot of the helper methods for arrays is actually in a class called arrays, which we'll take a look at a little bit later. So here's an example of using array copy. I have my initial array, which has 3 elements, And for some reason now I've decided I need the array to actually have 4 elements. So I'm creating a temporary array. At this moment, they're both pointing to the same array. Then what I'm doing is I'm creating a brand new array that is going to have 4 elements. And we use the system array copy to copy all the old elements into the new array. So it starts with what is the array we're copying from, what is the index we're starting at, what is the array we're copying to, what index are we starting at, and how far should we go. So that's the system array copy method. So far, all of the arrays that we've looked at have been storing primitives, but they can also store Java object types as well. So here's an example of creating a MyDate array. So new MyDate3, that'll store 3 MyDates. Once again, the biggest mistake that people will make is thinking, I just created 3 new MyDate objects. It looks similar enough to creating a MyDate, right? It almost looks like the parentheses. We got the square brackets. But what it's really doing is creating 3 element slots in the array. And they are all holding null at this point. That's the default. It's holding null. So we have to populate it. We create a new MyDate, assign it to date 0. Create a new MyDate, assign it to dates 1, to dates 2, and so on. By the way, this act of passing in an index to the dates is known as subscripting. We could use the inline initialization syntax with objects as well. So here's the curly braces, and I would just comma separate all of my new MyDates. Here's another example. We could do it with strings as well. So here are a whole bunch of strings which are being created and added to a string array. And of course, you've already encountered one array of strings. That's the main method. It takes an array of string as its only parameter. We usually call it args, but we really haven't explained why we have it. And the reason that args is there is it'll take anything that's passed in from the command line or when we start our application, and it will pass in that text as arguments. So for example, let's say let's look down below here first. So I'm going to write Java foo, which is the name of the program, and then 2 words, hello and world. And what's going to happen is when this main method is executed, hello is going to be added to the array of strings at index 0. World is going to be added at index 1. And so we can then iterate through and grab all those different words out. So why do they have that? Well, you can imagine that maybe we have Java foo debug, and we look for the word debug. And if that word debug is there, then maybe we add some logging code, or our code is a little bit more verbose when it shows error messages, things like that. So it's a way for us to pass in a command from the command line into our application. So arrays behave a lot like other variables in that whenever we declare an array, we're going to specify what is its type. And we're not just specifying that we'll hold that type, we're specifying we'll hold that type and any subtype. If it's an interface type, we're saying we'll hold anything that implements that interface type. So polymorphism is at work with an array as well. Let's take a look. Imagine we have this hierarchy. We've got a person on top, and we've got an employee extends person, secretary and manager extend employee. If we take a look at the code, look like this, notice that the person has a name and a date of birth. Employee adds a salary and an implementation of toString. Manager has a department and has yet another implementation of toString. And secretary also extends employee, but it's not adding anything, no salary, no department. It's not overriding toString and so on. Now you may have noticed that everything listed there was using the public attribute instead of using encapsulation. That was just done to make this a very simple example. In real world code, we want to do encapsulation. Make those fields private. Now let's revisit polymorphism. So with polymorphism, I can have a reference variable of employee. And what that is saying is I can accept any employee objects and any subtypes, including manager and secretary. Of course, we've seen this before, but now we're going to apply it to an array. And what we can do is we can create secretary and manager objects, and we can store them in an employee array. So it looked like this. We create our employee array. On the left side, we're defining the employee variable, staff. And on the right side, this is where we're defining how many employees it'll store. It'll store 3 employees. So for the first element, staff 0, we're just going to create a brand new employee. And then we're going to set the name of that employee. So in order to grab the employee that's in the array, in index 0, we use subscripting. We say staff bracket 0 to grab a hold of that employee. And then we can use the name property and set that name to be James. The next one we're going to add in index 1 is we're going to add a new secretary. And once again, we can grab the secretary using the subscripting syntax, set its name, in this case, to Moneypenny. And finally, staff 2, we're adding a new manager, and we're setting the name to Miles. So as you can see, an array is polymorphic. We can substitute one object for another, provided they're all of the same type. We declared that the array was of type employee, but that meant we could pass in an employee, a secretary, and a manager. One thing to note is that when we reference one of the employees in the array using the subscripting, like we're doing here, we're referring to whatever object is in staff 0. That reference is going to be of type employee. So the thing is, we are limited to sending messages to whatever's available to an employee. Now, name was declared in employee, so that is available. What if I wanted to change it and I wanted to add something like the department? Well, I'm not going to be able to just reference staff 2 and change department because department is not available to employee. And even though staff 2 is a manager, just like when you set a new manager to employee E, as we're seeing on the top here, then the only thing that I can do is I can say, let's call methods that are available to employee, and let's look at and set variables that are available to an employee. I can't grab anything that was defined in a manager without casting, and it's the same thing with an array. So if I want to change the department, I'm going to have to reference staff 2, which is the manager, cast it to be a manager. We place the entire casting operation in a set of parentheses to ensure that it happens first. And then I can change the department to be MI6. So after we've created this array, now we can go in and print out all the employees' names. And we can do this with a traditional for loop. I could go in and just create a for loop that says int j equals 0, j is less than the staff.length, and then keep incrementing j. And then all we'd have to do is grab staff j, which would start with 0, go to 1, go to 2, and call the toString method on it so that we could print out the employees' names. Or we could do this with another kind of loop. This is one we have not seen before. This is the for each loop. Now, even though it's called a for each loop, you don't actually write the word each. You just say for. And in the parentheses, there are two parts, a left side and a right side, and they are separated with a colon. Now the right side is the collection. What is the collection that we're going to iterate through? And the left side is a variable that we'll use in the body of this for loop. So it's going to iterate through all of the different elements in staff. One by one, it's going to take the current element of staff and temporarily store it in an employee variable. And then we can just simply say employee toString. So that's a nice simplified syntax to be able to loop through an entire collection. Now, because of polymorphism, because of the ability to override methods, what's printed out by calling toString depends on what the actual object is. So, like for example, the manager class had overridden the toString, so that's going to be a little different than secretary or employee. As we run through all of the different employees, we would see James for the first, Moneypenny for the second, and then Miles manages MI6 for the third. By the way, that call to toString that we've been doing, that's actually redundant. We don't need to do it. And the reason is that if we walked through the print line method and we saw what happens when we just pass in an object, we'd see that eventually that method is going to call toString. So you can certainly say, toString if you'd like, but it's not really recommended, it's not required. So in these examples, you can see that we are iterating through the entire staff array and just passing in, the staff element itself. In this case here, we are passing in the employee. And so it's just not necessary to call toString. So far, we've been looking at single dimensional arrays, and that's predominantly what you're going to be using. Java does, however, support multi-dimensional arrays. The way that we create this is that each dimension will have its own set of square brackets. So here's an example of creating a two-dimensional array. Notice that we've got two sets of square brackets on the left side, as well as two sets on the right. What we're saying is this is a two-dimensional array. Now, the way that multi-dimensional arrays work is that every single dimension except for the last one stores an array, whereas the last dimension are going to store the actual values. So let's look at populating this array. What we're saying is that the first dimension of the string is going to store 5 different arrays. And that's going to have the number 0, the number 1, the number 2, 3, 4, all the way from 0 to 4. The second dimension is going to be an array that stores 2 values. So 0 and 1, 0 and 1 for each dimension. And then when we're going to set the values, we just have to include both dimensions so we can say specifically what element are we setting. So this is kind of like a phone book. We can store 5 different people, and when we store the phone numbers, we can store 2 parts, right? We can store 2 different pieces of information, so the name and the phone number. So array 0 can have 2 different pieces of information, 0 and 1. Array 1 can also have 2 pieces of information, 0 and 1, and so on. So 0, 0 is the name, Paul, 0, 1 is the phone number. Now we'll go to the next array. 1, 0 is Scott, and 1, 1 is Scott's phone number, and so on. We can do the literal initialization like we did before. It just looks a little different. So first of all, we have the single set of brackets to represent the first dimension. And then what we're doing is listing each array inside of it. So in this case, we have an array with 2 elements, another array with 2 elements, and another array with 2 elements. So if we were to think about what is the length of the first dimension, well, there are 3 elements in that first dimension. So if I said, what is array.length, notice I'm not putting any specific element here, then it's going to give me the length of the first dimension, which would be 3. But then in this case, I'm asking for the length of array 0. Well, that's going to be this array that's inside of the second dimension. So that one will have a length of 2. Again, notice how each element of the outer array is an array, and each element of the inner array is the data. And you can get kind of crazy with this. We can have many arrays, or I should say many dimensions in our arrays. Let me show you an example of a 4-dimension array. So it says 4 square brackets, and then what each of the different sizes is. So that means that in the first dimension, we have 2 arrays. And for each of those 2 arrays, in the second dimension, they have 2 arrays, and so on, until you finally get to the very end where we can put 3 pieces of data for each of these different combinations. If we were to think about this or examine it visually, it would look something like this. So as you can see, multi-dimensional arrays can be really complicated. Imagine that I'm looking for, I want to get the value of string 0101. So 0 here, 101. What would that be? Well, this would be 0, this blue, and then 1 would be this yellow, because this would be the yellow 0 over here, the yellow 1. And then 0 would be the first pink thing here, and then 1 would be the second element inside. So right here, that's the index of 0101. The good news is you're not going to have to spend that much time creating such arrays, but just note that it is possible. The Java API includes a class that will help us with all sorts of tasks, including sorting and searching. It's in the Java util package. It's called Arrays. It's plural, ARRAYS. And that's going to help us with all sorts of searching and sorting and filling and all sorts of stuff. After this lecture, I do recommend that you go to the API and become familiar with what it offers. In this lecture, though, we will look at some of the more popular methods, starting with arrays.sort. So sort allows you to pass in some comparison instructions. The sort will take care of the complex logic of going through and sorting everything, but you can pass in some instructions of how things should be sorted. This is done through an object called a comparator, and that's something that we'll talk about in an upcoming section, so we'll hold off on the comparator for right now. But even if you don't pass in a comparator, if you're dealing with primitives, then what's going to happen is it's going to use the natural ordering to sort it, which in this case would be the Unicode value. So the precedence would be all numbers have a higher precedence than capital letters, and capital letters have a higher precedence than lowercase letters. So here's an example of running the sort. I've got an array called letters. We've got D, A, C, and B. These are primitive chars. And we call arrays.sort. Notice it's a static method, so I don't need to instantiate arrays. And we pass in the letters array. At that point, it will be organized as A, B, C, and D. And that sets us up for the next method, which is binary search. The purpose of binary search is that we give it an array, we give it the thing that we're trying to find, and then it returns the index of where we can find it at. Now, an array must be sorted for a binary search to work, so you always run the sort first. But after that, we can run the arrays.binary search. We pass in the array. We pass in the thing that we're looking for, in this case, a char called C, and then that's going to return the index of where it's located in the array. It's a little odd, but if the search value cannot be found, then what it does is it returns an int. And this is a little complex. This is something you're going to probably want to write down, especially if you're taking the exam. But what it'll do is it'll try to figure out what is the index where it should have been. Where would I have expected to find it? And then what it does is it adds one more to that and turns it into a negative number. So let's look at an example. Our letters array had A, B, C, and D. Now imagine that I'm trying to find E. So it would probably expect to find E at an index of 4. What it'll do, since it doesn't find E, is it'll take 4 and it'll add 1 to that, so that's 5. And then it'll turn it into a negative number. So rather than getting a normal index, we would see an index of -5. There's a method to help us fill all the elements of an array with a single value that's called arrays.fill. So here's an example. We're taking letters and we're filling every open element, or rather every element, with the letter Z. This example, of course, was for our array of chars, but the methods are overloaded and it can handle any type of an array. Let's talk a little bit about some of the problems that you might run into with an array. You know, the array syntax can be a little bit confusing. It's a little different than Java objects, and as such, even experienced Java developers will occasionally run into problems. So we'll talk about some of the more common coding mistakes that you might run into. Some of the mistakes that you run into are caught at compile time, and that's actually great because that means that we can fix it before we even try running the program. Unfortunately, others are only found at runtime, and so we'll look at some of those as well. So the first common mistake is really to forget that an array is 0 index. So when we create an array, we don't want to skip the first element. This is an example of a for loop that's trying to loop through everything, but it left off the first element in the array. And it did that because it started with int j equals 1. So really that should have been int j equals 0. Here's a similar problem that's related to counting. So we're going to go a little too far past the array. Down here at the for loop, you can see now we've got the right starting point. We're starting with j is equal to 0, and we're going to less than or equal to the staff.length. That's a problem. Remember, it always has to be less than the length because we're starting with a 0 index. Make it really simple. Imagine that you've got an array that has 3 elements. So we have an index of 0, 1, and 2. If you're going to go all the way to the length of that array, that means you're going to go to 3, and there is no number 3 index in an array. That will give you a runtime exception. It won't be caught at compile time. It's a runtime exception. It's called Java lang array index out of bounds. We'll talk a lot more about exceptions in the final section of this class. Also remember that the length is a read-only attribute, and it's not a method. So this is a common mistake. Staff.length, parentheses. Remember, parentheses means it's a method. and length is not a method that's not available, so this won't even compile. It's not a surprising mistake to make because as soon as you start getting used to encapsulation, you're going to start thinking, I don't access fields directly. I don't access these instance variables directly. I call a method. And this is one of the weird use cases where, in fact, it is a public attribute. You can access it directly. Also, in other classes, there may be a method called length or a method called size, and so that can start to throw you off a little bit as well. So just remember, with an array, it is a public read-only attribute. Another issue that you might run into, but this is one the compiler will catch, is when you're trying to declare a size in the wrong place. So here we've got int, and we're specifying 100x. You don't declare the size at the reference variable. You declare it when you're creating the array. So only in initialization can the array size be set. This is legal. Where we say new int 100, we can't put the size in the reference variable. As you write more and more Java programs, you're inevitably going to run into a scenario where you need to have a method, and that method will accept a parameter, but you don't really know how many arguments should be passed in until runtime. You want to be able to accept a variable number of arguments. Well, we just learned about an array, and that's a great way to be able to pass in a variable number of arguments. Like, for example, here's a method that says, my method takes lots of ints. And so we're passing in an array of ints, and we can then loop through that array using a for loop, in this case specifically the for each loop, and then do whatever we need to with the ints. The great thing is that every time this method is invoked, there may be a number of different ints. We just work with whatever's given to us. That gives us some flexibility. The way that this would be invoked, if we look down below the code here, we would create our int array, and then we would pass the array into that method. Now that works fine, that's great, but there is an optional syntax to do the same thing, and it's called var_args. The syntax for var_args is you specify what is the argument type, and then you use an ellipsis, which is just 3 dots. So here's an example. My method takes lots of ints. Now I say int ... And what that means is that this method will take 0 or more ints, whatever that type is. The way that we work with the value once it comes in is the same way that we work with a regular array. So we're just looping through here and going through all the different ints that were passed in. And the nice thing is that when we call this now, we don't have to create the array prior to passing it into the method. Notice that my method here, I just put a comma-separated list of all of my ints. And another time that I call it, I have a different set and a different number of ints, and so on. So it's a nice shorthand so that we don't have to wrap our variable arguments in an array. So underneath the covers, Java is just treating this as an array, so we access it like it's an array. There is one limitation. When we define a method that's going to accept an array, that can only occur once in a parameter list, and it must always be placed at the end of the parameter list. So for example, let's say we got a method that has some other arguments. In this case, we've got a method where it takes in a string and a double. As you can see, the int variable arguments is at the very end. If I had that int ... in the middle or listed first, it wouldn't compile. As a side note, it's not common to see in code, but you can actually legally write the front door for our Java applications, the main method, using this syntax. You can say public static void main string ... args. So that's it. var_args are just an alternative syntax so that we can accept a variable number of arguments without having to wrap everything in an array.
We've talked about the array, and we saw that it's a great way of creating collections of related objects together, but we saw that there were some limitations as well. So we're going to look at something that's a little bit more flexible. It's called a collection, and so we'll start right away talking about array lists and so on. Let's start with lecture number 1.
When we code, we very frequently have to put together collections of things. We've seen that we have an array, and that's one way that we can put together a collection, but there is an alternative in Java. The API includes something called the collection framework. And this is a set of pre-built data structure components that are part of the Java util package. Now, arrays and collections have their strengths and weaknesses. Both have their place in Java applications, but it's a good idea to know what these differences are so you can choose the appropriate data structure. So here's some high-level differences between an array and this collection framework. Starting with the array, an array is not resizable, and I think that's probably the biggest downfall of the array, is that you can't change the size once it's been created. An array does store primitives and objects, so that's nice. There's flexibility there. It does have to be homogeneous, meaning that they're all of the same type. Now, we saw that polymorphism is still okay with an array, but it still has to be related. Everything has to be of the same type. An array does have special notation, the square bracket notation to access elements, and it does have a special syntax for initialization. I'm not sure that I would say either of those are pros or cons, it's just a notable difference. Now with the collection framework, most of the collections are dynamically sized, meaning that as you add to the collection, it will grow. And as you remove things from the collection, it will shrink. And so that's really nice that we don't have to worry as much about, creating something and knowing what the size needs to be in advance, and then having trouble dealing with any changes to that size. Now it says here that collections only store objects, and that's true. However, there is a way for us to get primitives into a collection. Essentially, we wrap the primitive with an object. We'll talk a little bit about that in this section, but in the next section, we'll talk about something called autoboxing, which really makes that transparent to us. Collections can be heterogeneous. You can put anything that you want in a collection, but that's not necessarily a good thing. If you get something in the collection that you weren't expecting and it pops out and you call the wrong method on it, you're going to get into trouble, right? So there's actually a syntax that's been created called generics, and that helps us say really only a certain type of thing should get into this collection. So while collections can be heterogeneous, there's been some movement and activity to reduce what it is, reduce that flexibility, because it isn't always beneficial. With collections, we're dealing with just regular objects. So when we want to access elements, when we want to remove elements, and so on, we just use methods on an object. There's no special syntax, no square brackets, no curly braces for initialization. It's just a regular object. There are two basic types in the collection framework. Both of these can be found in the Java util package. The first is the collections framework. We'll spend a little bit of time talking about lists and sets and queues. All of those belong to the collections. And then there are maps, and maps are like dictionaries or phone books, or if you've ever worked with an associative array, that kind of an idea. So they're two separate APIs. They're both a part of the Java util package, and we'll examine both in this section. One of the best places to start when talking about the collection API is the array list. An array list is a lot like an array, but it's dynamically resizable. Working with the array list is almost as easy as working with an array. So let's take a look at the code. Here's an example. So first of all, notice that we're importing java util.star. So this array list is in the Java util package. And we instantiate it just like we would any other object. So new array list. And once we have it, then we can just start adding values like hello and world. Here we're printing it out using the system out print line, and we're just passing the array list in. Here's another example. Same type of thing. We're creating the array list. We're using the add method to add additional strings. So we've got Bruce Banner, Barry Allen, Bruce Wayne, Clark Kent, and then we're printing it out again. So notice that we're using printline to show the contents, and that's what you're seeing right here, a comma-separated list of all the different names. And the reason that we're getting this comma-separated list with the brackets surrounding the entire list is because the collection API overrides the toString method. So we can pass in any collection, toString will be called, and we'll be able to see the contents of that collection. Although it's a little bit more common to iterate through the collection, just know that this is a nice handy way to quickly see what do you have. The other thing you might have noticed is that in the array list, we did not pass in a size. We can, by the way. You can pass in a size to say how big you think it will be, but you don't have to. And so what happens is the array list will grow as we add stuff to it, and it will shrink as we remove things. Each array list is going to keep track of the number of elements that it has. So if we want to find out how many elements are inside, we call a method, and that method is called size. It is not length, and it's not a property called length. So that's one of the confusing parts when you're learning arrays and array lists, keeping all of that straight. But with the array list, we use the method. And again, the method is called size. And the size is going to be affected by adding and removing elements. Every time you add an element, the size will increase. Every time you remove it, it will decrease. There is a slight optimization that you can do, which is to set the initial size of the array list right in the constructor. Here's an example. We're setting this array list with an initial capacity of 4. Now, that doesn't mean it's going to be stuck with 4 things. It's just saying, when you first create yourself, plan on having 4 elements. But if it needs to grow, if it needs to shrink, it still can do that. Removing an element is pretty straightforward. There's a method here called remove, and you pass in the object that you want to remove from that collection. So after removing Barry Allen, if we print out the list, now we just have Bruce Banner, Bruce Wayne, and Clark Kent. If you're curious of whether an array list has some content, you can use the contains method. So here's a check to see if the list contains Gotham City. If it does, it'll return true. If it doesn't, it will return false. I should point out that the reason that this contains method works is because what it's going to do is it's going to call the equals method on the object that you pass in. And it's going to see if the object that's been passed in is equal to anything in the list. If it is, then it will say true. And it's the same thing for the remove method we just saw. If I go back a slide here, list.remove, what it's going to do is it's going to call the equals method to see if what we've passed in is equivalent to anything in the collection. And if it is, then it removes it. And that's why it's a really good idea to make sure that any kind of object that you think will be put in a collection overrides the equals method. And of course, what is the correlated rule? Anytime that you override equals, you also have to override hash code. Now, why do we need hash code for collections? Well, later we're going to see some hash collections like hash set and hash map, and they use that code to help find things in their collections. There's another method called clear, which will empty everything out of the array list. You can check to see if the array list is empty by calling isEmpty. And what you're going to find is that all of the methods I've talked about so far are available to all of the collection framework objects, and that's because they all implement the same interface, the collection interface. And what's nice is that it makes it really easy to learn the collections, because once you've learned one, like array list, now you know how to use some of the other things like a set. And furthermore, that makes your code flexible, because since the collections all work the same way, they can be easily replaced for one another. And where have we seen that concept before? Polymorphism. And collections take great advantage of this flexibility. So let's take a look at that polymorphism. Let's look at the collection interface and the collection hierarchy. Now, I'm going to show you a diagram that's incomplete, but it's just showing you some of the more popular members of the collection class. So we'll start here at the top. We've got the collection interface. And most of the methods that we're working with have been defined in here. There are 3 sub-interfaces that extend the collection interface and add some additional methods that are helpful for specific data structures. There's one for list, one for set, and one for queue. Now, these classes right here, these are abstract classes. We've learned about abstract classes. And the purpose of the abstract class is to provide default implementation of some of the stuff that is coming from the interfaces. In other words, let's say that I wanted to make a list. Well, if I had to implement all the methods that are available in list and all the methods that are available in collection, that might be a lot of methods that, maybe some reasonable defaults could have been made for me. And that's really what these abstract classes do. So abstract list provides default implementations for many of the methods, and then what we can do with our own collection types is decide which ones do we want to override. So the classes that we generally interact with are the ones in green. So our array list, linked list, hash set, tree set, array blocking queue, and of course there's others as well. And so the nice thing though is that when I'm using an array list, I'm treating it like a collection. I tend to use only the methods that are in the collection. And what that means is that I could swap out fairly easily a linked list for an array list or even a hash set for an array list, and it would have more or less the same functionality. Now, we're going to talk about the differences between lists, sets, and queues in a little bit, but that's the general idea, and this is what gives us all the polymorphism, the fact that all of these 5 classes at the bottom, array list, linked list, hash set, and so on, that they all ultimately implement the collection interface. And it's in the collection interface that we have methods like add, remove, contains, size, is empty, and clear. There's also a way to turn a collection object into an array with a call to the toArray method. And by the way, the arrays class has a way of turning an array into a list. They have a method called asList. So the toArray method, that ends up becoming important because there'll be times where you'll be calling into an API, and that API is expecting an array, but you've been working with a collection. Well, just note that there is a way to fairly easily turn your collection into an array. At some point when you have a collection, you're going to want to iterate through it. And there's an object that's provided to us from the collection API called an iterator to do just that. It traverses in a way that's similar to using a for loop, but it's an object and it has methods. The iterator is defined in the Java util package, and the way that we get it is we call the iterator method on our collection. So here's an example. Let's say I've got some kind of a list. What I can do is I can say list.iterator, and then that will return to me the iterator object. And then we just put it in some kind of a loop. Now what we do is we ask the iterator if there's any more objects. And the way we do that is to say iter, in this case, iter, has next. And it will return a Boolean if there is another element. So if that's true, we'll then iterate through. And to get the next object, you say iter.next. So the iterator interface really only has 3 methods. We've got hasNext, which returns a Boolean. There's next, which returns an object. And then there's remove, which will remove the current object. Now, if you want to move back and forth rather than just forward, then you're going to want a different kind of an object called a list iterator. So let's just take a quick look at the iterator and the list iterator and see how that they work. First of all, when you do the lab, you're going to see exactly what I'm showing you here, in that you're going to see a bunch of yellow, a bunch of warnings, yellow underlines, and so on. And the reason that we're seeing that is it's saying we don't know what type this array list is. In fact, I'll just show you what the error or the warning is. It just says array list is a raw type. References to generic type array list should be parameterized. And we will talk all about that in the next section. So for right now, just know that yes, this is expected because we haven't learned a certain type of a syntax. And when we learn it, that will go away. So for the first lab, it's okay to see all of these warnings. After this section, they will go away. So with that said, how would I get an iterator from this? Well, you just have iterator I equals, and right from the array list itself, I can say languages iterator. And then we have our loop, and I can say while I has next, and then we can print out whatever the current value is, I.next. And it will go through and print out each of these languages. Let's run it, just make sure it does what it says it'll do. Sure enough, there it is, Java, Swift, JavaScript. Notice that array lists, it maintained the order that I put it in. That is a characteristic of a list, but we'll talk more about that in an upcoming lecture. So that's really all we can do with the iterator. We can do has next, we can get next, I could remove something if I wanted to. But as I mentioned, if you want to go in both directions, if you want to do has next and then maybe a has previous, you're going to need a different kind of an iterator, and that's called a list iterator. So what we do is we would say list iterator equals languages list iterator. Now, one thing I want to point out is that a list iterator is only available for lists. So if we were dealing with some other kind of a collection, like a set, for example, this would not work. Once we have a list iterator, then we can do a whole bunch of stuff. So rather than just has next, we have has next, has previous. Or if we want to get the next object, we can set next, or we can just say previous. So we have a few more options when we have a list iterator. What we're going to do now is go through the different types of collections. We're not going to go through every collection, but we'll go through the major types and the most popular ones of each type. And we're going to start right now with the list. So we've got our collection interface, and it defines a bunch of methods for all of the different collection types. There is a sub interface, an interface that extends collection, and that adds a few more methods for specifically lists. So lists have the following characteristics. They maintain the order of the elements they contain. They allow duplicate entries for any given object. And they can be manually sorted into any order that we'd like. So they are ordered. And there are a lot of options you have for lists, but the two most common would be array list, which we've already started to look at, and linked list. So since the lists are ordered, that means they also have an index, and you can use that index for some of the methods that are part of the list interface. The list interface gives us methods to get, set, and remove elements by an index. So let's look at a couple of those methods. Here's using set, list.set. Now, out of all the methods that are part of the collection and set, list interface, I think set was the one they misnamed. I think it would have been better called replace, because that's what you're doing. The way that set works is you give it the index, and then you say specifically what you want the value to be. The problem is that you can only set things where something already exists. In other words, you can only replace things. For example, if there wasn't anything in the second indexed element, then this list.set2 would fail. We can remove by index as well. So in this case, we're doing list.remove1. And remember that the index does start with 0. So we're removing the second element here. And that's how lists work in general. What's the difference between an array list and a linked list? Well, an array list is really fast at random access. So if I pass in an index, if I say list.get27, it can find that element very, very quickly. But if I start adding and removing elements in the middle, then array lists are a little slower. And it's because they actually have to physically move the elements to make space. So for example, if I'm adding an element here and I'm going to add it at index 4, then we have to move all of the additional elements from 5 on down 1. And that takes, some processing. And of course, the same thing when we remove, we would have to shrink everything. So they're slower at removing and adding things from the middle of the list. Whereas linked lists are pretty much the opposite. They are a lot slower at getting by an index, and they're much faster at adding and removing elements. And the reason is because the way the linked list works is that it's not a set order of things in a specified space. It's an object that refers to an object that refers to another object, and so on. So if I need to add something in the middle, then look at what happens. First, what we have here on the left is our current linked list structure. And now that we're going to add something, all that we had to do is take what this second element was referring to and have it refer to the next or the new element that we've just added. And then we have this new element refer to the one that the second one had been previously pointing to. So you can see that that's a lot easier than trying to move everything down one. So that's what you do. You decide, how am I using this data structure? If you need a collection that maintains order, that allows duplicate objects, basically behaves like an array but allows it to grow and shrink, then you choose a list. And then if you find that you're doing a lot of adding and removing the middle, we'll go with a linked list. Otherwise, you're probably going to want the array list. The next type of collection we're going to look at is the set. And a set is another subtype of the collection interface. Now, the characteristics of a set is that no duplicate objects are allowed. And so it's going to use the equals method to determine whether or not an object is duplicate. Once again, another reason why you want to override equals. Generally speaking, the orders of the elements in a set are not maintained, although there is something called a tree set, which will allow you to determine what the order should be as it comes out. But again, generally speaking, the elements of the set are returned in no particular order when you're using an iterator. And sets don't have or use an index. The most common set implementations would be the hash set and the tree set. Now here's an example of the hash set. Creating our new hash set like we would any other object. We're adding strings to the hash set: Minnesota, Wisconsin, Iowa, and Minnesota. Now, since the hash set doesn't allow duplicate objects, Minnesota is already in there, so this second Minnesota will not be added to the set. It will just be silently ignored. And then here's an example of just seeing if the sales region contains a state that we are getting from the customer. So we're using the contains method, passing in the state. It's going to use the equals method to see if that state is in there, and it'll return true or false. Now the interesting thing here is notice that all the methods we've used are pretty much from the collection interface. And not just pretty much from, they are. They're from the collection interface. So that means if I really wanted to, I could change this first line to an array list or a linked list, and the rest of this stuff would still work. Now, the big difference would be that if we did a list, then Minnesota would be there, would appear in the list for the second time. With a set, it will not. A tree set is another set that we can use. It's known as an ordered set because when we use an iterator and we start to loop through the collection, they will be retrieved in an ordered fashion. So here we're putting in 88, 53, 66, 12. But when we iterate through them, it's going to come out in an ascending order, so 12, 53, 66, 88, and so on. And the reason that this happens is that a tree set is going to rely on a method called compare to figure out how it should order these things. There's a natural order for primitives and strings, and the natural order is basically like Unicode. It's numbers first, it's the capital letters next, and then lowercase letters. When we're using a tree set, we can pass in a comparator that will allow us to figure out, or rather determine, how things should be ordered. So both of these topics of comparator and compare to, that's something we're going to cover in the next section. So internally, the tree set is going to use a tree structure to organize the set, but we don't really have control over that tree. We really only have control of saying how we want the objects to be handed off to us as we iterate through them. And even though tree sets are ordered, there's still no index, so we can't fetch things or remove items from the tree based on a specific index. The next type of collection we're going to look at is a queue. So a queue is an interface that defines a data structure that has the concept of a head and a tail, which is similar to lines that we stand in. Often we'll even say that we're on queue, we're standing in queue. And what we mean is that we're in a line where people are being added to the tail, and as the next person's able to be handled, they're being removed from the head. So we have a separate queue interface to add, remove, and examine elements in the queue. And we have these different methods because this is such a unique data structure. So within each of the different queue operations, there's two types. There's one that can throw an exception. For example, queues can have a capacity. There's only so many people or so many things that we can put in the queue. And once we get past that capacity, one or two things could happen. It could throw an exception. Now, we haven't talked about exceptions yet. That's going to come up in an upcoming section. But for now, just know that it means that something went wrong. The Java platform lets us know that something went wrong, and we can write special code then to handle that. So there is the method add, for example, to add to a queue. And if we go beyond the capacity, it's going to throw an exception. We have a non-exception throwing method called offer. And what's going to happen is that if we go beyond the queue, we could look at the return type that comes back, and if it's false, then that means whatever we tried to add to the queue wasn't successfully added. No exception is thrown, but we can check the return value. Other than that, we've got removing from the queue. You can call remove. You can examine the head of the queue. You can call element. And again, these are exception throwing methods. The non-exceptions are offer, poll, and peek. Of all the queue implementations we have, the most popular would be array blocking queue and priority queue. So let's look at the array blocking queue. This is one that implements a first in, first out queue. So the head of the queue is the element that's been there the longest time. The tail of the queue is the element that's been in the queue the shortest time. So as new elements are added, they're added to the tail, and as elements are pulled out or examined, that happens from the head. Now, we've been talking about collections having a dynamic size. Array blocking queues hold a fixed number of elements. So when we create the queue, we're going to create a capacity. Once that capacity has been created, it cannot change. So here's an example of using an array blocking queue. We're starting with a capacity of 5. So new array blocking queue 5. And then we're adding the first, second, third, fourth, fifth. Notice we're using the method offer. These will not throw an exception. And then we're trying to add another one, Hal Jordan. That will just simply not be added to the queue. And if we were to look at the return value, we'd see that we get a false. So now we try to print out the queue and we see all the names except for Hal Jordan. And then when we call queue.poll, what that's going to do is remove the first one on the head. So we call queue.poll and we print it out, and that will be Bruce Banner. That's going to be the very first element. And then we are calling queue.peak. And what peak does is it says, give me a handle to the reference of what's ever at the head, but don't remove it from the collection. And by the way, for the removing, we could have, instead of just calling poll, we could have called remove. And for the peak, we could have also called element. Now that's an array blocking queue. We also have a priority queue. And that's kind of like, if you're at an airport, I see this all the time, that there's a couple of lines, right? There's the line that the first class people get to walk through, the frequent flyers, and then there's the rest of us that have to watch them bypass us. That's the way that a priority queue works. We can assign different priorities to the things that we're adding to the queue, and so it'll sort of order itself based on these priorities. So anything with a higher order is moved to the head of the queue. Now, how does it determine that? Well, it's going to determine that by the natural ordering. And once again, that is a concept that we're going to talk about when we look at comparator and comparable in the next section. The nice thing about a priority queue is that it's unbounded in regard to capacity. So we don't have to specify how many elements will be added to this collection. We can just keep adding as we need to. As elements are added to the priority queue, it'll just keep growing. So here's an example of adding 5 strings to the priority queue. So we're creating the priority queue up above here. We're then adding them through the offer method, Clark Kent, Bruce Banner, Hal Jordan, and so on. And look what happens as we start to remove these objects and see what we have. They're coming out in alphabetical order by first name. So Barry Allen, Bruce Banner, Bruce Wayne, Clark Kent, and so on. So what happened is that it used that natural order and decided based on strings that it would order everything by number first, then capital letters, and then lowercase letters. And of course, we can customize that by using these comparator objects, which is something we'll talk about in the next section. There's another type of queue that's called a deck. And a deck allows elements to be inserted and removed at both the tail and the head. So deck is short for double-ended queue. And as you're hearing me pronounce it, it's normally pronounced deck. Typically, there's no capacity on the number of elements allowed in a deck, so it can grow and shrink as it needs to. So there's an additional interface for a deck for adding and removing and examining elements. And of course, this is necessary because now we can do both types of activities on both ends. And just like the queues, there's 2 implementations. We've got one that can throw an exception if the operation fails, and the other will just return a special value, either null or false if there's any problems. So let's go through the different operations. We can add to the head of the deck, and that's going to be either add first, which if something goes wrong, it'll throw an exception, or offer first, which doesn't throw an exception but can return false. So that's adding to the head of a deck. We can remove from the head of a deck with remove first or pull first. We can just examine the head, tell us what's there, but don't actually remove it from the collection. There's get first and peek first. And then we've got the other end, so we can now add to the tail, so add last and offer last. Remove from the tail, so remove last and pull last. And finally, examine the tail of a deck with get last and peek last. One of the more common implementations of the deck interface is called an array deck. And there's no size limit to the array deck. It can grow, it can shrink as it needs to. There is a limitation. You can't put a null element into an array deck. And also, array deck objects are not thread safe. That may sound like a bad thing. We talked a little bit about this before when we talked about string builder and string buffer. But in general, if something doesn't need to worry about being thread safe, then generally you want an object that is not thread safe because it's going to perform a lot better. So here's an example of an array deck. And let's kind of look and see what's happening here for the output and how it's built. So we created the array deck. We're not specifying a capacity. And the first thing that we're doing is we're adding center. And so we're doing offer first, which means put it at the head. Then we're saying offer first Bruce Banner. We could have also called add first, but we're just using the offer first variation. And now let's look down at the output that we're eventually going to get to. You can see we've got center, and then Bruce Banner was added to the head there. You know, normally with a Q, we would have added to the tail. This is kind of cool. We can add to the head. And now they're saying offer last Barry Allen, so that would be right behind center. That's right down here. And then offer first Bruce Wayne. Offer last Clark Kent, and so on. So you can see what they're doing. They're just adding to the tail, adding to the head, adding to the tail, and so on. Then what they're doing is they're printing out that whole deck. They're calling pull last, which in this case is Hal Jordan. It's the very last thing. Then they're calling pull first, which would be Peter Parker. And then when they print the deck out again, you see that they removed the things that they had pulled. The final collection that we're going to look at is a map, and it's part of the collections framework. It's in the Java util package, but it is not associated with the collection interface. It's not a part of that hierarchy. And that's because map has some unique requirements. It has a unique data structure. So we have a totally different interface to use with that. Here's the hierarchy for maps. Again, not the complete hierarchy, but some of the more important pieces. We've got the map interface at the top, and there's an abstract map class right below that. The two most popular implementations are hash map and tree map. The hash table that's here, that's considered legacy. It's really not used that much anymore. So a map is a collection of data that's associated as key value pairs. Specifically, maps have the following characteristics. For the keys, they are object keys rather than a numeric index. And that key is important. So we use that key to add objects to the map, to remove objects, and also to do sorting. There is a rule that you cannot have any duplicate keys. And if you think about that logically, it makes complete sense. If I had duplicate keys and I'm trying to retrieve a specific object, how does it know which object to grab? So no duplicate keys allowed. As far as what makes up a key, it can really be any object, but typically it's going to be a string or an integer. And you'll notice that that's an integer with a capital I. That's a wrapper class. We're going to talk more about wrapper classes in the next section, but an integer with a capital I, that's a class, and it wraps an int. It turns an int into an object. Even though we can't have duplicate keys, we definitely can have duplicate values, just as long as the values are associated with a different key. So let's look at hash map. That's probably the most popular implementation of the map interface. We create the hash map just like we would any other object using the new keyword. And then what we're doing is we're creating 3 MyDate objects. So there's a birthday, an anniversary, and a tax day. And now we're going to put those objects into our hash map. We do that with a method called put. Notice it's put and not add. When we use the method put, we have 2 parameters. The first one is going to be the key. In this case, we're using a string for the key called birthday. And then the second parameter is going to be the value, which in this case is the MyDate birthday object. That's what we mean when we talk about key value pairs. Do the same thing for anniversary and the same thing for tax day. And then when we want to retrieve one of these values, we say map.get and we pass in the key. Now, in the next section, we'll talk about generics and we'll see a way that we can get out a MyDate object without having to cast. But for right now, note that you are going to have to cast. So we are casting this object to be a MyDate. Otherwise, when it comes out, it'll just be a regular type Java Lang object. And the reason for that is polymorphism. When we look at the HashMap put method, it'll take an object and an object. Those are the two types it takes. It takes Java Lang object and Java Lang object. So what does that mean polymorphically? What could we pass in when a method says it accepts Java Lang object? And the answer is all objects, right? Because when you look at the top of that object inheritance chain, at the very top will always be Java Lang object. So that's a nice way to make the collection very general so that it can accept any object. The problem is then when we pull out the object, the reference is now of type object, so we have to cast it. So that's what we're doing here. We're calling get, we're accepting the birthday, and then casting that to be a MyDate. We can also remove based on a key. So here's the string tax day. We could remove on that, and so on. So as you can see, the time when you really want to use a hash map is when you're doing a lot of random access. When we've got a lot of objects together, we typically don't care how they're organized, just that we want to be able to look something up by an ID. That's random access, and that's when hash maps really shine. Here's kind of an example of what it looks like to be a hash map. It's similar to a phone book where the key could be the name and the phone number could be the value. Now, this isn't a perfect example because we know that in a phone book, a lot of people can have the same name. But imagine that wasn't the case, that every name would be unique. That's pretty much how a hash map works. So the put method is used to take a specific key and a specific object and then link them as a pair. So that gets known as a key value pair. And when we want to retrieve that object, as we've seen, you use the get method and you pass in the key as an argument. We have the remove method, so we can remove an object by the key. And then we also have a method called clear where we can just remove all of the key value pairs from that map. If you want to check to see if a key or a value is in the map, you can do that with the contains key and contains value methods. And both of these methods will return a Boolean telling you whether the key or the value is in the map. Here's an example of that. So map contains key birthday. I pass in the key, and it'll tell me if that key is in the map. Or map contains value. I can pass in a specific value object, and then it will double check to see if it's in there using the equals method. By the way, underneath the covers, the way that it's organizing things into containers is it's using the object's hash code. So this is one of the reasons why you want to sort of synchronize your equals method with your hash code method. There's some other methods like key set and values. Key set is going to return a set. We just talked about sets. That'll have all of the key objects. And then there's values, which will return a collection of all the values. So here's an example of that. We've got our map, and we say key set, and that returns us a set of all the keys. If I say map.values, that'll give me a collection of all the values. Now, can you make a guess as to why one returns a set and one returns just a general collection? If you want, put it on pause and think about it for a second. The reason is that keys have to be unique. We can only have one key, and we can't repeat that key ever again in that particular map. So a set is a collection where everything is unique. It doesn't allow duplicate objects. So it makes sense to get back a set. But the values, there could be duplicates. So we can't get back a set. In that case, it's just returning to us a general collection. So that's the hash map. There's also a tree map, and the two are comparable to hash set and tree set. So tree map is a way for us to declare some sort of an order to how the items come back out when we start to iterate through the map.
We're going to add a little bit to our concept and understanding of collections. We're going to talk about generics, and we're also going to talk about how to sort and search through our collections.
So I think you'll probably agree that collections are much, much easier to use than an array if you don't really know what size you're going to be working with, or if that size is going to grow or shrink over time. And that's what's great about collections. They can grow as we need them to, and they can shrink as we need them to. But there are some limitations to collections. The first limitation is that you can't store primitive data types, and that's sort of a true statement. A collection can't store a primitive. It can't. We couldn't just directly put a primitive into a collection. But Java has been fixed to help us get around that limitation. Basically, collections can only store object references. So when we see code like this, creating an array list, creating an int j equals 7, and then adding the j, you'll be surprised, or maybe not, to find that that actually works. But that's a primitive, and I just said that you can't add primitives to a collection. Well, what happens is that we use what's called a wrapper class. It's an object whose primary purpose is to wrap a primitive so that it can be treated like an object. In Java SE 5 and greater, this process happens automatically. It's referred to as autoboxing, and I'll show you some examples of that in a little bit. But here are the wrapper classes. And by the way, if you're going to take the exam, you want to study the API on each of these wrapper types so that you're very familiar with what it does and all the methods that are available. But basically, every primitive type is going to have a corresponding wrapper type. So byte with a lowercase b is the primitive, and then byte with a capital B is the wrapper type. And most of the object wrapper types are the same name as the primitive, except for like int versus integer, so it's the full name, char versus character. Everything else, though, is exactly the same name, but it has a capital letter. And this kind of shows you how conventions in the way that we code can really help readability and understandability. I know when I see a type with a capital letter that it's not a primitive, that it is a class. So conventions can help our understandability of code. So wrappers have a couple of uses. We can use them to add primitives to collections. We can attach functionality to primitive data types. Remember, one of the rules about primitives is that, or not rules, but facts, I guess, is that a primitive has no behavior. There are absolutely no methods that we can call on a primitive. But when we use these wrappers, now we can add behavior. We can have functionality to these data types. So to create a wrapper instance, we just pass the primitive either into the constructor for the wrapper, or better yet, use this method called valueOf. ValueOf just happens to perform a little bit better than using the constructor. But you can use the constructor if you want. You could say new integer and pass in an int. But I'm just going to encourage you to use the valueOf method instead. So here we're creating an array list. We're setting j to be 7. And then what we could do is say integer, call this static method valueOf, passing in the int. That will create a wrapper of the object, and then we can add it to the collection. If we want to get the primitive back out of the wrapper object, then we just call the value method. So each of the different wrapper classes have different named value methods. It's whatever the type is, and it's concatenated with the value. So in other words, we have an int that we've wrapped, so wrapInt.int value. If I want to get the character value out of it, I have char value, and so on. And so that will pull the wrapped value out of the wrapper. So that's the first limitation of collections. And honestly, it's not really that much of a limitation, at least from a usage standpoint. You know, I showed you a code example that made it look like we were storing primitives into the collection. And that's really how it works on a day-to-day basis. That's called autoboxing. We'll see it in action in just a little bit. But the second limitation is that we can only add object references. And in a way, that's a feature, because with polymorphism, that means that we can add any object to a collection. In fact, we could have a collection with lots of different kinds of objects if we needed that. So in a way, that's a feature. However, what happens then is that the collection gets generalized. And so as we try to retrieve objects from the collection, they come out as general objects, which means we have to cast. Let's look at another example where we can see that again. So here I'm creating my array list, and I am creating an employee, setting the name of that employee and adding it to my array list, doing the same with the secretary, and so on. And now when I try to get the element number 1, I have to cast it. I have to cast it back to being an employee. Otherwise, it'll just be an object. So to help deal with these limitations, 2 things were added back in Java 5 called generics and autoboxing. So let's look at some examples of how these issues were dealt with. So here's an example of trying to store ints into an array list. What we would have had to do is wrap each individual array list into an integer wrapper class explicitly. We would have had to say new integer, or in this case say integer.valueof. Now in this case, everything that we're putting in the array list is of the same type. It's homogeneous. But in order to get the int out of the list, first we're going to have to cast the object into an integer and then extract it from the wrapper object, and it would look something like this. This is just to get a single value out of the collection. So first we'd say primes, let's get the value at index number 1. So we're really trying to get this one right here, the number 2. That's a little confusing because we're using integers, but when you say primes.get, when we say ArrayList.get, what we're specifying here is not the number we're trying to match, it's the index. So get not the first one, because that would be index 0, get the second one, which is index number 1. And what do we have at index number 1? That would be the number 2. Hopefully you followed that. So we get that value and we cast it to the integer type. Then once we have the integer type, to pull the int out, we would say int value, and that would give us our int x. And if you're looking at that and thinking that's pretty crazy, well then you know how all of us felt back in when Java 1.4 was available and earlier. So they gave us a way to specify what's going to be inside of the collection, and it's called a generic. Generics are not limited to collections, but it's one of the most common places you'll see them. And so what a generic says is that I'm hold anything. I'm generic, but you can specify a parameter type, and you do that in between the brackets that you're seeing here. So what we're saying is we're going to have a reference variable that's type list, but specifically the parameter type is integer. And then we're creating our new array list, and right next to the type, once again, we're specifying that this array list that we're creating is going to hold integers. So now we add all of those integers to the collection, and when we get it out, notice that I didn't have to cast it. I can just say primes.get1 and then call int value, because it knows that it's going to be an integer, so it returns an integer type. Now I still had to call int value to get the wrapped int, but we're a little closer to reducing the code we write. So if you go to the Java docs, you'll see this syntax in a lot of different collections and even different classes. What you'll do is you'll see, for example, bracket E bracket. And then when you look to see what that type parameter is, it'll say E is the type of elements in this collection. And then as you dive down deeper into the methods, you'll start to see that whatever you specify as E can then be used in methods. So here's an add method, and it takes whatever element we specified we would use. Again, going back here, that's what we did. We said we've got an array list, and what we're going to put in there is integer. So the add method is expecting something that is of type integer. Again, that's known as a parameter type. So that solves the first problem of having to constantly cast our object references. The second was that, the wrapper. First of all, the wrapper doesn't go away, but what autoboxing does is it automatically wraps or unwraps the primitive. So let's look at some code. Here's how it works. In many cases, when I have an int, if I am going to be storing it in a wrapper type, then autoboxing will automatically wrap it for us. So prior to Java 5, this would not have been legal. We would have had to say new integer, or we would have had to say integer.valueof, but now we can just say, here's the int, and automatically wrap it into this wrapper type. So this does compile. It prints out 5 at runtime. And the underlying bytecode that is generated is exactly the same. It's as if we had wrapped it ourselves. So autoboxing is really just what we would call syntactical sugarcoating. And we can go the other direction too with unboxing. So now we've got our integer, our wrapper object here, and we're going to store it in an int. Well, then it will call the int value method for us automatically. So when we print out z, that'll print out the int 5. And ultimately, autoboxing and generics working together just really helps us keep our code cleaner. So first of all, notice with the generics that we are still using the wrapper type. Again, autoboxing doesn't mean that the wrappers go away and that we can actually add primitives. It's just that it'll do the wrapping and unwrapping for us. So in this case here, we've got primes.add 1, 2, 3, 5, and 7, and it really is underneath the covers. It's generating the code that is wrapping it in a wrapper type. So it's doing the boxing, the auto boxing. And then when we want to get a value out, now all I have to do is say primes.get1. I don't have to cast it to anything. I don't have to unbox it, unwrap it. It just arrives as it should. So generics allow us to be more type safe when we're coding. We can say specifically what it is we're trying to put into the collection and therefore give us what we're expecting when we pull out those objects. However, adding the types to both the reference and the instances can be a little tiresome. Like for example, look at this code. Here we've got our array list, and on the left side we're saying that the type is string, and we're also saying it on the right side. And I'll tell you, developers just hate typing. We just don't want to do this. We just don't want to say that it's type string on both the reference variable and when we're instantiating the object. We feel that it's redundant. So in Java 7, a new operator was introduced. It's called the diamond operator, and it's really there to just reduce typing. It's called the diamond operator because it looks like a diamond. It's the less than and the greater than symbol put together. So when we use the diamond operator, only the reference has to be specified with generics. And when we instantiate the object, it's going to use that diamond operator to suggest that it's going to be the same type as whatever the reference variable is. So our array list would look like this. Now we've got the array list, which is of type string, and over on the right side where we're actually instantiating the object, we use the diamond operator, and it's just repeating whatever's here. The diamond operator gets to be a little bit more interesting when we have data structures within data structures. Let me show you code to explain this. So here I've got a list, and the list, each element in the list is going to be a map. And a map is built of an integer key and a string object. So that's a little more typing involved. If we didn't have the diamond operator, we'd have to repeat that on the right side. But now with the diamond operator, we only have to list the list, map, integer, and so on the left side. And on the right side, we just simply use the diamond operator. When we were working with the arrays type, we saw that there was an arrays class, and it just had a whole bunch of nice methods for sorting, searching, and filling, and so on. Collections has the same thing. It's a method, or excuse me, it's a class called collections, and it does all the same kind of things: search, fill, shuffle, and so on. If you're taking the exam, just like the arrays class, this is something you're going to want to study. Go to the API and look at all the different methods that are there. But let's look at some of the more popular ones now. There's a sorts method that we can use to sort any kind of a list. So in this case here, we've got our array list. We're adding a bunch of names, and then we're calling collections.sort. We also have the binary search method, which will then try to find an element and tell us what index it's at. Binary searches, as we mentioned before, are pretty efficient, but they rely on the collection being sorted. So in this case here, we could do a collections binary search on our list, in this case looking for Wally West. We can also change the ordering of a list, so collections.reverse, collections.shuffle, and that will change the list based on what we've called. So there's a bunch of different methods that are available in both the arrays and the collections class. Even if you're not taking the exam, it's a good idea to load up those APIs in the Java doc and take a look and see what they can do for you. In the previous lecture, we saw that we could sort a list with that collections class. And in a previous section, we saw we could do the same kind of thing with an array. We had an example of a char array doing the same thing. In both cases, collections and arrays, we've seen that these can be automatically sorted without any help from us saying how it should be sorted. And the way that it does that is that with strings and primitives, they all have something called a natural ordering. And the natural ordering is going to be following Unicode. So the highest precedence in ordering would be numbers, then capital letters, and then lowercase letters. But if we're going to sort custom classes, then we're going to have to implement the comparable interface to help the sorting methods understand what they should do. And this is the same case for both the collections class and the arrays class, which provides the sorting method. So here's an example. We've been working with a MyDate object. It's got an int day, an int month, and an int year. And let's say that we're going to create an array of these MyDates. So we make an array of MyDates, and then we say, let's sort them, arrays.sort. And obviously, if we had done a collection like a list, then we would have had collections.sort. Either way, we would have seen the same error, which is what we're seeing below, right down here. And it's saying we've got a class cast exception. MyDate cannot be cast to Java line comparable. And by the way, this is a runtime exception. We wouldn't see this when we compile. It's when we would run. But what does the exception mean? Well, what it's trying to do is it's trying to cast it to this comparable interface, because if our class implements a comparable interface, then it knows that it can call a method called compareTo. So if we want our custom objects to be sorted, then we have to implement this interface. And this is what it looks like. We would say that we implements comparable, and then we have one method to implement, and that's compareTo. Now, compareTo takes a generic object. So what we're going to first have to do is cast the object that we're being compared to a MyDate. And then we're just kind of going through and we're just trying to see, look, if the year is not the same, then let's subtract my year from the year that was just passed in. And what's going to happen is that means it's either going to return a positive number, a 0, or a negative number. If I return a positive number, then that means this date, the MyDate object that I am right now, should come after the year that you just passed in. If I return a negative number, then that means I come before the year that you just passed in. And if I return a 0, then that means we are the same year, or we're the same, we are equal. And so we're just kind of going through and checking the year, the month, and the day, and we're just trying to see whether or not we should come before or after, or if we're the same. And that may feel like we're doing a lot of the work, but in fact, it's really the sorting algorithm that's the most difficult part to implement. So we're just simply saying, you're comparing me to someone else. I'll tell you if I come before, if I'm the same, or if I'm after. And once again, I return any kind of a positive number if I should be sorted after the object you're comparing me to, or a negative number if I should be sorted before the object you're comparing me to, and 0 if we're equivalent. So with that example, all the MyDates are going to be sorted in ascending order. If we wanted to swap that, if we want to go in descending order, we just need to change our math. So now I just kind of flip the numbers around. And now I'm returning the other object's year minus my year. So let's imagine that the other object is 2000 and I'm 1950. So now if I want to go in the opposite direction, if their year is more, which it is, 2000, and I'm 1950, I'm returning a positive number. So I'm saying I should be sorted after that year. In other words, we're going to go from 2000 to 1950. The reason that we often will implement the comparable interface is because there are a number of classes that will try to cast us to be a comparable because they're doing some kind of sorting. That could be in the arrays sort method or the collection sort method. We've seen that there are collections such as tree set and tree map that will use comparable to find out how you should be sorted. But there's another option that we have as well, and it's called the comparator interface. And it's a little bit more flexible. The comparable interface is saying we're going to be compared, this particular object is going to be compared to another, whereas the competitor is kind of this third party. It says, give me any two objects and I will tell you how they're ordered. And what we can do is we can pass in this comparator object as another parameter to the sort methods in arrays, collections, and other classes. So the sorting object is just one that implements the comparator interface. This interface is located in the Java util package, just like comparable. And any class that's going to implement this interface has one method to implement. It's called compare. It's very similar to compare2, but compare will take two objects as arguments, the objects that are going to be compared. And then what's going to happen is the compare method will return a positive number if the first argument is larger than the second, meaning that the first argument should come after the second. 0 if they're the same, and negative if the first argument should come before the second argument. So here's an example of a comparator. We've got our compare method. Everything that's coming in is just of generic type object, so we'll have to cast it. And then in this case, what they're doing is they're starting to compare the dates, and so they start with the year. And they say, if it's not the same year, let's figure out which year comes first. And so they subtract D1 year from D2 year. Let's imagine that the first one is 2000 and the second one is 1950. So that would return a number of 50. That's a positive number. So they're saying that the first year should come after the second. And if the years happen to be the same, then they would check the months. And if the months are the same, then they would check the days. Otherwise, it's returning 0, which means they are equal. If we wanted to go the opposite direction, we just flip our numbers, just like we did in the compare2 method. So now we're subtracting the D2 year from the D1 year. We flip those numbers around. And if the numbers were still the same, if D1 was 2000 and D2 is 1950, now what we're returning for that year is a negative 50. So we're saying that the first argument should actually come before the second argument. In the previous examples, it was assumed that both of the objects are my dates, but it doesn't have to be. That's one of the powerful aspects of a comparator, is that it can compare any two objects. Now, when you're comparing like objects, typically the comparable interface will be used, the compare2 method. And the power of the comparator is that you're able to compare two objects that aren't even related. So if you have some kind of a collection that has a lot of mixed stuff, you're definitely going to want to use a comparator instead of a comparable.
In this section, we're going to talk about how do we write code to handle situations where things might not go as according to plan. I'll give you an example. You're running a program, it connects to the database, but the database is down. How do you prepare for that in your code? Well, Java gives us something called exception handling, and that's the concept we're going to learn in this section.
Whenever we write a program, we really hope that everything is going to go according to plan. But the reality is that things can disrupt the normal flow of a program. For example, imagine that I've got a method that needs to connect to a database. What if that database is down? How do I handle that? Well, Java has an infrastructure in place that allows us to create an object that sort of encapsulates what went wrong at that time. And we call that a throwable. So it's an event that disrupts the normal flow of a program. So when we call a method and something goes wrong, an object is created, and the object is handed off to the Java runtime system. The object that's created is known as a throwable object. And it's a class. It's a class that's defined in java.lang. So it's part of the API. So this object is thrown by the runtime system, and what we do is write code to catch that object. Here's an example. So we've created a string here, and we want to get a character in the string. The problem is when we say string character at 20, there is no index 20. We've gone too far. So this method creates a throwable. In this case, it's called a string index out of bounds exception, and then the runtime system throws it. The throwable object has all the information we need about what went wrong. It's a snapshot of the entire execution stack at the time it was created. Plus, it has a message in there that gives us a human-readable, I guess we hope, a human-readable bit of information of what went wrong. And if it's possible that this particular issue was caused by another issue, there can be a link from one throwable to another throwable. Now, specifically, we don't usually work with a throwable class. We usually work with something called an exception. And in fact, there's two different kinds of throwables. There's error and exception. Now, an error is some catastrophic problem. We don't typically recover from those kind of errors. Like, for example, an out-of-memory error. There's no way to really recover from that kind of a problem. But exceptions we can recover from. And so we can look and see what's happened and see if there's code we can then execute to handle the problem, or at least log what happened. So if you open up the Java docs, you'll see that there are a number of exceptions that are included with the Java API. And the general exception and errors are all part of the java.lang class. But there are a number of exceptions that are already pre-built, which we certainly can handle, but we can also create our own custom exceptions as well. So let's take a look at how we're able to catch an exception. Here's the same code that we looked at before, but let's look and see what happens in more detail when the problem occurs. So we are creating a string. It's just called a char string. And we're printing out a line here before the problem. And then we're calling on the string class a method called char@, passing in an index, and then we're writing after problem. So what happens here? Well, as we saw, an exception is thrown once we try to access that character because the string is only 13 characters long. It's an exception, and it's known as a string index out of bounds exception. And at the moment, we don't have any code to catch this exception, so it fails at runtime. What we would see in the console is something like this. We'd first see before problem, and then we'd see the stack trace along with a message about what went wrong. So in this case, it says exception in thread main. It tells us the exception, string index out of bounds exception, and then tells us what went wrong, string index out of range 20. The lines underneath it, that's the stack trace. Now think about, we've spent a lot of time talking about the stack and the heap. What happens every time we call a method? Well, a frame is placed on the stack. That's what we're seeing here. We're seeing all the different frames, all the different methods that were called that are on the stack. In this case, it started with main, and when it got to line 7 in main, it called char@, and that's where the exception was thrown. But that's what happens if we don't try to catch the exception. Here's some code that we'll add that will actually catch a string index out of bounds exception. The first thing that we do is we wrap the code that we think might throw the problem in a try block. So we write the keyword try, we put our curly braces to specify the block, and then after that block we put catch. In parentheses we write the name of the exception, give it a variable so we can handle it if we'd like. And then we have another code block that's the code that will be run should that exception be thrown. So let's walk through the code. So we create the string, we write before problem, and we see that right down here. It says before problem. We try to get the character at 20, and that's where the exception is thrown. So at that point, it stops executing the code in the try block. Instead, it goes to the catch and says, do you handle the string index out of bounds exception? And the answer is yes. So then it prints out, hey, your string's not that big, and then it continues on. The code that we've written in the catch block can either, say something to the user, it could write to the log, or it can actually do something to handle the problem. In that example, in our catch block, we had an argument E, and its type was string index out of bounds exception. That specifies what type of problem the catch block will capture. You can actually have multiple catch blocks for any try block. So here's another example. We're catching a string index out of bounds exception. We're also catching a null pointer exception. You can have as many of these as you need. So each catch block is a handler, and it handles the type of exception that it specifies. By the way, polymorphism is at work here. So what we're saying is we'll catch string index out of bounds exception and any subtype. Here we're saying we'll catch null pointer exception and any subtype. So you can catch any number of exceptions, and if you want to, you can even try to catch errors, although that's not typical or recommended. Another thing you'll often see is that the very last catch block will just be a generic exception. It would look like this. The very last one will just say catch exception. And that's considered sort of a general catch all the rest of the problems, because in Java, when we make an exception, it's going to inherit directly or indirectly from exception. So it's, with polymorphism at work, that means it'll catch any of the exceptions that we didn't catch above. But polymorphism can bring a problem. What if we had a very general exception like we catch exception, and it's the first thing that we list? Well, none of the other exceptions would then be caught. But that's okay, the compiler is going to help us with that. If we happen to list the more general exceptions first, then the compiler will complain. It actually won't let us compile. We'll get this kind of an error. It'll say, this exception that you're trying to catch has already been caught. When you see that, all it means is that you've got a more general exception before a more specific exception. And as of Java 7, you can actually catch multiple exceptions in the same block. We use the single OR operator between the different types, and that just lets us write one block of code for a bunch of different exceptions. So here's an example. Here we've got a catch, and we've got our string index out of bounds exception or null pointer exception. Notice that you only have one variable for each type of an exception. And we really haven't seen yet how we're going to use that variable, but that's coming up. So this catch will catch both a string index out of bounds exception or a null pointer exception, and all the subtypes of both. So in the previous example, the catch block is what allows our code to handle the problem and move on. Once again, if we didn't have that catch, then the program would eventually stop executing and we'd see some kind of a message, an error message in the console or in a log. The one thing that the catch block doesn't allow us to do, however, is finish anything that was inside of the try block. So anything that was after the problem is just skipped. And that might not be acceptable. We may have some code that we absolutely want to execute no matter what happens. So for example, let's say that we had a connection to a database or a file, some kind of a stream. After the exception is caught, we want to make sure that that connection is released. So that's where a finally block comes into play. It's part of the try-catch system, so we've got try, catch, and then you list finally. And so the way that this works is finally is going to be executed just in any type of situation, with the exception of maybe an error or doing a system.exit. Let's say that we go through the happy path and no exception is thrown. So all these lines in the try block would be executed, and then the finally would be executed. Let's say a string index out of bounds exception is thrown. So it would execute all these lines. Once it hits the string index out of bounds exception, it stops the execution of the try block, goes to this catch, and then goes to this finally and continues on. Another possibility is that an exception would be thrown that we're not even catching here. So in that scenario, let's say it's thrown here. So some kind of an exception is thrown. It stops executing the try block. It looks in the catch to see if anything handles it. It doesn't. So it does the finally block right here. And then it's going to go up. It's not going to continue on at that point. It's going to call the method that called this. It's going to go up the stack and say, hey, does this frame have any code to be able to handle the problem? But basically, the finally block is going to be executed in most situations. Unless there's an error, unless there's a system.exit, the finally block will be executed. Java 7 also gave us another addition to the exception handling syntax. It's called try with resources. So prior to the syntax, any code that we would write to close a connection, to close a stream, would be put in the finally block. But the problem is oftentimes that code itself would also throw an exception. So we'd start to write crazy code like this, where here we are trying to do something with a connection, we catch an exception, and finally we would try again to see if the connection is not equal to null, and if it isn't, if it's still there, we can close it. But notice that in our finally block that we've got another try catch, and a lot of us found this code to be quite maddening. So try with resources allows us to omit that finally clause. And what it'll do is the system will automatically try to close the connection at the end of the method or before an exception is thrown from that method on our behalf. This is available to any object that implements the Java Lang auto-closable interface. So this is try with resources. We create the try block, and in parentheses, we establish our variables that we're going to want to close. In this case, connection con equals driver manager, get connection. And that's it. It will automatically close that connection as if it was in a finally block for us. So let's put this all together. When we have a try statement, it's going to either have 0 or more catch blocks or 0 and 1 finally block. So here are the possible combinations. We can have a try with as many catches as we need and a finally. We can have a try with as many catches as we need. And we can also have a try and a finally. You can't just have a try on its own. It's got to be one of these 3 combinations. At this point, we've been catching exceptions, but we haven't been doing anything with the throwable object itself. And the throwable object contains a lot of great information. We can either log it and let the developer see what went wrong. We could potentially recover programmatically with what went wrong. So each throwable object has a set of methods so we can see what actually occurred. And here are the methods. So we have getCause, and that will return the cause of the throwable, or null if it's not known. We have getMessage, which will just be that human-readable message of what went wrong. There's the stack trace. We've talked about the stack. When I call a method, and that method calls another method, and that method calls another method, each of these methods are placed on the stack. This includes all of those methods so that we can see what was the path that we took to get here. And finally, there's print stack trace, which will just do what it says. It will print the stack trace to the standard error stream. So here's an example of logging the problem. So we are catching the string index out of bounds exception, and then we're just printing out to our console or to our log, depending on how we've configured our standard out. We're saying there's a problem in main, and then we're getting the message. And that's that first line here. Problem in main, string index out of range 20. That's the e.getMessage. And then when we do the e.print stack trace, it says what the exception was. So in this case, it was JavaLang string index out of bounds exception. It includes that message again. And then we have the stack trace. What was the path that we took to get to this problem? When we look at the hierarchy of all of the Java problems that can be thrown, we've got throwable at the very top. And underneath throwable, we have error and we have exception. And remember that errors are something that are really serious. We don't try to recover from them. We don't typically catch an error. An out-of-memory error is a common example. Hopefully not a common problem, but a common example. Exceptions are problems that we might want to capture or we might have to capture, and that's what ties us into this concept of checked and unchecked exceptions. So here's the hierarchy. If you look down here, we've got our throwable, and then we've got error and exception, which inherit from throwable. But exception can be broken down into 2 different types as well. We've got JavaLang runtime and any exception that inherits from that, and then we've got basically everything else. And that's how we differentiate between checked and unchecked exceptions. So anything that inherits from runtime is considered a runtime exception, and we can try to catch it if we want, but we're not required to. Everything else is considered a checked exception, and those the compiler will force us to handle in some sort of way. Any exception that inherits directly or indirectly from a runtime exception is a runtime unchecked exception. We've talked about string index out of bounds exception, class cast exception, arithmetic exception, array index out of bounds exception. There's also null pointer exception. All of those inherit from runtime exceptions, so they're considered unchecked. Most exceptions are not runtime exceptions, but checked exceptions. And what that means is we must handle them. We have a couple of options of how we can handle it. We can use the try-catch block that we just talked about, or we can rethrow the exception. Typically, you're going to want to try to handle the exception with try-catch, but there are situations where it makes a little more sense to rethrow the exception so that something else can handle it. Some examples of checked exceptions include SQL exception, file not found exception, and really most exceptions that you'll create yourself. Let's look at some code. So here I've got a main method, and it's calling an open HTTP connection. We're creating in that method a new URL object. URL object is something that's part of the Java.NET library. It represents a network connection, like it sounds. And if we were to write this code and we were to compile it, we would get an error. The error would say, unreported exception, JavaNet, malformed URL exception must be caught or declared to be thrown. And it shows us that the problem is with the URL constructor. So what they're telling us is that we can't do that. There's a checked exception that this constructor can throw, and so we have to handle it. So here's how we can handle it. We add our try-catch to the constructor. We catch the malformed URL exception, and then we do something with it. And at that point, now we can compile. We've handled the error, or rather, we've handled the exception. But there are times where it makes more sense to say, I don't have enough information here to reasonably recover. I will throw this exception to whoever called me. So here's an example of that. Imagine that our open HTTP connection is given a URL. And so when we say new URL, we don't really know where we were trying to go. We don't know if whoever called us has some kind of recovery plan in mind. If this URL doesn't work, maybe they can give us another one. So rather than putting a try-catch here, we can write on the method throws malformed URL exception. And now any code that calls our method will be forced to try and catch, or they can declare that they throw it themselves. So now the try-catch is up here. In the main method, we've got the malformed URL exception, and it could recover or do whatever it needs to do. But even the main method doesn't have to handle the malformed URL exception with the try-catch. It too could say that it throws the malformed URL exception. But that's really not a good idea. This is known as passing the buck. And remember, main is the front door of our application. If we throw an exception here, our program just crashes. So this is not a good idea, even though it's legal. Java's exception handling infrastructure allows you to create your own throwable subclasses if you'd like. You may have something that happens in your application where there's a unique kind of problem, and any code that calls into the area, into the method that could potentially exhibit this problem, this might be a time where you want to say, here's an exception. This is what happened, and allow all the calling code to recover. And the way we do it is we just make sure that our exception class directly or indirectly extends throwable, although it's not as common for you to extend directly throwable. Instead, what we typically do is extend java-lang exception. If you do that, then it's going to be a checked exception. If you extend java-lang runtime exception, then it will be an unchecked exception. By doing that, we're going to inherit a lot of the behavior we need. In fact, most of the exception objects that I've seen really don't do anything. It's really just the name of the exception that allows people to write code to catch it. And once they know what the type of the exception is, they just use the regular throwable methods to get more information about the problem. But it's really the name that's the power of the exception. It allows us to decide what we should do when a specific type of exception occurs. And of course, we're going to need to create a constructor. Remember that we don't inherit constructors, so we will define our own. And let's look at an example. So we've got a banking application, and there are times where an overdraft could occur. So we've created here an overdraft exception. It extends exception, and notice that the only thing I put here is a new constructor. This is pretty common. You accept a string, so what is the problem? And then you call the superconstructor an exception and pass it that message. So here's some code to show that. First of all, you define in your method that you throw this exception. So throws overdraft exception. And then if we get a scenario where there's an overdraft, we say throw new overdraft exception, passing in the message. So now the code that called withdraw can handle the overdraft exception and possibly notify the user that something went wrong.